Hello and welcome everyone. It is November 13th, 2024. We're live and kicking off the fourth Applied Active Inference Symposium. It will be a great program, and we will begin with Karl Friston and Lance DaCosta discussing scale-free active inference. We discussed in Livestream 58.1 with Lance last week, and in 58.0 with Arun 2 weeks ago, a bit about this work. And today, Karl, thank you so much for joining and presenting on it. So, looking forward to it. And throughout, in the live chat, please feel free to write any comments. Thanks again, everyone, for joining and looking forward to this.
Well, thank you, Daniel. It's a great pleasure to kick off the symposium this year. I'm going to rehearse a presentation I made at the Active Inference workshop a few months ago, but this time I hope in a slightly more relaxed and unpackable way. So I'm fondly hoping for lots of questions and embellishments from the audience and from Lance. This is a bit of a colloquial presentation. It's just going to focus on something specifically that we've been working on for the past few months, which is effectively addressing the question, how can one scale active inference for high-dimensional real-world problems? And the solution that we've been pursuing is to adopt a scale-free approach. This work has been written up and put on archives. However, it's also been submitted for publication, peer-reviewed publication, to a special collection in memory of Hermann Haken. And we've equipped the peer-reviewed version with a little forward. So I just wanted to frame or preempt the scientific part of this presentation just by motivating why the work of Hermann Haken is foundational and underwrites many of the ideas and procedures that underlie this scale-free approach to active inference. So Hermann Haken was famous for synergetics, a physics-led approach to self-organization, and in particular, the importance of understanding the coupling between different scales of dynamics in self-organization. And if you go to the Wikipedia entry, you will read about macroscopic and microscopic variables and how they are coupled to each other in the fashion of circular causality. So there's both bottom-up and top-down causation, where the top-down causation is sometimes read in terms of the slaving principle. I'm going to present this approach to harnessing this notion of a scale-free universe in terms of installing that scale-free aspect in the generative models that we bring to the table to solve decision-making, to simulate or emulate active inference under discrete state space models. So let me start at the beginning. The nature of things and the free energy principle. And this is just to rehearse the fundamentals of the free energy principle. It all rests upon the notion of a Markov blanket, where we can separate internal and external states by boundary states or states that constitute the Markov blanket, namely the sensory states and the active states. And for those people not familiar with this particular partition of states of any random dynamical system, it's just specifying systemically a system, say a brain, in terms of its inputs and outputs, and just formalizing the conditional dependencies that define what is an input to a brain or an agent and what is its output in terms of the sensory and active states, that thereby render the system of interest, in this instance a brain, open to the environment, the eco niche, the heat bath if you're a physicist or a chemist, in virtue of the fact that the inside can influence the outside via the active states, the outputs, and the outside can influence inside via the sensory states or the inputs. And with this setup, we can elaborate a kind of physics, namely Bayesian mechanics, that is almost, well, formally related and inherits exactly the same mathematical and functional form as all the other mechanics that we find in physics, including quantum mechanics, statistical mechanics, and classical mechanics. The only thing that separates the Bayesian mechanics is the fact that we have in mind explicitly this partition between internal states and external states, and the blanket states that intervene and couple the internal to the external. And that Bayesian mechanics is effectively summarized here in terms of variational and expected free energy, where we can read the expected free energy as effectively prior beliefs about the kind of outputs or actions that, in this instance, a brain could exert on the external states, and the variational free energy keeping implicitly the internal states a good model, so that it's tracking in a probabilistic sense the dynamics on the outside, and we can combine this to create a generalized free energy that now teleologically or perhaps even anthropomorphically, we can now read the gradient flows that subtend this Bayesian mechanics in terms of action and perception just by identifying the internal and active states of any agent as autonomous states, and noting that they effectively flow on the same free energy functionals. So that's the basic setup. But what I want to do before applying the free energy principle in the service of things like active inference is just back up and reflect upon the fundamental role of the Markov blanket and how that leads to a scale invariant picture or view of dynamics and self-organization. So what I'm going to assume is that ultimately we will assume that Bayesian mechanics means that the dynamics of anything that is defined in terms of its boundary or Markov blanket can be described in terms of active inference. But before that, we have to think about the nature of things. And in particular, if one goes back to the particular physics paper, the nature of the states that constitute things or particles. And there's a bit of a subtlety here, because before you can start talking about states, you really have to define what is a state. Is it the state of something? Is it the state of a particle? And that presents an issue because you're defining a particle in terms of this particular partition into internal, external, and boundary or blanket states. So there's a slight not tautology, but there's a slight problem in resolving how you define states of things or particles and particles that possess states. And the resolution of that is to adopt a recursive definition so that the particles constitute a set of microscopic blanket and internal states, while the states are a set of macroscopic eigenfunctions, eigenmodes, or just simply mixtures of the blanket states. So I'm here deliberately using the notion of macroscopic and microscopic states just in as a nod to synergetics, and in particular kind of synergetics that Hermann Haken developed and subsequently championed. So this is cartooned or illustrated on the right-hand side here. So we sort of take some states and then apply a particular partition on the basis of which states are coupled to which other states and the conditional independencies that ensue. And then, having done that, we can then take mixtures, eigenmixtures of the boundary states that then generate new states. And then we can effectively, by taking those mixtures, we effectively reduce the dimensionality so that the higher scale coarse grains the lower scale, and then we reduce it, and then we just rinse, wash, and repeat. And we do that, and every time we sort of pass through this cycle of RG operators, reduction and coarse graining operators, we move to one scale above successively. And this is the scale invariant aspect of that I want to leverage in the remainder of this presentation. I use the word RG deliberately because one way of looking at this or articulating this is to use the apparatus of the renormalization group. So this is where renormalization gets into the game, that you're recursively applying these operators, coarse graining things, in a way that conserves their dynamics, and that's an easy criteria to meet for us, because we know that anything that has a particular partition can be described in terms of a gradient flow on a variation or generalized free energy. So we have everything that we require in order to apply the apparatus of the renormalization group. So what that basically does for us, once we recognize that particles are composed of states, where the states are eigenmixtures of particles in this scale invariant fashion, gives us a view of any universe that comprises things of things of things, as inherently resolving a chicken and egg problem through scale invariance by application of the renormalization group. So here's just another illustration of how that actually works in practice when you write down the equations. I'm not going to bother going through the equations. This is just used iconically, just to make the observation that as you move up scales, so for example, in an evolutionary context, this would be the sort of the dynamics of phenotypes, and then we move up to the an evolutionary scale by effectively coarse graining in a way that Hermann Haken would exactly prescribe in terms of taking those slow macroscopic variables that decay very, very slowly, which are technically the eigenmixtures equipped with very small eigenvalues whose real part approaches zero from below, effectively saying that these patterns decay very, very, very slowly, and they have a kind of persistence that lends higher and higher scales a temporal dilation, so things change more and more slowly as you increasingly coarse grain things. And that this falls out of the maths when you simply apply a particular partition and put that partition in as the coarse graining operator in this scale-free formalism. So, in short, Bayesian mechanics entail a generative model of external dynamics, but we've just seen that just by defining things in terms of particles that have states and defining states in terms of the eigenfunctions of particles, that external dynamics are inevitably scale invariant. It can be no other way. And therefore the generative model must be scale invariant, or when expressed as a graphical model, scale free. And I just slipped that in as a nod to the fact that people often talk about scale freeness. Generally speaking, when people apply the notion of scale invariance to anything, if that thing is a graph, then you can call it scale free. So a scale free thing is a graph that has this scale invariance. Crucially, in both time and in space, because we are dealing with dynamical systems and we're doing this dimension reduction or coarse graining using these eigenfunctions that necessarily pick out these slow macroscopic, sometimes called stable modes. They're stable because they don't decay or dissipate almost infinitely quickly. So they're stable in the sense that they decay very, very slowly. So how can we harness that observation, that truism, at least truism under the world as described by Haken, in the construction of plausible generative models, and in particular generalized Markov decision or partially observed Markov decision processes? Well, what we can do is we can just look at the different kinds of depth and ask at what point would we be able to leverage this renormalizing aspect of the cause-effect architecture of any given world that we're trying to navigate and predict. So here's the normal depiction of a generalized Markov decision process. And by generalized, what I mean is that there's an explicit representation of not just the states of things that are generating outputs or things that can be measured or observed on the sensory sector of a Markov blanket, but also their dynamics in terms of the paths that specify the transitions between states, as we know, normally encoded in terms of a transition tensor B here. So just by putting in the paths as explicit random variables that accompany for each given factor the hidden states, we have a generalized kind of Markov decision process encoded in the usual way in this instance in terms of tensors that themselves can be parameterized as Dirichlet distributions. So that parameterization equips these kinds of models with a parametric depth, in the sense that if something is deep parametrically, that means that the parameters of various probability distributions are themselves random variables that have their own probability distributions. So, for example, the likelihood mapping that maps from sensory states to outcomes here, usually encoded by an A tensor here, mapping from latent states to observations, is itself encoded in terms of Dirichlet parameters, lending this kind of model a parametric depth. And one can ask what the implications of that are. Well, the implications are another kind of depth in terms of you now have to optimize or apply Bayesian mechanics to the latent states, the hidden states, and that would be inference. And then you also have to consider at a slightly slower time scale the optimization of the Dirichlet parameters, and that would correspond to learning, and so on. If I wanted to go to the structural learning of the model in and of itself. We also have implicitly a temporal depth, in the sense that we're going to be rolling out into the future and that there are dynamics here. And this temporal depth is generalized in virtue of having these explicit path variables that we're going to exploit later on. We can also have hierarchical depth, in the sense that we can compose many Markov decision processes in the sense that the outputs of one process now constitute the inputs or the empirical priors, the top-down constraints, the inductive biases on the dynamics and states of the level below. And the dynamics are the kind of outputs of the upper level that provide empirical priors on the paths, and the initial conditions are supplied or mediated by a mapping between higher levels, slower states, and the initial conditions or initial states of the lower level by this D tensor here, that you can lump together in terms of a sort of high. You can lump together the D and the E tensors. They play the role effectively of the A tensors in sort of mapping from one level to the next level. There's also a factorial depth, which many people will be familiar with, in terms of for any one of these lumped states here. There may be many, many different factors that have a certain independent structure, such that you have interactions between factors in determining outcomes. You can look at this in terms of a generative model, when equipped with factorial depth, effectively entangles latent states to generate outputs or outcomes, which themselves can be prior constraints on the states and dynamics of the level below, such that the inversion of these models effectively disentangles the data or the content that is being observed to explain it, or in terms of a disentangled representation, which is the latent state and dynamics of the generative model. So what we have here then is a generalized discrete state space model with paths as random variables. Just to return to this fundamental aspect, that as one ascends scales in real life, in terms of the external states, things slow down in virtue of the synergetic mapping from fast microscopic states to slow macroscopic states. The same thing can now be implemented in these Markov decision processes that have a hierarchical depth. And the way that is done is effectively to discretize or quantize time, such that there are more updates at any given level than the level above. So for every update at this level, there are say 3 updates or 2 updates at the level below. And that affords a temporal scaling in accord with the scale invariance implied by the synergetic view of self-organization. And I've tried to cartoon that here in terms of, if you imagine lots of these little Markov decision processes populating this circumference here, and that as we go deeper and deeper and deeper into a model with hierarchical depth, as we consider updates in universal or clock time, there are more updates at the peripheral level, exposed, say, to the external states of an entire brain, relative to the updates that as you get deeper and deeper and deeper into the model. So that's where the temporal depth becomes, if you like, intimately tied to the hierarchical depth. The higher the hierarchy, the slower the updates, which is why we generally parameterize the initial conditions or generate the initial conditions and the initial path from the states above, and that path can pursue a trajectory over multiple time steps until a certain horizon, in which case it then sends messages back to the level above, likelihood messages, that then cause belief updating in the subsequent step at the level above, and then generating priors about the subsequent path, the next path at the level below, and then so on recursively to the depth of the model. So that's the time bit. What about the spatial bit? What about the sort of spatial coarse graining, the lumping together of various states? And of course, this depends upon the particular partition. So in the general physics formulation, you'd be looking at Markov blankets and Markov blankets. In practical applications, one can take a shortcut. And that shortcut effectively rests upon the simplifying assumption that for most systems that are composed of coupled dynamical systems, the interactions are usually local. So if we just think about some system that can be described in terms of local interactions. So, for example, in a Euclidean world that comprises some massive objects that bounce around. And if we ignore gravity for the moment, then they're only going to influence each other or depend upon each other when they're touching, when they're proximate. Effectively, what that means is that the particular partition that defines all the Markov blankets in this particular state space is composed of lots of local little tiles. So what we can do is we can use a device very prevalent, or indeed ubiquitous, in applications of the renormalization group, which is called a block or a spin operator that just groups together local tiles or quadrants of a, say, two-dimensional arrangement of of states. So I've illustrated that here just by in terms of how we do the spatial coarse graining in these what we will refer to as a renormalizing generative model with spin block transformations in terms of this little this hidden state or hidden factor with its states and paths here is responsible for generating predictions about the dynamics of these two factors at the lower level, and in so doing, what we are effectively doing is successively grouping together sets of sets of sets of sets, so that any set or group at one level is accountable for or trying to generate the dynamics of a small local group at the lower level. This is quite fundamental. This kind of architecture is quite fundamental, because what that means is anything at the lower level only has one parent. And if it only has one parent, and if you remember, the Markov blanket is constituted by the parents and the children, the parents of the children, because there are no co-parents, there are no parents of the children. And what this means practically is that we can now ignore dependencies between, or effectively resolve or dissolve any dependencies between the factors at any given level, because each factor is only responsible for its children, and it doesn't share any children in virtue of this particular spin block transformation. So this leads to a very efficient kind of generative model, or certainly an efficient kind of inversion of the generative model, where we've got all these converging streams, but the streams don't have to talk to each other until at the point that they come together through these blocking or spin block transformations. So at some point, all the tiles or the groups at the lowest level will actually come together at the top or very deep in the model, at which point we're now encoding quite long trajectories, technically 2 to the power of the depth -1 in terms of updates. But at the lower level, there are no interactions between the different blocks as we ascend them. And this is just to remind you, we can treat these D and E, the initial states and the initial paths, effectively as likelihoods that couple one scale or level to the scale below. So how if that's the kind of model that we aspire to, because we think that's appropriate for any world that shows this scale invariant aspect in space and in time, or in state space and in time, how are we going to build one of these things? And this is the sort of second, if you like, thing that we have been working on, because it's going to be very difficult to specify by hand these scale-free or renormalizing generative models. We really want the model to learn itself. So basically, how does one build a renormalizing generative model? And what we're going to do, we're going to use very fast structure learning. And this particular kind of structure learning is necessarily recursive, and in the sense that we're going to build these models through the recursive application of these RG operators or renormalizing operators. So what's fast structure learning? So fast structure learning basically equips the model with unique states and transitions as they are encountered. So to put that simply, what we're going to do is grow a model from scratch, from nothing. And how are we going to do that? Well, we're effectively going to take one observation and say, okay, that was generated by some latent state. And then we're going to take the next observation and say, okay, I haven't seen that particular observation before, so I'm going to induce a second latent state. And furthermore, I've seen these two observations in sequence, therefore I'm going to encode that with a transition from the first to the second state. And then I just repeat. I take the third one, and if I haven't seen that before, I induce a third latent state and a second transition, accumulating all the unseen or unique instances of observations in a likelihood mapping that just grows and grows and grows until we have seen something before. So we don't induce a new state or implicitly column of the likelihood matrix if we've seen the previous state. That's just an instance of something that has been seen before. It may well now come along with a different path, so the next state may not be the same as the subsequent state following the previously seen instance of this state, and therefore I'm going to induce a new path and slowly grow my B tensors and my probability transition matrices until I can basically encode all the dynamical structure of effectively the training sequence of observations summarized in a maximally efficient way. And I mean maximally efficient in a technical sense, in the sense that the implicit mapping that we are growing from scratch has the highest mutual information between the latent states and the observations that are at hand. The way that you can think of that in terms of free energy is that the expected free energy is just the mutual information in the absence of any expected cost. So the expected free energy is just the mutual information of any mapping, plus or minus an expected cost, where cost is defined the usual way in terms of constraints or prior preferences. So one can actually look at this fast structure learning as a particular kind of active inference, but not about, it's not active inference over states or active learning over parameters. It's active selection of the right model in terms of the size of the likelihood tensors and the transition tensors, and the criteria for whether we accept a new latent state or a new transition is simply, does it optimize or improve the expected free energy? Namely, does it preserve or conserve or maximize the mutual information? So we can actually look at this structure learning as just another instance of active inference, but here deployed in terms of Bayesian model selection, or some people call this structure learning, that has exactly the same rules as planning and accepting parameter updates, provided they maximize expected free energy as well. The application of this kind of fast structure learning to these renormalizing models looks complicated. Here's the algorithmic description of it. Again, please don't worry about the details here. It's relatively simple. All we're doing basically is ingesting observations, but we're just doing it for local groups. And then we are combining the initial conditions and the paths into new outcomes for the next level. And so because we are doing this for local groups, the number of groups just gets smaller and smaller and smaller as you get higher and higher and higher. But obviously the number of combinations of paths and initial states increases as you get deeper and deeper into the model. And you may be asking, well, how do you bound that? How can you possibly assimilate all the data without having an extremely large number of latent states very deep in the model that are now encoding effectively evolving patterns or paths over quite a large number of time points into the future? Well, it's trivial to do that because the size of the highest level, I'll call them generalized states that basically generate paths and initial conditions for the lower levels, is upper bounded by the number of elements in your training set, so that you can control and upper bound the size of these renormalizing operators or likelihood mappings and transition tensors simply by giving it canonical training data, the kind of data that you want this agent to generate or this agent to recognize and thereby predict. So here's a particular example of that. What we've done here is just ask, can we very, very quickly learn a generative model that will generate a simple movie? And this movie is simple because it begins and ends in the same state, so it just loops over and over and over again. So we only have to supply one loop to this fast structure learning so that the model builds itself and can then be used in generative mode to generate the movie time and time and time again. So here's one depiction of the results of the learning, the fast structure learning, and subsequent inference when exposed to this kind of image. So the coarse graining here at the very bottom, in fact, uses a slightly finessed version of the spin block operator by harvesting local eigen modes or eigen images of little patches of the video to get it into a reduced or coarse-grained representation that then is just passed up using these spin block operators. And in this instance, we just need two levels to the model to have the highest level see the entire image. And then if we present the image after discretization using the singular value decomposition or the sequences of images to a model, it learns the model, and then we can generate little movies simply by moving through these paths or episodes. I use the word episode because, remember, these generalized states at the highest level encode paths or trajectories into over 2 to the n-1 time steps in the future, when n is the depth of the model. And these episodes themselves have dynamics, so we just go through a little loop here, go back to the beginning, and thereby generate this image at the bottom. What else can we do with these kinds of models? Well, one thing we can do is present not the entire data, but just a little prompt. So in this example, what we've done is actually show it just the upper right quadrant of the movie, and see what this this generative model believes is going on in terms of the predictive posterior in output space, in image space in this instance. Now, because during training it's only learned to recognize a dove flapping her wings, That's all it can believe is the cause of its sensations, even if those sensations are very partial. So basically what we have here is a kind of pattern completion that inherits from the fact that this generative model only knows about latent causes that constitute an entire dove flapping her wings. So even though this is what the dove is actually exposed to, it's sensing, this is the predicted, after a couple of frames, it very quickly is able to predict what it should be seeing, or what it would have seen had it been given the entire data. And another way of thinking about this remarkable ability to sort of fill in the gaps is from the point of view of compression. So just a little digression here. A lot of the Bayesian mechanics and variational inference that ensues from variational mechanics can also be likened to the same fundaments that underwrite efficient information transfer. So we've talked about maximizing mutual information in the context of algorithmic complexity and the associated universal computation. Then what the objective function looks like is basically how much can I compress this content to represent it in the most efficient way. So you can look at this past structure learning under these renormalizing or scale-free generative models as the most efficient way of compressing whatever your data you've been exposed to. And because we've compressed it in such a way that it can only now recognize a dove flapping her wings, then it can, if you like, fill in the gaps in a very efficient way when just given partial or noisy data. And I use the word noisy here because you can regard the missing 3 quadrants here as extremely imprecise data that has extremely low signal to noise, for example. So here's another example. In the previous example, we took effectively a movie or a dynamic or a system that had a periodic orbit, which was each flap of the wings. Will this work for aperiodic orbits and generally for stochastic chaos? Yes, it works. It works relatively efficiently. So this example, we used training data that was generated through creating images of a white ball that moved with a chaotic trajectory governed by a Lorentz system. So this is the kind of system that governs or is used to describe chaotic events in meteorological systems or in fluid convection. So by applying exactly the same procedures as in the previous example, we're now generating, this is a 3-level hierarchical or renormalizing model that now accommodates the stochasticness or randomness induced by not only random fluctuations on the dynamics of this stochastic random dynamical system, but also if there were any deterministic aspects, the deterministic chaos that ensues from exponential divergence of trajectories that now has been summarized stochastically in terms of probabilistic transition matrices here, which means that we can, having compressed the training data, we can now withhold not a quadrant, but just simply withhold the data, to stop the data, but the model will keep on generating what it predicts would have happened given the statistics of the dynamics that have been installed in this renormalizing generative model. And what we've done here is for the first few hundred time bins at the lowest level, we've basically rendered the images or the input very, very imprecise, so that everything is governed now, or everything is generated from these top-down priors or posterior predictive posteriors that inherit from precise priors because there's no precise likelihood. And then we've actually removed the imprecise input completely and just allowed the agent to generate its own beliefs about what's going on. So here, this is fairly precise in the first instance, and then we remove completely the stimulus, but it still imagines or generates its or predicts what's going on in terms of this chaotic dynamics. And then with a degree of uncertainty then continues to then generate the dynamics associated with this kind of stochastic chaos. Here's a prettier example using exactly the same technology and approach, but here explicitly talking about video compression. So we literally just presented a video of naturalistic dynamics, in this instance a little bird, a robin, feeding itself, and compressed that using this renormalizing generative model, such that we can again simply remove stimuli at certain points in the video, and yet in the agent's mind nothing has really happened, because all it knows is that if it was like this previously, then this must have happened, and so on through this, in this instance, orbit that doesn't have a closure. It's just a trajectory through from the beginning to the end of the sequence. And here's the posterior prediction after just being exposed to a couple of frames right at the beginning, in the first 6 time frames of about 120, of 80. This example applies exactly the same approach as previously, but now we're not talking about ingesting or learning or compressing images. We're talking now about compressing or ingesting sound files. And that is, if you like, a simple or limiting case of this two-dimensional compression that we talked about before. So in this instance now, what we're doing is compressing one-dimensional frequency summaries of a particular wave file or file that describes fluctuations in the intensity of a sound, that then is summarized in terms of a continuous wavelet transform, and then the succession of different trajectories in this time frequency space is then ingested or assimilated or learned by the generative model. Now, unfortunately, you can't hear this, so I'm not going to bother playing it, but this is what the agent was trained on. It's basically jazz piano. And these are the ensuing predictions in the absence of any inputs. It's being used to generate music using the stochastic transitions through various bars of music that it has learned, returning to one or other bars of the music when it reaches the end of the orbit, to generate something that sounds at least jazzy, if not. Oh no, I started it, but you can't hear that, so I'm not going to pursue that. So to summarize what we've done so far, we've gone beyond generative AI in the sense of having a true generative model that entails active inference and agency. And in the setting of these, what we are going to do now is go beyond just simply generating content, having been trained on the basis of some training data. And we're going to now consider agency by putting action into the mix. And in the setting of the simplified setting of optimal state action policies, where we can effectively ignore the imperative to maximize expected information gain or explore in the sense of responding to epistemic affordances, we can do one of two things. We can either use some universal function approximator, say deep learning, to optimize the mapping from sensory to active states to maximize the expected cost or the expected utility part of the expected free energy, or we can use active inference to realize predictions under a normalizing generative model of rewarded events. So what I'm doing here is deliberately setting up a dichotomy that tries to distinguish the active inference approach to purposeful behavior, where the purpose is provided purely by the prior preferences or the constraints, usually encoded in the C tensor, against a sort of reinforcement learning approach. And this is a rather busy slide, but I think it's probably worth just briefly rehearsing the distinctions between active inference and reinforcement learning. So the story with respect to action as a gradient flow on free energy, which basically reduces to picking those actions that maximize the predictive accuracy, in the sense that if you look at the expression for the variational free energy, the only thing that you can change is the accuracy, in the sense that free energy can be written as accuracy minus complexity minus accuracy, and the complexity does not depend upon action, whereas the accuracy does. So that picture basically says I can describe behavior in terms of a generative model that is optimized through perception in the usual way, cast in terms of, say, variational inference, that basically generates predictions about what should happen next. And then I can pick my actions to fulfill those predictions. In continuous state formulations, this would be sort of minimizing the prediction error, usually in the proprioceptive domain, but you can generalize this to any consequence of action. I'm just going to pick that action that brings about, or is most likely to bring about, what I predict will happen next. And what I predict will happen next is optimized through perception, through variational inference, based upon my learned and selected generative model. So this is very similar to sort of model predictive control, and in neurobiology could be cast in terms of perceptual control theory, which puts action in the game basically of realizing, evidencing predicted states. So I've tried to summarize that here just in terms of our Markov blanket, where we're optimizing our beliefs about the world, noting that planning in this instance, so planning as inference, is all about the paths. It does not have to be about action. It's just about how does this world unfold, and from the point of view of these scale-free generative models, we're really thinking about how do episodes follow each other, which episode is going to follow this this episode, and we can say, well, you are in control of that. Imagine a benevolent world in which everything happens according to your beliefs about how to be an expert in this particular world, and the agent can plan a series of episodes generating predictions all the way down to the bottom, which then slavishly action can fulfill just by fulfilling those predictions. So one could, in some sense, think of this in terms of controllers inference at the bottom level in the spirit of model predictive control, and planning as inference at the top level, so belt and braces in terms of realizing active inference. In this particular example, where I repeat, we are really just worried about state action policies. Why are we worried about state action policies? Well, these are the kind of policies that reward learning schemes are aimed at, and have a similar architecture, but to my mind, a slightly more over-engineered architecture. First of all, you actually need explicit inputs, which are rewards. There are some proxy for the constraints under which the basic mechanics would normally operate. But more importantly, you're basically sending your inference scheme is basically about selecting the right policy. I've used Q-learning here to maximize the discounted reward. So similarities and differences, but we're going to focus on active inference in the particular setting of these renormalizing models, where I repeat, planning and thinking or imagining a future can proceed at the very highest level. That has no notion of action. They're just patterns that unfold. They may or not be caused by me. I don't know. I don't care. But the action at the lowest level, the reflexes, as it were, are in a position to make my predicted posteriors come true simply by picking those actions that realize the predicted outcomes. So how are we going to leverage that kind of merely reflexive active inference in the context of building or learning from scratch renormalizing or scale-free generative models that would be apt for doing something, implementing a state action policy? And I'm going to appeal here again to this notion of active selection as one way of looking at action, which can always be at least mathematically expressed in terms of doing something if it minimizes expected free energy. And in this instance, what we can do is actually apply it not to the selection of the model, but the selection of the training data. So if we just apply the diktat that you only select something if it minimizes expected free energy, that includes the expected cost, what that basically means is I'm only going to select those data features or those training sequences that don't come along with a high cost, namely those that are rewarded. And that's what we're going to do here. We're basically going to learn to play a very simplified game of Pong, where this ball bounces around inside a circle. And we can move the bat in a way to return the ball so that we can avoid penalties when the ball hits the upper boundary and secure a reward whenever there's contact of the ball and the bat. And how can we learn this kind of dynamic, these episodes, in exactly the same way we learned the video of the robin or the dove flapping her wings? Well, what we can do is we can just select instances of random play that conform with our diktat that we cannot include those costly events. And so what we've done here is just generate training data, training sequences using random play, but omitted anything that does not, that contains a costly outcome. And furthermore, just to make things more efficient, we've restarted the random play after a reward is secured, and then just use the subsequent play if it actually attained a subsequent reward. So basically chaining together, bootstrapping together, or splicing together sequences of rewarded play, and then use that or submitting that for fast structure learning, and now we have a generative model of expert play, effectively, or a generative model that entails a state action policy that can be realized through reflexive active inference. So active data selection, and I'm sort of cartooning that here in terms of applying a certain kind of Maxwell's demon that only lets through non-costly episodes. Basically, yes, admit this sequence for fast structure learning if there is a reward. If not, ignore this sequence. And this effectively learns or furnishes a generative model of events that lead to a reward and nothing else. So now this agent can only recognize expert play, and therefore all of its predictions have to be the predictions of an expert player, and because action is fulfilling the predictions, it will look as if it is an expert player. And here are the learned trajectories at the highest level of different episodes that we'll see shown in an alternative format in the next slide. So here's the initial starting episodes, little events here. The red dots correspond to reward. So, first hit, second hit, and then it falls into a nice little orbit, and this completes this orbit indefinitely by it's the way that it has learned. So remember, it's only been trained on random data, so this particular style of play is unique to this agent, but it is sufficient now to play with 100% performance, simply because it's now going round and round its orbit, very much like the wing flapping her wings. These are just different ways of portraying the same dynamics and the things that have been learned. The first 8 frames and then subsequent frames of expert play. This is the usual format showing the posteriors at different levels, the posteriors over the states and the posteriors or predicted posteriors over the paths, and then rewarded play as a function of the free energy at different levels, here illustrated by the red dots every time there's a hit up until 512 timeframes here. And here's this rather long orbit through 50 episodes, each 4 time steps in length, that subtends this kind of play. This is an interesting one and speaks to the fact that we've actually switched on inductive inference at the highest level. So what does that mean? Well, what we've done is just basically take each of these highest level states, worked out the sequence that it encodes just by computing or projecting down through the model. And if that sequence includes a hit, we said that's an intended state. That's the kind of state that I want to work towards through the successive 4 time step epochs. And if I want to be at some point in the future in one of these intended states, in this instance rewarded states or episodes, what states must I avoid in order to preserve or conserve the possibility of getting in or getting to one of these intended states? Basically, that's the technology behind inductive inference, and it's sort of summarized here in terms of the latent states of 50 or so of these latent states, in terms of how many time steps would it what's the shortest number of time steps until the intended state, and basically as we move from state to state to state, we want to keep in the white areas here, avoiding these dead ends, if you like, from which there is no possibility of reaching an intended state. And it's really trivial to evaluate these areas that you have to avoid, because you know the probability transition matrices. So you just multiply it by itself and give a number of times, and you can work out, can I get from this state to this state? And if you can't, then you get this black area here, and you know you have to move from here to here to here to here to get to your intended state. So that's inductive inference in brief, and we've applied it at the top level. So you just tell the agent, this world is under your control. Imagine imagine what you want, noting that these particular episodes or events contain, are things that you should pass through or should experience, and then deploying inductive inference to basically predict what will happen all the way down at the bottom, and then using reflexes to make that happen. We can apply exactly the same technology or the same procedure to different kinds of games in a slightly more complicated game. It's meant to emulate Breakout, where we've introduced certain stochasticity in terms of the initial conditions and sticky action, but the overall behavior is the same. It's just basically choosing paths through episodes into the future, given what it knows that can be achieved in order to get to rewarded states. So effectively, what we've done is create an attracting set of episodes at the highest level of these scale-free generative models, where all the allowable paths and paths that now in this generalized state space or event space lead to reward. We can go a little bit further and just add in various episodes by merging or assimilating new data, new training data, if and only if the path actually leads to an existing part of this attracting set, and I've just illustrated that here in this final example. So this is the path or the orbit or the attracting set that was learned at the highest level by the ping pong playing agent. But now we can fill in this effectively allowable dynamics to include all states that lead to a path on the orbit, or thereby all paths will eventually lead to reward or to roam. So we can augment the model of expert play with paths that lead to an orbit, namely this attracting set, and paths that lead to event that lead to the orbit recursively, and get quite a dense set of allowable transitions that we can be guaranteed always keep within the attracting set that will contain these preferred states or states that we have constraints where we have constrained those states that are not visited simply because they cannot be recognized. And that's it. Thank you very much indeed.
Amazing, Karl. Thank you. Awesome. Okay. Arun, if you'd like to lead in with a first question, and Lance too. Thank you, but go for Arun first.
Yeah, thanks very much, Karl. So my first question is based on a sentence in the paper, which talks about any model being sparse must be renormalizable. Could you say a little bit more about why that must be?
Oh, I can't remember. Give me a clue.
I'm presuming it has to do with Markov blankets, and
yes.
Yeah, that's as far as I got.
I see. Yes, no, I remember now. It may have been in reference to some work done by Dalton, showing that with probability 1, provided the system is large enough, there will be Markov blankets, and as soon as there are Markov blankets, there is now an opportunity to take Markov blankets and Markov blankets in the spirit of that applying the renormalization group that I started off with. So as soon as you've got, as soon as any sparsely coupled random dynamical system can now support a particular partition into Markov blankets, you've now got the opportunity to take Markov blankets and Markov blankets and then apply that renormalizing procedure that I said before. So all you need to posit is any system that has a Markov blanket at any given level. And as soon as you've got that, you've got Markov blankets all the way up, not necessarily all the way down, but you've certainly got them all the way up. The physics approach would actually also require for there to be Markov blankets all the way down as well, but that's another issue. What that basically means is that all you require is a sufficient degree of sparsity that would lead to the conditional independencies that are definitive of Markov blankets. And in one sense, much of the sort of the maths behind the free energy principle as it inherits from random dynamical systems, or in physics, say, Langevin equations, is simply showing that a sparse coupling, a sparse causal coupling in a physics or control theoretic sense, not a philosophical or Granger or cause-effect structure sense, but in the physics sense of a coupling, so that the change, this state influences the rate of change of that state. So that kind of, which could be written as an influence graph. So if there's a sparse coupling on the influence graph, the equivalent Bayesian graph or probabilistic graphical model induced by that sparse coupling now can be interpreted in the sense of Pearl's Markov blankets. So all you need to get to the application of the renormalization group to Markov blankets is sparse causal coupling, hence sparse random dynamical system that is sparsely coupled. Just out of interest, the spin block, the motivation for the spin block, applying the spin block or blocking transformations, that basically comes from the assumption that many systems that people deal with, both in computer vision and in idealized models in physics, has an exquisitely sparse distribution, and that's because the causal inferences are all local. So as soon as you look at a coupled map lattice or a globally coupled map, you'll notice, let's take the lattice, for example, let's take a sort of idealized crystal. So what you're saying when you write down a lattice is I'm only connected to my neighbors, to my Moore neighborhood, or to my Markov blanket. That means that in a large lattice, where I could be connected to n squared neighbors, I'm only connected to 1, 2, 3, 4, 5, 6, 7, 8. So a fantastically small, almost empty set of possible connections. And I use that phrase because there's, I can't remember who said it now, but I really liked it. The notion that if one looks at the connectome in the brain, in terms of the connections, it's almost empty. The number of actual connections, white matter connections, external connections, and indeed intrinsic external connections, are almost zero in comparison to the total number of possible connections between the 10 to the 11 or whatever neurons in the brain. So that's not surprising, and it's one of those nice examples that the anatomy, the functional architecture of the brain recapitulates the anatomy of the lived world, in that it has this incredible sparsity. And that just means that universes in which there is the action at a distance is quite rare. Means that you're just interacting, you're just coupled to your neighbors, and that gives you, if you then look at the Markov blanket structure or the particular partition for these lattice structures, you get to the spin block, the blocking transformations, as a way of carving up nature, in terms of little patches on Markov blankets.
I do have a follow-up question on that, but then I'll hand it back to Daniel or Lance. So the lattice example is really interesting because I think there's a symmetry there that maybe we lose when we talk about blankets that only have one parent. So in a normal lattice, as you say, you're just connected to your 8 neighbors in 3D space. When we looked at the spin block transformations before, we were going, let's look at this square, and everything in this square has one parent, but then the square along is connected to a separate parent. So now if you're at the boundary, we are breaking some symmetry there.
Yes, technically or practically, a very good point. It doesn't really, it doesn't really have any material impact upon the algorithms or the partitioning. So just practically what happens is you just take your tiles and then you have a half tile or a partial tile until you get to the boundary. So these groups in the grouping operation or the blocking operation are not necessarily the same. They're not the same size, and indeed in current work, we're actually dealing with sort of multiple streams. So you can have sort of audio files and video files separately tiled and then converging right at the top. Ideally, what you'd want to do is not use this blocking transformation, but to try and identify the Markov blanket structure at the particular scale in question and actually use the Markov blankets based upon well, there are a number of ways of doing that. You can either use a Markov blanket discovery algorithm of the kind that Jeff Beck works upon, or you can use empirical analyses of the dynamical coupling by estimating effectively the Jacobians. For those people who are interested, there's a worked example of that in the particles and parcels in the brain paper in network neuroscience. It's really framed in terms of data analysis, but you can use the same principles to identify a particular partition from a large number of states or voxels or pixels in 3 and 2D respectively. There's another thing though that I think your question speaks to, which is you've got one block of 4 and then another block of 4, and then because of the sparsity, they're separately modelled at the level above. So I thought you were going to ask, how on earth now do you start to repair the obviously rather facile assumption that you've got just local action? Because of course in our world there's lots of action to distance. We are talking to each other over thousands of miles or kilometers, and we have vision. So all and we have linguistic communication via sound. So it is interesting that we have actually violated much of the local action. If I was a virus, this would be perfectly okay, because the only thing that's really going to affect me as a virus is the things that actually are in molecular contact with me. But for you and me, and the worlds in which we live in, we can't. There is no such thing as just the action to distance now starts to really matter, and effectively because the two latent states, generalized latent states, generating stuff, initial conditions and paths for the 2 blocks below, because they themselves now constitute a single, contribute to a single latent state at the level above. As you move deeper and deeper, you start to now repair the simplifying assumption of conditional independence between the groups. So it is at the higher levels that you now you're able to see this action at a distance, these coupling. What happens over here really matters in terms of what's going on over here, but you'll only ever see that. You only have that as part of the generative model right at the top, which is why all the inductive inference is implemented right at the top level where you can see everything. So that it becomes, if you like, you are now in a position to model and thereby generate appropriate predictions that rest upon these long-range dependencies. And of course, using the word long range, I mean in the sense of the coupling distance, from, in a dynamical sense. Is that what you had in mind?
That was exactly what I had in mind. Thank you.
Thank you, Arun. Lance, do you have any remarks or want to add a question? Or I can yes, please go for it.
Yeah, I have lots of questions. Thanks a lot, Karl, for the talk. So I'm just wondering about this all roads lead to Rome slide that you had at the end. And I'm wondering whether you have some sort of a curse of dimensionality as you increase the dimensionality of the system. So it sounds to me like the manifold of expert play, because you're taking temporal trajectories, that's going to be a one-dimensional manifold. Now, as the state space of the game increases in dimensionality, you're going to have an ambient space of trajectories that's much, much higher dimensional. And so it sounds like the amount of trajectories they need to, construe to bring me back to your one-dimensional expert manifold is just going to grow and grow and grow. And it sounds like it might be hard to fill that space. So could you comment a little bit on that and whether it's a problem?
Right. Yeah. In general, in my world, these things aren't problems, but they're challenges, and I think that challenge is yet to be met. So what I imagine people will do is that you will ingest extra episodes or sequences that bring you onto your attracting set up until some bound, and then you will switch off active selection, by which I mean the structure learning. So you stop growing the model, and then you switch on parameter learning, so that now you're forcing the transitions and the expression of various generalized states to accommodate variations around the training data that you have been previously exposed to. So that fixes the size of the tensors and hence the dimensionality of the state spaces in question, but will, in principle, now accommodate by using sort of active learning, in the technical sense that you only update a parameter if it does not increase expected free energy or decrease mutual information. Then you're now in a position to become more robust. And perhaps I should qualify this answer. The whole point of this adding in extra, if you like, insets onto an attracting set is just to equip the agent with a certain robustness should itself find itself outside or off that attracting set. So I know Lance knows this, but I'll just make this explicit for everybody else. This kind of learning and state action policy implementation is very much like learning to ride a bike. So you basically just accumulate and remember those experiences that were successful. So, for example, I managed to rotate the pedals by one cycle and I don't fall off, and I remember that. And then I have another go and I wait until I've actually done 2 cycles and I don't fall off, and I remember that. I forget everything every time I fall off, and then I keep on going until at some point I connect back my last cycle was identical to the first cycle, and then I've learned to ride the bike. But because I've forgotten all the falling off, I can't recognize or know where I am when I've fallen off. So I've got a very brittle expertise that will not allow me to recover if I fall off the edge. So another example which makes this slightly clear, I think, is like mountain climbing. If I want to be an expert mountain climber, I cannot learn by my mistakes, provided I'm climbing a sufficiently high mountain. Should I fall off it, then I will die. Another example here is learning how to cross the road as a child. You cannot learn by experiencing being run over. But the cost you pay, or the price that you pay, is you can't recognize when you are being run over. And that, I repeat, lends a certain brittleness and a lack of robustness to agents who may be exposed to danger that doesn't actually terminate them. So putting this robustness back in by growing the attracting set, or basically putting these insets on in this sort of generalized phase space, it's just to make it more robust. In numerical studies, it does seem to converge. It doesn't seem to grow indefinitely. So those likely violations are moving off the attracting set are themselves quite small, relatively small in number. Practically speaking, if you've controlled the sources of stochasticity or unpredictability. So it may not be always the case that you need to have an explicit bound on the size of the very high level tensors. If you do, then one has to now think of a principled way of making that upper bound an emergent property of expected free energy minimization. It may be that you violate now the mutual information, that certain rare events are just so rare you're actually compromising the mutual information by including them as a particular option or a particular column of a likelihood mapping. But I don't know. But these are all really interesting questions to pursue.
Thank you, Karl. All right, Arun, go for it.
So following on from that, I think it's an interesting question on the uniqueness part of ingesting data. And the question is, are there many more ways to fail than there are to succeed? So if you're passing your data into our sort of Maxwell's daemon with a gate saying, accept this data, reject this data, if this improves my mutual information. If there are many more ways to fail, but then get back onto the successful path, but there are only a few paths that actually keep you there, would it not make sense to just continually accumulate these sort of recovery states? Because the mutual information will keep increasing, and then you stop there. Then you learn parameter-wise, because we're not including the sort of prior distribution of how likely you are to be succeeding at any given moment. Because with the uniqueness thing, you don't know, 10 times out of 10, I'm cycling. Or like 9 times out of 10, I'm cycling, and 1 times out of 10, I've fallen off the bike.
Yeah, I think it depends. Again, I don't have any explicit numerical analyses or mathematical analyses of this, but intuitively, I think during learning, there may well be good mileage in ingesting failures or routes to success, if you like, or to the attracting set that actually traverse regimes that would normally be excluded by my constraints or my prior preferences. Just taking the view of the role of the C tensors or prior preferences from the point of view of physics, what that basically is saying is it's actually carving out vast regimes of state space, latent state space, that you should not be in, because it would be uncharacteristic of you to be in these things. So it's really not so much about the rewards and the preferences. It's really where you shouldn't be, and that's what defines the attracting set. However, before you've learned that attracting set, it may be useful to include constrained regions of state space that offer a route into or onto that attracting set. So I can certainly see that would be a useful device. But notice that once you're on the attracting set, you will never visit the constrained regions, because you now keep yourself on the attracting set. And therefore, if you've encoded those, but you never visit them, your mutual information will actually fall. So what that means operationally is what you probably do is have this sort of slightly over-inclusive structure learning, learn how to cope with all the necessary sources of randomness so that your attracting set is sufficiently robust, and you do actually visit from time to time, but not never. Sort of excursions from the attracting set are drawn back onto the attracting set, and then use Bayesian model reduction to eliminate all the states that you don't want to recognize simply because you never go there. Once in a, when I was younger, I would certainly be able to recognize what it's like to fall off my bike. But now, as an expert bike rider, I really don't want or need that. So, and that's just basically getting old and wise, and implementing Bayesian model reduction to remove the redundant parameters, which would, in this instance, just be the columns and associated slices or rows of the transition matrices. So I think you could, perhaps another way then of answering Lance's question is, you just keep accumulating, but start to engage Bayesian model reduction. At some point you should reach an equilibrium, which will be an attracting set that allows you to survive in the characteristic states that define you in this particular environment with this particular volatility.
Thank you. Awesome. Okay, I'm going to bring in a question from the live chat. Okay, Javier wrote, so stochastic plus dynamical probabilities learned by the agent itself are scale-free. Will this hierarchical learning also be applied to the goals of the agent, different abstractions, granularities of goals self-learned?
My answer would be yes, but I'm going to ask Lance to answer that one.
Oh, that's cheeky. Yeah, I would say for sure. Because typically when we operationalize the goals in our generative model, they need to have the same structure as our generative model itself. So I would imagine then we would have hierarchical renormalizable goals, which kind of makes sense.
Cool. Okay, I'll bring in. Oh, yeah, go for it, Karl.
But I was just going to say, just to unpack what Lance just said in terms of practical things. If you're trying to do, you're trying to say, what my goal is to go is to have dinner. That naturally unpacks hierarchically into, I've got to move from the living room to the kitchen, then I have to find you open the fridge, and I have to find the food, which then unpacks into, I have now opened them, and all the way down to the finest muscle movement. So almost by definition, intended narratives can always be decomposed in this scale-free way, this is very similar to sort of motor chunking and hierarchical decomposition in theoretical motor control, for example, and you probably find it a lot in robotics, that there's a sort of global long-term plan that provides empirical priors or constraints on shorter little chunks that themselves provide constraints on shorter and shorter chunks, and that's exactly the if you like, the architecture implicit in these scale-free models.
Awesome, and totally ties back to the synergetics. Okay, I'll ask 2 questions from ML Don. He wrote, how can we inject the same separation of timescales by imposing smoothness constraints on, say, the parameters as opposed to playing with proportional update rates at different levels? And this relates to something Arun and I talked a lot about in the .0 and leading up to it, is identifying which windows to use. You could imagine picking the right separation of timescales. If the classes on campus really do shift on the hour, then the hour course grading is going to be great and effective. But the 59 or the 61 minute might alias you with the real variability of the system. And so there's not necessarily even a smooth landscape for determining the windowing or the binning of coarse graining. And coarse grainings may have dependencies on each other. So how do you go about playing and finding viable approaches and robust ones amidst all these different levels of meta optimization that are opening up?
Right, I'll take this one, and Lance could take the next one. Then that's a really good question, because there is an implicit separation of timescales between so vanilla implementations of inference and learning. However, in these schemes, there isn't. So the MATLAB version or implementation of active inference under these, and in fact all Markov decision process models, unlike the procedures that you might find in data analysis, where you acquire, you basically do some filtering on an epoch of data, and then at the end you update your parameters, and then you rinse, wash, and repeat. In active inference simulations, and also in some applications of what's called generalized filtering, you have continual learning. So the update of the parameters actually occurs at every time step, at each level of the model. So the likelihood parameters at the lowest level are updated every time that routine is called. So there is continual learning. The learning is, yes, you're absolutely right, it's smooth in the sense that you're slowly accumulating Dirichlet parameters, but the temporal scale of that learning is the same as the inference. And you could also argue, well, could one also put Bayesian model reduction into play at the same timescale? So basically, can you at every time point, at each level in the model, identify redundant parameters and remove them using Bayesian model reduction? In effect, that's what's done using active learning. What I said before, active learning will only proceed if the expected free energy on mutual information improves. That's actually also implemented. So the rate at which it looks as though things change between inference, learning, and model selection is certainly distinct. I don't think that's quite the same kind of separation of timescales that is implied in the renormalization group. That's, as you were intimating, Daniel, exactly specified by the number of ticks or updates at level n per single update at the level n+1, and that is, I think, the key question you're asking. How do you get that right? And of course, the answer to that is the model that has the greatest model evidence, or smallest free energy, or greatest marginal likelihood for the kind of data generated by this environment in this world. So are there any sort of useful priors you can put over this? Well, one useful prior is that things are changing as well, one prior which is actually used in operation is you take the lower limit on what's called the temporal RG flow, which is basically the length of the window at each and every level. At the moment, that's 2. What does that mean? How can you motivate that? Well, it's the most expressive in the following sense. But if I just imagine what this discrete discretization of time means from the point of view of classical notions in continuous state space, like position and momentum, or position and velocity. If I use a scaling of 2, which is basically means there are 2 time steps for every time step of the level above. What I'm effectively doing is modeling 2 time steps for every state at the level above, and that basically means I can model the initial condition and the subsequent condition, basically in terms of the change, which of course is the velocity. And And what does that mean for the level above that? Well, it now means that I'm modeling the change in the velocity. So I'm now modeling the acceleration, and then so on up until the highest order of motion. So what that means is by taking this limiting case of T, the temporal horizon, or the ratio of time steps from one level to the other level, as 2, means that I got a very expressive model that can handle, can recognize things that change very, very quickly in their acceleration, their jerk, and the implicit context sensitivity that gives you. If I didn't do that, I'd have to assume that I coarse grain over long periods of time, and therefore the path is consistent during that time. Now, that sometimes is a useful approximation, and indeed there's a whole industry called switching linear dynamical systems that makes that approximation. And it means you can approximate all the nonlinear, complicated, high-order motions in some evolving pattern or system with a series of linear trajectories that basically go, that intercede between a series of points at which you switch. The problem with that is that the length of the linear trajectories, for us, for example, I'm committed to one path U, so one slice of my B matrix for the next 8 time steps. The problem with this is that you don't know when you deviate from that transition dynamics. So then you get into the game, well, perhaps I could make my scheme reactive. So sometimes I do 3 steps, sometimes I do 8 steps, sometimes I do 1 step, and I have some criteria for saying your predictions about my trajectory have now been met. Please, I'm going to give you the evidence that I'll be pursuing this path. You update your primary level above and tell me what you expect me to do next. So this now speaks to a particular kind of reactive message passing that starts to have implications for the computer science and the sort of the CRD, the CRUD, or as I think we've rehearsed before at the Institute, the original conception behind the actor model in computer science from the 1990s. So it's all about reactive message passing. I will send you a message when you send me. I will return a message to you if you send me a message. And what these renormalizing time models have, and I should say that this also applies in the absence of the spatial renormalization. So any deep temporal model will have this aspect. What that means is that from the point of view of any given level, I will be responding to messages more quickly from my subordinates than from my superiors. So once in a while, I'll get a request from a superior. My response to that is to ask my juniors to do a series of things. They report back to me, and when they report, I give them the next bit of request or guidance until they complete their job. And when all my juniors have completed their job, and of course in the renormalizing, spatial renormalizing context, I'll have a whole group of juniors to worry about. Then I have gathered enough evidence for me to then return the message to my superior. So you get in terms of the reactive message passing in this sort of actor model of computer message passing, you get the separation of temporal scales inherits from the number of messages or requests and responses exchange with the people lower down in the hierarchy relative to the number immediately subordinate. And in principle, they don't have to be fixed. So there could be a criteria before I pass the message back up to the higher level. I think that's, Daniel, probably what you were getting at. I'm not. There may be somebody who's done that, but I haven't done that, and I don't know. I can't give you an example of somebody who has done that. You may find somebody in Bert de Vries's group who are sort of some of the world experts in reactive message passing who have considered these kinds of things. You know, in principle, there should be a way of each level testing whether I have fulfilled the predictions of my superiors, and now it's time to get more guidance, based upon the free energy.
Awesome. The organizational technology I didn't know that my PhD needed. Okay, I'll ask a question as we get close to the end, and this will be for anyone. ML Dawn wrote, how does the training time of active inference compare to that of reinforcement learning, and how does their scalability compare? And it would be interesting just to hear anyone's very 2024 takes. Where are we at with that entire arc from problem conceptualization on through the training and the inference? How do we even grapple and describe with similarities and differences in the training time and resources and all of this?
That's definitely Lance for at least 5 minutes, I think.
I'm a bit incapacitated in terms of talking. I think this is actually a good question for Arun. But yeah, I mean, I can say a few things. So scalability in active inference, I would say it has been a challenge, and there has been much less man work hours that have been put into that than in reinforcement learning. Now, for the past few years, we've had a lot of work, a lot of it led by Karl, actually, trying to scale the structured learning in active inference. And I think we've done a lot of mileage on that. So there's been the supervised structured learning paper, there's this paper. There was also some interesting work presented at the International Workshop on Active Inference. I personally think there are still some challenges ahead, and I think one of them is the one that we just talked a few questions ago about. If you learn an expert orbit, how do you get back on the orbit as the dimensionality of the system increases? So this is definitely one challenge. Now I know much less about reinforcement learning, so maybe Arun has more things to say there. But what I will say is a lot of reinforcement learning is powered by deep neural networks. When we use deep neural networks, we sacrifice the interpretability of our generative model. So this is one of the strengths of active inference, is having more interpretable dynamic causal models where we can actually peer into them and see, okay, well, this representation encodes this other one encodes that, and so forth. The fact, though, that reinforcement learning typically uses deep neural networks means that it has been much more scalable, just because there has been so much work done in training deep neural networks. So this is a bit of my my perspective. I don't think it fully answers the question, though.
I can come in with a little bit on that, but I must admit that I have not trained any reinforcement learning agents myself. I have worked with people who have. I'd agree, Lance, that the infrastructure generally is much more advanced for training RL agents for doing stuff, and completely agree with, as you say, the explainability and the interpretability of why did an RL agent pick a particular action is very opaque. And I think the deeper those networks become, the harder it is to understand what's going on in the hidden layers and generally why they do what they do. I think with active inference, yes, we do have more explainability, but I do wonder if we go the fast structure learning approach, think Karl had a particular comment earlier about looking at the highest level, identifying the desirable states learned by the agent. From what I understand, that identification has to be done by a human. They have to look at the model that's been learned by this renormalization approach, look at those top levels, and then say, what do these levels mean? So an example in the paper is the MNIST classification. It's the case of a human being looking at those top levels and going, these top levels each correspond to a digit in the handwriting task. So we are sacrificing some explainability, I think, by doing this fast structure learning compared to what might be the old-fashioned way of creating generative models by hand, by thinking, sitting in my armchair and thinking, this is how I might model the world, these structures, these likelihoods, these states. And when you do that, I think just by hand, you have 100% explainability. That model just might not perform very well. So I think there's always going to be that tension there. But in terms of how quickly these things learn, having not trained either, I'd be having a reckon. And at the moment, I would say probably an RG active inference agent would train faster, simply because it's able to use the structure in the data much more effectively. That would be my take. And I think as well, really interesting thinking about the active data selection part of this too. I know that there is some stuff in the paper about the efficiency being both a curse and a burden, but I'll hand over to Lance and Karl to give more details on that.
Yeah, Lance?
Yeah, just to echo what Arun said. Also, so the structured learning in active inference and in reinforcement learning is also very different. In reinforcement learning, we typically have a model with deep neural networks that's massively over parameterized, but it has some fixed representational capacity from the outset because the structure of that model will be specified. And then typically the model will learn, and then probably you would prune it using some techniques like dropout or other things. If we looked at that from the perspective of active inference, it would be like specifying a massively over-parameterized model and then pruning it with Bayesian model reduction. But now in active inference, we have this Bayesian model expansion, for example, in this paper. And what this Bayesian model expansion does is it learns from the get-go the minimal model for explaining the data. And so in that sense, it's extremely efficient. And also provably because it extremizes the marginal likelihood or the mutual information.
Yeah, I just wanted to echo that last point. That's a really important point. So Lance is drawing the distinction, and there are many distinctions you can draw with deep RL and deep active inference, read in a more in its generic sense, and that distinction at the level of structure learning or model selection, I think, is absolutely crucial. So, deep RL starts with an overly expressive model with a known functional form that is deliberately over-parameterized and then shrinks it or reduces it to maximize the mutual information, the expected free energy. Sometimes they refer to as a cross entropy in machine learning. So the reward function now becomes there's no explicit reward in unsupervised learning. It's just replaced by the mutual information or the cross entropy, which should be distinguished between supervised reinforcement learning, such as digit classification, for example. Whereas the active inference under fast structure learning is exactly as Lance says. It starts from nothing and stops when it's minimally complex, which means it's maximally efficient, and that efficiency translates in many guises through to sample efficiency, through to statistical efficiency, through to thermodynamic efficiency, And this matters because from the point of view of climate change, this is the right way to do it, as opposed to building power stations to power large language models and transformers that need big data. So the efficiency on all levels, whether it's the sample efficiency or using the right data, or whether it's right through to how much electricity do you need to actually train your model, and how many millions of dollars do you need to train a foundation model, all of these are reflections of the failure of machine learning to write in the efficiency into the ultimate objective function, which, as Lance said, is just the marginal likelihood or the evidence for this model of this kind of content or world.
Awesome. Okay, final question, and a very apt one as we head into the rest of the symposium. So just give any short thoughts. Tintin wrote, "Hi all, thanks for the incredible event. Does the sequence in which the training data is fed to the AI structure learning model impact what the resulting learned structure would be?" So the learning curriculum, aka symposium program challenge.
Well, the answer is yes. Sorry, I'm mindful that Lance is recovering from his jaw surgery. Yeah, absolutely. And this is again just in relation to the last question, something I think that it eludes conventional RL. Certainly, that it rests upon classification procedures, because the active inference as an application of the free energy principle is all about the dynamics of self-organization. And dynamics means time, and time means sequence matters. So inevitably, at some level, the order in which you see things is absolutely crucial for getting the right kind of generative model. That is even in the case actually of static image recognition, because you're assuming that there's no ordinal structure or correlation structure to the presentation, say, of MNIST digits. You're assuming that they are selected at random, as opposed to seeing all the tens and then all the ones and then all the sevens. So even in these edge cases, which are the focus of 20th century RL, static image classification, for example. Order does matter, but it matters absolutely acutely, because, of course, the order in which you see content in this in fast structure learning determines how you populate the transition tensors. And it's the transition tensors that enable the separation of temporal scales, that enables the ability to encode narratives and plans that far transcend the actual rate at which you sample the environment. You could also argue that this issue has emerged in a strange kind of guise in transformer models. So the attention heads operate on the past. So the where you select from the past in terms of which token is going to predict the next token most efficiently, again, is exquisitely dependent upon and sensitive to the order in which you train these models. So, Daniel, have you thought carefully about your ordinal approach to the?
I let the
What's
structure
coming next?
I let the structure of the niche and others' constraints provide the first pass and make requests from there. So, thank you, Karl. Thank you, Lance, for joining again. Thank you, Arun, for all the contributions with the .0. Karl, great to see you. So, next up, we'll take a 30-second break, and we'll be back with Michael Lennon. So, thanks, fellows. See you soon. Okay, welcome back from that brief break. We're here with Michael Lennon, and the session is Co-inferencing organizational symbiosis. So, Michael, thank you for joining. Take it away.
Hello, yes. I am so grateful to be here. I would like to approach today's conversation in a conversational style where I share what led me to active inference and how the discovery of the principles of free energy principle and active inference changed how I understood as a practitioner, and how that has led both personal, professional, and organizational shifts in conversations, one of which will conclude in an invitation to this community to experiment with an organizational structure designed for building both the global knowledge commons as well as building individual ventures. So similar to the way in which, for example, Linux is open source, and then you have ventures building off of Linux to do things in the world that experimenting with such an organizational model for the active inference commons is an experiment worth taking on. So I don't want to let the final invite get away, but I'm going to backtrack and do this very much in a storytelling fashion. So I have some slides, but I'm not going to spend too much time. Well, in fact, let me just skip that. Just to recap what this conversation is about is different ways in which not just active inference, but science has collided with internal intuition and led to transformational journeys of different kinds. And so I would describe I started out as an individual, as a economist, and as a technologist working at institutions such as the World Bank and IBM, and doing large-scale IT implementation projects. And that work often, although there was a lot of engineering, it was often the human factors that got in the way of success or failure. And so that has been a kind of orienting how to both be informed by what the science and the math provides, and then build how does the biologically based, if you will, a way of sense making affect or alter the evolution of successful project implementation. So just a little bit about where this project, prior to coming to active inference, well, I say project, my journey led me through was I had, as I said, been trained as an economist. And one of the things that economists have is a point of view about what it means to grow the culture, to grow the society, and primarily denominated in dollars, and using GDP as a way of tracking whether or not one was impacting the experience of flourishing. And I came across a chart by an economist that showed that GDP had tripled in the last 60 years, both in the UK and the US, and that well-being had not changed at all. And this economist, who had been in office in the UK at the time when he left office, was kicked out. He went back to academia and started looking into what does science show moves the needle of well-being, and how do we make this socially more contagious? And I both loved the idea, but I also was shocked by that information, because as someone who was trained in a particular lens, a particular perspective, what I had been trained to do and how to cause effect and impact was in fact not moving the needle of well-being. And so there was this kind of personal and professional crisis that arose from this knowledge. And as I say, that led to this journey of unlearning in some ways, and in both personal, interpersonal, and organizational ways, recalibrating the experience of what does it mean to pay attention to thriving. And so that journey has been very satisfying. Not only do I understand how I need to be to experience more goosebumps in my life, I understand how I need to be to experience connection and belonging, and to co-create with others a sense of purpose and of meaning that I had not had previously. And it's one of the ways I sometimes describe this relationship between the subjective internal experience and the scientifically objective, let's call it, was that I might know how to go to the gym and flex my arms to get a workout, but by understanding anatomy, I could learn the bicep had a particular placement in the body, a particular arrangement, and I still had to do the workout, but I could more effectively and skillfully do the work that needed to be done of working out. And so similarly, the study of the science of well-being and social sciences of connections of groups and of how, for example, one of the surprising findings for me in the realm of happiness was a finding by an epidemiologist, and basically he was studying how do emotions spread, and he, in studying this, realized that your happiness was not only more heavily influenced by the people that you're surrounded by, but also by the next degree of separation, the people to whom they are connected, and even the third degree of separation. And so that these three degrees of separation predicted your happiness more than the way that I had been explained what happiness was, which was that it is an inalienable right, like life and liberty, the pursuit of happiness, and that it's subject to individual traits of my own, that if I just do me the best I can, that I'm going to be happier. And so all of a sudden there's this disorienting insight in that it's not about being my best, but it's just as important to be my best. And so it's like, well, what the heck does that mean? What does it look like to inhabit one's own experience and one's own skin in a completely different way? And I know a conversation that you and I, Daniel, once had about the impact of active inference. You were describing how you might have been driving on the right-hand side of the road your whole life, and that all of a sudden you go to a place where everybody drives on the left. And so some intuitions still work exactly as they used to, but others are completely counterintuitive. And so this developing the capacity to go against intuition, against the familiar, is part of what sometimes these new forms of knowledge, there's knowledge that adds to what we know, and then there's knowledge that changes how we understand. And happiness first did that for me intuitively at the personal experiential level, right? At first was like, okay, I am playing the game of my own life inappropriately. How do I begin to be my best instead of be my best? And this is where some subsequent work in working personally and with groups and organizationally led to paying attention to what was happening in a different way. And so as I say, this crisis led to a very fruitful learning journey, and excuse me, I got distracted. Some of this led to writing different ways of describing how to do work. And so, for example, one of the spaces that I've been working in was in government consulting. And in government consulting, top-down is often the way to direct the effectiveness of the organization. You come up with the right strategy, you figure out all the components, and you then execute on the plan. And so, in a sense, if there are two forms of probabilistic prediction, Bayesian being one at the heart of active inference, and another one being Fisher. Fisher is one that says it knows where you need to go, and the way that you relate to surprises and to mistakes and to errors is you correct back to what you felt your original plan was. Whereas Bayesian probability obviously can have similar results, but also can update, instead of reacting to surprise as something to be fixed, it can sometimes be something to be adapted to. And it changes the way that you manage the emergence of differing information from what you originally predicted. And so in the same way that I described that happiness had a disorienting effect on how to practice it, active inference has a similar disorienting effect about how to co-regulate, how to supervise the evolution of differences between what you expect and what you get. And one way in which I describe this to folks is it changes your understanding, or changed my understanding, of how cause and effect works. That as I arrived to active inference, there were a couple of intuitions about how the world operated that active inference helped evolve. The first was that instead of the world being composed of objects that were fixed and stable, that the mathematics of how to explain things was much more of a dynamic verb. And so to look at the world as being not nouns, but verbs, and a way that I describe this for myself when talking to people about it is that instead of seeing myself as a self, a noun, that I'm a being. And so that paying attention to the continuous verbing and the relating to others is a different game. And so the interesting thing about active inference was that there was a mathematics for describing this that related the internal states and the external states through mathematics of information. That the way in which science works is familiar and intuitive to many of us. Let me rephrase this in a different way. That when I say the inside and the outside are informationally connected, that the outside is all the information, all the stimulus of the world, and that the inside creates a map of that world, and that the mathematics of creating that map not only reduce the world and is a mathematically efficient way of describing how to get the most signal for all the information that's being received, but that it also it also enables, like I was describing earlier with the understanding of the bicep, a more accurate way of sensing the world, of orienting to the world, and of responding to the world. I should have shared my slides instead of trying to talk through them, but I'm going to take a pause and ask any questions, or shall I proceed?
Yeah. I'll ask one question and then looking forward to slides. DSK wrote, there has been a lot of talk around GDP not being a good enough metric of national development. Has your research informed you on a better metric? If so, does it have a working name?
So yes, and it's a different answer than a single metric. So a single metric was one of the problems, and the fact that it was denominated in currency was one of the problems. So one of the things that has shifted some of the work of the UN, of really a group led by Bill Bowie and Ralph Thurm on what are called contextual indicators, are that instead of an indicator being GDP is both currency, and it's set to a single, the denominator and the nominator of the indicator are both set in the same thing. So let me describe this in a different way. There has been a diversification of what are the things to pay attention to. So not only dollars, but also subjective experience of well-being. For example, better predicts the outcome of elections than does financial income. And so the idea that dollars are predictive, accurately predictive of outcomes has been often relied upon and turns out to be maladapted, right? And so that's whether you're talking about biological phenomena, whether you're talking about social phenomena, there's a whole range of extra indicators that are now seen as not a single one, but better visibility into these different nested levels of life. The second, what I would call breakthrough type of indicator beyond GDP that I was describing, denominator and not numerator, is that most organizational reporting, for example, is Starbucks might say, we are using 10,000 gallons less of water than we did last year. So we are improving our consumption and the way that we are related to the watershed that we might be related to. And all that reporting is, if you will, individual centric. And when you center your, just like as with happiness, where if you're just looking at the individual, you're missing an important part of the picture. When measuring your relationship to resources, to commons, to natural commons and social commons, if you put your individual behavior within the context of the collective, so let's say Starbucks says we used 10,000 gallons last year out of the total watershed, then you can begin to draw comparisons about how everybody is using the watershed as a whole, and how the percentage behavior of usage of the water has shifted that can be compared from one to the next to the next. So if you will, you're putting these indicators in a similar language, in a similar, they're speaking in a similar base than when they are reported individually. And so, when looking at well-being, it's important not only to add additional things beyond money, but it's also important that these indicators be set to the same denominator, or you wind up not having the visibility that you need. And there's a huge catfight about this, because there have been a whole series of privileges and a whole series of social practices that are grounded in the way in which individual corporations are structured. And so this kind of points to a different kind of natural mean that I wanted to bring up that might be of interest. So we talked about how with happiness, we're doing it individually and that we're missing the relational. When you look at cells that are part of an organism, if they are traumatized, they become more individualistic. They consume more, they reproduce more, and they grow into what we call a cancer because their, if you will, relationality is traumatized and they become more and more selfish. And so there's both a huge importance of paying attention to relationality at the level of the cell, at the level of the individual human, and some would say at the level of clusters of humans, such as organizations. And that with cancer, part of the new form of treatment has been to call the cells informationally back into relation. So instead of punitive burning those cells and killing them, it's to remind them of their relatedness, to restore them from a traumatized state back into relationship with other cells. And they begin to behave again in better relation to the body around them. And so that metaphor speaks to the importance of how do we call each other back into relation if the language of individualism is permeating both our individual behavior and the language of corporations is equally traumatized, because originally when corporations were first formed in the 1600s in the Netherlands, they were really people coming together to venture and do together what they could not do alone. So trading with the Far East was something that no individual business owner could afford to venture, but by pooling their funds, they were able to do, and they were able to become a great trading power globally. This model of groups behaving as groups, so a different cluster of existence, groups, and then behaving pro-socially with each other, is what grew the next level of economic performance and economic effectiveness. However, over time, some would say that organizations have become traumatized and have become disconnected both from the places where they originated as well as from all the stakeholders that they were serving. And so, for example, here in the US, when the Supreme Court last century, 2 centuries ago now almost, decided that financial stakeholders were the foremost important stakeholders in corporations, they distorted the relationality of corporations. And so it has become a kind of cancer that has become extractivist both upon its employees, upon the ecosystems in which it inhabits by architecture. So there are plenty of people that will tell you in an organization, we want to be more attentive to these other considerations beyond finance, but we don't even have permission because the agreements of the corporation have evolved from mutualism to selfishness, if you will, to more consumerism, more productivity, more surplus, and those all have a place. They're important, but they've become like the cells in the body that become cancerous. They've become overly they become individually oriented alone and not sufficiently skillful at mutualism. And so this all comes back to a new basis for equipping organizations to pay attention to how they're interrelating within, between, and to things beyond their current purview. And it is as much of a disorienting and challenging bit of information as I was sharing the idea of learning how to be more skillful at happiness was to me personally. It's like, oh, I have to pay more attention to you for us to be happier, or to be the third degree of separation, as I was describing earlier, means that not only the people to whom I'm directly connected, but that it's my Dunbar number, the Dunbar number being presumably the 150 to the 250 people that you have meaningful relationships in your life, the Dunbar cubed. So it's beyond your direct sensory observation. And it's like, how do you co-harmonize across groups? How do you sing, to use a different kind of language, songs in common to which you're co-oriented? And these are some of the things that active inference provides a mathematics for how this works, that is fascinating, of how the synchronization of the individual to the group and the nesting and how the signaling happens across the nested groups. And so it's fascinating. The mathematics can be daunting, but the promise of it and the ability to do these things more skillfully and reliably is just, it gives me goosebumps. It gives me goosebumps. And this is part of why I'm trying to tell this somewhat ineffectively, I would say today, in a story manner and through experience, so that people can pull on the intuitions that they have, the memories that they have, and say, I dare to tackle this uncertainty, building upon these intuitions and feelings that I have, and co-experimenting with others forward. And so this is at the heart of what the original invitation that I mentioned was about, was, that instead of the classic hierarchical corporation that has as part of its founding documents, when you plant a seed and you use the template that says we are organizing according to these rules, even if you want to change, it's like, it's a lot harder to change the Constitution than it is some minor policy in a back office in some app that you might be writing the code for, and similarly, it's important to incubate organisms that have the relationality, the mutualism, and the holistic perspective codified into, and the interhiving codified into how they behave individually, interclustering, and then in relation to the commons that they might serve. And so before I take a turn into the case for the experiment that I was hoping to invite people to do together, any more questions popping up?
Sure, I can ask some short questions, then slides and invitation. Okay. Lightning round. Okay, Arun asked, isn't there a cyclic dependency of economic factors and happiness? For example, high inflation made everyone sad over 2024.
So there are time lag factors that impact how the economy operates and how individuals operate, and these are not necessarily in sync. One of the things that I found from the science of happiness was more effective ways to carry the suffering. And so some have that this change that just happened politically, for example, is a bad thing. Often when things break open, there are whole new realms of possibility to be had. And so happiness is not just about having all positive emotions. It's about well-being is the word actually I should be using, is about absorbing all of the signal that the universe is giving, all that's coming in, and then optimizing within that. And so the breaking down can also be a breaking open for what there is to become. And so that is not to say that there is a lack of struggle or pain or friction. One of the great intuitions for me that arose from studying people explaining active inference was how things emerge. And the person explaining it was using water, and they were describing still water as being the way in which current conventions of how things got done and how people calculate it. So if you're in still water, if you're in a lake and you're trying to get across, the way you row your boat or the way you swim is all set by the conditions of the water. In flowing water, even though that same water has the same physical properties as still water, it weighs the same, no matter whether it's moving or not. When the friction of the water over rocks creates new dynamics that emerge, it creates whirlpools, right? And that those structures that persist, the creation of order out of disorder, allow for the emergence of also other meta patterns that are, again, described by informational mathematics rather than the physics of the water itself. And this is again trying to get at what is so hard to intuit. It's like, whether it's a single whirlpool coming into existing or whirlpools interwhirlpooling into greater movements, that these frictions are also creative. And so to really be willing to settle into what you were calling the cyclical disconnect and asymmetry, as something that is a signal also that can be driving learning, driving better calibration, can be driving new learning, because at the heart of all of active inference is a mathematics of continuous learning. Yes.
I love that, and just flows like water with our previous sessions. Okay, next question, and then back into the flow we go. Social Design Studio wrote, so curious about the transition away from individualistic and mechanical into collective and organic. Where's the most levered locality to start?
Well, that's a great question. And here's a way in which I would answer this. In the world of project evaluation, so there's a point of view in the world of systems thinking. There's a certain order of what are the, Donella Meadows is well known for the way in which she created this categorization of ways to intervene in a system. And in the world of evaluating projects and programs, complex projects and programs over time, there's been some meta studies done about what are the things that best predict that if the supervision is done, attending to certain factors, what are the things that seem to produce effective and positive results? Because we're talking about complexity, you could pick 1,000 things, but in this research, they identified 3 things, and I'll add 2. The 3 things that they said, when people look at the following things, they tend to not only manage what they thought they were looking for, but also what emerges. In other words, managing the surprise and the unexpected more effectively. And these 3 things were looking at the interrelationality. Surprise, surprise, right? We're paying attention to the interbeing, and the interbeing across not just the individual or whatever our individual unit of focus was originally, but who are seeing the system more holistically. Second, multi-perspectivity, and the way that I describe this for myself is say looking within, looking between, and looking beyond, having one or more disciplines and perspectives and ways of knowing about those lenses of attention on what is happening. If we look within, we often become a better compass for our own lives. If we look between, we often develop and harness the intelligence that collectively and the insight that we have. And when we look beyond, we often detect patterns that are beyond our collective purview that might break open and enable us to transform in powerful ways. So again, to return to that second point, multi-perspectivity, And I suggest with those three lenses, which is what I call the me to we to all, and it's kind of the label that I'm putting on this invitation I'm going to bring up later, is a good starting point. Is it enough? No, but it's a great starting point. And then thirdly, and here's where it gets messy, and is the non-answer to your original question, is scope definition. Because the moment you pick what are the boundaries, what is my Markov blanket? What are the boundaries of the map that I'm going to use as my lens? You begin to abstract everything else into what fits in that lens. So if you say we're going to have this conversation in English, the way that everything we describe will be denominated mostly in nouns instead of in verbs, and with concepts that exist in English but don't exist in other languages. And so the attending to what are the boundaries that we will use to focus is a gigantic mechanism for seeing how you're holding your attention. And so again, it's not a fixed answer, but it's a way of attending to perception. Again, repeating: relationships, diversity of perspectives, and scope definition. The other two that I like to add in that were not part of that research. So that research, by the way, was 100 years of developmental evaluation, hundreds of studies, and so it's very robust. And you can go to the bank that's a good place to start building your dashboard, or not the dashboard, your conversations about the dashboard. The other two that I would add, and these in part come from Active Inference and from other systemic places and views, is looking at patterns. How are we, what are we clustering? And looking at flows. What are the core flows? Are we looking at energy? If we're looking at biological systems, are we looking at the water flows? Life organizes around water. So do we understand what are the core flows of information, of energy, whatever, in the system that we are observing? That gives us a key insight into the way in which causality unfolds, and causality organizes itself around, and that it's not the mechanistic geometry that we may have intuited in for the longest time, but that by looking at source, by looking at flow, we develop a better compass for the world.
Thank you. It's awesome, and the live chat is super lit. You'll see it after. In the last 20 minutes, do you want to share your slides and open the invitation letter?
Yes. So let me switch here to share. Share. Are you seeing my screen? Okay. So the invitation was to test a new way of organizing, and Fair Share Commons is a kind of a mutualistic co-op that first originated in the UK and has been endorsed by the financial. I should have written it down here because I can't remember. Like the Finance Trust Accounting Board of the UK. It's spread through many countries of the Commonwealth of the last 15, 20 years, and it's primarily an adapted form of organizational structure that is intended to both cultivate the practice of mutualism within the group. So it's kind of like a co-op in that everybody has power to participate. It's self-governing, and that it attends to the relationality of the founders, the workers, and external, whether they're investors or whether they self-organize. It's really there is a pattern language about forming co-ops, and one can use that pattern language to form these commons, and that these, whether they are to create ventures or to create full businesses, that the pattern language is useful for that effect. And so, as I described earlier, akin to Linux, it's intended to grow the commons, but also to support the application of those commons and build the organizational traits for successful ventures. And what I am hoping to find allies around. These are again suggested, and there are many ways to go about it. But there's certain core agreements that differ from, if you will, the extractivism, and the foundation is relationality, which drives mutualism and symbiosis. The invitation is to constitute one in service of the active inference community for growing both the commons and the capacity to prototype and develop both the experience of mutualism, but also projects. And that there be two starting experiments. The first around prototyping agents for accelerating access to money. So often folks incubating a new project are looking to find funding for that project, find funding for what that project might serve. And often there are people willing to fund those projects. And the idea of writing up what are the sources of different funding, what are the sources of what are the needs that they have that they're looking to fund? How do I discover and engage that funding is an important agent that can be used in common after common after common. And so possibly developing an agent, or there are plenty of methods, but agentifying, if you will, that component as one of the key flows. That in business, the flow of money is an important element to inactivate. And that the second is about finding resources of a different kind, competence and complementarity. And what are the components? Often, for example, the active inference community has a wide diversity of competencies, but it is highly technical. And so to engage with people who have complementary skills, and to support the accelerated discovery of allies, not only based on competencies, but also on other holistic considerations, is the attending to the flow of mutualism. And so those three actions is kind of a starting point, is something that I would like to, I'm already in action on the with other groups and a variety of groups on the constituting the legal structure of a fair sharing commons, and I would like to enroll the active inference community to become an ally with kind of other competencies and other types of mutualistic, eco-minded, socially minded groups to grow the capacity for mutualism. And it's early stage. I literally this is germinating, you could say, and really would like to find allies who, knowing that we don't have all the answers, but that we're willing to grow not just the methods, but the relational soil, is what this is really about. So, yeah, I'll stop there.
Awesome.
Questions?
Exciting. I can ask some questions from live chat, and we can explore just a little bit of a
Shall I leave this on the screen or keep going?
Sure, you can leave it up. I'll ask. Okay. There's a lot of great comments. I'll just start with the direct questions so people can add more in this last 15 minutes. Okay. Yep. Social Design Studio wrote, does the commons use emergent hierarchy so as to accommodate contextual expertise and thus relational power?
So, great question. And there are several definitions of commons, but I'm going to go with Leonardo. She won the Nobel Prize for it, and she basically defined it as it's whatever Markov blanket people choose and then self-organize around. So there are many variations, and in order, she identified 8 principles for common to not just be a nice idea, but to be able to persist sustainably, right? Just to do a little sidebar, she was trying to make a business. The reason she won the Nobel Prize is because in the profession, everybody was explaining most of the economy's activities as either being driven through hierarchies or through marketplaces, the dynamics of those two collective groups. And she said there's a third kind of group, a common, and it has the following properties. And the socially mutualistic side of the world was just in love with her, and this is why she won the Nobel Prize, because she developed not only a body of science and a series of 8 principles that predictably describe those that succeed. These 8 include, a sense of boundaries that they have in common, and whether they decide to self-organize around a fishery, whether they decide to organize around a data commons, around a knowledge commons, that is up for the group to decide. And then the way in which they co-regulate, there were many variations, but basically there was there had to be agreements on where to place shared attention, and as people diverged from the norms, that there were ways to call them back into relationship and to have escalating consequences if people deviated. Now, all of that sounds lovely, but that was not enough either. There had to be the ability to enforce one's boundaries, not only internally, but externally. And so I'll give you an example. I have some First Nation friends with whom I've been meeting every Friday for years to work on decolonizing our minds. And they have a point of view about a piece of land that is their Garden of Eden and sacred, and how it should be used or not be used. And they use all these principles, but they cannot enforce their agreements on other people. And so what they have is a wish list. I mean, I know that's kind of rude, and they'll be very, very pissed to hear me say this, but without the capacity to enforce your boundaries, you don't have a commons. And so this idea of how enforcement happens, and whether that is done in a hierarchical manner or whether that's done by self-organizing, like when in Valencia recently there was a gigantic flash flood. The government did a very poor job for the first week, and the response was done by self-organizing ant behavior of neighbors helping neighbors, coming in, doing whatever they did. And that happens in crisis after crisis after crisis. And so there is a capacity to self-organize, if you will, and get things done. Often what a government structure can do is help prioritize, bring order to what are the most pressing needs, how to discern what will make the biggest difference collectively. And so there is a value to having a coordinating role, but how that emerges or evolves or unfolds is can either be by cultural precedent of what the rules are, or it can emerge through and from the group. So that's my long comment about commons and commoning and how to be in relationship to the common.
Awesome. I'll read a comment from Scott. Even before you mentioned Ostrom, Scott had written, Commons, Eleanor Ostrom, is a co-management regime framing, nicely consistent with active inference in human organizational contexts. See Scott Shackelford et al. At U of Indiana for Awesome's Commons programs. Commons analyses have historically been focused on, quote, asset-based commons. This nicely anticipates commons co-management beyond asset management, i.e. risk management, skills, coordination, etc.
Yep. I should have made the point that one of the things that commons do that the marketplaces and the institutions have not been able to do is, for example, it is financially rational to fish to extinction to deplete the forests because the price just keeps on going up. So the logic of markets is insufficient for sustainability. And this is why organizations that don't have a logic of that friction of considering other factors other than profit maximization will inevitably deplete the resource. And so what she created with this case for commons was that there were sustainable organizations and that these existed both in indigenous, in original peoples' cultures, they exist throughout developed economies, they exist in a variety of places and are unrecognized. And what you're hearing in this invitation is like, let's use commoning. Even though it's unfamiliar, even though it's different, it's actually much more widespread than we ever have experienced. It's like believing that there might be something other than McDonald's. You see McDonald's everywhere, so you think I have to eat burgers, but there are other ways to eat than McDonald's. And not trying to pick a fight with fast food, but
how are we going to carry this forward into 2025 and beyond?
Yes. So the invitation to join a conversation is the beginning. One of the allies is that is both co-incubating other commons and that I wanted to use for if there's energy here is a group called Evolute 6, based in Germany and South Africa and UK. It's a small firm dedicated to incubating and helping commons type organizations grow. It's kind of so trying to both invite the interested to begin joining the conversation, sharpen a vision and an understanding of what it is that we think we can be in action on. What is it how that active inference can be applied to particular problems, the search for funding. There might be a better way. I had to scramble to get something plausible, but as we have conversations, we might very well identify much more important points of intervention. With the question that somebody else was asking earlier, we might decide that there's certain flows and certain dynamics that are in fact a better starting point than what I imagine right now. But the invitation is, come, let's convene and do this in a systematic way and both be transformed individually, interpersonally, and ripple out into the world.
Awesome. Okay, a few more questions while we're still here. Fraser wrote, I'm not sure what this language of trauma means. I'd like to hear this elaborated.
Yes. Excellent. Sorry, I forgot to explain that. So lately in psychology and in organizational psychology, there has become a modified use of the word trauma. And what it refers to is the equivalent of memory in computation. So you can have a traumatic event and be traumatized by it. And then the trauma, as I'm using it, is the memory, the scar that's left either in you or if it's a collective trauma, that has a different property. And I'll describe it in a moment. But when I say it's the memory, the scar is what remains in you, and how you carry that, whether you heal fully or whether it becomes a debilitating dynamic, is when the word trauma can be used to describe it. Collective trauma is, and this is an important distinction because sometimes the same language can create confusion. When I'm acting as an individual cognitive system, all the trauma happens within my body. So I feel something, I fix something, or I have a story about something happening to me. All of that is personal trauma. If I'm part of a hive, the hiving is happening in the signals that we are sending back and forth to each other. And so the language of how we signal and the meaning of what that means is what can become traumatized. And let me give you a simple little example. And And those are called trauma agreements, ways in which you agree to carry the significance, the pain, the feeling about the situation that you're looking at. So my father took me fishing when I was 8 years old for the first time. And we caught a fish with fishing hook, and the fish was flapping and resisting, and I was kind of shocked. I'm like, oh my God, that fish is suffering. My father's like, no, 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 no. You just grab, whack them on the head, knock them out, and they don't feel pain. And in that moment, I entered into a trauma agreement, a different understanding of how to be with what I was observing. And as a group, we would talk about our reality, assuming that shared trauma agreement, that shared way of understanding. That same kind of dynamic, whether it is what it means to be a certain gender, what it means to be an organization that is beneficial to the world. Is it because it makes a profit? Is it because it makes a contribution? There's a whole series of assumed agreements that it's like, oh, we need to surface them, that they're not the truth. They are an agreement into which we stepped, and we're now willing to reevaluate. And this is both the gateway to disorientation, but also transformative adaptation, because it changes what has been a habitual way. When I started considering that maybe animals are still an omnivore, but when I started considering that maybe animals had feelings, I had to start thinking differently about what had been my ordinary eating patterns. And so this is a language for surfacing anti-symbiotic ways of being that we are now developing a pattern and a way of recognizing them and renegotiating them.
Awesome. Great answer. Last question. Music Minded wrote, how does Michael see the future of businesses? Or more simply, do you have exemplar businesses that are commons type in your view?
Yes, there's a whole range of commons businesses. And so even though we're talking here about incubating a new one, in a sense, I believe that the important work is about what I was describing about treating cancer, calling back into relation. And so some of us, and this, if there's interest in this, I've been working with global standard setting groups about how to measure and monitor well-being, and then so there's the sensing it, and then there's how do we digest it? And this was another benefit from active inference was the way of framing the cognitive process, not just think, but sensing, integrating, predicting, responding, adapting, and really helping organizations think about in that cognitive flow, in that collective cognitive flow, how to recalibrate their attention so that they see more of the world with a planetary denominator rather than an organizational denominator. And how do they then more skillfully interrelate with the different factors in which they're engaging?
Perfect. Thank you, Michael. Great presentation. A lot of people appreciated it in the chat. So see you next time. Thank you.
Thank you.
Okay, welcome back, everyone. We are here in part one of the workshop that John Clippinger and our partners at First Principles First are coordinating. So with that, for the next session, please, John, to you, and take it away.
Well, thank you very much. I would like to just to share a deck with the group here, if I could, and provide a sort of an overview of what we'll be talking about in this particular session. Can you see that now? Is this good for you? Okay, great. And we'll be anticipating with Andrew Bashir will be coming on and providing the tutorial, but what I would like to do is, in the first instance of this, is being able to provide an overview of why active inference is important, why active inference agents, this whole perspective that we're taking here, is worth people's attention and paying and being concerned about, and what it has to offer to address some of the limitations of the current AI systems, for example, large language models and some of the agentic architectures that have come out of them. And in that context, what I'm looking at is sort of what is the current state of large language models and agentic and agents. And I think there's a lot of activity that's been talked about, but there is still no mission critical applications yet. There's a lot of exploration. You have people like Salesforce developing little Einsteins that can do various kinds of workflow automation. You have Copilot and Microsoft, but it's not really core critical. Not to say that it won't be, but it is still on the experimental phase. And it's still a black box. We do not know a lot how it works. Hence, you have issues of data provenance. You have a question of how to govern it. And there's a concern about you've invested $1 trillion, but there's an unknown business model coming out. So there's a lot of money that's going into it, but it's not clear that the current framing of AI, as it's now known, is really is going to be viable. And part of the issue here is that and I love this example from the New Yorker, is like who's modeling whom. We're actually putting data into the models. We're training representations and we have that interaction, but there's not necessarily an abstraction that's coming out. So it's kind of this relationship of seeing ourselves, mirroring ourselves, and going into this sort of cycle. And what we have now is a certain hype cycle. So it's around the peak of this is 2023 from the Gartner Group. And it's the generative AI is at the top of the hype cycle, and then it's hard to read this particular graph, but you'll see that principled AI is basically on the early cycle. It's on the early phase of it, but it's not seen as taking very long. Where something like you're going to have AGI is seen as being like 20 years out. It's the top of the hype cycle. I think if we update this. There's now, I think, it's starting to be appreciated that the generative models and the expectations and the kind of problems and the costs associated with them, and then the lack of improvement, the lack of degree of improvement through successive models is starting to show through. So the next generation OpenAI shift strategy is a rate of GPT AI improvement slows. In other words, the new Orion model did not have the level of improvements that they were expecting. I think that is something to take into account. And hence the cost of training and inferencing is extremely high, and with that, the fact that you have this enormous consumption of energy, that Microsoft is going to have to recommission 3 Mile Island and drive one of their own data centers. This shows the impracticality of having to have so much computation in order to have work and make these models work. And I think that this is starting to be recognized within the limitations of large language models and sort of the parametric approach to modeling AI modeling. And I think just to start to step into what we have now, what we're looking at. I mean, I love this is like another cartoon from the New Yorker, and it says to think it all began with letting autocomplete finishing our sentences. And well, autocomplete is a sort of form of Markov chain. So we are having these sort of chains on top of chains, and we've been able to develop some pretty rich representations of human activity text and actually forms of cognition, but there's not an underlying model there. And so what we're looking at, there may be some foundational issues that are coming up in very large language models, and that the fact that it is a black box, it's not explicable, it lacks internal causal models. There's not a way of reducing the complexity. It's sort of a batch processing. There's no real-time updating, and that batch processing we see is extremely expensive, and so we're caught on that issue. It's not agentic. It has no means of a spontaneous adaptation and correction on its own. And it suddenly doesn't know what it doesn't know. And it has no way of representing its completeness of its knowledge and adapting coherently to that. And also I would say it's not derived from really sort of fundamental scientific principles. It's really sort of an engineering phenomenon on a case-by-case basis. Now this is changing. And I think the same issue, if you start to see foundational issues for multi-agent LLMs, in other words, the transition to making agentic architectures where you can create a particular agent that's optimized to do a particular task or role. A lot of the success of that agent is depending on the quality of the prompts of that. And sometimes those prompts are good, sometimes the prompts are bad, but there's not a really principled way of doing that currently. And so they have a very fixed way of and specialized kind of goals. It's sort of a mechanical, it's sort of the instantiation of an industrial model that we see. Now, what we rather than having a sort of biological self-correcting model, it is sort of these fixed static models. Now, what I would say the active inference difference here is that it's really developed from first principles, and I think and I think you're going to see that Andrew's going to go into this much more detail, but it really cuts across different disciplines that themselves have been maturing fairly quickly in the last 2 or 3 decades, and so it is going to, in basic physics, quantum information theory, the whole idea of computational science, biology, and cognitive science, all these are intersecting into creating a new way of looking at what intelligence and life are and how they're interconnected. And it also builds on well-established statistical methods, including Markov blankets, Bayesian belief models, the stuff that work has been done with J.D. Pearl. And basically what you look at active inferencing does, and just sort of highlight, is it codifies a predictive brain thesis that's been nurturing in neuroscience. And so and then that in turn sort of mimics the processes of the scientific method. And so we think about what the method is that you're trying to codify, and I turn to Richard Feynman's comment, well-quoted comment that what I can't create, I can't understand. So there's a new kind of criterion for what it means to have to understand something, is be able to model it, to create a digital twin. If I can recreate something, then I understand what it is, and if I can replicate that behavior, and that's sort of the principles that you find in active inference from the very beginning is how do I create a generative model? How does a living agent have a generative model of itself and its world? And this really owes its work, its origins back to the work that's done with J.D. Pearl on his understanding of causal reasoning and also Markov blankets. What is an autonomous thing? And this is where Karl Friston done his work. How does something maintain its separation from the world in which it is in? And so it is not governed by that things, but maintains its autonomy. And there's a certain kind of topology there that something has certain kinds of internal states, it has external states, observer states, and action states. And there's a lot of deep concepts that's in it. I'm sure Andrew will go into that much more detail. And then what we have is the active inference agents themselves as sentient live things. So you're creating something, and it's very different than, say, a large language model. You're something that has agency, and it has a representation of itself in the context in which it's trying to stay alive. And so it's self-organizing, it's self-healing, it's self-replicating, and it's symbiotic in the sense that it involves complexity, mutual synchrony with other living things in its world, in its niche. So it's a joint niche construction. Hence, sentience is sort of a kind of situational intelligence, an awareness that's grounded in the survival of that particular agent. And the person that's sort of the context of the person who's really behind this is Karl Friston, and my own experience of being someone who was very interested in sort of in artificial intelligence from many years ago, and self-organizing systems of cybernetics. It really hasn't been until the last 5 or 6, maybe 10 years that this has come together in a coherent, not only a coherent theory, but a whole coherent formalism. And to what Karl would call a physics of living things. And he's one of the most cited scientists in the world as a neuroscientist that's done, basically developed a reputation in neuroimaging and inferring the structure from the brain from neuroimaging. And he applied the free energy principle, which we'll go into more discussion to later. And so I love this idea of a trefoil knot. It's sort of like, okay, it is sort of this autocatalytic biotic system. It's really important that it's a living system and it has certain kinds of characteristics that are all intertwined with itself. One cycle synchronizes its extraception, or it's a representation of the external world to minimize uncertainty. The other does it internally. It has to align that with the external world. And then you have another cycle that has expected free energy minimization. It makes predictions about how to change itself in its world. And so what we have here is basically what I think active inference offers is a soundness, a grounding in biology and physics. And so you have a sort of a ground truth of evidence base. Do I make predictions, and do those predictions allow me to act and survive in the world? So it can be explicit, it can be explainable, and we'll talk about this later, but you can have, since it has causal models and language and knowledge graphs, it can explain why it's doing what it's doing. And also it can explain how much it doesn't know. There's degrees of uncertainty associated with it. And there's also the potential self-policing, self-correcting mechanism. And I think this is really important. In other words, you can design a active inference agent to live within certain constraints and bounds, and you can build in certain mechanisms that have for self-governance that cannot be captured. So its actions are within the limits of its design mission and not to generate negative externalities. So I will sort of leave with this one, and then just to quote William Blake, who talks about this in a poetic form as the fractal nature of reality. See the world in a grain of sand, and heaven in a wildflower, and hold infinity in the palm of your hand, and eternity in an hour. This just sort of pulls it together in a more poetic sense. So on this, I would hope to hand off to Andrew. If he's, thank you. Listo.
Great. Yeah, thanks, John. And so, hi everyone, I'm Andrew. Andrew Pache. I'm currently involved with the Active Inference Institute. It's been great partnering with Dr. Clippinger, with the director of the institute. You know, we've been doing some really exciting work lately. And I want to address a lot of the points that John has made, although most of that will come tomorrow when we give some major updates on our biofirm. So today, in the spirit of like an initial workshop and kind of introduction to active inference, I'm actually going to refer back to this tutorial that I gave a couple months ago at an international conference for computational social science, meaning folks who are involved in sociology, economics, a broad range of fields. And the context was applying active inference and a lot of these principles that John is referring to social science research. And I basically make the claim and the argument, this is already being done, so I'm not necessarily providing a bunch of new information, but it's just to kind of extend the dialogue to computational social scientists, like, here's how we can apply active inference to, your particular setting in different ways. So we'll just kind of cover some of of what I went over. And, I apologize if there's any whiplash from how quickly I go through these slides, but we're just going to move a little quickly. So the context, again, of this tutorial that I gave was it was split into 3 parts. It was a 3.5-hour workshop where we started with talking about agent-based modeling, how it's traditionally been done, and then followed by that, something that I would call a cognitive turn in agent-based modeling that's happened over the past couple decades. As there are these kind of calls for, we have the computational resources now. We have an immense amount more of, empirical research and validation of different kinds of principles related to human cognition, coming from neuroscience, neurobiology, cognitive modeling, studies of neuronal dynamics, organisms in their environment, all those the kind of things. So there's a shift to that. And then the most recent, means of trying to establish that in the broader state-of-the-art area is using reinforcement learning agents. So we'll touch on what those are and kind of how that works. And anyone who's kind of been looking at the agentic framework for what's being done today, they'll probably already be familiar with reinforcement learning. And after that, we'll go into active inference and how that kind of bridges together a lot of these different things. And apologies, I want to just mention real quick. You can actually go to this link. The quickest way of following that is just by going to Google, type, my name, Andrew Pache, and then you could type GitHub or IC2S2. In any case, you'll come up to the landing page for this. You'll see links to all previous slides I've made, slides that I'm making for tomorrow. I'm also making a lot of this open access. So there's code that people can, play around with and things like that. So agent-based modeling, this has been done, this goes back to roughly 70s, 80s with a lot of, initial developments of computer technology and being able to realize that, we can simulate people, right? In some loose sense, in some kind of simplistic sense. How can we simulate people? And why would we want to do that? We would want to do that so that we could maybe imagine hypothetical scenarios. Imagine you're designing some kind of policy or want to test a policy and see, if I recreate that in a simulation and have people in the environment where I'm implementing that policy, what happens? What's the collective outcome? What occurs? And so all kinds of fascinating work from Schelling and the traditional way of looking at housing segregation, for example, handling those kinds of problems. Where do people land? How do they settle? In like a residential environment. Even more interesting work later after that, Santa Fe Institute recreating an artificial stock market, where you have agents who are basically interacting with this kind of financial environment where they're looking at stock prices changing. They make choices to, buy or sell, etc., and see how that plays out. Recreation of housing booms and busts. Excuse me, not housing, financial. So this can be applied in many different ways. Point. And so what is agent-based modeling, in its fundamental principles, and how does that relate back to active inference, which we'll get to? Key components of agent-based modeling is that we have agents, kind of the catchword of the day. Traditionally, agents are, they just represent some entity, a living organism. This can be used for biological and zoological studies of trying to understand, how ants or insects interact in environment, or at a broader scale, how humans and entire societies and cultures might interact with their environment. And so what's really important about this with agents, environments, and simulations is that we just kind of run a simulation over a series of time steps. And so we let dynamics play out. And then what is it that composes those dynamics? It's the assumptions we make about agents. What is their behavior? What do we think that they do? How do we program them in this way or in that way? And then also, what are the aspects or characteristics of the environment? And so again, given that a lot of this work was done starting in the 80s going forward with very, we're nearly archaic at this point, forms of like computational resources, it's like things were kept as simple as possible. And there are a variety of guidelines that need to be used to develop agent-based models for running these kinds of simulations. And so some of them, even running up to 2007 here, this is the work of Drs. Laser and Friedman, who are respectively have been involved with Northeastern University and Stanford. They give some guidelines for how to do this. Guideline 1 and 2, in sum, is you need realistic assumptions that you're making about your agents, but not too realistic in the sense that they're too complex. 1, because we don't have computers that are advanced enough to run highly sophisticated complex agents. And then also, if we make too many assumptions, then the situation won't generalize well. You might be making an agent-based model for one very, very particular scenario where it's not adaptable across different real-world circumstances, right? So we need some kind of balance in terms of the complexity of the assumptions we're making and the simplicity of the assumptions we're making. The rest are a bit more plain, which are 1, reproducibility. You should publish your code. You should document it very well. Other researchers should be able to kind of take up the torch and be able to experiment with your code. We at the Active Inference Institute, we're constantly putting out new GitHub repositories and documenting our processes so that other people can come and get involved. So I just, want to mention that there's a big problem in reproducibility in science today, and it's very well known. So just want to touch on that. And the non-triviality, it's like, why do agent-based modeling if it doesn't help us uncover anything? Why not just sit down and have a conversation about, what do we expect to happen? What are our thoughts about what's going to happen? Why, do all of this with setting up these programs and agent-based models and designing them if we can just come up to the same conclusion through speaking? So you want your results to be interesting, and you want to make realistic assumptions that, we can kind of have all these things synthesized together. So I made some points about balancing simplicity and complexity. This is just a representation of, these are common problems in machine learning and deep learning. You go and get, the university education. These are the core components of all of your courses. This isn't specific to active inference. This is like wide-ranging, concern. How do you create a model that is realistic enough to capture and explain the phenomena you're looking at, but simple enough to where it's adaptable to different circumstances. And there's, these are kind of in part, just as Dr. Cloutier referred to Richard Feynman. Just some reminders from famous statistician George E.P. Box. All models are wrong, but some models are useful, right? We're always trying to approximate a reality, and so the question is, how do we come closer to approximating our reality? And so how do we actually, using modern computational resources, using all of these new advances in all these fields, how do we actually make, new forms of what we'll call cognitive agents who exhibit the kind of mental dynamics and social dynamics between them that actually better approximate real human behavior? So I give some definitions, the differences between traditional agent-based models and what agent assumptions are being made. And more often than not, for the sake of simplicity, an agent is pretty one-dimensional. If they observe X, then they do Y. Otherwise, they do Z. These very simple pre-programmed rules. They're not autonomous. They're kind of like, you can think of them as like thermostats or something like that, right? If the temperature is too high, you turn it down. If it's too low, you turn it up. That kind of reactive framework. There's no beliefs about what's going on. There's no internal goals per se, aside from a single homeostat that is, maintain the temperature at what you set. Cognitive agents, however, the expectation for those, this is throughout the recent agent-based modeling literature, is like, how do we achieve cognitive agents who exhibit internal cognitive mechanisms? They exhibit perception, action. They actually learn and update their models. I'll make a point that, as John referenced, in the case of LLMs, which I'll cover much more deeply tomorrow, LLMs do not, it's so expensive to train them, and you typically just train them once, right? And so they don't learn in real time. They're kind of stuck with the knowledge that they have. They have a lot of it, to be fair. They've been trained on, thousands of documents and so on. But that's it. Like, that's what you have, and then we have to figure out how to work with LLMs from there, with cognitive active inference agents, as well as other kinds of cognitive agents. The idea is that they can learn in real time, meaning in the moment, and adjust their expectations and their beliefs to what's actually going on now. And then also planning. So the capacity for being able to infer or guess using evidence that they take in, like what's going to happen in the future, right? And that's immensely important in today's climate, right? That's in part the reason we're doing agent-based modeling, is to attempt to plan, to test things, to come up with our own inference about what's going to happen in the future, and then act in actionable ways to realize our own goals in the future, right? So that's ideally that's what an agent would do and be capable of. And then with this cognitive turn, we're also looking at a broad synthesis of all these fields. As John mentioned, we're looking at things like cybernetics and machine learning. We're looking at physics, information theory. People are starting to. It's great. It's fascinating that so many interdisciplinary conversations can come up, and collaborations between researchers of various backgrounds, because it's like, once we realize what it is we're trying to do here, we can start to pull from maybe principles or relate principles from other fields to this field. What works, what makes sense, what's empirically, what can be validated, and so on. So it's a very rich field right now. And then furthermore, a lot of traditional agent-based modeling has been done using software called NetLogo, which is very specific. It's good if you want to do agent-based modeling, like you just learned this one programming language. There's a GUI, like an interface for using it. It's highly simplistic. It is not integratable with other tools, not integratable with, LLMs, with natural language, all those kinds of things. And it's very narrow. It's good at what it does. With cognitive agents, we would want to be able to pull from all kinds of other resources that are, available, including open source ones. Being able to use APIs, being able to pull in other kinds of real world data, not just purely simulations. So there's just a lot of richness behind this idea of moving to cognitive agents. And then there's some basic, ideas of what makes a cognitive agent. Again, perception. They take in observations and they infer what's going on in the world. And kind of like what we do. My stomach growls and I infer that I'm hungry, for example. It's a very simplistic example. And then agents are generative in the sense that they actually come up with their own plans or choices of what actions to take based upon what they believe, such as I observe my stomach is growling, I infer I'm hungry, I will now choose to go eat food as like an affordance that's available to me in my environment. So this is a new way, in a certain sense, of doing agent-based modeling, where before we were looking at modeling an environment with a bunch of one-dimensional agents, predictable agents on the inside. If they see X, then they do Y, otherwise they do Z. But now we have models in a model, in the sense that we're actually able to internally inspect our agents, right? By having this beliefs-based framework where agents observe real data or information and then infer beliefs about it, we're able to then retroactively look inside the agent and see what its beliefs are, as opposed to these kind of, very difficult to interpret black box models that we find very commonly in deep learning and very, very highly performative, yet very difficult to interpret, like neural networks and architectures like that. With agents, we would want to be able to see in almost like a human sense, like what are their beliefs that they're holding and why are they doing what they're doing. So we need to be able to accomplish that in order to actually realize all the additional benefit of doing this, which is being able to look at, internal cognition. What are agents learning whenever I implement a new policy or something, right? I want to be able to know what's going on with them internally. I want to know the full impact of what it is, this plan I'm considering like actualizing. So to bring it back, how do we address all these traditional criteria? How do we make realistic assumptions? How do we, how do we make our code reproducible? That's an easy one, because it's like, well, we're still coding the whole time. And then, how do we derive useful insights from this? And what are other problems that are going on? Like now that we're getting into cognitive architectures, and we are starting to brush up against the potential of recreating more black box models, right? We need to keep things simple enough. Like how do we navigate all of this? A common problem in social science research in general, but also in data science, machine learning, and those kinds of fields. Reinforcement learning, common issue is how do we handle what's called the explore exploit trade-off? This is famously an issue. If you have an agent who comes up with a suboptimal solution to a problem, let's say an agent who's they're trying to figure something out, they find something that they deem to be good, they get a positive reward signal or positive feedback from that, but it's suboptimal. There's actually a better solution exists. They just don't know about it yet. How do you get an agent to actually be willing to explore? And same thing for humans, right? We don't always stick with the first decent looking option available to us. Sometimes we explore in the sense that we seek better solutions to problems, and this is especially important in something to be addressed in agentic frameworks, where if you're trying to use agents for, say, software application or a use case, like you want them to be able to find better solutions, ideally, at any given moment, especially in a changing context that might call going forward for better solutions. Say agents who are maintaining an environment that's subject to natural disaster or climate change, right? Like that might call for a whole new set of policies or actions that need to be taken, that couldn't be relied upon in the past. So we need agents who seek new information. Unfortunately, in reinforcement learning, that this is still an issue. People are trying to figure out how to kind of manually define what defines exploratory behavior, and it tends to boil down to kind of simple mathematics of defining, like, okay, well, we'll modify these agents so that 90% of the time they go with the best solution they know about, and then 10% of the time they'll just pick something random. That way they're at least exploring 10% of the time. You could put it that way. Active inference, again, I'm sorry, I'm kind of zooming through a lot of this. Recall this is an over 3-hour tutorial. But with active inference agents, this kind of gets naturally resolved in terms of what's called the free energy principle, which we'll be getting into. But basically, the idea is if you're able to have agents who naturally seek information, perhaps align with how we do, right? That when they come up against something, they see, oh, there's value in seeking new information to find even better solutions than the ones I already have, and being able to do that in a way that isn't some kind of ad hoc rule of the 90% versus 10%, as I mentioned. That's kind of a key component, a key consideration in designing agents. So this brings us to the active inference, which I describe here as a framework for doing agent-based modeling. It begins with the free energy principle. I'll make a lot of mentions to this nice textbook that Thomas Parr, Karl Friston, and their other co-authors published a couple of years ago. But there perhaps even some more updates to be made because it's such a lively field. But that textbook really lays out a lot of the core principles and ways of getting started with active inference. The free energy principle: everything that changes in the brain must minimize free energy. Now, despite all of this interdisciplinary communication, dialogue between, again, cybernetics with psychology, with behavioral economics, that actually sounds quite simple, right? To be able to boil everything down to, oh, we have a brain, it's trying to minimize free energy. That almost sounds simple enough to where we might be able to employ that as a kind of simple assumption that we made in agent-based modeling. It's quantifiable. It's a presumed is the wrong word, but something like a principle that can be applied in any given circumstance whenever we're looking at these organisms who are self-organizing, such as humans, such as living organisms, such as plants in an environment that's being taken care of. that they exhibit this kind of characteristic of minimizing free energy as a form of quantifiable uncertainty. So we'll touch back on that again in a moment. But what active inference provides is a kind of normative, holistic framework for what I argue should be applied to agent-based modeling. It itself addresses agent-based modeling. That phrase is used in the textbook. This is not a foreign, out of left field kind of invasion of active inference into agent-based modeling. They're proposing there's so much overlap, and I think it's just an underutilized connection that's already been made, right? Active inference is based in it provides neural process theories, meaning that we're not just assuming in the same way with agent-based modeling, we might assume, all people are utility maximizers. In this case, we're not just assuming it. We're looking at neuronal dynamics. We're looking at decades of research into using neuroimaging studies and looking at how does the brain really function? How does it handle uncertainty? Different kinds of behavioral studies and tasks where you can record fMRI or EEG along the way and look at the dynamics of those of that data that's being collected along the way, and then from there we can start to kind of model how that works. So as I already mentioned, we're still looking at a kind of belief-based framework, which is to say, we're looking at for agents who have beliefs and they update their beliefs, and they do that by way of the free energy principle, which is minimizing uncertainty. We start to see these organisms that we're modeling, humans or otherwise, they start to have naturally emergent adaptive behavior, right? By trying to figure out what's going on in your environment and then adapting your actions in order to better understand it, to better realize your own goals. You're effectively minimizing your uncertainty, and the free energy principle basically is a kind of free energy is like a proxy for that uncertainty that renders a lot of these things computationally tractable, meaning that we're able to quantify it, we're able to record it. Whenever we run agent-based modeling, we're able to actually look on a chart and a graph how much of free energy is being reduced over time, and look at the agent's internal beliefs about, what is it that they're figuring out within their environment over the course of the simulation. The view from this perspective is that another aspect, I already addressed the exploration-exploitation balance and trade-off. Self-evidencing. This means that agents, in order to minimize their uncertainty, one way that they can do that is to try and act to realize their goals. There's something they want, something that they expect, right? And so it's as if you have this prior set of beliefs of what you want to see in reality. This is the this is the kind of framework that active inference deals with, but also referring back to Judea Pearl, as Clippinger mentioned. This is a kind of Bayesian idea. This is rooted in something like Bayesian statistics or even mechanics, where the idea is that you have your prior knowledge, you bring it to the situation, and then that will impact how you update your beliefs based on new information, right? So we're not always starting from some blank state, some starting from scratch. We're always coming to a situation with what we thought before, and then that gets updated. How does that get updated from active inference? That standpoint is through free energy principle. So, I made some points in this tutorial because I realized we're really, I want to make sure we have time to kind of bring this back. But with active inference, that we already have so many aspects of reinforcement learning and active inference which overlap. We're trying to create cognitive models. Active inference, I don't want to say it's necessarily competing. I don't know if that's the right word, but it's making advances that reinforcement learning is trying to make itself. And with active inference, it's like, well, with active inference, we're actually basing this on, a variety of principles, that, again, sorry, zooming through, we're able to cognitively model, what's going on in the mind in various ways, that reinforcement learning is really lacking today. It's really lacking that. These models are being built to be highly performative, but they're missing the mark whenever it comes to something like realism and basing these reinforcement learnings in something like science that extends beyond just the mathematics of machine learning. Right? We want to be able to find biological, physiological substrates for how all these things happen, right? We want to be able, from there, to be able to apply everyday words and interpretability. So what is it that defines what a habit is? What process is involved whenever a goal is formed and made, and then from there, attempted to be achieved through action? What defines planning? What is prediction? So I just want to see if there's anything else I might be able to touch on. This was a nice, for anyone, and maybe I should have started with this, but this is a little bit more of an intuitive glance. And these are not words from Karl Friston, surprisingly. They're from Sarah Feldman Barrett, who's at Northeastern. She's nearly as reputable as Karl Friston in the neuroscience field, and I just personally, as someone who's also interested in neuroscience and cognition, I find her work fascinating. She's done a lot of work on emotions and kind of affective neuroscience, so it has to do a lot with looking at what's going on inside the mind of especially humans. And so this is kind of trying to provide an intuitive glance at, how can we think about Bayesian frameworks, about inference, about active inference as well. So it's like, this is a long quote from a podcast that she did. Your brain receives sense data from the world, sights and sounds, and smells, and so on. Receives sense data from the body. And so when there's a loud bang or a tug in your chest, your brain receives that information as the outcomes of some set of causes. But what caused that loud bang? What caused that tug in your chest? Your brain actually doesn't know. It only receives the outcomes. It has to guess at what the causes are. This is called an inverse problem. You know what the outcome is. You don't know what the cause is. So your brain has another source of information available to it, and that is past experience, memory. Apologies for just like doing a slideshow karaoke here, but you can read it for yourself, I suppose. But the point is, and with some of this highlighting, it's like we're actually taking account of a variety of things. We're taking account of interoception, meaning observations that arise from within the body, or for an active inference agent, it has to kind of model itself. I mentioned earlier that if I'm hungry, this goes beyond the five senses in that kind of perspective, right? Touch, taste, feel, all of that. With this, it's like, well, I need to understand what's going on within my body. I need to understand what's going on outside of my body, as Clippinger, referred to earlier, the idea of a Markov blanket. It's kind of like, I need to figure out what defines the boundaries between myself and what's around me. On the one hand, I need to have a model of myself in order to maintain it. Otherwise, I succumb to the environment around me, to use some of the language that's used in the textbook. It sounds a little bleak, but we're referring to real world circumstances. If I don't take care of myself, I will naturally decay. Like, that is kind of the sort of the principle. The world is entropy, so to speak, right? It's like, if I don't eat food, I fall apart. So I need to have a model of myself, what's going on within. I need to have a sense of what's going on without. And then I need to be able to kind of synchronize those things in such a way that I can continue to exist as an entity within this environment around me. And that's a very intuitive, perhaps not very well technically described, but for now an intuitive sense of kind of what defines a Markov blanket. So this is a sort of foreshadowing for tomorrow. We'll talk about this really interesting project we're working on called the Biofirm. With Daniel and under guidance of John, in that sense, we're trying to develop homeostatic agents. Homeostatic meaning agents who, their own sense of their survival is predicated on the homeostasis of their environment around them. So we're trying to create agents who actually take care of and attend to the environment around them, as if their own survival depended upon it. This is a very interesting kind of flip, where where you actually want to match and model the environment around you, but also take care of it in a way that you can maintain it within those bounds, just as, you know, I have to eat in order to maintain my energy levels. You know, the agents need to take care of their environment, you know, within some kind of range to where it has, you know, enough caloric energy, so to speak. You know? I think for now, John, is there anything that you think I have not addressed that might be useful to our audience, or if anyone else would like me to touch on anything, maybe something I skipped or otherwise, I'd be happy to speak more.
No, I think you've covered some of the really key points that what I think is what you've done is what differentiates active inference from the more traditional agent-based modeling. I think it's important because when people think about agent-based modeling, they sort of default to what the traditional models are. And I think that you've done an excellent job of sort of highlighting what the difference is and what the having that broader perspective, that more grounded interdisciplinary perspective, you're able to more not only represent the complexity of it, but also provide a way of modeling agents within that complexity. And I think the notion of the homeostatic nature of an agent trying to live in conjunction or really harmony with the world around itself is depending upon its survival and its ability to stay alive and differentiate and have complexity, but the synchrony of the environment is really another key point. Because I think, well, a lot of people, they think, oh, well, you may say like navigating a fitness landscape, you're just trying to optimize different levels, but in fact, the landscape itself is shaped. You're doing joint niche construction, so it's a much more complex notion than traditionally understood in general modeling. And I think in consideration of what we're looking at tomorrow, this whole idea of the mimetic character of modeling and having it based upon principles in biology and nature, and being able to create an economic agent that acts that way, I think is really quite important. And so maybe some people have some questions about that we want to focus on or not, but that's something that I think it's important to highlight.
Yeah, awesome presentation, Andrew. Ernesto, if you have a question, also anyone in the live chat is welcome to ask a question.
No questions. Thank you very much. This is so inspiring.
Well, Ernesto, just to put it in context, I know this is something that you're very interested in this whole idea of a mimetic economic system, and you've been looking at this yourself. So this is really trying to lay down the principles, really the scientific principles and computational principles of doing this, and we'll get in more to that tomorrow. But that's the intent here.
Yeah, a lot more to say. Again, in our remaining 40 minutes, I'm happy to read questions from the live chat. I'm also happy to screen share and look at some of the registered participants' backgrounds and interests.
Sure.
Okay. Okay, you can unshare, Andrew, and I'll pull up some word clouds. All right. Okay. Okay, so let's let it load. Okay, these are word clouds that are generated from the participants' registration information, and we'll zoom in on them, and I'll just kind of mention them, and we'll zoom in, and if anyone has a remark or something that they want to like highlight or call out about it, just go for it. Okay, so this is a word cloud of the 150 or 200 registered presenters overall, asking about what is your personal background. So the biggest, and this is scaled just by number of uses of each term. So one person mentioning a term a ton of times might make it large. So just to be taken as sort of a representative, we see those tiny two letters, AI, which could mean almost anything at this point, and a lot of other terms like computational research systems, neuroscience, cognitive, philosophy, social, academic, robotics, technology, practice. This kind of speaks to the broad range of topics that leads people into joining and at least entering that information on the form. Any thoughts on this, or we'll keep on exploring these word clouds?
Okay.
Okay. All right. Again, just raise your hand or go for it.
Interesting.
Okay.
Well, I'm interested in the notion of community and systems. I mean, applications. The community seems very strong.
Yeah, and that's the center of a later one. So here we asked what would be useful, and by asking what would be useful and what would be interesting, we alluded a little bit to the dual composition of the expected free energy. What would be useful, what would be utility, what would be pragmatic, and then what would be interesting, what would be epistemic. So here in what would be useful, here we are in Applied Active Inference Symposium, wondering about how does active inference go from being a unifying framework for ecosystems of shared intelligences and all these different kinds of things that we've heard already and we're going to hear in the symposium to come. So interesting that systems, a way to operationalize and really move forward from framings of complex adaptive systems to having the implementations and also the community and the people understanding research, models, collaborators, and then a lot of different topics that are being explored in more mainstream computational science fields like multi-agent algorithms. Andrew alluded to that and kind of brought that up in the context of the Goldilocks parameterization question. The agent-based model can be so simple, it gives you a great intuition. It shows at a demonstration layer how simple behavior can lead to complex outputs. On the other hand, the agent-based modeling can go the other extreme where it's so sophisticated, then it loses its transferability. So that's what people would find useful. And then here's what they put for what they would find interesting.
Mm-hmm.
Applications make sense, as that's what this symposium is all about. And again, a lot of other ideas thinking about different specific systems, research ideas, architectures, synergies, toolkits, insights, implementations, support, collective directions. Here's asking, what would help you in your learning and applying active inference? And community looms large. Other people, as well as some of the more tool, resource, textbook, education, examples, frameworks, interactive tutorials, different languages, Python. What does anyone think about this?
I'm a little surprised that we're not seeing the phrase LLM anywhere. I just kind of noticed that. It's one of the points that I have been trying to work out and I hope to speak more on tomorrow is you know, integrating active inference with LLMs, and there have been attempts to do this, and even with Friston and Parr and other folks, there's been attempts at trying to pull out an agent's beliefs and then use an LLM to process those beliefs, like kind of decode them and re-encode them in natural language, so to speak. It's as if the agent is speaking and saying what it thinks and believes, and why it did what it did is, another layer of interpretability. And I don't know, I'm slightly surprised to not see LLMs anymore. Maybe it's a little too, maybe that's a little too on the frontier right now. I know it is in many other areas, and it's, sorry, in the couple minutes we have, I just, something that I've been working on personally, and this is feeding into the bio firm, is how do we use LLMs in a way that we can actually integrate them with all these major priorities that we have, where we want to have agents who actually have defined goals, right, and ways of trying to stay alive, in a way that they interact with their environment in a way that it's as if their own survival depends upon it. We don't want LLMs, which, again, I'm just saying this quickly, I don't mean to sound disparaging, but LLMs in one sense can act as like functionally as talking heads, where you just send in some text and they try to predict what would be the best text in response. They're still subject to hallucination, to confabulate, making things up, so to speak, even though the answer looks structurally sound, and so my point is that rather than viewing LLMs as agents, I don't think they are. I think that you could have an active inference agent who is augmented with the capacity for natural language by having it interact with an LLM. Right. So
yeah,
sorry to
Yeah,
go so deep into
this
a
is
precursor of my own talking, but yeah,
scanning across all the registration fields for LLM mentions. So, how does active inference apply to the design of LLM systems? AI outside of LLMs, better ways of designing internet scale protocols and governance systems, and should converge with tiny ML to challenge LLM's deep learning. So it is interesting that it's referenced with only a glancing blow, and we've even seen earlier, like in the responses to similarities and differences with reinforcement learning with Friston earlier, about the increased amount of attention and tool development and the later and more professional maturity of training environments. And this is like one of the key foci for the open source active inference ecosystem and for the Institute, is to develop those kinds of methods and trainings and all onboardings, all these different aspects of increasing the professionalization. So let's look at the challenges. So this was, what are the challenges facing your learning and applying active inference? People, interesting. The problem and the solution. Models, the math, software, maths again, mathematical understanding, difficult physics, scaling, simple examples.
It's interesting, because in the larger conversation about what AI is, I mean, it's that conversation is so dominated by large language models and quote generative models within large language models, and well, at least I've been observing, and I tried to refer to my initial slides, is that they're starting to appreciate the limitations of the large language models, move towards more agentic models and more towards causal models, and hence creating agentic architectures that do work with large language models. But they're still they're still not based upon biological principles that we're discussing in active inference. There's sort of more of the mechanical models being applied over it. And I think to me, from a point of view of sort of the sociology of science, there seem to be these different worlds that I mean, the number of people that I've known sort of in the open AI world, they're very unaware of active inference, and some of the critiques that are, if you listen to the Gary Marcus, he's got a very pointed critique of large language models and not being able to achieve abstractions, but that doesn't extend to appreciating what the opportunities are in active inference. And so there's sort of these islands of understanding that they still exist. And I think that's one of the challenges. And when you talk about developing an infrastructure, I mean, there's huge financial resources that are going into the large language models infrastructure. And where I think that totally biased on this, I think all the opportunity is totally within the active inference of free energy principle, and I think that's where the science is going, and yet it's sort of in this isolate world, and I think the only way to get out of that is start to really start to show the applications and showing with results, and because but it's interesting. I mean, to say that they're different worlds. But I think that there's a peaking, and so the hype curve around the large language models, and they're going to descend. My bet is they're going to descend into a valley of doubt, and you're going to see that showing up in NVIDIA stock going down, and then people are saying you can't destroy all the natural resources or run these models. You don't have to, the other thing, and Karl alluded to this in his earlier comments today, I mean, he was talking about climate change and models and compression. And I think that's going to be a driver of this. But that's some my observations on these clouds is, yeah.
I'll bring in a question from the live chat. Also, welcome, Mao. Just thought I'd bring you on if you wanted to participate in this panel or just chill. So, Stephen Sillett wrote, is the lack of LLMs mentioned because large language models are different to dynamic agent belief modeling?
And do you want to take that?
Yeah. Could you repeat that? Question.
Is the lack of LLMs in the word clouds here, but just more generally thinking about similarities and differences between active inference generative models and LLMs, is that because large language models are different than dynamic agent or belief modeling?
I don't want to approach this question in the wrong way, but I will say that as far as, whenever it comes to LLMs and dealing with, their internal parameters are obviously highly quantitative, and then they're dealing with natural language as tokens, and then switch back to looking at active inference agents, which, are highly quantitative in nature. And typically, if you're making continuous time models, you're looking at, again, quantitative information. And then even with discrete models, you're looking at, these kind of discrete values that you could potentially move in the direction of trying to, make it. I think this has already been done, but there are agents who, have been used to try and understand, like, we can read individual tokens, then move up to another layer, and then we have entire sentences, and then move up to another layer, we have entire, paragraphs or ideas. That kind of thing is done. But I think this kind of like LLM with quantitative grounded agents, like that connection is still, in my view, that's kind of the frontier of where things are at. And so it's difficult for people to conceive, like, how can we translate, encode, decode, re-encode natural language in a way that's readable by these quantitatively oriented agents, and then vice versa, how do we transition quantitative beliefs into natural language? That's the very thing that I've been looking at, thinking about recently. I made like a active inference, like POMDP agent who, what they do is that they use their beliefs about which action to take, and then that action that they carry out is actually corresponding to a prompt to an LLM. And then you can actually take those beliefs, the quantitative beliefs, find some way of meaningfully interpreting them, and then putting that into these blank spaces in the prompt as if you can have the agent say in real time, I currently believe this with probability this, give me, a solution to this problem, based on that. So being able to find this kind of numeric versus the quantitative and the qualitative, it's a historical problem when working with data that goes back centuries at this point. So it's really exciting though. It's really exciting to think of how to bridge that kind of gap, and I still haven't seen anyone, nail that down. This is the frontier. This is where we're at, and I think that's kind of the next thing for everyone to really be considering, thinking about, working on. And I'll give my view on how that could be done tomorrow. So.
Mal?
Yeah, I mean, effectively, LLMs don't really encode explicit beliefs or really maintain a persistent model of the world. Even when we sort of give them a sort of loop by which we communicate with them, that loop in itself doesn't actually factor into the predictions that it's going to do. So they just lack a framework for recursively updating beliefs, which is probably why it's not being thought of here. But also mainly that, LLM agents are only agents by virtue of sometimes being connected to stuff and having explicitly stated goal, but I don't think that actually qualifies them to be agents.
I totally concur with that. From my perspective, I think that the reason that LLMs are not looking at are not looking at, or that whole mindset is not looking at belief structures in intersubjective experiences, I think is a product of a whole sort of objectivist, reductionist methodology that has been tuned not to look at agentic systems. I mean, in my generation, if you were in biology, you were in and you talked about agentic systems, you were outed. I mean, that was verboten. And I think there's a whole school of thought. There's a whole set of in a Kuhnian sense, a normal science built around a sort of objectivist, reductionist, non-agentic notion, and so it's a new generation that's coming in both in biology and in modeling and cognition. There's recognizing this notion of an agentic perspective of beliefs and updates, and that's a huge shift, I think, in sort of the epistemological perspective of a lot of what has been traditional science.
That's really interesting. There's also just operationally the difference between taking a very large fixed number of parameters in a given model, 70 or 7 or 405, training on existing data, and then finding patterns or eigenmodes or activation summaries that have secondary interpretability. But there's not really an effort of trying to find interpretability at the level of activation of a given neuron. It's about looking at patterns and trying to find collective level interpretabilities, like in the AI interpretability field. Contrast that with designing from the ground up an example agents where the beliefs are explicitly encoded numerically. And so that's a different mode of building, and also one that's hinted at in this 2023 paper with Mahault and others, that highlights that element of explicit semantic interpretability and also explicit semantic interpretability of uncertainty estimates. Whereas a string of tokens emitted by an LLM that says, I'm not sure, it's sure about saying that, but that doesn't mean that it has a given certainty about the referent. So understanding what the communication semantics of LLMs are is incredible in what they do. And I think when we look at this cloud for people's responses, how can active inference make a difference in 2025 where there is LLMs? Here, many kinds of systems, and that's sort of like a microcosm of what the symposium is, different people with different systems of interest, asking how do these different attributes of the model that we're talking about, the first principles grounding, semantic interpretability, surprise and uncertainty, and its bounding as a central component as opposed to reward, how do all those things really play out? What does that demonstration look like in different systems?
Yeah.
Here's another.
Really
Go for it, Andrew.
No, I was just going to say on that previous one you were just looking at, I really appreciate the kind of broad-mindedness that people seem to be exercising. I like seeing terms like symbology, scientist, governance, industry. I mean, those are some I'm very excited to see people who want to, so much work has been put into kind of the theoretical and then sort of like in vitro and in lab and in simulation kind of work that's been put into active inference. So I'm just really excited to see, with the international, the conference, the active inference conference that was given recently, and being able to see like a drone that's flying based upon the free energy principle and things like that. I'm just really excited to see more like kind of real world applications, right? And kind of creating systems and applications for like real world use cases. It's really cool to see some of those terms there.
Yeah, I think that's going to be really critical. See, yeah.
Here's the cloud for how are you applying active inference? Again, systems, I think just reflecting people talking about variety of different systems types, and also reminding me of my own journey to active inference, being excited about complex adaptive systems, however, not really having a software toolkit or a formal way to proceed past, okay, we think about nested multi-agent systems, and then where's the software toolkit? And then we're right back to where Andrew showed us on the slide. It's like, well, we can do a really simple one in NetLogo, or we can engage on this enterprise scale engineering research program. And here's a more incremental, interoperable way to have portfolios of motifs and generative model components and be assembling and scanning across these different kinds of compositions, like 3 ant nestmates in the desert, 3 ant nestmates in the forest, and these different kinds of environments, being able to compose them. And over the last several years, seeing a lot of the advances in the category theory, in the first principles physics surrounding all of these sort of research things. And it's like, that's kind of the water drawing out. And then that's the question about how it looks when it is applied. And that's what I guess we convene around in this symposium and are seeing differently in 2024 than in previous years.
Just curious. So, what's the change that you've seen in previous years versus this year, and then so looking forward, more of an application?
Andrew or Mahault, what do you think? But absolutely, that is, Mal, please.
Yeah, I mean, I feel like the work of Maxwell Ramstad, Casper Haas, I mean, obviously Karl, but a lot of people who perhaps came from more dynamics decided to take a real interest in what we could do with something that was so scale free. And I find that it's been really, really rich in terms of the different kinds of theories we've tried to sort of reformalize. I know that's most of my work is a reformalization of existing social sciences. And to your point, Daniel, the problem we still have is that we're missing like these key little plugs that, yes, you could couch as, you know, just different schemes of message passing, but you still need some interesting tools to have a very good description of the vast variety of types of structures that we have, which social sciences have done a really great job at, if not intuiting, at least describing properly, but we still don't have the best tools to make accurate predictions. And that's part of the reason why most of our polls, when we make them, are nil, they're useless. And that should be the main thing we apply them to, is just literally just understanding where we're at, not even making predictions, just understanding where we're at. And we still fail at that. So I'm very encouraged by seeing this, and I hope that we will start valuing more and more interdisciplinary perspectives that are sometimes more technical, but also sometimes more philosophical or social.
Awesome.
Yep.
Also, while we're in this, in the coming workshops, tomorrow will be more of a bioregional, biofirm focus, and then day 3 will be entirely with Clippinger et al. On this topic, and I wanted to show one really operational open science crossover with LLMs and active inference, which is, and I'll put it in the live chat as well. Here, I used Perplexity, which does an internet search, summarizes and translates information using LLMs. So here, we'll pick on Alexey. There's a profile, a learning plan, and a set of small, medium, and large project proposals about active inference. So this is just summarizing expertise and experience. Here we have a learning plan. It's just a starting position, but this brings a new low bar to the kinds of resources that everyone can take on in their learning and use as like a syllabus or a curriculum, and even as an interactive tutor. It will not get bored with you asking to explain concepts again and again, or using different metaphors, or making it applicable, making it like this poetry format, putting it in this narrative context. And so even asking, how do I start with this, or can you help me understand what I don't know, that puts such a centrality and highlights metacognition in learning. And then the project proposals, each of them structured according to essentially what a grant officer would be looking for, and what a project manager would be thinking about in terms of small, medium, and large projects. So this unprecedented high throughput way to fuse even scanty input from a participant in a inclusive open science setting into real projects that, if enough people think, hey, that looks kind of interesting, then we're well down the road of actually making it happen using different kinds of funding, which is something Michael Lennon mentioned a little bit earlier. So it's sort of like we can get really detailed and technical and architectural thinking and finessing the differences between reinforcement learning, deep learning, active inference. And we saw slides to that, like when Karl showed the action perception loop, similarities and differences. Okay, active inference doesn't have a reward function. It's not optimizing based upon this trained auxiliary reward concept. It's just doing something direct with likelihoods. Like, that is critical. That is what makes the active inference generative models what they are. But then looking at something like this, which wasn't so accessible 1 to several years ago, that just feels like opening up and unleashing what people can do, and about using these as tools in our niche. And I think it's a total open and unknown what happens when you can get to this level of project and learning plan for an arbitrarily complex field with the patience of an AI that's just going to accept questions all day long. Like, that's almost the bigger applications question. Again, just zooming out from how the architectures and the parameters are similar and different to how are we going to do what is authentic and right and best given the tools we have. There's a bigger picture beyond just holding the magnifying glass to different computational artifacts.
That's well said, Daniel. I really agree. It's transformative.
If anyone has questions in the chat or here, or any other things they want to mention.
Yeah.
What's going to happen in the next 2 sessions, John, or what would be your goals or preferences for this arc of the symposium for you?
Yeah. So I think, as Andrew alluded, the session tomorrow is going to be really on the application of active inference agents to a design of a economic agent, a new kind of firm, called biofirm, that's homeostatic. And the objective of that is to develop a new kind of incentive structures, a form of the collective action that are based upon mimetic principles that I think we'll see address a lot of the issues that people are having in the whole idea of bioregional finance and how to deal with climate change and how to create those incentives. So one of the things I'll kick off with, I've been talking to a number of people in the whole fields of regenerative finance, what they call biofi. It ties into the work that was done in Eleanor Ostrom's work on how common pool resource, how do you manage a common pool resource, how do you incentivize people at different scales. I really think that, and once you identify some of the requirements that people are looking for in order to address these problems at scale, and I think what we'll be talking about is to the implementation of active inference principles into an economic agent, that it provides, I think, a reasonable way of addressing these issues, and so that's part of the conversation that we want to have and bring together these two worlds. Then the third session is to really look at this from a broader point of view, is saying, where is this going? And so the people that we have in the panels are very much involved with enterprises, applying it to nonprofits, applying it to certain problems, looking at what they can do with LLMs currently and what the certain current agentic architectures are, and what happens when you go to full autonomy. What does it mean to have autonomy in a biological sense, something keeping alive, and what does it mean to build systems that have autonomy? I mean, this issue of autonomy is sort of fundamental when people think of autonomous cars or decentralized autonomous organizations, or the whole idea of the central bank. The principles behind something like a Bitcoin is like, oh, that is autonomous, but is it really autonomous? What is this new notion of autonomy if we base it on biological principles? And I think that opens the door to a very different set of discussions than we're currently having. And it also opens the door to new notions of governance and how we can build governance in to maintain the homeostatic states. And Andrew's alluding to that. So I mean, that's where I become an optimist. And I'm not an optimist around the extension of LLMs and OpenAI and the tech the tech giants, but I am an optimist in being able to apply these principles to some of the fundamental issues we're having around climate and social equity and economic equity.
Awesome. Okay. In the closing minutes, if anyone has last comments, and David's question too, if you want to address it, Andrew or anyone else. Any thoughts about how we start to develop a multi-scale approach to ethics?
What?
I want to allow time for other people, so I'll briefly say. So tomorrow, we'll present various aspects of the biofirm. There will be a little bit of a redux of some of the things I went through today, just to kind of thread the narrative, and I'll kind of talk about Homo economicus and all these kinds of assumptions about human behavior and things like that. But multi-scale governance. What we're trying to do with our biofirm is to, and Clippinger referred to Elinor Ostrom's work on the commons, and so I'm going to address that a little bit too. But the idea is to be able to have a kind of like adaptable system of multiple agents, and so we have a kind of small society, so to speak, and they're kind of governing the commons around them, and by being able to have something like the capacity for one, shared goals, and two, adaptive learning, such that they can actually adapt what they do and what they believe and the actions they carry out. Have those be localized to the current context, which is an essential part of Ostrom's work. Is it's not so simple to just give a singular top-down instruction that applies in all places. I mean, to be able to have that kind of adaptivity and awareness of the local, while at the same time having agents who are kind of synced up in these various ways. I think that's one way of trying to approach governance. And then from there, you might be able to have kind of layered, you could have individual hubs, and then you could have some kind of interconnecting system between them that extends that to an even broader scale of multiple hubs and interaction between them. So just some breadcrumbs there. Thanks.
Yeah. Mao, and then John with the last word on this session.
Yeah, so I mean, the question of ethics is it's obviously complicated, but the key part about whether we coordinate around multi-scale goal sharing, etc., shared potentials, that's intrinsic to hierarchical active inference, right? It just is. The question that isn't going to be solved is what is good, because you can always say, well, what is good by virtue of being contextually sort of stable, but there may be other ways to be stable or that might prioritize other kinds of individuals or entities, etc. So I don't think we're going to solve that question. However, what we can solve is the global versus local coherence of certain kinds of beliefs relative to what might constitute goodness at given scales, and find where the friction points might arise, because this version of goodness is incompatible with this version of goodness, and therefore something's got to give somewhere, an error is going to have to propagate. So I think that's going to be answered, but the larger, broader question, you'd have to look into different schools of thought around what constitutes good, because we don't necessarily want to go towards moral realism, because there's a lot of things that are baked into that, but you might want to go into the ethical implications of neo-materialism and how it is about interactions and locality, and at that point it becomes about how do certain pockets of ethical frameworks sort of form and allow to just coexist away from other pockets, and what happens when they start interacting, which again we may be seeing right now in the US.
Yes, good point.
John, any last comments on the session?
No, this is great, and I think we're now surfacing some of the issues that are really important to talk about, and I think at least what we're going to be presenting is a framework that at least we can have these discussions in a more rigorous way and a testable way, and I think that's part of the way moving it forward. So yeah.
Awesome.
Thank you.
Okay, we'll take a 1 minute break. See you soon.
Okay. Thank you.
Should I
Welcome
introduce
back.
us, or
Welcome back. Hello, Sonia and Mao. Again, we are in the session, Physics and Metaphysics of Social Powers. So, thank you both for joining, and take it away.
Thank you so much for having us. I was just asking if we should introduce ourselves, which we will. So I will introduce myself, and then Mao can introduce herself, so that I don't make any mistakes, because my brain is on hyper abstractions at the moment. Anyway, I am Sonia. I'm a PhD student based in Rotterdam at the Erasmus School of Philosophy, and we've been working on this paper with Mao recently. And Mao, please.
Yes, so I'm a PhD candidate at the Université du Québec à Montréal in cognitive computing, and I'm also a director of research strategy at Versus.
Thank you. So yeah, as Daniel said, we're going to be talking about the spectrum, the big spectrum of between the physics and the metaphysics of social powers. Very inspired by the work of Ramstead here, Hesp, Heinz, and by Mao's work on power recently with Sarah Grace Mansky. And then we're trying to combine that with some work that I'm doing with two other colleagues, Wilkins and Clavel Vasquez, on the concept of active ignorance, which we will be continuing to work on in the coming time. So yeah, and then generally inspired by ideas of semantic attraction from Hinton, and by major names in philosophy and sociology who have been treating these concepts through different avenues, less kind of formal avenues, but still relevant nonetheless, now that we're actually capable of joining the physical with the metaphysical. That's what we're gonna try here with this presentation. So the concept of power, we argue, can be explored at several scales, from physical action and process effectuation all the way to complex social dynamics. So this kind of spectrum-wide analysis of power requires attention to the fundamental principles that constrain these processes. And in the social realm, the acquisition and maintenance of power is intertwined with both social interactions and cognitive processing capacities. So socially facilitated empowerment grants empowered agents more information processing capacities and opportunities, either because they're relying on others to bring about desired policies, and or because they're able to enjoy more information processing possibilities as a result of relying on others for the reproduction of material tasks. Material is in brackets because these tasks need not be material. So the effects of social empowerment imply an increased ability to compute information, thereby augmenting the evolution of a specific state space. Specific is a key word here, really commenting back on what Mao just mentioned at the end of the previous talk. So, empowered individuals attract the attention of others. Attention is one of the central focus of our paper. So they attract the attention of others who contribute to increasing the scale of their access to various policies effectuating these state spaces that we mentioned. So the presented argument posits that social power in the context of active inference is a function of several variables, among them an individual's or group's ability to attract the attention of others with access to or the ability to facilitate desired policies, and an individual's or group's capacity to effectively process information. As a result of its power amplifying effects, this extended computational ability also buffers against potential loss or possible vulnerabilities. Semantic social artifacts, so narratives, ideologies, histories, representation at large, are attentional scripts which ensure the coordination of social patterns. So you can think of anything from psychological schemata, habits, groupthink, insulation, policies, etc. And these are the structures under and by which agents mediate and leverage power. And they're, because of that, the main focus of attention here. So thinking about this, the linking between the physical and the metaphysical concepts and the world, gravitational metaphors abound in language. This is like really prominent in the work of Shepard, Lakoff and Johnson, of course, with spatial metaphors. I've done some writing on it at the beginning of my PhD, and also Lachlan Kent did some really nice work that's also up on the Active Inference archive, and in his papers, of course. So the idea of power being pulled towards complex social attractors was also famously presented by Pierre Bourdieu, who linked various concepts of capital, cultural capital, political capital, social capital, to power as this kind of social attraction and also traction. And he borrowed the metaphor from physical field theory, in fact. So there is already, the connection is really present and obvious there, only in a metaphoric way, which we're kind of trying to expand on here. So expanding also on his legacy to take the epistemological and the empirical as totally inseparable things that we're analyzing, and his desire to actually ground sociological analysis in a scientifically tractable manner. We're trying to frame these kind of attentional attractors that move systems towards certain configurations through active inference. And this framing allows for a new take on the dialectics between the individual and the collective, again, linking back to what was just mentioned at the end of the previous talk. So in terms of questions of information processing capacity, not only are resource distribution and the division of labor a systemic fact, but also the modulation and projection of future possibilities cannot be computed at the level of the individual, clearly. So this is something rather obvious in our context and how we're framing power. This is how and why the minimization of uncertainty for social systems is in fact social, right? So agents seek alliances and policies which ensure that cognition, so information processing and future projection can be distributed. And this allows for efficient practical traction because, and here I quote from Steinberg et al., 2023, epistemic confidence in knowing, interpreting, and acting together is that traction that happens when we're socially distributed. And this is in contrast with this kind of individualized agency where one's estimation of, and here I quote again, divergence in mental states between self and others is what allows for the sort of prediction and interpretation of others' behavior, which we might kind of want to frame as something that has a shorter range traction on the future. So now we're going to look at the theoretical framework, and I pass it over to Mahault.
So obviously, you have heard this 15 times, but I'm still going to go through it because there are some concepts in here that will become relatively salient after. But to go over it briefly, active inference explains how biological agents really minimize variational free energy to align their internal beliefs with external reality. So effectively, they've reduced discrepancies between expected and actual sensory inputs, and we sort of leverage this descent on free energy to couch model perception, cognition, and action through Bayesian belief updating. And so free energy is the upper bound on surprise or the unexpectedness of sensory data relative to an agent's predictions. And so direct computation of surprise is complex. So agents use variational free energy to approximate based on their internal and generative model. And so you can see that, for example, the KL divergence term measures how closely the internal beliefs match the true posterior. And so agents align their beliefs with actual data as they minimize it. And so the log likelihood term ensures predictions align with observations. So to minimize free energy, agents update their beliefs. They allow for adaptive action selection that supports coherent goal-directed behavior. And so there are two strategies: perceptual inference to adjust your beliefs to match the sensory input, and active inference, which is acting to change the environment and align new sensory data with internal models. Active inference, interestingly, and as we saw earlier with the whole word cloud, spans or can span multiple scales, from cellular processes maintaining homeostasis to cognitive systems using predictive coding to update beliefs based on hierarchical prediction errors. And so this really gives us a broad biological principle where minimizing free energy promotes systemic efficiency and optimal homeostasis across scales. And so reducing free energy really means that you minimize entropy as well, and you align your beliefs with reality to reduce this uncertainty. Important to note is that we also factor action. So expected free energy can be decomposed into extrinsic, goal-oriented, and epistemic, uncertainty-reducing components that balance exploration and exploitations. And so this dual strategy ensures that agents achieve immediate goals while gathering information to adapt effectively in uncertain environments. And so central to active inference, we really have this concept of a generative model, which allows agents to predict sensory inputs and their hidden causes. The generative process represents the real-world states that produce observations, and generative models reflect the agent's hypotheses about these processes. The agent's actions correct mismatches between its model and real sensory inputs to align the model with reality. Going quickly over the different terms in a hierarchical structure, each level predicts the states of the ones below, and it corrects predictions based on sensory feedback. And there are conditional dependencies that cascade between layers that support belief updating and adaptation. We have observable states that are the sensory inputs the agent receives and tries to predict using its model, the hidden states, latent variables that represent underlying causes inferred by the agent to explain sensory inputs. There's a series of parameters that define the statistical dependencies between hidden and observable states, the likelihood function, which indicates how well the hidden states and parameters predict observed data. We have a prior distribution, which is the initial beliefs about the hidden states, and the posterior distribution, which is the updated beliefs after observing data and combining likelihood and prior. And then obviously we use the marginal likelihood, which is the probability of observed data under the model, to integrate over hidden states. And so we use this for model evaluation and comparison to determine how well a model explains sensory inputs. So the generative model really enables the agents to align its beliefs with the sensory data, sometimes through hierarchical predictions, realistically most often through hierarchical predictions and feedback loops, and they refine their understanding of the environment to improve action selection for adaptive behavior. And so this picture is really very individual. So we can see, though, that within this picture, it's really, really rife to couch power dynamics. So we start from individual agents as predictive systems that minimize uncertainty through prediction, through perception and action. And so Bruinberg really made a salient point about this with this paper on the primacy of I can, where agents develop, empowerment through embodied interactions, which enable them to affect the environment. And so if we scale this up to social power, agents use generative models for self-prediction, but also to predict others' intentions. They form the basis of social understanding and collective action. Karl has lots of work about this. Connor Hines as well, Axel Constant, Maxwell Ramstead, Casper Hess, Natalie Castell, which I believe will give a talk as well. And so attention is driven by deep preferences, and it shapes what becomes salient, which influences both individual and group behavior. At the group level, shared predictive models facilitate coordinated actions. So stigmergic processes, as explored by our very own Daniel, environmental modifications that guide behavior, allow distributed control, while deontic cues, as explored by Axel Constant, enforce social norms. And so cultural practices further shape collective attention. It creates shared perceptual landscapes, which is something that we explored with Toby Sinclair Smith. I think I said his name wrong. I called him Toby, so I don't really know how to say his name. And finally, we have to know how to couch joint attention. And this is work that Rémi Tison and Pierre Poirier at the University of Quebec and Montreal have also posited that this mechanism basically enables efficient coordination through mutual recognition of action possibilities. And so power here, power structures emerge through self-organizing subgroups based on belief similarity. So again, this is work that has been explored by Natalie Castell, which we can call decentralized. Influence spreads within network structures, and they amplify certain narratives while marginalizing others. And so these processes create cultural capital where shared norms and knowledge facilitate efficient social interaction. The tension here is thus shaped by those preferences, but it shows that the importance of critically constructing shared narratives without homogenizing scripts that stifle diversities is an important thing to consider. So it's a point made by Hannah Arendt. Simplistic, one-dimensional views, like there is no alternative, constrain attention and reduce complex systems to narrow goals, which is why fascism tends to be very attractive, especially in times of high uncertainty. And so distributed generative models over time, including historical narratives and generational dynamics, give us the tools to envision power as possibilistic, which is a term that Sonia introduced here. This shifts the focus from isolated agency to collective dynamics and hierarchical organization. We get a richer analysis of how agents and groups interact within constraints to shape future possibilities. So active inference really gives us a frame for social power beyond very simplistic, atomized ideas of agency and focus instead on this emergent, distributed process that structure collective behavior and potential.
Thank you. So, yeah, to return to the concept of narrative, because it's sort of the thing that frames something that might go from the small scale to the large scale in different ways, and something that we can all colloquially sort of latch onto. Narratives are social mechanisms which have the power to make or break power, you can say. The cognitive exploration of the not yet engaged, right, of scripts that are not yet there, but one may kind of latch onto or sort of effectuate. Anything you can think of here, things like speculations, fictions, future possibilities of all sorts, can be understood as semantic attractors that enable kind of relatively risk-free learning, right? So you're projecting to imagine what might be the case if, and the simpler the narrative, usually the easier it is to sort of minimize like vast uncertainty. So these possibilistic explorations in the form of narratives allow agents to explore counterfactual scenarios and minimize uncertainty without this sort of exposure to the real world consequences of this. This safety mechanism frames both the evolutionary advantage and persistent appeal of narrative engagement in human culture. And in the context of power, leveraging strong narratives, as Mahault just pointed out, such as us versus them, that's like the one that, that's the biggest semantic attractor that we seem to keep returning to all the time, these types of reductionisms that greatly minimizes uncertainty about an agent's or group's current predicaments, and they become, because of this, very, very appealing and sometimes self-fulfilling, unfortunately, policies that bring about their effects, resulting in collective behaviors which can benefit, which can be beneficial or detrimental to the greater whole. The effects of variational free energy minimization can be observed, of course, at the level of the basic structures of language in this sense. So semantic attractors like redundancy, rhyme, alliteration, etc. can be understood as patterns which aid memory, communication, informational retrieval policies, because they permanently reappear, right? So pulling attention to the same phenomena, and here I use scare quotes very, very strongly, the same phenomena, thus greatly reducing the need to interpret and organize linguistic interaction and cognition anew every time, which is very costly. So we can understand, for example, the possible emergence of rhythmic patterning in communication as enabling the storage and access of information collectively. By connecting a sound pattern to a phenomenon, we reduce uncertainty about reality once that sound pattern is witnessed. Again, in sort of true Pavlovian fashion. By way of the same uncertainty minimizing mechanisms, simple or complex narrative constructs create cognitive situations where agents reduce complex aspects of the world down to preferred scenarios. And now we can look at how active inference is a useful applied framework for this. I pass it over to Mao again.
Thank you. So I'm here drawing on work that is currently ongoing from other people as well with whom I'm collaborating, and I want to make sure that these ideas are appropriately attributed to them. We're going to talk about individual agency and empowerment, and so autonomy can be defined as a system's capacity to self-govern using internal norms. Again, this is a topic explored by Jacqueline Hines, Alex Kiefer, Ignacio Pulido, in part at Verses. And so empowerment here is measured by the maximum mutual information between an agent's actions and resulting states. And so this reflects how much influence an agent has over future states. Higher empowerment means greater potential for desired outcomes. And so empowerment maximizes the entropy of actions and states while ensuring strong action-state correlations. Autonomous agents are thus more driven by intrinsic motivation. And this is a premise that, again, Alex Kiefer is one of the pioneers here. It's thus connected to drives and control to systems that optimize future action state paths. And so under active inference, agents minimize expected free energy to balance exploration, information seeking, and exploitation, goal pursuit. And so this involves perceptual inference to update beliefs and generate model refinements through action outcomes. And so here, power operates as an attractor in social systems. It draws agents towards influential entities through access to resources and strategic advantages, capital. It leads therefore to amplification through feedback loops. Powerful agents help others minimize their expected free energy by providing some degree of stable, predictable frameworks and reshaping the informational landscape. And so high power entities have privileged access to information and can model their environment more effectively. And they also influence what can be modeled and how, impacting the collective predictive landscape. Powerful agents can offload cognitive demands as well, processing complex information more efficiently and directing narratives to manage error absorption and uncertainty. So power here enables agents to shape others' focus, directing attention to favorable states while diminishing access to alternatives. And this leads to feedback loop where control over the environment enhances influence and perpetuates power. The whole story around the 1%. So power grants a broader range of operational capabilities and extends influence over others' state-space policies within its domain. And so here, active inference reveals power as this emergent property of the connection between perception, action, and social structures, where powerful agents maintain and expand their control by shaping both informational and physical environments. So let's go over three main components: precision modulation, belief alignment, and ultimately minimizing divergence. First, precision modulation. Powerful agents shape expected outcomes by altering the social or informational environment, as we saw. They create narratives or scripts that effectively reduce the dimensionality of the state space, forming stable attractors such as social norms or shared stories. And these attractors direct collective attention and ensure that other agents align their actions with these preferred states. But here, basically, the posterior belief about states has an alpha that modulates the impact of precision on these beliefs. And so in belief alignments, the power to direct attention and utilize precision modulation really enables the leaders to make specific aspects of reality more salient for others. And so by establishing these attractors within the belief space, the leaders guide others' interpretations and behaviors, These attractors act as a focal point, reducing ambiguity and encouraging agents to align their beliefs and actions around them, thus fostering a shared understanding. And so the alignment process naturally emerges from minimizing the expected free energy. And so, for example, where P of O given S and pi is the likelihood of outcomes given states under policy pi, and Q of S given O and pi is the posterior beliefs about states. And so this decomposition shows us the intrinsic and extrinsic components which balance uncertainty reduction with goal-oriented behavior that is shaped by this precision that we mentioned earlier. And so finally, minimizing divergence can be represented just using a Kullback-Leibler divergence, which is a measure of the difference between two agents' belief distributions. And so a lower KL divergence indicates closer belief alignments. And so leaders influence this alignment by modulating this precision, which amplifies confidence in specific interpretations. And so the process minimizes belief divergence across agents, which promotes synchronized understanding and cohesive group behavior without the necessity for direct coercion, although that is yet another way to minimize the state space and therefore is an available practice. So precision modulation sets the framework for control, belief alignments ensures collective cohesion, and minimizing divergence formalizes this alignment. So basically we capture the dynamics and influence, the dynamics of power and influence within social systems.
And so finally, we come to the conclusion. We have a lot more in the paper that we're still working out, so look out for that. Yeah, so what we're thinking about here in terms of this kind of shift, attentional shift from ideas of territorial and material power to this new realm of informational and computational power. Well, this for us requires attention to attention, for sure. Something that we can look at in ways that we can formalize. And of course, we propose that active inference provides crucial theoretical tools for making power structures visible and therefore analyzable, and so allowing possibly for the potential to rethink current social asymmetries. So again, given this sort of apparent transition between the organization of life around the centrality of physical work and matter and things moving in space towards the centrality of attention and information, especially considering the whole attention economy idea, we kind of try to think about a possible sustainable social future, which requires the addressing of both resource and information distributions. And the latter is best analyzed through the power of attention, as we've tried to show, as a major factor or one major vector influencing social dynamics. And of course, this is very important to mention, hierarchies are inevitable in complex thermodynamic systems, but we propose, if we can begin thinking about this, fostering transparent plastic hierarchies that remain contestable and thus open to novelty, open to learning, right? This approach has to acknowledge historic and thermodynamic constraints while also acknowledging space for systemic evolution. And while hierarchies are inevitable, social scripts should be read-writable by those with an interest in survival within them, right? And this helps reorient our understanding of an unfolding, globalizing, interconnected, and interdependent life. And participation in a system is only participatory if those involved are able to track the consequences of the variables and thus future state spaces at stake. A true distribution of information processing capabilities is essential for systemic sustainability and proper equitable development. And when thinking through evolutionary biology lenses, for example, let's try to polish them clearly and not fall into social Darwinism narratives. And to quote from the Xenofeminist Manifesto, lovely colleagues there, Patricia Reed, for example, if nature is unjust, then we change nature, which is what we are all in the business of doing here a little bit. All right, that was our presentation.
Thank you. Awesome. Okay, we'll be back in a few minutes.
is Karl.
Hello. Welcome back, everyone. I'm here with Alex Aurora. We may have Karl join. We may have someone else join. If you want to join, maybe write it in the YouTube live chat, and maybe I'll email you a link. Otherwise, write some questions. However, to kick things off, Alex, feel free to say hello and start in, and I know that there's things that we can explore together.
Sure. You just kicked it back to me, and I was saying to you. All right, well, I'll just introduce myself because I'm not entirely sure how most of the audience, if they know of who I am. So I'm Alex Aurora. I am a computational neuroscientist and cognitive scientist who has worked for active inference and specifically predictive coding versions of it for quite some time. I'm Karl's friend and collaborator. Some of you might be aware of more of our recent arguments of mortal computation, which is a corollary or a new corollary or another corollary of the free energy principle. And I'm all about what's wrong with deep learning and machine intelligence. And I'm usually the guy you go to if you want to attack backpropagation of errors, large language models, transformers. Kind of relates to a lot of the discussion I was able to catch snippets of earlier today. So if you want me to help dismantle what's the problem with deep learning, that can be fun too. So that, at least if nothing else, everyone now knows who I am. Karl needs no introduction.
Maybe start off with that while I try to figure out why he cannot join.
Oh, okay. What part of that do you want me to... I mean, I can go into manifesto, but I'm not sure that's what this panel should be about.
Maybe beginning with a 5-minute manifesto, and then there will be some questions, and we'll see where we get.
Well, maybe to try to make it useful to the audience for the moment, although I wasn't intending the panel to be focused about that, maybe one thing that we can talk about is there was this discussion during the Active Inference workshop about metabolism and sort of instilling a homeostatic metabolic drive, a survival almost orientation to machine intelligence. And so Karl and I have now been arguing for probably now about more than a year since our paper came out, around November, actually start of November, talking about another way to redesign, reformulate, to use Mao's earlier wording, intelligence itself, particularly machine intelligence. And so mortal computation without, again, for those that might not be familiar, actually my friend Jeff also 2 years ago introduced this phrase, the idea that computation or intelligent calculations and substrate are in biological natural systems are entangled, and it's very hard to divorce those two concepts. Whereas computer science and a lot of what ChatGPT is, or large language models, or your favorite deep GPT structure is immortal, which is the idea that we can copy that program, including its weight tensors and its encoded knowledge, and place it on any GPU server you want, and it'll behave roughly the same. There's nothing inherent about its physical instantiation in this universe that dictates or shapes or necessarily embodies it, right? And so there's this move to embodiment. By the way, active inference and the free energy principle has all of these characteristics. Mortal computation, which is, again, the concept I explained earlier, Karl and I sort of recast it. We strongly redid it and said that, because while Jeff didn't want to necessarily directly explore it, we put it as it's just basically thinking of the free energy principle and taking it to its natural extreme conclusion, which is that machine intelligence systems, because they are inherently bound to their substrate, must focus on this survival objective, right? And the free energy principle, and one of its ways to talk about it, basically is saying, we have a markup blanket or a nested system of markup blankets, and our goal in this universe is to protect those internal states, yet interact vicariously with our external states. And so that eventually gives us our ultimate goal, which is to prevent ourselves from disintegration into a heat bath. It's a very physics form of thinking about identity and identity construction. But this is kind of what's essentially missing in basically all of machine intelligence. Is this the completely right path to go? There's plenty of criticisms, and I'm not one to say that there's only one direction we need to go if we ever want something like artificial general intelligence. But this might be a path worth exploring. It also addresses the energy efficiency arguments I was hearing earlier discussed. Transformers, particularly in large language models, are grossly negligent of their energy costs. They oftentimes have the carbon footprint of a large city, and that's actually now out of date, as Karl and I wrote that about a year ago. There's even discussions I find kind of humorous by individuals I'm not going to particularly name, saying we should be powering now these transformers and large language models with nuclear power plants. And so we're kind of going down the rabbit hole of let's just burn as much of our resources as we can to just get this particular type of intelligence. I argue very strongly narrow AI, and we're cheating ourselves of looking and embracing actually energy efficiency, which would lead us towards the real grand goal of green AI, because global climate change is clearly and empirically a thing, and we should be a little worried about that. So mortal computation sort of helps steer everything into sort of what I would argue, hopefully, maybe in multiple years' time, the emergence of a whole new field. Because I consider, or at least my personal take, I'd love to have heard Karl wherever he might be, but I envision actually mortal computation as not just like the framework and definitions that Karl and I talked about, which kind of take free energy and active inference to the strongest conclusion to a naturalistic machine intelligence, but maybe perhaps a new domain of thought, of biomimetic intelligence, and where everyone else can come together and play in this really interesting space. And there's a lot to unpack there, but I don't think we want to make this about that. There's plenty of talks I've given, including Active Inference Institute. We've had a podcast, actually, I think it was right when the paper came out. So for those that are interested, I just recommend you to go to the YouTube channel and watch wonderful videos that Dan led. Oh, is there a new link? Okay. Sure. Was I just blabbing there to no one?
No, that was perfect. We just hot swapped.
Okay, I was trying to buy Karl. Yeah. Welcome, Karl. We were talking about you.
Okay. Thank you
let
for
me
the
try to get my
overview on mortal computation, and it was a highlight of the year. Karl, with the evening sunset now, how goes it? Wait, I don't hear you. Continue. Sorry. It's all good, Karl. Continue.
Can you hear me now?
Yep.
Excellent. Yeah, I'm sorry about that. I got locked out. I was paying the price for enjoying myself for the first 2 hours. Right. So I'll just wait until. I really enjoyed the intervening sessions and look forward to sort of commenting about some of the cross-cutting themes.
Yes. Okay. Alex, mute. It's a little noisier on Jitsi, and then Karl, also a little quiet, but we hear you. So, what were the themes that connected the presentations that you were in or otherwise?
Well, one thing that struck me. Can you hear me all right now?
Yep.
Is this? Yep.
Yep.
Excellent. I mean, there are lots of little golden nuggets throughout all the presentations. But one cross-cutting theme was this notion of community that emerged in various guises, such as the notion of commons, that was the subject of a lot of the exchanges in the first presentation, and then the notion of community that was a denouement of the workshop, and then the notion of coherence and synchronization and narrative social science accounts of that, and how that might be formalized in terms of joint free energy minimization ensembles of agents, finding a coherent, communal, and empowered free energy minima. So I feel that was a common theme, sort of focusing much less upon individual agents, but what happens when you have an ecosystem of agents, and what principles can be brought to the table to understand interactions or ensembles of agents. So I have a number of lots of things came to mind. I was trying as a physicist to sort of rewrite all of these wonderful concepts in a mathematical way or a physics way. So, for example, I was thinking about the importance of commons, and it struck me that one way that we could motivate the choice of capital C for prior preferences would be that these are the common goals and the C characteristic states that are shared between multiple agents. And of course, the last presentation took us through some of the mechanisms and the capital C circular, capital C causality that leads to this capital C coherence, so, which originally was meant to be constraints in the sense of a constrained maximum entropy principle, or cost in the in a reinforcement learning setting. But coming back, of course, all this started when I was hearing about commons and how it underwrote communities.
It is very interesting how development and the presentations have proceeded a lot more about the communication and somewhat of the multi-agent coordination, as opposed to a longer memory train for individuals or deeper prospection for one individual. And in a way, the renormalization method brought a clarity or a rigor to what had already been qualitatively explored from 2013 and Life as We Know It and all these other works that were talking about multi-scale systems and about blankets of blankets. And within this year, to make it timely, we start to see some of the ways in which that compositionality can actually be brought into the generative models that we've seen. I mean, it looks like the textbook figure 4.3 and the nested models, and now that's actually the motif that gives a way of looking at a multiplicity at the more inactive level as having a unity at a higher level. Alex, in your designing your work, how does the single agent or multi-agent design come into play?
Now. Yeah?
Yeah.
You can hear me? Okay, good. Yeah, I was having mic troubles earlier. Well, so it's kind of interesting. I think I've spent most of my career at the single agent level, in the sense that I want to build. I don't think we have right the single agent. And I think it's kind of important to sort of scope that out from an architectural learning perspective. I'm very much a fan of like Karl's arguments, and I echo them myself a lot, which is the idea of the inference learning and structural timescales. I still think we have a lot to do, but if I were to say how in my research the multi-agent approach really comes into play, well, I do think a lot in terms of assemblies or ensembles, right? Putting together multiple circuits. I'm a huge proponent of another type of, this comes from cognitive science, called the common model of cognition. I'm not sure how many in the audience are familiar with it, but it's sort of like a generic blueprint that has emerged over the last several decades of cognitive science to say that we can think about and take our current knowledge from neurophysiology and cognitive studies that brain has these rough levels of organization, different types of memory. We have the motor cortex, we have the basal ganglia, we have all these very important structures, and we can start appending to them some functionality. And so in that sense, that's where I think of multiple agents, right? Because you can start breaking apart using, again, Karl and I have argued this, the mean field approximation. There's natural mean field approximations that emerged through the result of evolution, where you have these little substructures that communicate with each other. Obviously, the sparse connectivity that Karl mentioned in his talk this morning is kind of indicative of how these little substructures emerge and then communicate and perform, sort of like what Marvin Minsky would have said, you know, sort of a society of mind, right? So it's kind of a callback to that. And I think in that regard, I often, one branch of my work often tries to highlight, emphasize, bring forth that notion of cognitive blueprinting or cognitive structure, because then we can start filling in the pieces with what we know about neurobiology. Like, for example, I use predictive coding quite a bit, you know, to fill in those gaps. And so I think in that sense, I think a lot of interacting subsystems, you could think of those as agents. And then my final comment, without letting myself blab too much, I have worked in neuroevolution. So there is another scale above this, which is, you know, you do need to account for how multiple mortal computers or multiple agents interact with each other. And so I think in that regard, I have done some work with very simplified agents where you can kind of abstract away the neuroscience and just say, I want to look at these little tiny systems that interact, and then we can, you know, modify them through genetic algorithms and neuroevolution. So there is a little bit of that like higher level societal kind of learning. I have looked at that, and I think a big challenge, just to bring it to the audience for the panel, is merging those timescales in a coherent and efficient way. I still think, well, there has been good work. I know, Daniel, you work on end colony optimization as well, and other types of kind of aggregate algorithms. I think bringing those timescales together and really interacting with what we currently know about single agents, even like the common model of cognition, and going back to the highest level, which is this multi-agent evolutionary timescale, is a grand challenge. And how do we, of course, effectively simulate those in a way that anyone can play with this, I think is a big challenge. And yeah, and I think I'll kind of stop there before I go down more rabbit holes.
Neuroevolution and neural Darwinism, something Karl and others have also explored. It's like they're all, and then the multiple nested timescales, multiple nested spatial scales. It's like there's this attractor to want to come back and find the unifying patterns, and how those can be applied is kind of an exciting question. I'll read one question in the chat, so feel free to give it thought or take it any direction. David Highland wrote, Do you view mortal and immortal computation as binary categories, or are they more like 2 points along a spectrum?
I actually want Karl to answer that. I mean, I could give something, but I really want to hear your thoughts on it.
It's your favorite subject, though. It's design.
I know, but I'm actually really curious if you think of it as a spectrum, because remember the conversation we've had with Mike Levin and Chris Fields, and we've been sort of debating, you know, how important it is to lean into mortality versus immortality. Do you think that there could possibly be anything in between? Because I honestly am, you know, I think of it kind of more rigidly. I'll just give my answers that, and I firmly think we need to like focus on mortal computation. But Do you think that there can be a hybrid in between? So sorry to turn it on you, but I'm very curious to know your thoughts.
I mean, my instinctual answer is no. Having said that, I am sure that you can present some description of mortal computation in terms of immortal algorithms. I mean, I'm just thinking back to sort of the trilogy due to David Marr. But does that mean that these kinds of descriptions are apt for simulating, reproducing, understanding, or describing the actual process? I suspect not. They may be at one level of description, they may be, but when it comes to applying the principles, usually in computer simulations, I suspect that just would not work. I mean, because Daniel and I were wrestling with Zoom and other communication things, we may have missed whether you've taken people through the key distinction between mortal and immortal computation. So, Alex, did you sort of briefly rehearse the sort of the two cardinal views of the distinction between mortal and immortal computation?
I did. I just wasn't sure if anyone heard me, so I wasn't sure what was going on.
It was
from
heard.
Zoom. Okay.
Yeah, I mean, certainly from the point of view of the free energy principle, the free energy principle is a description of a random dynamical system, and as such, it is a system that constitutes the world, the lived world, perhaps not the lived world, but certainly a mortal world, that has characteristic timescales, and therefore the free energy principle and everything that ensues from that, including active inference, rests upon that primary assumption that you are describing a process, a mortal process, a process that could have a physics, although the actual free energy principle itself is almost pre-physics. So you have to derive basic mechanics and classical mechanics and quantum mechanics from the existence, the mortality of this process cast in terms of time evolving systems. So in that sense, there is no such thing as immortal computation. But I don't know if you said it out loud, but I also liked your more playful take on mortal versus immortal. That if software was immortal and it had some autopoietic aspect to it, then it wouldn't care about dying. So there would be there'd be no incentive to have characteristic states, coming back to another big C. So in that sense, there cannot be immortal computation, simply because that is removing the definitional, stipulative definitional aspect of the characteristic states that we are trying to describe through the free energy principle and active inference and specific variants of that, such as predictive coding. But just picking up on this cross-cutting CC theme, you also celebrated that with common cognitive models. So again, we've got this sort of notion of commonality, and you asked the question, how would one apply these notions, and if you like, sort of naturalize the common cognitive model under a less anthropomorphic or functionalist active inference account? And you gave the answer implicit in your question, which is how would you simulate these things? And I think Daniel asked the same question. Indeed, the whole point of this symposium is about applications. So I just wanted to put a question to the two of you. I was impressed with the very clear distinction between agent-based modeling and the common cognitive equivalent, where the agents, the members of the ensemble, were actually, for example, active inference agents. That seems to me a very big move and a very difficult thing to actually do. Most of the literature I know in this area has at most taken baby steps into having ensembles of true agents with authentic agency in the sense that they can plan. So I'm now limiting the notion of an agent beyond a thermostat or a virus to those kinds of systems that have in mind, or part of their generative model, the consequences of their actions, so they can be future pointing and they can plan and select from alternative policies. And of course, the numerics and the practical difficulties of actually simulating, doing agent-based modeling, for example, with authentic agents in the mix, in the ecosystem, I think is a really important challenge and a really important distinction between classical agent-based models, where you put lots of thermostats or Lorentz attractors together and see what happens. And of course, they have a synchronization manifold, and you can certainly wax lyrical about generalized synchrony and joint free energy minimization of a generic sort. But I think that misses the point, and I think Mao was making, that part of the multiple loops of circular causality in sort of cultural niche construction, for example, really does rest upon the capacity of any individual within an ensemble to act, given they have selected a particular course of action, a particular path into the future, which they have beliefs about the consequences of. And to me, that is an authentic kind of agent. So, I mean, perhaps, well, both of you, but Daniel, I mean, your ethology background, are you aware of anybody who's actually sort of bitten the bullet that was introduced to us during the workshop and actually started creating active inference agents that actually plan and learn from each other and carve out their own Waddington landscapes, finding those sort of joint minima?
I don't know specific citation, but certainly you've given a research direction, and it reminded me of in the shared pretensions work, where thinking about what does a shared ensemble, what would it be for a planning ensemble or for a collective? It could be a shared protension, as in there's the same plan disseminated across the ant nestmates. It could be that they have different, maybe non-overlapping, but complementary parts that would be shared. It could be having a shared reference, but they could have different plans. Or it could even be a shared consequence without even a shared reference. So there's so many ways in which, especially when we consider ensembles that are heterogeneous, and they have different kinds of umwelts, different kinds of ways of engaging with the niche, and possibly some common niche, as well as some uniquely accessible components. There's so many flavors of ensemble that I can only hopelessly or helpfully try to think about what tools and infrastructure and coordination would even give us a grasp to be able to sweep or design or visualize across that. Otherwise, we might be locked in way too early to what it means for the ensemble to have a collective protension, and then that's not going to apply to every ant species. And if it can't even apply to all the ants out there, then it's not going to work for aliens.
Alex, can I just respond to that and then ask for your view on that one? So I think it's a really important point, isn't it? One of the big takeaways for me on our paper on the variational synthesis, applying the renormalization group to the coupling of evolutionary to sort of phenotypic time scales, was that it was not feasible or appropriate to talk about conspecifics in isolation. That it was, you had to have all the varieties of predators and preys and things that we that are not even animate and not even agents in the mix to actually derive the non-equilibrium steady states at particular scales, which speaks directly. It is not useful to as you know, if you like, take the idealized gas mentality of 20th century physics and now apply it to agent-based modeling, to assume that all the agents are exchangeable and are identical in some sense, and then are converging on some common narrative or some common, is not the right way to simulate these things. You can't do predator-prey relationships. For example, you can't have even simple economic games. But furthermore, when people talk about depletion of resources, you actually have to model the resource. Whether it's oxygen, food, or water, as things in that ecosystem. So I think that's a really important observation, which just speaks to the challenge of using numerical studies to test out some of the hypotheses that we've been exposed to. If one just pursues agent-based modeling without introducing that heterogeneity, I think one is making exactly the same mistake that people make when they apply equilibrium physics to non-equilibrium systems. A true gas is not an ideal gas, and it only has the kinds of properties and breaks detailed balance and expresses non-equilibria in virtue of the fact that there is no exchangeability. You can't assume that every atom or every agent in our context is exchangeable with every other agent.
And to connect again to commons and that model of, well, within the firm, we assume cooperativity and hierarchy. In the market, we have a flatness and a competitiveness. And then there's this commons that has sort of elements of each. So then I think about doing ecosystem modeling. It'd be like, well, we have within the ant colony, we assume cooperativity, possibly hierarchy. Among ant colonies, you have red and tooth and claw and competition. And then it's like, but can there be a unifying framework that would have the 2 genotypes and 2 phenotypes and 2 species and 2 adjacent niches and keep on adding in these levels of distinction and seeing all those different variables in their joint evolution across multiple time scales, rather than the concatenation of a cooperative hierarchical game within a lateral competitive game. It's like capturing what those models get the width and the height of, but bringing it into a framework where it's being seen as just one joint evolving process. So C is the letter of the day.
Alex, can you speak to C's of cells and what that kind of heterogeneity and structured diversity would look like from the point of view of a tissue, for example, or an organ?
Okay, wait, what was the C word you said? I just didn't hear you.
It's any word starting with the letter C you can use, but you have to.
I have to use, okay, this is the game. Community. I'm going to pick that one just because it starts with C. Okay, Karl threw in organs and organelles, but I'm going to push that aside for just a minute to address, I think, one of the questions I heard emerge from yours and Karl's discussion, which was, is there anything like what you are arguing for, which is avoiding the mistakes? And by the way, predator-prey model came immediately as you were speaking, Karl, about these classical models that assumed interchangeable agents. And is there anything that looks at these heterogeneous systems or heterogeneous agent interactions? And a couple of thoughts. I don't think there's anything like directly what we would want. And I think that ties or centers around even the arguments you and I and many others in the community are making about why it's difficult to showcase why active inference is so important, even for places like machine intelligence. But I did write some thoughts quickly. So I do think the first thing that came to mind, weirdly enough, was an application in the world of machine intelligence where they had some environment where they had a community of, even though I say it with slight distaste, large language models or chat GPTs or GPTs that had some extra modality equipped to them. and they had this like little community. Now it was a virtual, very simplified niche, if you will, but the idea is that they could observe this community. And so these different GPTs would, and I can try to dig up the paper and send it to Daniel later. It's one of my students that actually pointed it out to me. They would assign different roles. They had different personalities, if you will. And I know that they investigated that to some degree. Now, of course, that doesn't have any active inference in there. And I'm not sure what degree of maybe perhaps light reinforcement learning they introduced, but there is something like that. And there is slight baby steps, if you will, in investigating some notion of embodied, multi-embodied agent systems. I think the AI community is still sort of barely starting to embrace embodiment, let alone enactivism, and let alone embeddedness, which is the idea of a community, to go back to the C word, of multiple agents interacting with each other, and investigating how do social norms emerge, or cultural norms and cultural constraints and relationships at this like more global level. So I think there is a little bit of those sparks of that thought, and obviously I might not be aware of further follow-ups. Another place that I at least see the potential of no longer having these interchangeable particle-like agents is in multi-agent robotics. I know that they have done things like soccer competitions, and they have these little, and again, each of those robots, they are the embodiment of what you and I want, which is a version of a mortal computer. So it's a little like assembly of mortal computers, and there's a cooperative nature, so, and then a competitive nature. So you get a little bit of a very constrained, real physical, real world niche. Obviously, it's in the constraints of it's a soccer game or some very simple task. So I know in multi-agent robotics, there is some development along this path, and it'd be wonderful to have like a hardcore, because I'm more of a simulation roboticist, a hardcore roboticist to talk to us about the state of multi-agent robotics. I think that's the place where you could begin to test hypotheses and kind of or theories that are constructed even from an active inference point of view, into these real world robotic multi-assemblies. So, you know, and they have like, we could analyze the competition cooperative dynamics. I think that's our best bet in terms of what maybe exists at the closest to literal agents that aren't just very simplified, even though they make simplifications in robotics too, in order to have a little brain in there that, you know, does something meaningful. Usually learning is turned off, which is my own criticism of robotics. And I think the last comment I wanted to make, and again, getting back to the notions of what we need. So again, you and I have a fondness, I think, for some of cybernetics, and cybernetics has this notion of complex emergent systems. And we, you know, you have little building blocks at one level that follow their own physics or their own physical laws, and then they maybe assemble or emerge into these higher level building blocks that are subject to their own laws. And then you have bottom up and top down causation, which is a notion that, you know, comes from cybernetics. And we always talk about that, but then I think about like you might be familiar with the Santa Fe Institute and all their wonderful work, like what was it? Not just Herbert Simon, but John Holland, and all the wonderful work on complex adaptive systems. But they always did, at the end of the day, when they simulated it, they did the particle thing, this interchangeable particle simulation, and then tried to analyze like those convergence properties or those emergent rhythms or patterns that kind of emerge in those systems. With no, to my knowledge, and you know, and I did study complex adaptive systems a while ago, not with that heterogeneity, and let alone any of the complex agents that we could begin to design today, even with deep learning, regardless of its limitations. And so I think that that maybe even turns into an answer to your question, highlights an open opportunity, maybe revisiting and recasting notions of cybernetics and complex adaptive systems in this idea of, well, can we actually build more complex agents, for example, that actually have neural substrate structures or something that we can simulate, and then learn to acquire their own characteristics in their niche. I think the reason that maybe a lot of people avoid it, or maybe why I don't perceive development in that direction, is the problem also of niche. And you and I also had and not to try to highlight this paper, but in the appendix, we talked about the body niche problem. And that is this issue that you need a niche. If you don't have a niche and you're designing these agents independently, like deep learning typically does, to apply to any niche, you're missing really half the problem, which is understanding the physical laws and how do we simulate them such that people can then play with those models. Maybe you don't have access to a xenobot like Michael Levin does, or I don't have access to organoids, though I wish I did. But maybe we can simulate these. And so I think that we need the community, maybe this is a call to the community, to develop viable niches, virtual morphologies, virtual areas that we can then connect these agents and then simulate many of them and try to analyze and understand the things we predict, even with these interchangeable particle models, apply to these heterogeneous communities that might emerge. And again, I guess that just to wrap up, and I promise I'm done, you brought up organelles and organs, and I think that highlights something that I wish I had more easy access to rather than being put into this position where I need to build it, which is these virtual organ systems or virtual organelles, and trying to understand how these dynamical systems interact. And then I can kind of take that as that's my body, or that's where my and I can kind of start to put some instantiation of Markov blankets and then say, okay, I want to instill maybe a neural circuit, maybe I put in a predictive coding model into this kind of virtual morphology so I can analyze and understand, do these interactions of the timescales actually come through when we actually build, physical instantiations of these models. And so I think that's going to be one of the biggest roadblocks to even my dreams of mortal computation, which is this notion of morphology, something that we can actually work with, that it gets as close as we can to reality without reality, and then niche. Because once you have those problems solved, then you can start building and if you have an efficient way to simulate them, and I'm sure lots of people that are watching might be worried because it's very hard to simulate, real physical systems, let alone allow machine intelligence researchers to play with them. So I blabbed a little bit there, but does that sort of give you something to bite on based on your questions?
Something to chew on, something to consider. In the last little bit, I'll ask some questions. So I'm gonna read one from the live chat, and then anyone else will just do some quick, fun, random questions, sort of like sampling from the expressed uncertainties of our live chat colleagues. Okay, Pablo FM wrote, is playing a simulation acquiring knowledge/experiences through simulation of scenarios? And how can we use active inference to do games? How do you fellows make your active inference work playful and fun? If or when?
Let you go, Karl. You go first.
I'm not sure if there are two. there are two questions there. A practical answer to why you might want to instantiate a simulation environment with active inference agents, or indeed just a single agent in the spirit of computational phenotyping. But I think probably more interesting in the context of communities of agents, is in the spirit of this sort of cognitive agent-based modeling, is the ability to parameterize the priors of the agents to best explain or replicate legacy data from a particular ecosystem, be it financial, epidemiological, meteorological, purely ethological, and having optimized the parameters, you then roll out into the future. And in rolling out into the future, you now have the opportunity to have a grounded, in principle, Bayes optimal plus inactivism and embedment estimate of what is likely to happen in the future. Again, in the spirit of weather forecasting. But of course, this becomes much more, if you like, useful when you have control of the system, so financial market forecasting or epidemiological forecasting or climate change forecasting, assuming that there's a substantive anthropomorphic anthropological contribution to climate and all the other factors that pertain to resilience and resistance to things, heat, health and the like. As soon as you can intervene, then once you've got a digital twin of this ecosystem that has been optimized in relation to the past data, in the sense that this now has the highest model evidence or marginal likelihood in relation to that legacy data, you've then got an opportunity to do scenario modeling with interventions. So you can now ask questions. What would happen if we cut this supply chain? What would happen if we impose this lockdown in this viral pandemic? What would happen, and so on and so forth. Furthermore, because you've got uncertainty in the mix, because this is effectively going to be using variation procedures that we use in active inference to actually simulate the behavior that best matches the legacy data. You've also got for free uncertainty quantification. So not only can you say, if I intervened on this system and did this, then we would, I can predict that in 6 months' time or in 6 years' time, that, and I can give you base incredible intervals over that. Moreover, you can now apply the principles of active inference to roll out under different interventions, which now become policies, and evaluate the expected free energy of each policy, and select the one under the constraints, the common, the characteristic outcomes that you commit to at this point in time. And you can now use this scheme to make recommendations on the basis of the relative probability of this sequence of interventions versus that sequence of interventions. So I think there are great practical importances of being able to put these principles in silico and basically do evolution very, very quickly, so that tomorrow you can read the consequences probabilistically of evolution in this setting and that setting, where the setting is actually something that we can intervene on, or indeed if we can't, just to know the consequences of our collective behavior to date. So I think that would be that's why you might want to make to invest in these applications. With the fun and having and play, I think that's a different issue. I think that's basically one way of looking at the way that authentic agents behave under the free energy principle, which is basically to explore and gather the right kind of evidence that provides literally evidence for their generative models of their world, which basically entails novelty seeking, but now complement this with this Bayesian model reduction we've been talking about, also trying to find the minimal explanation for the data and the evidence that has been secured by exploratory playful behavior, arriving at particular insights, which those aha moments that say, oh, I see, it's just one of those, or this one thing explains all of this playfully acquired data. And perhaps that kind of mechanism may be a really important aspect of the communal cognitive agent based, or cognitive agent based, I can't quite remember the acronym. It was very nicely laid out in one of the, I'll have to go back and look at the live stream.
A follow-up question from the live chat. Arnaud wrote, I agree with the approach to calibrate to past data and forecasts, but it's already quite challenging for current models that only have a few parameters to be calibrated. How then does one calibrate prior beliefs of millions of agents? I'm talking about epidemiology and economic agent-based models.
Sorry, I got to give a technical answer before Alex gives a more detailed answer. You do it. It's only difficult because 99% of agent-based modeling uses the sample distribution. You do not do that. You use variational. You actually simulate and roll out the probability distributions themselves using variational calculus, and that means that what was yesterday really difficult agent-based modeling, and certainly epidemiological modeling, now becomes really trivial, orders of magnitude more efficient. What you have to take care of is exactly the thing that Daniel was highlighting before, which is the heterogeneity. You need to put that into the mix, and this manifests in a number of ways. So when you apply variational procedures to effectively roll out population density, probability density distributions over various states of being, am I infected? Am I staying at home? Have I died? You have to make sure that the heterogeneity is part of the generative model. So this is sometimes called stratification. So, for example, in epidemiological models, you'd have 8 bands for different age groups. And if you notice the way that the epidemiological data was generated, it was usually age segregated so that people could stratify their models. Another way in which this heterogeneity becomes absolutely crucial when you come to agent-based modeling in the context of epidemiological or infectious disease modeling is called over-dispersion. Now, over-dispersion is the fact that you get heavy-tailed distributions that inherit from the heterogeneity. So you get this for free once you put heterogeneity into the model, but it does mean for every, if you like, subgroup of the population, you do induce more parameters. But remember that the number of parameters, it doesn't really matter. It's the amount of time that you take to effectively invert your model. And if you try and do that using sampling-based approaches, which is currently the norm, you could take literally weeks to do something. Whereas if you use variational procedures, then you could do that within minutes. So it's a really important question, a very practical one.
Yeah, to restate, direct variational inference on beliefs about ensembles themselves being variational belief inference on agent level semantic beliefs rather than sample from the sample what the agents are sampling.
Yeah. You're invoking the twist. Yes. How on earth can you model a variational density over things that have variational densities? You can do it under the Fields principle, because the only observable things about an agent are on its Markov blanket. And of course, they are not belief structures. So there is a lawful relationship between, you can, if you like, simulate cognitive agents using traditional agent-based approaches, but what you have to do is to amortize or to basically work out the mapping between the history of what something sees and what it actually does. But in principle, you can do it by marginalizing out the beliefs of the agent. In principle, and that's why I asked. That's why I was so intrigued by this distinction, because that will be a challenge.
Alex, and then Karl, just in our last minutes here, what would you say was a favorite memory or moment in theory and practice for active inference this year? And then what are you excited about for next year?
I'll go first. So a favorite memory of active inference. Let me think quickly. Well, I mean, I'm going to be a little biased just to give a highlight and a shout out, and everyone will get to share in that memory if you stick around after the roundtable, is actually some of the results from one of my PhD students, Viet, and he's going to give a talk soon. And the idea is that one of the things I was proud of is he's been working in the area of robotics, which I think is a really good playground. As difficult and hard as it to democratize for everyone to work with robotics, I think it really shows you how far we need to go, and I think that's a good place to make strong advances in active inference. And one of my memories is that I remember him kind of showing me, because he's working with partially observable Markov decision processes, and how difficult and unaddressable or lightly addressed it is in the field of working with raw sensory data to try to construct these continuous models. And I remember him showing me some of his models rolled out trajectories in the future. And I'm always kind of in a fondness in my heart for generative models. And I remember him playing out sort of these robotic memories of this robot trying to, fantasize where it would want to go to kind of like move this block or to knock a ball towards a goal. So that was one of those moments where we were really proud, because the idea is we actually made a breakthrough in actually showing that we can construct a very robust framework that applied across all these robotic control problems. And so I was immensely proud of that. And so I think my students drive a lot of some of my fond memories. And then we got Chris Buckley, shout out to him, to kind of give us his insights into our work too. And it was a really, really nice work. And so I think the best way to say it is stick around if you want to know how that all works. I was really proud of that. So it's one of my favorite memories of the year.
Awesome. Karl, with the last words, a fun memory and a direction or an excitement for next year.
Right. I'm not going to tell you about my most fun moments. That's very personal. But my excitement for next year is to see whether any of your hairs go grey after you do the master ceremony of not only these symposia, but all the meetings. Because for those people who don't know, Daniel has to run this almost single-handedly, non-stop, for a marathon, sometimes 10 hours at a time. I don't know how he does it. And unless you're using hair dye, you're standing up physically remarkably well, sir. So I'll just see how long that lasts.
Thank you, Karl. I look forward to the marathon changing, continuing, and flourishing in the coming year.
We appreciate you, Daniel.
Thank you, guys. It's been awesome. Okay. Thanks a lot. See you soon.
Nice talking to you guys. Bye, everyone.
Hello, welcome back. Now we have the much anticipated student presentation that your advisor Alex recently told us will be awesome, by Viet, Dung, Nguyen, on dynamic prior preference learning for scalable, robust, deep active inference. So thank you, Viet. Take it away.
Hello, hello everyone. My name is Viet. I'm from the Neuroadaptive Computing Laboratory, Department of Computer Science, Research Institute of Technology, and I am Alex advisee. And today I'll be talking about dynamic prior preference learning for scalable, robust active inference. So yeah, first of all, I want to talk about the motivation for this. So nowadays, frontier work in robotics excels in implementing robots' behavior and planning. For example, creating autonomous robots that can actively explore in the environment. Additionally, we can also do a lot of robotics applications, for example, acquiring knowledge and learn skills continuously. This also envisions cognitive and developmental robotics. So there's just a goal for robotics research that we can try to build a robot that can continuously develop through interactions with their environments and their learning processes. And it is also better to have interactions with their physical and social world in a manner of human learning and cognitive development. So there's a lot of robotics applications around. And for example, one application can be to build asexual robots and building social collaborative robots and stuff like that. So underlying all these robot work, it's like active inference research, where we often build generative models. So the developments of robotics actually depends a lot on active inference framework, because there's a great need for research that integrates the generative world model into robotics control system. As also deep learning is increasingly used in constructing complex action planning algorithms for solving control tasks. So we can see that there is a need for scaling active inference systems, especially a deep active inference system, to integrate into the real world applications. So research in active inference has led to many improvements in terms of robustness of model-based agents that applies to both Markov-Decision processes and partially observable MVPs or POMVPs. So an example of an MVP environment would be mountain car. For those who knows or studies reinforcement learning already, and this mountain car environments in MVP, we only know position and velocity, right? And that is the actual state of the environment. But when we get to POMVP, for example, like robotic tasks, we as agents see only the image frame, and we do not know the underlying states, such as position and orientation of the block, or joint states of the robots, for example. Right? So basically, active inference is basically a form of inference and learning that seeks to balance, first of all, the goal-orienting objectives or prior preference. So this signal exploit the instrumental signal so that the agents can seek the goal and try to pursue its goal. And the other thing, it needs to balance the epistemic terms or epistemic signal, where the foraging, it cares about foraging and exploration driving signals. So researchers often actually encounter great difficulty in providing the agent with effective prior preference, as well as computing useful instrumental signal from the agent's the priors, especially in the real world applications where the environment is very complex, the robotic control task, and the trajectory or pathway to be desirable and task-specific goals often requires a very, very long trajectory of preference. So it is not that actually practical to provide a prior preference distributions, especially the stream or rollout of goal images. So that is the reason why we need to find a way to also learn to generate the prior preference signal in active inference. So on the right here is just our preliminary results, but we'll get to that in a moment. So yes, so we actually, given with that all of this, right, we need to predict a draw out trajectory of a goal state dynamically, right? It can be a goal state or goal observations, but basically the goal is, if you look on the figure on the top here, the top row is the real trajectory where you see the mountain car, right? There's a car that it needs to go backward and to build some kind of a momentum, and then go full to the right to get to the flag. If it is only going to the right, then it does not have enough momentum to go to the top of the hill. So so in here is the actual observations. You can see that the trajectory is a successful trajectory, and the goal here is to for each observation at each time step, we predict a immediate predicted preference image or goal at that single time step, so that we have the instrumental signal or idea of what we are trying to learn, and then from that we learn the actions planning from the prior preference signal. So in this talk, we specifically analyze this issue, the issue of prior preference learning in the current literature, and discuss potential resolutions for scaling the instrumental signal inherent to active inference by introducing the contrastive recurrent state prior preference, or CRSPP. This is the model learning framework that we also have done in the past. So this methodology frames active inference agents in terms of progressively constructing and adapting a prior preference at each time step. So this also facilitates the dynamic emission of a useful or dense, very dense instrumental signal at each time step. So we also study how our prior preference adaptation scheme, when operating jointly with the latent space-driven epistemic foraging terms, offers active inference agent a very nice flexibility in challenging problem contexts, such as sparse reward environments, and also composed of continuous observation and action space, for example. For example, robotic tasks, we often do not know the sparse, do not know the dense reward functions in the actual real environment. We only know if the robot has reached the goal or not, right? And also all these environments has varying goal states. So we can also see that providing the or manually craft the distributions of goal is not very practical. So yeah, so here's the outline of this talk. The introduction I have just covered. So first of all, I'll just assume that everyone is new to active inference, and I'm just gonna briefly cover active inference background and deep active inference, and also cover a little bit about prior preference learning and problems of all those prior preference learning framework. And then I'm just gonna go through the actual methodology, which is the dynamic prior preference learning. And then first of all is the world model. Next is the self-revision mechanism. And then next is the learning prior preference models. And then finally putting all of them together to make an agent. And then I'll show the results and then discussion. Okay, so first of all, I want to cover a little bit about active inference. So just a brief overview about how active inference work and what is the underlying theories behind it. So it is a mathematical framework that describes how intelligent systems or human interact with the environment. So it also describes the environment as the generative process, and the intelligent systems or the agent or us as a generative model. So active inference is built on top of the free energy principles. This means that we as agents or intelligent system continuously observe the environment and forming and correcting our belief or our own representation of the world. So the generative process defines a real world environment here, right? This is treated as the data generation process, where the information patterns are sensed by the agent. So you can see that's the hidden state underlying hidden states denoted S here. It's generate a sense of some kind of observations denoted O, and this is also sensed by our intelligent system. So on the right here is the generative model, is the actual agent that we are trying to build on the intelligent system, right? The intelligent system also has an internal state, which is trying to estimate the generative process states. So this is called the prior, or the internal belief prior to the observations of the environments at a particular timestamp. So this is denoted as the random variable S, or state, and P of S here is the distribution over the random variable S. So this makes the agent's generative model. The generative model represents the agent's approximation of this generative process in this world by continuously seeing the observations, or making the observation O, and modified or updating its belief. So we actually call the belief S after being updated after making the observation for the posterior, because it is the posterior after making the observation, right? So in order to learn the model and estimate the posterior, we first need to introduce these terms. First of all is the prior over state, which is denoted as PS, which is also the distribution over state, right? P of O here is the model evidence. It is the distribution over the current observations, denoting how well is our model at predicting the real data. And in order to compute this easily, this is often written as the sum of probability of observation given every single state. And then next one is P of O given S. This is the likelihoods, and the probability, this is the probability of an observation given a state. So this is a function. It gives the probability given an input state. And then the last one is the posterior functions, PS given O, which is the posterior function that maps the observation to the states. So normally in traditional active inference, the posterior function would be the transpose of the likelihood matrix, for example. And deep learning literature, it is often called a encoder, and the likelihood here is a decoder. So how do we estimate the posterior now? We have to find a belief that maximizes the model evidence, right? Because at the current time points, there is only one single observation O here, and it is real, right? So P of O, P of that observation, it's gonna be 1, right? So it should be the probability of 1. And then we use the states to estimate the observations, and then it has to be the probability of 1, 2, right? So that arrives us at the conclusion that we have to maximize the model evidence P of O. So maximizing P of O is also minimizing equal to minimizing minus log P of O, right? Because it is minimizing the surprise. So in the beginning, we say that we continuously update our belief after making an observations of the environment. We call the belief after making an observation a posterior. This is Q of S, right? So to compute a posterior, we want to put in a, we just want to call this, any kind of distributions over the states. Then, for example, we can sample it, we can randomize it, right? And then we try to gradually trick this distribution so that it's used the highest model evidence, or it's used the lowest surprise. So how do we choose the actual posterior so that it gives the lowest surprise, right? So in minus log P of O here is the actual minimizing surprise, that objective that we are wanting to minimize, right? So we can analyze it like we can do it with a Bayes theorem. This is not Bayes theorem, but Bayes formula or theories, yeah. And then to evaluate the surprise minus log P of O, we need to sum out the hidden variable S from the joint distribution POS. But, well, this summations, there's a problem, right? Because we do not know like all the hidden states, all the hidden variables in the environment. It is hidden from us, right? So it is normally very, very hard to sum up all these state values. So if we cannot sum it up, then we can try to approximate it. So first we introduce a posterior into this sum, right? We multiply both the denominator and the numerator by the posterior. So this is the belief that we are trying to tweak, right? So in here, we're trying to tweak this posterior so that we can minimize this term. So this gives us a weighted sum where S, the ratio POS, and over the distributions Q of S is weighted by the Q of S. This is like weighted sum, right? So according to the inequality of convexity, or Jensen's inequality, says that the convex function of the weighted means is always smaller than the weighted means of the same convex function. So you can see the convex function here is minus log of something, right? So minus log of something is just a it's just a parabole, something like here, and this is smaller than a weighted means of the convex functions. Also, we put this sum outside, right? So this is also applied to the context of probability theory, and then we can arrive at this, equations. So formally, it's called an upper bound. This one, right? A quantity that approach from the above, right? So this is also means that this is a free energy. When we find a posterior that minimizes this free energy term, we will have a chance of approaching the lower surprise points, which potentially increasing the model evidence. So after we have these terms right here, we can just put the minus inside, and then it's become this form. This is the conventional form that we call variation of free energy. And after decomposing this, we will have these two forms, which is the KL divergence between the posterior and the prior, minus the weighted sum of the log of the P of O given S, which is the posterior functions. Or no, this is likelihood. So basically, the KL divergence term is called the complexity, and the minus log P of O given S is called accuracy term, where the complexity terms compute how surprise our states, two state distributions, posterior and the prior, are far away from each other or not, right? And the accuracy terms defines how accurate our model is predicting the actual observations, right? So this is also relatable to the variational autoencoder, where we compute the loss of the variational autoencoder to be the KL divergence of the posterior and the Gaussian distribution with a mean of 0 and a standard deviation of 1. And then we also have the mean square errors of the actual predictions of the images, right? And then VFE and MFE is a little bit different than from variational autoencoder. VFE is variational free energy, and MFE is marginal free energy, as in the Active Inference tutorial, the paper. So marginal free energy says that we compute the KL divergence between the posterior and the prior, and the prior here is computed from the transition model, not the normal distributions of mean of 0 and the standard deviation of 1. So here is the general model of trying to build a deep active inference model, right? So here's first of all, we're trying to encode, right, using the posterior functions. So in traditional active inference, this is the PS given O is the transpose of the likelihood matrix, P of O given S. This is normally learned with the categorical distributions and using Dirichlet conjugate prior. And then in the deep learning literature, this is often known as the encoder. That's often parameterized by the neural network. And then O here is often be an image, and state here is just some hidden vectors that we are trying to compute. And then next one is the likelihood function, right? So normally we text in the states of the agents, and then we're trying to estimate the predictions, the observation predictions, right? So in traditional active inference, this is known as the likelihood matrix or likelihoods per se. This is also learned with the categorical distribution and using Dirichlet conjugate prior. And deep learning literature, this is often known as the decoder that is often parameterized by a neural network. So as we know the variation of free energies formula, the complexity term is KL divergence here, right? And the accuracy term is the minus log PO, right? Even S. So here we compute the KL divergence between the encoded states and the actual prior states here. And then next one, we compute the actual log probability of the predicted observations and the actual observations right here. And that makes the whole objective where we compute the two objectives right here. That's also the variation of free energy formula. So we just talk about how inference in active inference work, but there's more. We want to build an inference system that can interact with the world, right? So when it comes to interaction between the agent and the environment, we also need to have actions and also roll out in time step, right? So basically, we have another element here, which is AT. And remember, I also mentioned the transition model, right? So after we take an action in the world, the world or the environment evaluates one step, right? And it changed its own state and then emits a new observations. And we as agents or intelligent system also try to predict, given the action and the current states, what is the next states, and this states is the prior over the states of the next time step, where we have not made the observation OT plus 1 yet. So after we have the ST plus 1 as prior, we do the same process as I have mentioned before. So we make the observations, try to change our belief after making that observations, and then learns from the new observations to trick our prior into the posterior. So here we learn it using the variation of free energy or marginal free energy formula. So as you can see from the previous slides, we do need somehow to plan the actions to interact with the world. So if we're trying to minimize or surprise with the current observations, so in the action planning, we aim to take actions that minimize the similar free energy term in the future. This is often called as the expected free energy, by the way. So in here, we introduce some new terms, right? Theta is the modal parameters. The reason why it is here is because we want to also compute the modal, the surprise over the modal parameters, or the uncertainty over the modal parameters. So you can see that the expected free energy in the future is kind of similar to the version of free energy formula. It only needs another modal parameters, and given the pi or the actual planned policy or planned actions. So after a lot of derivations, right? I will not getting into like the real derivation here, but here's the end results. That's something minus the weighted means of the log p of ot, right? So I'll just focus on this term, is because this is the goal of the talk today. So basically, this term log of POT is the expected free energy derivations of the instrumental term. So basically, this also means that we are trying to maximize we're trying to take the action that maximize the future observations that matches our prior preference distributions or what we want, right? So normally, to learn to take actions to align with what we want to see in the future, we often need to craft and provide the prior preference manually in advance, and then we take the action based. We take the actions that maximize the likelihoods given that distributions. But this is often not really practical in the realistic world, and because we cannot like craft the manual distributions like every single time we encounter a new environment or encounter a new task, right? So what we can also do is we can also provide a goal state or goal observations directly to the agents, which is more practical. But in the end, the prior preference distribution is very sparse, and this provides little to no learning signal to the agent. As you can see on the figure on the right and the left, right? So left is the prior preference distributions, and right is the single goal state distributions or goal state image. So what can you do to dynamically produce the prior preference, right? We can try to learn a prior preference model, right? That produce a goal image at each time step. So here is on top is the prior preference model that predictions, right? And in the bottom here is the model prediction of the future given the sequence of planned actions. So we are trying to say that we want to take the actions that have the rollout in the future's predictions matching the prior preference rollout in the future. So how do we do that? We first have to learn the model first, right? So in learning, we can try to say that each time we achieve a goal, then we mark the whole trajectory as the prior preference trajectory or the positive trajectory or expert trajectory. And then for each observation marked as goal, we use a deep learning, like another deep learning model to estimate that observations, for example, right? And then in inference time, we actually train, when we train the policy planner to propose the actions, right? We make the policy planner proposing the actions first, and then predicts the future observation based off of that actions that is planned by the policy planner. And then we actually learn the policy planner based on the signal that is emitted from how aligns the predicted future observation would be to the predicted goal. The predicted goal here is the actual prior preference model outputs, right? Then we train the policy planner with the mean square error or some kind of objectives that predicts some kind of objectives between the predicted goal image and the predicted future observation. So there's this problem where it exists between all these learning schemes because it is very computational expensive. So it is generally expensive because we have to work directly with the images. So for example, in learning, we have to use a decoder of the of the prior preference model to actually predict the goal image at each time step, right? In inference time is also computationally expensive, is because it has to learn from the images itself and compute it down from the back propagations will have to flow through the decoder back to the action planner. So here it comes to the actual methodologies. We actually use dynamic preference learning in the state space instead of the observation space, right? So first of all, I want to talk a little bit about the world model. So this model architecture is basically what I have just drawn in the background sections, but this looks with robots images. So in here we have the observations, OT, and here's also the observation, the same observations, OT minus 1 OT. And we text in the encoder. Encoder is the encoder posterior. Text in the encoder, and we have the transition prior, and then we have the decoder, right? Encoder encodes the image in, have the states, and then decode the image, the state back to the image, and then computes the accuracy loss. Right, accuracy loss is minus log prop of the PO given S, as we have discussed in the variational free energy sections. And then the complexity is the KL divergence term between the posterior and the prior, right? So how do we compute the priors? We compute from the previous steps states, and then we use the transition model to estimate the next state's prior, right? So that's how we can get the prior. So current work and popular works regarding the world model or generative models often integrates the model called RSSM, which stands for recurrent state space model in the transition model. So it's to zoom out a little bit. We are trying to integrate some kind of temporal information through time, right? So that's the state of the environment or the states that we're trying to predict be more accurate, and it carries more information with time. So for example, we cannot encode the enough information from just a single image, because, for example, there can be like position and velocity, right? The velocity is acquired through multiple images and cannot be acquired from a single image. If that makes sense. So what we often do is we try to integrate a recurrent neural networks that takes in the previous states or the previous recurrent states, h by t minus 1, and then we also takes in the encoded observations, and then in transition we produce the recurrent neural network. We produce the current recurrent states, and also predicts the outputs to put into the transition model. And also it's the recurrent states will also be served as inputs to the posterior network. So that's basically the idea. And then the other way around, we could just do the model as normal. So in active inference, the agent takes in the actions that it believes that would lead to its preferred outcome using instrumental signal. To construct this prior preference, Pascal has, for example, provide a goal state observations directly to the agents. For example, Mazzaglia in 2021 with contrastive active inference. We can also manually craft a prior preference distributions. We can also dynamically produces the preferred observation at each time set. But as I mentioned already, all these methods is one way or another very expensive, or it's very not practical or in the real world applications. or it is very computationally expensive for dynamically producing the actual observations for the goals. So we can also use behavior cloning, but its trajectory diverges from the training trajectory due to small mistakes made by agents as well as environmental stochasticity, and also it is because of independent and identically distributed assumptions of positive expert data distribution. So we can we will kind of avoid it because it's not gonna be the same, right? So two distributions of the actual trajectories in the environment will not be the same as every single positive trajectory of the expert data. So to tackle this, we try to leverage a small quantity of seed imitation data to learn a neural network that's dynamically produce the preference over states, not observation, but states at each time step. So this effectively produces an easily generated dense instrumental goal signal. And we also design the agent such as that it moves according to the trajectory that is shaped toward its own estimation of the future states or future preferred states. So it's trying to nudge its own trajectory towards the imitation or positive data distribution. So as you can see on the figure on the left, so you can see that in behavior cloning, it's trying the actual trajectories diverges away from the actual imitation data, where the prior preference over the states trying to trying to be shaped toward the imitation data itself using the model signal. And RAIF is our agent. Is called robust active inference. And it learns from both epistemic signal and instrumental signals. But in here, we'll just focus on the instrumental signals and how to construct it. So, yeah, so basically we use a decoder or the likelihood functions of the generative model to only visualize the preferred observations. Note that in training or test time, we do not use the model learning. We do not use the actual observation goal observations by itself. We only use the hidden states. So the goal here is to get the states, the goal states at each time step be predicted by the prior preference model, right? So you can see that's on the top here is the real trajectory, and the bottom here is the actual dream. That's the dream of the robots that it wants to be, right? And then we are predicting that dream, right? So here is the actual model of the contrastive recurrent state prior preference learning. So basically, it has also similar architecture to the RSSM, to the world model. It also have an encoder. Here, it also has the transition, but it does not have the decoder. So how do we actually learn this prior preference model? So first of all, we learn the generative world model as normal, right? But when we say whenever whenever the trajectory is positive or a successful trajectory, we try to contract the state of the crispy. I just call it crispy. We try to contract the state of crispy to the world model state, and then whenever the trajectory is negative, we try to push away the states from each other, so that the crispy model can only predict the positive states. So how do we determine if it is a positive trajectory or the negative trajectory without having a very sparse signal? So we will have a thing called raw or the prior preference signal. So how do we compute this raw signal? So imagine this is the real trajectory, and it is a successful trajectory, for example, right? So we're trying to compute the prior preference rates by having the rates of the successful states is at 1, and it starts from 1, and then it decays backward. So it decays very fast, and if so in this like really far away states from here, they do not have enough signal because there's no goal, like there's no direct goal from that states. And then there's real trajectory that is failed, right? You can see that the mountain car cannot reach the flags on the right here. So whenever it's failed, we can just flag the very, very last observation as -1. And then we start to decay backward negatively. And then we have the prior preference rates signal as very negative. So the reason why it has to be last is because we want to blame the last observations hardest. So in order for the agents to just push away from the failing states very, very, very strong in the very last stage. So in the real trajectories that have like multiple successes, we try to put all the 1 in all the successful states and then just decay backward. That's similar to how we would decay backward in a single success case. So with that said, we now know how to compute the rho, and then this will serve as the dynamic signal to the contrastive loss, and it creates a dynamic behavior of the contrastive loss that's trying to either push away or contract the 2 states of the crispy state and the world model states. So, for example, in here, if there's positive rho, the contrastive loss would be contracting all these states together and maximizing the similarity between the crispy states and the world model states. And then we also learn to minimize the KL divergence between the the posterior and the prior over the states of the crispy model. This is because we want to estimate the transitions, right? So we transition to the next goal state, and then this goal state has to match the actual goal. That is the current state of the RSSN model or the world model. So in contrast, right, if rho is negative, then we're trying to push away all these states away, right? So we're trying to maximize this distance or minimizing the similarity between the world model states and the crispy state. And in here, notes that there's no complexity objective is because we don't want to predict the next goal that is the failing state. That's basically the idea. So that arrives at the general formula for the objectives of the contrastive recurrent state prior preference model. Basically, it is just masking out the sign of the rho and then multiply with the KL divergence or the complexity between the posterior and the prior of the crispy model. And then we minus the rho and sim of the actual predicted states and the world model states. So sim here can be very much any kind of similarity functions, for example, cosine similarity. And then in our work, we actually use the actual cosine similarity. So in train time, we have just talked about training time, right? So we have successfully, assuming that we have successfully learned the crispy model that predicts the future goal. And in inference time, we use this crispy transition model to estimate future rollout trajectory of the goal, right? So we can see that on the top here is the observation, actual observations, and in the second row is the actual prior preference rollouts or predictions of the future goal, given the current observation. So, given the planned actions, we're also training the planned actions, right? So the actor trying to predict an actions given the observations, the predicted observation in the future. So we're trying to say we're trying to compare the actual prior preference rollouts with the actual predictions given the actions. And then we're trying to learn the action planner based on the signals or how diverged the future goal is to our future predictions of the world given the actions. So there can be so many reinforcement learning agents and active inference agents that can utilize this technique of prior preference learning. So active inference agents, I put my works here. It's RAIF, and then there's also Chris Buckley's work and Baron Smith's work about deep active inference in variational policy gradients methods, and also Otto work is the scaling of the active inference in POMDP and Norton-Carr environments, and so on, right? So reinforcement learning agents, there's all these sorts of actor predicts algorithms like Dreamer series, soft actor critic, dreaming, DDPG, TQC, and TD3, and so on. So there's a lot of agents that can utilize the framework because there's no change in the original architecture. There's just an add-on to how an agent would apply the prior preference learning signal into the system. So here's the actual flowchart of the agents. Basically, we start the agents, and for each episode, we evaluate the environment using the world model and the policy planner. Actually, basically, we evaluate in the environment. We let the robots play, we let the robots do the task, and then we collect the data and add them to the replay buffer, for example, right? And then we can get the main training agent logic. And then first of all, we sample the training data from the buffer. So in here, we trying to have, we also have to use the self-imitation learning buffer. So self-imitation learning is a very good technique, normally to balance the number of successful and failing trajectories. And we also learned, so first of all, we learned the world model encoder, decoder translation on RSSM. And then we trained the epistemics model, but in this case, we don't need to care about it. And then next is the contrastive recurrent state prior preference model from the data. And then next, we imagine the future trajectory using the world model and the policy planner, right? We try to estimate the future actions to be what is the optimized future actions, for example. We estimate the future action based on how the current state is, and then the world model will be continuing to roll out in the futures, and then we dream of the futures. And next is the part that we actually infer on the crispy model. We use a crispy model to imagine the future preference trajectory given the goal, given the current observations, and we predict the future goals, rollout goals, right? So after that, we learn the policy planner, right? Using the instrumental signal. The instrumental signals here is computed from the difference between the future goal and the predicted future dream of the world, right? And then with that, the policy planner can learn from the instrumental signal. So here's our preliminary results on active inference agent. So basically, we can see the two top rows is the mountain car environment, and the two bottom row is robotics meta world push button environment. So let's look at the first row, for example. The observation here is a mountain car that has reached the goal, and for each observation here, we predict a preference rollout or preference or a goal state at that single time step. So in here we can see that if the car has not have the momentum yet, then we have to build the momentum by predicting the car going to the left, for example, right? And then after it has built some kind of momentum, we're trying the actual prior preference model predicting the car would go to the right, go forward, right? When it goes here, and the prior preference model will predict the car to be going closer to the goal, something like this. So the same applies to the robot environments, where the actual observation is the third row, and the prior preference rollout is on the fourth row. So we can see that it is also trying to estimate the dream, or the dream of the goal of the robots is to actually push the button. So there's different kind of experiment setup that we are trying to learn. Basically, we have 4 trials on each environment, and then we train the experts using soft autocritic or PPO, proximal policy optimization, to collect a small amount of seed data. Normally is about 20 episodes, something, 20 to 30 episodes. So we test mostly on 3 main environments or suits. First of all, is mountain car. There's only 1 task. Meta world is 13 tasks. So here's all red robots. Here's meta world, and then the robot suit we have 2 tasks. And then regarding camera setups, we use 3 views for meta world and 4 views for the robot suit. So the green check mark here denotes that the robot has successfully solved the task. Here's the robot suit, open door. And then here's robot suit lift, where it can successfully lift the block. And here's more solving agent tasks. So basically, agent with Crispy exhibits an ability to perform successfully early on. So agent without Crispy struggle to actually succeed on solving the environment. And we also test on our other environment as well. For example, gymnasium robotics and risk tasks. You can see in the middle image over here. So actually, we go to the discussion sections. So actually, I want to make a note that with respect to the Crispy submodel, our model utilizes contrastive objectives to adapt its parameters. So basically, it solely learns on estimating the world model encoded states while pushing itself away from undesired world model states or trajectory. So this does not require the learning of the decoder. So we only make sure of the learned decoder in the generative world model to visualize the preferred observations from the estimated Crispy states. So experimentally, we remark that this is we only use this decoder as an auxiliary tools to prove that's the states of the contrastive recurrence prior preference model is useful. So theoretically, behavior cloning will be unable to achieve a great success in multi-goal environments due to its reliance on a fixed and finite size imitation sample pool. The expert trajectory in this fixed pool might further differ from the actual trajectories that the agents needs to take to solve the problem at hand. For example, there's a distributional gap in observations, and therefore, it requires different sets of actions to be taken. For example, right? So on the other hand, right, Crispy learns to produce dynamically the goal states and not the goal observation, right? So we can empirically confirm in simulation that our agent with dynamic prior preference learning does not suffer from the goal mismatch problem in the training phase. So this is very applicable to the multi-goal environments. So we can see that this prior preference learning techniques has a lot of practical applications in different robotic tasks. With, for example, those with potential dangers in the operations and functioning. For example, when human safety must be considered, right? For example, trying to drive a autonomous driving car system where it has to have, or it has to predict the future goal, right? The future goal is not to hit the human, for example, right? And we can also make a lot of advancement in imitation learning in research community, and it can be applied by the wide range of reinforcement learning and active inference agents. And then the last one is to scale the active inference agents on the real world robotics agents. So future works actually considered importing or integrating the dynamic prior preference learning in latent state space model, for example, variational dynamics, discrete variable autoencoders, or tension weighting models. And also, there's another models, physical neurorobotic system, which entails an embodied and active and survival-oriented formulations of active perception and world model learning. So in this talk, we have discussed a lot of ideas about being able to estimate the particular goal or preferred states at any particular time step is very useful for cognitive control agents. So as our results demonstrates, the agent can then learn to adapt to take actions that leads to a estimated goal. And then in contrast to the approaches taken in the imitation learning and behavior cloning literature, which train the agent's policy solely based on the fixed collected expert data sets in our framework, the expert signal is estimated dynamically through an adaptive prior preference model, right? Closing this gap, the domain gap between the actual trajectories and the collected training imitation trajectory or preferred trajectory. And then we also discussed the generative model and encoder-decoder transitions and how the variational free energy work, and then how to learn the model. And then we discussed the contrastive recurrent state prior preference model with a self-revision mechanism, and then discussed the model learning and then inference objective and how to integrate that into the agent's planar learning system. And then we show the results for the robotic task, and then mentions how it can be applied to different fields. So that concludes my presentation, and thank you very much for listening.
Thank you. That was amazing. Really great job with the background math, done only like a PhD student can, but it was great to see how you brought it all together and connected your research to it all at the end. So thank you. That's all for now. See you later.
Thank you. See ya.
Okay.
Hi.
Welcome back. Welcome back. Hi, Denise.
Hi,
Thank you
Dan.
for joining and looking forward to your presentation. So take it away.
Oh, thank you so much. And thank you for having me today. Today, I am going to talk about the potential impact of decentralized AI through active inference and spatial web technologies. And what we're really going to be discussing is the potential aspects of this next era of computing. It'll be incorporating a lot of the research that you're hearing about here over the next 3 days. And in my talk, decentralized AI is kind of taking a main focal point here. And there's a couple of aspects in technologies that are evolving right now that I think it's really important to be aware of. And they factor into what I'm going to be talking about today. So one of the main things that is occurring right now is our internet is evolving. We have a new protocol layer that's layering right on top of the other protocols that are part of the same internet that we're talking across today. The difference is what these protocols, HSTP, Hyperspace Transaction Protocol, and Hyperspace Modeling Language is the programming language. What these are going to enable is for us to have programmable spaces. So instead of just programming pages in domains with content, we are going to be able to program digital twin spaces of anything. And this is going to enable context to be baked into everything in every space. So all of the attributes about various things in various spaces and nested ecosystems and all of their interrelationships to each other. So one of the things this is going to enable is active inference agents to be distributed across our internet. And I see this as the next wave of innovation. And through active inference, these agents will be aware of each other and the network. They'll be able to sense the world in real time and learn from each other. And this is going to provide unprecedented levels of interoperability. So what we're talking about here is first principles, automated systems, and distributed collective intelligence. So first, let's look at the challenges in traditional centralized AI structures or architectures. Centralized processing constraints, you have high energy demands and scalability issues, limited adaptability to real-time changes. And, we're all familiar with the limitations of these deep learning models. They require massive amounts of labeled data and processing power. They have limited ability to generalize across different tasks and environments. AI models lack adaptability to real-world complexity. They're only good for one thing at a time, optimized for one type of an output. And they lack interpretability and transparency in decision-making. They have high computational resources leading to high costs and inefficiency, and they struggle with generalization across different scales and tasks. Now, we need decentralized AI, and decentralization really matters because it increases resilience and scalability for autonomous systems. It reduces reliance on central servers and data hubs, and it enables autonomy across distributed networks. So this bridges the gap in AI. We move beyond centralized AI for scalable autonomous systems that can operate independently and locally. Now, we're all familiar with this guy here, Dr. Karl Friston. And he gave a great talk first thing this morning on renormalizing generative models. So what I'm going to be talking about are various components in some emerging technologies along with active inference that potentially realize this research paper, Designing Ecosystems of Intelligence from First Principles. Now, this paper was published in December of 22, and it really laid out a new framework for autonomous intelligence that mimics self-organized systems of nested intelligence found in nature. And in this paper, it described a cyber-physical ecosystem of natural and synthetic sense-making in which humans are integral participants, what we called shared intelligence. And this, in the paper, it says this vision is premised on active inference, a formulation of adaptive behavior that can be read as a physics of intelligence, and which inherits the physics of self-organization. And in this context, we understand intelligence as the capacity to accumulate evidence for a generative model of one's sensed world, also known as self-evidencing. And at the end of the abstract for this paper, they also note, we also consider the kinds of communication protocols that must be developed to enable such an ecosystem of intelligences and motivate the development of a shared hyperspatial modeling language and transaction protocol as a first and key steps towards such an ecology. So what I'm proposing in this, and what is proposed through all of this technology together with all of the various parties that are involved in building these components, is that the future of AI is shared, distributed, and multi-scale, an entirely new kind of autonomous intelligence able to overcome the limitations of machine learning AI. And as we know from understanding active inference, this AI is knowable, explainable, and capable of human governance. And it operates in a naturally efficient way. There's no big data requirement, and it's based on the same mechanics as biological intelligence. It learns in the same way as humans. So what I want to do is start with the spatial web protocol first, because this is kind of the framework for these agents to be able to have this distributed intelligence structure. So what is the spatial web protocol? It's just the evolution of our internet into spatial domains. So people refer to it as Web 3.0. It's just the next evolution of the internet. But this protocol has become a global standard, a new global standard. For the last 4 years, this standard has been in development with the IEEE, which is the largest core standards body in the world. And back in 2020, they deemed the spatial web protocol a public imperative, which is their highest designation. And this summer, it was voted and approved as the new global standard, and it's in the final administrative cycle with the IEEE before it becomes public. So there's a couple of things that are happening with this. Through HSML, the programming language for this new protocol, all emerging technology, whether it's IoT or AR, VR, distributed ledger technology, all of these technologies, they're all going to be able to converge across the internet because they will have a common language for interoperability. And in that, you also have a language that AI can understand and communicate together and communicate with these various aspects of technology as well. So this is going to produce the next era of computing, and Deloitte called it back in 2020. So it's the next evolution of the internet, and it's going to be empowered by active inference AI. Now, just to kind of understand what this means for the internet, let's take a look at what a website domain is today. With the World Wide Web, a domain basically contains a website, and these websites, they serve up content. So whether it's, images or video or audio or, information data, that is what websites are capable of doing. Now, a spatial web domain is quite different, because a spatial web domain could be anything in any space, right? And it can be programmable. A spatial web domain is an entity with a persistent identity through time that has rights and credentials. So you're talking about going from a library of pages in our internet to the internet of everything. And HSML becomes a common language for everything. So it provides unprecedented levels of interoperability between all current, emerging, and legacy technologies. It's a programming language that bridges communication between people, places, and things, laying the foundation for a real-time world model for autonomous systems. And what you have are programmable spaces. HSML is a cipher for context. Anything inside of any space is uniquely identifiable and programmable within a digital twin of Earth, producing a model for data normalization. And from this, we get adaptive intelligence automation, security through geo-encoded governance, multi-network interoperability, and it enables all smart technologies to function together within a unified system. And then this produces a knowledge graph and digital twins of anything, everything, potentially our planet. So as this knowledge graph grows within the programming of all of these spaces across the network, you get this universal domain graph that enables a digital twin of our planet and all nested systems and entities within it. We get nested ecosystems. There will be intelligent agents, both human and synthetic, across this network. They will be sensing and perceiving continuously evolving environments, making sense of the changes, updating their internal model and what they know to be true at any given moment, and acting on the new information that they receive. So why do we need a spatial internet protocol? Well, the increasingly graph-like nature of global data, the opportunity for automation and autonomic activities using context-aware cognitive AI, the need for composable systems and applications, including the governance of such systems, the intrinsic need for secure transactions, the rise of machine learning and neural network computation and edge computing, the need for explainable AI and robotic governance, and the rise of IoT and sensor mesh. And some of the guiding principles of the spatial web standards are spatiality, representing information as locations and relations in hyperspace; ownership, users own their data and digital property; security, secure data collection, transmission, and storage; privacy, individual control over digital identity and personal data; trust, reliable, permission-driven validation of users, assets, and spaces; interoperability, seamless navigation and asset transfer across spaces; and responsibility, creating technology ethically for the benefit of humanity. And what has become of these global standards is a socio-technical standard. So the spatial web is a socio-technical system of systems. It takes into the account so the development of the spatial web must address both technological as well as sociological considerations. Socio-technical standards integrate and balance the technical, social, physical, and legal use of technology. And the spatial web standard is a socio-technical standard. And what this results in is multiple scale cognitive computing. So the spatial web plays the role of a collective nervous system for smart infrastructure. It hosts cognitive computing, inference, perception, learning, and action selection. By combining and abstracting distributed information, the spatial web enables the formation of complex ideas and facilitates decision-making. Cognitive computing occurs at multiple scales in the spatial web. Individual nodes host cognitive computing functions, and networks of nodes collectively perform emergent cognitive computing. So HSML, hyperspace modeling language, it's a human and machine readable modeling language and semantic data ontology schema. There are some key elements to it. There are entities, activities, agents, contracts, channels, credentials, domains, and it includes hyperspace and time. So HSML enables the expression and automated execution of legal, financial, and physical activities in the spatial web. And all of these entities are identifiable and knowable by these intelligent agents through this language throughout the network. Now let's look for a second at the agent aspect, agents and activities. So agents, and that can be human agents or synthetic agents. But these agents are entities that sense, respond, maintain a model of their environment, and take actions to achieve goals. And the activities that occur, they're single actions or partially ordered sets of actions that are performed by the agents, and they unfold over time. So agents interact with domains and other agents to perform activities in the spatial web. So what the spatial web facilitates is a distributed ecosystem of intelligence. If you look at current state-of-the-art AIs, they're siloed applications. They're built for optimizing specific outcomes, and they're really unable to communicate their knowledge frictionlessly and collaborate with other AIs. But this facilitates an ecosystem of intelligence that is a self-evolving system. It's learning moment to moment and upgrading its world model. And in that way, it mimics biology while also enabling general intelligence. So this is shared intelligence at the edge of everything. So how active inference works in the spatial web, it enables real-time decision-making. You have agents that are predicting and adapting to their environment from their frame of reference in the network. They're continuously learning from their environment, enabling real-time adaptation. And unlike traditional AI, which relies on pre-programmed rules and static models, Active Inference continuously updates its models based on new data, allowing it to adapt in real time. So these Active Inference agents would seamlessly communicate in real time with each other, sharing their knowledge and perspectives and learning from each other. These Active Inference agents excel in handling complex, uncertain environments by continuously minimizing uncertainty. In fact, they can quantify their level of uncertainty, and this makes them suitable for applications where conditions are constantly changing. So decentralized AI takes the processing to the edge devices. You have a distribution of processing and power. Superpowered GPUs are not required. The processing can take place on local devices throughout the network with infrastructure that already exists, like your laptop or your mobile device, or devices that haven't even been invented yet. But we're already seeing a lot of those kinds of devices coming into play with, Apple Vision Pro and the Meta glasses and different aspects of these technologies. So the processing takes place on these local devices throughout the network. You have faster response times and reduced network congestion, and it uses real live data, real-time data from IoT sensors, machines, and ever-changing context that's embedded in the network. So this is the sensory information that's coming in for these Active Inference agents so that they can, perform this action perception feedback loop and continually update their model of the world, of their environment from their frame of reference. And it eliminates the need to tether to a giant database. Active Inference agents throughout the network learn and adapt from their own frame of reference within the network, enhance data privacy by minimizing centralized storage, and it minimizes complexity. It uses the right data in the moment for the task at hand. And with HSTP, with Hyperspace Transaction Protocol, there's natural guardrails included in this framework. So it creates a secure, ethical, and user-centric environment for AI applications, fostering trust and reliability in digital interactions. You have data privacy and sovereignty, transparency and explainability, security and authentication, bias mitigation, ethical AI guidelines, interoperability and standardization, user empowerment and control, accountability and governance, safety and reliability, dynamic policy enforcement. And what this results in is an intelligence at scale. Through this network of distributed intelligence. It enables a cognitive architecture of the collective intelligence of multiples of agents that continuously communicate, coordinate, and collaborate with each other. You have individual and specialized intelligences together on a common network, speaking a common language, HSML, efficient and powerful cross-communication to perform tasks, regulate systems, and address problems in real time. And it scales up and grows in tandem with humans. Through HSML, we can take human laws and guidelines, make them programmable for these agents to understand and abide by in real time. So we're talking about unprecedented levels of cooperation between human and machine intelligence. And what you get then is an ever-evolving collective intelligence. Decentralization is an imperative for intelligence at scale. These agents represent scores of people from all over the world, sharing their individual and specialized knowledge, all coming together on a common network. And it's based on each agent's own world model. You have unique perspectives from whatever frame of reference within the network, nested ecosystems and levels of self-organization, and collective shared intelligence. So the idea is that anybody can impart their knowledge and their wisdom into these agents from wherever they are in the world. And this actually acts to preserve all of the cultural differences, all of the belief differences, the governing styles. People, whether they're in Kenya or Singapore or anywhere else in the world, they should be able to create these agents to solve their local problems and then share that with the world, because then these agents can share their intelligence with each other. So the Spatial Web Protocol enables a decentralized, secure, and interoperable web with the potential to profoundly transform global industries and everyday human life. Now, let's dive into kind of the potential that exists for this idea of RGMs, these renormalizing generative models, and the spatial web. And we heard a great talk this morning by Dr. Friston. He talked a lot about the science behind these RGMs. So I'm going to kind of maybe break down some of the aspects of how these work as leading up to then what they can do within this potentially within this architecture. So, with RGMs, one of the interesting things is that it's a universal architecture. They're a unified scale-free framework for AI that's capable of reasoning, learning, and decision-making. And they can generalize across multiple tasks, handling small and large-scale data efficiently. They combine perception, learning, and planning into a single system, and they can be used to learn scalable architecture over space and time, similar to human thinking. They require significantly less training data than traditional models while achieving superior results. So, what are these RGMs? They're a new class of AI models based on active inference. They use renormalization to simplify complex data into hierarchical structures, and they operate on the free energy principle to minimize uncertainty and adapt in real time. So the significance is that they represent a leap forward from traditional deep learning methods. They reduce data requirements and improve efficiency. And it's one single framework for all applications. So the science behind RGMs, renormalization, and multi-scale learning. Renormalization is a technique from physics that's used to simplify complex systems to maintain consistency at different scales. And RGMs break down data into multi-scale representations. Hierarchical structures. RGMs are actively learning from small details to large patterns simultaneously. And they analyze, like with an example would be like an RGM can analyze an image by recognizing edges, then objects, then scenes, and understanding the concepts at every scale. So key innovations and advantages of RGMs, why they're superior to traditional models. They learn efficiently with less data. It's a unified system that handles perception and planning simultaneously. And they understand conceptual relationships, not just patterns. And they can adapt to new environments with minimal training. Aspects of them are scale-free modeling, renormalization, discrete representation, hierarchical structures, fast structure learning, unified perception and planning, and explicit handling of uncertainty. So if you look at how the brain processes data, we perform coarse graining all the time when we're learning, right? We break down sensory data into hierarchical patterns that help us focus on the most relevant information. Kind of this chunking of concepts to grasp different aspects of whatever it is that we're learning or focusing on in the moment. And RGMs can mimic this approach by processing data hierarchically, focusing on important patterns. So it's a first principles approach, using a way to simplify models without losing important information. They can model space and time dimensions like we do, and can learn the causal structure of information. And it helps handle large-scale problems efficiently using less data and less energy. Now, when you consider scale-free modeling, scale-free modeling, these RGMs, they operate across different scales. So from very fine details to high-level complex systems. So unlike deep learning, which struggles when moving between small and large-scale problems, this scale-free architecture allows RGMs to seamlessly work on a variety of problems, including small data problems and large-scale strategic planning. So when you're thinking of the concept of scale-free, this is a great example here of a green apple. You can see the green apple as a concept of just, pixels in an image or a volumetric object or on a branch on a tree or in an orchard. And, the way that these RGMs can model these conceptual understandings of things is it can understand all different scales of what a green apple is. So when you think of like the supply chain or factory operations or anything like that, these agents can understand what's happening across the manufacturing line on a very local level, but also what's happening across the entire distribution line throughout the entire system. So they can predict both short-term movements and long-term outcomes. So the fine details as well as larger outcomes with the high level complex systems all at the same time. And they don't lose accuracy when switching between local and global data scales. So hierarchical modeling in RGMs, hierarchical data processing, RGMs process at multiple levels of abstraction from fine-grained details to high-level concepts. They use recursive learning. They continually loop over data, learning at each level, continually refining their understanding of concepts as they process new information. And you get hierarchical representations. They build models of the world by zooming in and out of different layers of detail. And this is similar to how human cognition processes both micro and macro scales. So, think about when you're thinking about the concept of driving a car. If you're talking to somebody about driving a car, or you're focused on the aspect of driving, you're not thinking about the car as all of its various parts that make up that complex system, like the brakes and the steering wheel and the seats and every aspect of the engine. You just call it a car, right? Because that's all you need to know in the moment for whatever you're doing with that concept. And so this is kind of a similar idea. And this layered approach allows RGMs to understand complex multi-scale problems without requiring vast data sets. So conceptual modeling for decision making. RGMs then focus on conceptual modeling versus just mere pattern recognition. Deep learning can recognize patterns, but struggles with conceptual understanding. It can recognize correlations without understanding relationships. And it can recognize patterns, but it doesn't understand the underlying meaning. And RGMs, on the other hand, focus on conceptual modeling. They capture multi-scale, hierarchical structured concepts that represent both fine-grained and abstract features. It builds a hierarchical understanding of the world, capturing cause and effect relationships. So RGMs understand the why behind patterns, not just the what. And the key difference, RGMs are not just a better generative AI, but a transformative AI framework that builds a hierarchical understanding of the world. RGMs can reason about cause and effect relationships, making decisions based on conceptual understanding that are more aligned with real-world outcomes. So how do RGMs leverage active inference? By incorporating active inference, active learning, and active selection, while incorporating real-time data to adapt its predictions and actions. So what you get is real-time learning. They adjust their beliefs based on new sensory input, making decisions on the fly, optimizing both learning and decision-making processes. And they also are able to have unified perception and planning. So deep learning typically separates perception, like recognizing an object, from planning, like deciding an action. RGMs can combine both in a unified model. They handle both within the single model and learn concepts that guide both recognition and future decisions. So for example, you can have an autonomous robot that can recognize a door handle and also plan how to open it using the same model. So what does all this have to do with the spatial web architecture? So the potential that I see with RGMs is that the nature of how they work fits very well with the nature of this architecture within the spatial web. And just to kind of bring you back to what I was talking about earlier, you have hyperspace transaction protocol. This manages data flow between interconnected systems, and it facilitates interoperability between different AI systems. And the hyperspace modeling language provides a common language for these systems, enabling computable context and decision-making. And it provides a shared framework for context-aware decision-making. So this protocol aims to create a standardized way for different technologies and AI systems to interact and share information across programmable spaces within our global internet. And this unified model, this becomes a unified model for diverse applications, handling complex multi-scale systems through unified perception and planning. It's a single framework that can handle multimodal tasks. So you have versatility. They can perform across multiple applications, whether it's object recognition, natural language processing, strategic planning, using a single universal model, and it reduces the complexity. It integrates the data analysis, the perception, and the strategy execution, which is the planning within one model. So you have cost savings, it reduces the need for multiple specialized AI models, it streamlines system management and saves resources. So how the spatial web enhances the RGM capabilities. The combination of this scale-free active inference with the spatial web protocol could enable seamless integration of the physical and digital. These protocols allow RGMs to operate across distributed networks, exchanging insights and information between physical and digital environments, enabling more sophisticated IoT applications. Context-aware computing. Through the spatial web, RGMs would operate in context-aware environments. These agents adjust their behavior based on the physical and digital surroundings. And interoperability. Multiple RGMs, these active inference agents and autonomous systems, can operate in different environments, whether it's your home, smart city, businesses, and they could communicate, collaborate, and coordinate actions through the hyperspace transaction protocol. They're energy efficient distributed intelligence. Instead of relying on centralized energy intensive data centers, intelligence could be distributed across networks of smaller, more efficient devices. And this creates a nested ecosystem similar to a Holon architecture. And if you're not familiar with what a Holon is, it's something that can be both a whole in and of itself and also part of a larger system. So the spatial web and RGMs would form a nested ecosystem where each node in the network, whether it's a domain, device, agent, or subsystem, functions as a Holon. It's autonomous, yet interconnected, contributing to a larger system's goals as part of the larger interconnected network, like a smart city infrastructure. Your smart home could contribute data to your neighborhood grid, which informs the city infrastructure decisions, all while functioning independently. If you look at this picture here of, part of a supply chain image, each item packed inside of each of those boxes is a whole in and of itself, but it's subject to and it's part of the larger system, the box. The box is subject to the trucks that are moving it and distributing it, or whatever's happening within the factory with those boxes. And then that factory itself is its own whole that is subject to a larger ecosystem of the entire supply chain as a whole. So when you're looking at what this next era of computing really enables, it's just nested ecosystems that can be empowered by this natural intelligence. And Active Inference AI and the Spatial Web Protocol can work together to create sophisticated, adaptive systems at various scales. So RGMs for autonomy and self-organization. With recursivity, the scale-free models naturally form a nested hierarchy. Each level of abstraction in the model is complete in and of itself, and yet part of a larger whole. Autonomy and cooperation. Active inference agents exhibit both autonomy in their decision-making and the ability to cooperate with other agents. And self-organization. The renormalization technique introduced in the paper allows the system to dynamically organize information at different levels of conceptualization, similar to the self-organizing nature of holonic systems, or these nested ecosystems. So this last part, I want to explore the transformative potential of decentralized AI for the future of intelligent systems. So the impact of distributed collective intelligence, the impact on this next era of computing would be enhanced problem solving and innovation, increased efficiency and scalability, democratization of knowledge and technology, resilience and robustness, enhanced decision-making, personalized and context-aware services, ethical and responsible AI, collaborative platforms and ecosystems, enhanced learning and education, empowered communities, accelerated scientific research, and environmental and sustainability solutions. And the implications for future systems and society. The convergence of RGMs in the spatial web could transform industries, enabling decentralized, context-aware systems that operate with minimal human intervention. Industries that could be impacted, smart cities, you would have autonomous systems that improve efficiency at all levels. Global supply chains, RGMs could optimize processes from local shipping to global networks. Personal to critical systems homeostasis. So whether it's personal devices or critical infrastructure, a continuum of intelligent adaptive systems can maintain homeostasis at each level. In our healthcare systems, personalized treatment by integrating real-time data from wearables and medical records. Education, we can have AI-driven adaptive learning systems that evolve with student needs. And environmental management, we can have ecological systems that could be modeled and managed more effectively, from individual habitats to global systems, balancing local interventions with global goals. And the future of AI and human civilization, the development of renormalizing generative models within the scope of active inference and the spatial web promises to have far-reaching implications. More adaptive AI, these systems are highly adaptable, capable of operating in new environments with minimal training. Efficient edge computing, RGMs enhance the power of AI on devices like smartphones and IoT sensors, reducing the need for large data centers. Improved human AI interaction with explicit uncertainty models. These systems interact naturally with humans, seeking clarifications as needed. Safer AI systems, they recognize and handle novel or ambiguous situations reliably, preventing catastrophic failures in unfamiliar scenarios so they can fail gracefully. And accelerated scientific discovery, RGMs expedite research in fields like genomics and climate science by rapidly identifying patterns and formulating plausible hypotheses, thereby guiding further experimentation. So the key takeaway here is that all of this research and all of these technologies together can provide us with a future where AI systems can interact seamlessly with the physical world, autonomously optimizing operations and improving human lives. So, yeah, there's my website. I have a podcast, and I'll stop sharing now.
Thank
Hi,
you,
Dan.
Denise. Awesome.
I don't know what time, how are we on time?
We have 15 minutes, and I'll read some of the questions in the live chat.
Okay, sure.
Right. I'll start with Pablo, who wrote, how will all of this affect the gamification of processes in organizations?
Well, I mean, the interesting thing is through HSML, you know, all of these emerging technologies are going to converge together and become interoperable in ways that we've not experienced before. You know, we've had this kind of vision of this augmented reality existence, but the framework hasn't been there. And this is going to provide that framework. So I think when you're talking about gamification in every aspect, it'll probably become kind of a natural part of our existence and how we move through our day, how we interact with our work, with brands, with, you know, anything. You know, I think that there's going to be a lot of really interesting ways to kind of perpetuate that.
Cool. There's a lot of great questions in the chat. So I'll read one from Tintin. So they wrote, it's impressive. The obvious question I have is of alignment of this system in terms of that alien message from Eliezer Yudkowsky, for example, and then they clarified what that exactly is. So the key idea there is that simulated agents evolve and came to think faster than their creators. So at a moment, they took control to ensure their own survivability. It's the question of how to ensure that way more intelligent and faster systems keep aligned with our values.
Right. And so one of the things that is really interesting to me about this is through HSML, we can actually collaborate with these systems in the sense that we can take human laws and guidelines and make them programmable. So these agents can understand and abide in real time. And, versus who, Dr. Karl Friston is their chief scientist. They were involved in a program called Flying Forward 2020, and they were doing a lot of testing around this. And because it involved a drone project that I don't know, there were multiple countries throughout Europe. It was with the European Union that were involved, and testing whether they could program in laws around airspace laws and things like that. They did all kinds of scenarios of medical supply delivery, perimeter security, all kinds of things. And what they found was through HSML, you could actually program these guidelines, and these agents abide by them. So I think we are going to experience this unprecedented level of cooperation and collaboration, so we can grow in tandem with with these agents and their intelligence. And I think that we can also take some solace in the fact of how active inference works, and how our human knowledge grows. I think we're going to see a similar pattern with this knowledge among these agents. And the only difference is, and this is just me speaking from my own perception and perspective of this, but they're going to be dealing with real-time data and with a real grounding of these program spaces. And those are the things they're going to be operating off of to make their decisions, right? Whereas if you look at a human, we have so many other variables going on, and when we learn through active inference, it's a very subjective growth. That's why you can have, multiple children growing up in the same household, and they all experience things differently, right? But when you have these agents and they're getting their learning through actual tangible programmed information, I think there's a stability there as well, if that makes sense. And again, that's just my own interpretation and feeling around this, and I could be wrong, but just kind of throwing that out there.
That's how we move forward.
Yeah.
Okay, next question from David Highland, who wrote, "Thank you for the informative presentation, Denise. Can you share any thoughts or information about the ownership model for agents? Is it a decentralized market? How do we decide which parts are public goods?"
Yeah, so with the protocol, with hyperspace transaction protocol, because it's interesting. It really shifts to this kind of self-sovereign identity aspect of the internet. Because right now, think about how web domains work. If you want to interact with a web domain, all the transactions are taking place under the umbrella of whatever centralized organization owns that domain. And you have two choices. You can either say, yes, you can have all my data and you can decide what to do with it all, or I don't want you to, but then I'm opting out of being able to engage with your domain. Well, in the spatial web, because now transactions can be at every touch point of every entity within the network, then permissions can be programmed in a very nuanced way, right? So it really puts that back in the hands of the user, of the entity within it. You can program guardrails around certain aspects of data while allowing permissions and freer accessibility for other aspects of data. So whether you're talking about a business, they can guardrail off their data, they can guardrail off certain aspects of it for certain departments of employees, some for their customer base, some for, partnerships, whatever, right? And we're going to be able to do that kind of thing too. And the thing with this is this takes into account time, the passing of time, so you can set expirations on permissions as well. So I think we're going to have a lot more self-sovereign control in this area.
Yeah, that's a part that really excites and piques me as well. Like with the web domain or the email domain, it'd be like saying, well, on one hand, we're not going to look in your email. Let's just go with that for now. But we do or don't accept letters from this area. So it's kind of all or nothing, and it's based upon, like you pointed out, the custodianship of the all or none permission based around what boxes you can send where. Whereas having a more nuanced way to talk directly about belief sharing means that instead of just like plugging the USB into the port, there could be even an active inference negotiation around what elements to share, how to share, when to expire, all these other features, which can help like incrementally build rapport and add to the relationship instead of doing all or none, which can be just very prone to false positive or false negative in cyber physical interactions.
Yeah, you're so right, Daniel. Yeah.
What do you think about learning trajectories and paths? I know it's an interest of all of ours, I guess. Like what can we do to be learning and thinking about all these things?
Well, so I actually have put together a series of courses to kind of give people a real kind of a prerequisite knowledge understanding of what this transition looks like and the different components and what it means from all aspects of like, basic understanding of active inference and the free energy principle and the spatial web technologies to, decentralized AI. What does that mean? Convergence of all this tech across the network. What does that look like? Safe AI. How does active inference benefit that? And then RGMs. Let's look a little closer at that. And what I try to do is I try to take the complex ideas, but make them more understandable so that people can really wrap their heads around these concepts, and then they can go dive into the more technical aspects of it. And I know you with the Institute, you have a lot of technical knowledge there. So I think that, between resources like, some of my resources, your resources, and then I'm sure there are resources out there that maybe I'm not even aware of. And I think there's going to be more and more resources available around this, modeling these agents, building out, these spaces within the network. I know that Versus is going to be launching a platform that'll be the first interface for the public around this technology. And I think it's coming to the public at the end of first quarter next year. And with that, there will be tools where people will be able to build these agents as applications within the network. And I think at that point, it's going to get really exciting. I just think over the next 6 months, we're going to see a lot coming about with this. And if anybody is interested in the courses I put together, you can visit my my website and sign up for them. They're not available yet, but they'll be available very shortly within the next week or two. So, yeah.
Cool. Okay, I'll for last question, ask the same thing that I asked Alex and Karl earlier. What is a fun or a memorable moment from learning and applying active inference this year? And then if you haven't already mentioned it, what's something that you're excited for next year?
This year, honestly, I think that I have been on this learning journey in creating this course material around it, and at the same time, I've been building community and kind of having them be my test guinea pigs around it and stuff. So there's been this whole learning aspect for me around building this educational material. So it has been, a constant feedback loop. And next year, I'm just very excited about the potential of building these agents and what that means, and how we can tackle some of the problems and the issues and the challenges that we have through this new exciting technology and this framework. So, yeah.
Well, thank you for all of your great learnings and digested and sharings and all the ways that what you talked about today, I think, connected a lot of the dots from hearing Karl's more technical view on the RGM, onto what does it mean to have multi-agent decentralized as opposed to just building up one agent. So thank you again, Denise.
Thank you, Daniel. Thanks for having me. Thanks, everybody.
Till next time. Bye. Okay, the next talk is going to be by Bradley Alicea and colleagues, Purposefully Nonstandard Cybernetics, an alternative to purpose-driven control. This is going to be a 1-hour pre-recorded talk. So, thank you. Enjoy.
Hello, my name is Dr. Bradley Alicea, and on behalf of Jesse Parent, Morgan Huff, and Amanda Nelson, we're from the Orthogonal Research and Education Laboratory and the Cybernetics Interest Group, and I'm going to talk to you today about Purposefully Nonstandard Cybernetics, an alternative to purpose-driven control. So we start with a question. What is the definition of behavior? And this has varied throughout history. According to the behaviorists, behavior was identified as a reflex elicited by stimulus associations, the consequence of reinforcement, and the current motivational state. If we go forward to the cognitivists, which is more or less the modern view, they would say that behavior is a set of internal mental states that are responsible for observable behaviors with goal-directed end states. Now, it's of note that both behaviorist and cognitivist views involve feedback. This leads to learning, a notion of what constitutes a state, and predictive capacity. So we start with this paper, Rosenbluth et al. In 1943, Behavior, Purpose, and Teleology, published in the Philosophy of Science, and it's a formative paper in the field of cybernetics. So in that paper, they have this typology of behavioral classifications. So we're going to return to this typology throughout the talk, and we're going to think about how we can reorganize this typology. But it basically defines behavior as a set of nested things. The red text non-classes, or they're basically all other things other than the black thing that we'll be talking about at each rung of this typology. So behavior is active, it's purposeful, it involves feedback, which implies some sort of teleology or end goal. It's also predictive, which involves extrapolation and involves an order of prediction. So you might have first order, second order, or third order prediction. So to understand what teleology is and where it comes from, we start at the Middle Ages, where teleology was the end state or the end goal of some behavioral process. It was thought of as divine causation. We then move forward to teleology as natural causation, and then it branches off into two directions, and the first was the vitalism of Bergson and evolution by natural selection, made famous by Darwin. Leading from Darwin's work, we had Ernst Marr, who talked about teleonomy, which is purpose versus history, and we'll talk a little bit about that later in the talk. Kind of discontinuous to this are two different streams. So the first at the top is where behavior is viewed as habit. That's by William James and Thorndike. That leads us to the and molecular anti-teleology of Francis Crick, and feedback as complexity, which is summarized by control theory and dynamical systems. At the bottom is our target paper that we just talked about. These are the views of Rosenbluth and Weiner, and this is feedback relative to a goal. This led us to cognitive science and reinforcement learning, or at least the modern versions of this, where people talk about goal-directed behavior, and variations on that in molecular biology, such as molecular vitalism, and the TAME and UAL methodologies of Levin, Jablonka, and Ginsberg. So we'll talk about a couple papers here and frame some of this in context. So if we think about behavior, it's essentially a form of functionalism. In the first paper here, Roddy and Germain, they argue that functionalism is a pre-scientific relic. So they actually argue that the whole idea of functionalism is something that comes from this era of divine causality. Biology is not designed, so why should we expect to function? And this is something that, of course, maybe is assumed about function, that it comes from some sort of design or comes from some sort of divine intervention. On the other hand, teleonomic systems are defined by spatial and temporal information and constant iterations over states. So we do have these teleonomic systems, but include modern components. Only select behaviors can be defined as selection of a goal or derived from signals from the goal. So that means that we can't necessarily paint behavior with a broad brush of teleology. Only some behaviors may be teleological and others may be not. Not all behaviors, and this includes biological and machine behaviors, are goal selecting. And while goal-directed behaviors seem to be purposeful, and it may be true that some of these behaviors that are known as goal-directed are purposeful, are there developmental and evolutionary antecedents? So are those ancestral behaviors, or those basal behaviors, or behaviors that occur earlier in development, are those also purposeful? And the answer may be no. So Rosenbluth et al. Define behavior as any change in an agent with respect to its surroundings. This is much broader than the neuroscience psychological definition, and it sets up a contrast between all behaviors and a subset of purposeful behaviors. So if a behavior is put under some sort of selection, or if a behavior is selection of something in the environment, this might lead us to a subset of voluntary behaviors, which then some of those may be purposeful. And so purposeful behaviors is actually a subset of all behaviors. To demonstrate this, we see that clocks, both mechanical and biological, are not purposeful, as there is no final aspirational state. Mechanical clocks can keep time, and you can set an alarm on them, but that alarm is imposed by the outside, and it's not a property of that behavior in and of itself. Furthermore, a biological clock runs via physiological processes like a circadian rhythm, and it can be entrained by external light, but that again is not a final aspirational state. More generally, teleology requires a signal from a goal. So it's some sort of signal from a goal that's specific to that behavior, and purpose is progress to that goal. So again, with our example of circadian rhythms, it's entrained by light, but that light itself is not a goal. It's just something that's out in the environment, and the system entrains itself to it. We can also see this with brains, in that brains produce behavioral outputs, but the exact mechanism is hard to pinpoint, and this is the Rust and Liddell article that we saw earlier, and this asks the question, signal from what to goal? So there's a signal coming from something to a goal, but it's not clear what that is. This is something one of our co-authors, Jesse Parent, works on. This is a frontier map for teleology and related complexity theory concepts. So the data from this is drawn from the Complex World book by Krakauer. This is published in 2024. And it kind of goes over 3 different concepts that are interrelated. So we have teleology, organized complexity, and emergence. And so you can see that our paper, Rosenbluth 1943, is at the top. And this is sort of the first paper that talks about teleology in sort of a scientific and in a manner of complexity. And so this is the first paper that talks about teleology as a property of complexity and of complex systems. So a lot of papers were influenced by Rosenbluth. This teleology was inherited by Wiener's book Cybernetics and Control in 1948. Two other papers, Adaptive Systems by John Holland in 1962, and Organizations and Complexity, also in 1962. The Good Regulator, of course, in 1970 inherited this concept, but it also inherited another concept from Organizations and Complexity, which is organized complexity. The Good Regulator then passes down this concept of teleology to the book Order and Chaos in 1993. And there's a direct link between Rosenbluth 1943 and the TAME concept of Michael Levin in 2022. Now, going back to the concept of organized complexity, this comes from Organizations and Complexity. The Good Regulator in 1970 and the autopoiesis paper in 1974 both share this intellectual lineage. The autopoiesis paper lends that organized complexity concept to this paper on dissociativity in 1982, into this book Order and Chaos in 1993, and then to the TAME concept in 2022. Finally, we have Emergence, which starts with the paper by Anderson, More is Different in 1972, inherited by the autopoiesis paper in 1974, in turn inherited by the dissociativity paper in 1982, in turn inherited by Order and Chaos in 1993. So you can see that we have not just teleology as a concept, in which we've kind of talked about already, but also a number of other related concepts. This is Levin, this is the TAME paper, and then Jablonka and Ginsburg, this is the UAL paper. And so Levin proposes the TAME, or technological approach to mind everywhere. Levin's principle here is it's cognition all the way down. We can see cognition in terms of minds, we can see cognition in terms of molecular phenomena, we can see cognition everywhere in between. And so behaviors, all of those behaviors are cognitive to some extent. And as a result, we get these diverse minds that have these different goal-directed competencies that allow those systems to achieve embodied agency. So in Levin's approach, teleology is a very important concept, not just for cognitive type behaviors, but behaviors that go all the way down to the molecular scale, and maybe even down to the quantum scale. Second, teleology is a means to explain why agents develop towards goals. And so, we can look at agents such as artificial agents, simple organisms like bacteria, and we can see that teleology is a way to learn how to move towards goals. The next paper is this UAL paper by Jablonka et al. And in that paper, they propose a concept called unlimited associative learning. And this concept is a minimal marker for consciousness. So in this paper, they also champion teleology as an intrinsic reinforcement system. You have this internally regulated model in service of attaining external goal. And teleology plays a role in attaining goals. So again, in both cases, there's a strong tendency to talk about goals, a strong tendency towards teleology. But we might ask the question, is behavior at these different scales, and any sort of behavior that's sort of motivated towards some sort of function, teleological and purposeful, or is it simply a product of the history of the system? So, we could talk about teleology and purpose, and we've kind of set this up that, this is something that has kind of come out of the natural study of behavior. But sometimes, we don't really fully, sometimes we ascribe teleology and purpose to things that maybe are just simply a product of the history of a system. First example I want to give is the Belousov-Jabotinsky reaction, or the BZ reaction. And at the lower left, you can see an image of the BZ reaction. And this is a deterministic internal model that we can model with differential equations, and we can solve those differential equations and get interesting solutions that produces a chaotic behavioral output, or the dynamics of the system, which are sort of the unfolding history of the system. So if we take an example of some sort of chemical soup, we can achieve Belousov-Jabotinsky reactions, or BZ reactions, by setting up this sort of set of differential equations, these ordinary differential equations, setting up an initial condition, and we get these spiral waves and swirl rings that result. And so if we have slight variations in the initial condition, we end up with very different systems, very different types of patterns in these systems. And we can describe this with ODEs. And one might say, okay, there's a purpose to this, but the purpose isn't necessarily clear when you run this simulation again and again with different types of initial conditions. there's a chaotic behavior and a variational dynamical output. So this is an example of the tip trajectories of BZ waves. This is from a paper by Braun and Engel in 1993. And it shows how there's a lot of variation in the pattern, but there's a sort of, constant aspect of the pattern in terms of the tip trajectories. So one might say, okay, the purpose is to produce these tip trajectories instead of the actual pattern and the interactions, which may be true, but then of course, that's something that I want you to think about as we go through the rest of this talk. We can also plug the Belousov-Jabotinsky reaction into a cybernetic model with higher level feedbacks. And so I talk about this in this Dimensions of Morphogenesis lecture on the DevaWorm YouTube channel. And what I'm getting at in that talk is that there are different dimensions of morphogenesis. There's one-dimensional morphogenesis, two-dimensional morphogenesis, higher dimensional morphogenesis. And so you see this kind of output, and so I'm asking the question here, is this purposeful or is this a product of sort of a dynamical chemical system with a history? And so we can also look at this as a cybernetic model where we have feedbacks and we have other sorts of complexity. And, we can fit it also into that behavioral typology of Rosenbluth. Okay, another example is this thing called an allostasis machine. So an allostasis machine is basically the output of an internal model. And so an internal model, of course, as we talked about, is something that has some sort of capacity for memory and learning, and maybe some sort of output that looks behavioral or cognitive in some way. So what we can do is we can take this internal model. We can have an oscillator, which is a stochastic process, or a deterministic process, depending on our oscillator. And we can have a memory with capacity. So we have this oscillator that produces an output. And we have sensory information that can drive the oscillator forward. This output creates a trajectory, which is an interaction between noisy perturbations and a historical trajectory that's shown in this red line. And the historical trajectory is stored in the internal model as a memory with a capacity. So as this red line unfolds, there's a memory of it in the internal model, and it responds to external perturbations which drive this red line in different directions, and the oscillator tries to recover to the original state, and so you get these dynamics that may look purposeful, but really have this stochastic and adaptive component. We get more into this aspect of dynamical control systems. I look at intrinsic motivation in dynamical control systems. So this is this Tiomkin paper in PRX Life. And so in this paper, they talk about how you might model maybe something like an allostasis machine as a set of actions generated without a specific reward signal. So in this paper, they talk about that as intrinsic motivation. They model this with X sub t states and A sub t actions. So an action maps to a number of states, and this results in a trajectory forced via observation stochasticity. This is entropy, so you produce the trajectory. There's an observation that you have, and that's the entropy of the system. And so you maximize actions that increase susceptibility rather than entropy. These are noisy observations that lead to imperfect observational states. And you can compare arbitrary length sequences of such sequences in the future. This gives your internal model the ability to sort of integrate information and to find sort of solutions to problems. The idea is that you have the system that can work towards a goal, but it isn't driven by any sort of teleology. It's just driven by this memory component and the stochastic component, and that's all you need. There are a number of other papers here that I'm going to talk about. I'm going to put this in the framework of anticipatory systems, our paper on teleonomy, and Benny and Friston. So to get to this, we need to reformulate our behavioral typology. So remember, we talked about behavior as having these different components. We have these non-classes. So in this case, we're going from behavior to active behavior to purposeful behavior, but that's contrasted with historical or Markovian behavior. Then we have feedback, prediction, and order of prediction. And so Ernst Mayr refined the Rosenbluth et al. Teleological category into two parts: purposeful agentic and historical Markovian. So if we go back to the Benny and Friston paper, they talk about the free energy principle is managing different forms of goal-directedness and how you need negative feedback to attain homeostasis. There's purpose in cases where the goal is known, which is a Markovian system, and surprise is minimized, which results in uncertainty, then we can expect purpose. Purpose isn't really just some sort of magical thing, or it's not some sort of thing that requires a strict goal. It's just certain conditions under which our behavioral trajectory exists. We can also look at anticipatory systems. It's the Louis paper. And this anticipatory systems come from a generative model with depth. So this is where we have temporal aspects of the system that lead us to teleology. So it's more that the teleology is the history of the system. And this depth comes from an internal model. So basically, if we go back to the internal model, we have some process that generates behavior. We have this memory. The memory is basically something that stores everything that the system has experienced, and that's how we get teleology. To kind of understand this a little bit more, we want to distinguish between a Markovian system and a non-Markovian system. So a Markovian system is where you have inter-arrival times, so there's a series of things coming in time. This is exponentially distributed. In this diagram, we have sensory information coming in. We have some sort of encoding. This encoding is a binary channel with noise, where we have these lines that represent some sort of sensory input or perturbation of the system. And the inter-arrival time is the area between these lines. So the inter-arrival time is obviously not equidistant in this example, but it's in between the red and blue lines or the red and red lines. And so we can take those inter-arrival times, and if they're exponentially distributed, we have a Markovian system. If they're not, then we have a non-Markovian system. And so we've kind of developed this distinction between Markovian and non-Markovian sensory information and how that relates to an information measure in our Gibsonian information work. So Gibsonian information is a Markovian, but can also be non-Markovian information processing system, and the citation is here. So going back to the behavioral typology, we have active, purposeful feedback prediction and order of prediction. Feedback is everything that is circular and non-transitive. This is the present, past, and future, where behavioral is controlled by a margin of error corrections of agent location, the time t relative to a goal position or state. And so if we think about this in terms of a feed-forward process, a feed-forward process is where the past is your input, present is your process, and the future is your output. In feedback, however, it's a little bit different. Your input comes in the past, and then you have this present state here, and then you have feedback, which is the past, and that loops back to your input, which means that your input is now the future. And so the future is actually present with past feedback. So you see the loop here. You have input to the present, you have this feedback, which is the past, and it goes to the future. So now you have this future state before the present state. And if that keeps going out, you get this output with alternative futures. So your feedback loop can be positive or negative. And in this case, it doesn't matter. What we're interested in is sort of the order of past, present, and future. So we end up with this input. We go to the present, we go to the past, we go to the future, we go back to the present. So we're sort of interdigitating different types of causality here. Instead of just having this past, present, and future aspect to things, we have this sort of convoluted aspect of past, present, and future. If we go back to our historical map, we recall that non-teleological things can be characterized as feedback as complexity. And so there are two papers here that talk about PID control that kind of get us at that idea. So PID control is proportional integral derivative control. And if we think back to our example of chemotaxis and phototaxis, we find that PID control can be applied to chemotaxis and other types of biological control. So this is the Baltieri and Buckley paper. They talk about this in terms of variational free energy minimization given a linear generative model. They talk about PID control resembling a reflex arc type mechanism. So this is the reflex arc we find in sensory motor control. And the free energy principle provides a more direct account of control. This is where we don't have any hidden states in the process of proprioception. So they're focusing on proprioception, but they also talk about chemotaxis, and so they kind of give us this sort of variational free energy interpretation of this. In Gu et al., which is a more engineering take on this, the PI and PD components, or the proportional integral and the proportional derivative components, and directed network synchronization are all sort of components of this control mechanism. In particular, the PI and PD components of PID define present, past, and future components in an internal model control system. We can then also start to think of feedback as complexity in terms of nonlinearity and complexity as well. So this paper by Westerberg et al., Stimulus History, Not Expectation, Drives Sensory Prediction Errors in Mammalian Cortex. This is from the Barger Archive. So the authors frame this in terms of predictive coding. So predictive coding explains cortical responses in two ways. A feed-forward model where an internal model of expected events occurs, or in terms of an internal model of expected events, or a feed-forward approach, and a calculation of prediction error for unexpected stimuli, or a feedback approach. The latter are actually global oddballs, which defy expectations in a local context. So in mouse and macaque, which are their two model organisms, they see two types of signal. They see a normal response, where the internal model is matched by most stimuli, and a global oddball response, which emerges as a higher order response to this normal response. We also can look at this nonlinearity in terms of behavioral output in general, and then burstiness or non-normality of output. So this paper, Burstiness of Human Physical Activities and Their Characterization, and Quantifying Postural Sway Dynamics Using Burstiness and Inter-Event Time Distributions, kind of gets at both this aspect of Markovian systems and a behavioral system that exhibits sort of nonlinear complexity. Both papers focus on the burstiness of postural sway. In postural sway, we have this paradigm where someone stands on a plate, and that plate is a force plate that measures the center of mass of the individual, and then we can measure this, and we get this nice dynamical trajectory that has different features that we can analyze. So it's a behavioral output that exhibits a lot of nonlinear characteristics and dynamical characteristics. Takeuchi and Sano focuses on burstiness and postural sway in terms of adult housework and children's play behaviors. They studied physical activities of children between ages 2 and 5, and they found that burstiness is not an acquired feature, it's something that's innate. Burstiness is present in healthy individuals, not in people with movement disorders or impairments. We also looked at inter-event time distributions and associated fluctuations. So we talked about inter-event times as being key to Markovian and non-Markovian systems. They found that they're bursty, so they're these stochastic signals that have a noise component, and sometimes this is a function of someone trying to maintain their balance, and sometimes it's just noise that's generated by the nervous system that's added to the stochastic signal. In both cases, this is not goal-directed. It's generated by physiological system. It's a very complex behavioral signal, and it's not explainable by either a Poisson or Gaussian model, which means that it has this very complex set of features. So if we do some experimental cybernetics on this, we can find that if we have the right internal model, we can produce some very interesting output signals or behavioral signals. Some of these kind of look like they could be teleological, but they're not. This is just simply running some stochastic signal. One example is just a pure stochastic signal. The other one is having a stochastic signal with feedback that then takes that signal and integrates it at a later date. So what we have here are two feed-forward processes. One is a purely stochastic signal in blue on the left, and then the other is a sum signal that is a stochastic delay of that signal, or the signal on the right. So on the right, we have the blue signal. You can kind of see it under the red signal. So the red signal is the one that's bursty, and it's just basically where at random intervals we sum previous output and we add it to the present output. So we end up with these bursts. And so the delay, which is this sum signal that represent our bursts, is the buildup of the input signal. It produces these bursts, or what we might call avalanches. And so we can see that we can produce these nonlinear signals from a simple internal model. So this is the classic Copiel paper from 1982. It actually has a couple of interesting things to say of cybernetic-oriented things. So we have this feed forward, which is where you have a process that goes from A to B to C to D. And we also have these systems that have strong backcoupling. So we have a process that goes from A to B to C to D. But then we have these backcouplings from D to C, C to B, and B to A. And so what's more likely to be the case of actual sort of complex behavior is not the feed forward signal, but the strong backcoupling. And this is where we have ubiquitous feedback. Strong backcoupling can be intractable to analysis, but produces the most interesting aspect of network interactions. And strong backcoupling produces things like collective behavior, emergent properties, stochastic outputs, and nonlinear outputs or avalanches, which we saw in our experimental cybernetics a few slides back. We can think about feedback, and we talked about this relationship between past, present, and future a few slides back. And we also talked about maybe some of these types of behaviors that are non-random, but maybe structured in a certain way. And we can think about feedback, just sort of revisit the idea of feedback that Rosenbluth et al. Gave us, which is that feedback was purposeful. So we can ask the question, is feedback purposeful or simply non-random? And so we can think of past, present, and future relationships as a trip around the feedback loop. Namely, that we can take our input, we can take the present and have a feedback loop that gives us past information into a new present when we get a new time point, and that ends up giving us a future that can then be recycled. So this has implications for prediction. We can go past, present, future to prediction, or we can have inputs that produce these sort of differently ordered past, present, futures and use that as the output. So feedback mechanisms reorder processes. Systems with a lot of feedback aren't teleology per se. Maybe they produce outputs that look teleological, but they're not teleological. And so going back to the different orders of prediction, which were kind of like the final output of our behavioral typology, what are the different orders of prediction? Well, we have our first, second, third, and fourth were higher order feedbacks, so we can have these feedbacks that have past, present, future, but we can nest them together so that we can have a past of a past of a past contributing to the present or to the future. And so that's really interesting because what it's suggesting is these higher level feedbacks maybe are also not teleological, but there's some sort of memory, or maybe there's some sort of, inter-event interval in the way it's structured. So there's some structural aspect of feedback that might be really interesting. That isn't teleological per se, but given some of these other examples, might have some structural significance. So if we build a cybernetic model that is really kind of complex and has a lot of interlocked feedbacks and things like that, we can get some really interesting results. So our different types of higher order feedback, we can kind of think of these in terms of the derivatives of position. So the derivatives of position, revisiting that from undergraduate physics, you have velocity, acceleration, jerk, snap, crackle, pop. And these are just where you start with velocity and you get a derivative of velocity, which is acceleration. You get a derivative of acceleration, which is jerk, and so on. And these can be thought of in this way of having these higher order feedbacks, or these reordering as a past, present, future to give you these really complex dynamics. In cases of derivatives of position and feedback, if it goes farther into the past, the effects persist farther into the future. So if we go back a couple of feedback loops nested on top of one another, and we introduce that to the new present or the new future, those effects persist farther into the future. So we get these really long-term effects in a dynamical system instead of just being local. How does this translate into the neural correlates of behavior? Well, we go back to our idea about behavior sort of being naturally teleological, and we have to think about kind of how we kind of assume that behavior does magic things. So if we get a behavior like this with higher order feedbacks, it tends to resemble the sort of magical aspect. It could be something like emergence. It could be something like burstiness, or something like a set of avalanches that occur. And so these are things that, give us really interesting dynamics, but are no more sort of magical or teleological than any other kind of behavior. And so more fully connected systems are perspective or might be sentient or conscious. That's sort of the idea of does magic things. So, we don't want to misattribute sentience or consciousness to something that isn't. And of course, this is something that we have a problem with modern AI systems, that people think they're sentient or conscious when in fact they just have this higher order feedback and this sort of, behavior that isn't necessarily what people think it is. Magic things, or, what we talk about like complexity, results from embodied function. A good example of this is kinematic chains, which we'll talk about in a little bit. And now we introduce this concept of convolutional cybernetic architectures, or CCAs. And so we go back to our behavioral typology and we ask the question, can we better understand the role of purpose or meaning and feedback or temporal order? So here we have active behavior, purposeful behavior, teleological behavior, and the non-classes of those are non-purposeful or random behavior and non-feedback or non-teleological behavior, respectively. But we're going to reorder this behavioral classification where now we have non-prediction leading to the order of complexity rather than prediction leading to the order of prediction. So we start off with behavior that's active instead of passive. Then we have non-purposeful or random behavior instead of purposeful. And non-active or passive and purposeful are now non-classes. Then we have feedback, which is non-teleological, versus feedback, which is teleological. Teleological feedback is now the non-class. Non-teleological feedback is now the path to the order of complexity. And then instead of prediction being extrapolation, we'll have non-prediction, which is also extrapolation. And then we have our order of complexity, first, second, and third order. So the more feedback we have, the more complexity we have. So this is an example of a convolutional cybernetic architecture. We basically have this toy example where we have an input and an output. The input is 0, 0, 0. The output is 1, 1, 1. And we have these boxes which process the present to the future, and then our feedbacks give us like some past state, and it feeds it back to the future or the present. So we have a ubiquitous feedbacks here. We have some feed forward elements. We have elements of feedback that do certain things to the sequence. And the question we ask here is, what is the maximal number of steps needed to transform the sequence from 0, 0, 0 to 1, 1, 1? So we start with 0, 0, 0. We put that in. We kind of move to our feedback loop. Our feedback loop does certain things to the sequence, and then we end up with 1, 1, 1. And we actually want to know what the maximal number of steps is, because we want to know, how far we can go through these different feedback loops and get our answer. This can also be restated in terms of temporal phases, past, present, and future. So we also have more explicitly this input of the present. We have the future as an output, and then we have these different loops that give us past information. And again, we're interested in getting the most diverse information possible. And so this is, again, this maximal loop that we're looking for. So we're trying to get the most variety out of these convolutional cybernetic architectures, instead of trying to find the most efficient path or the tightest path or the most goal-directed path. We can further understand this or restate this in terms of semantic components. So we can talk about this in terms of symbols, reference, and understanding. Symbol being the input, reference being the feedback or part of the feedback loop, and then understanding being the output. And so we want to accumulate as many references as possible for our symbol so that we get an output of understanding. And again, it's the variety that counts, not optimizing the process or trying to find a goal-directed aspect to this. So if we think about how these CCAs are assembled, we can look at the different components of feedback, and then we can start to assemble these more complex structures. So let's look at first-order feedback. So CCA has input, and in this case, we're looking at past, present, future, and maybe alternative futures and things like that, and they all produce a predictive output. So first order feedback would be an input going to a future, going to the present. And naturally, the future is just like the present plus the past. So the present comes in as input. It's passed to this feedback, which is the past. The present and past are added to the future. And then the output is some sort of predictive input. So again, we have this reordering of past, present, future in the first order feedback. If we have a feed forward only case, we have input, which leads to the present, which leads to some complex output. But of course, as a feed forward only system, we just only get the benefit of having the present. We don't get to talk about the past and the future. It's just like every input results in an output. And that output then is complex output within any context. Then if we put together a larger set of feedback loops, we can see this sort of convolved mixed feedback where we have first order feedback, second order feedback, and a feed forward component. So these are all different components producing two different complex outputs. So we have an input that gives us the present. We get a first order feedback that gives us some past, and we add those together to a future state that produces complex output. We can also have a feed forward part of that where the input goes to the present, and then the present is a part of that state. And then we might have a second order feedback where we have an input, which is the present. It passes a first order feedback loop to the past, and another first order or second order feedback loop to the past. And those can both be combined into the present, which is then informing a future state, which involves a longer memory, which has more information, and that gives us another complex output. But we also have this path from the second order feedback up to an alternative future, which then gets passed out as a complex output. So you see what we have here is we have an input that goes to the present. We sub-reference the past. We sub-reference the past again, and that gives us an alternative future. So this happens for every cycle. So you end up with these three different types of complex output. And given this topology, we can end up with these different types of characterizations of the system. Remember, again, with this convolution, what we're introducing is this variety, which is actually a concept from the Evergood regulator theorem and a lot of the work of W.R. Ashby. So we're dealing with producing the maximum amount of variety. So we need variety to control systems. So this is actually, overall, the appearance of purpose is replaced with an ensemble of positive and negative feedback elements with diffuse effects. So remember that we need to have not only a single closed loop feedback, but we need to have multiple feedbacks and maybe some open loop feedbacks in there so we can have maximize a variety. So the imperatives of such a network are to gain processes or to maximize the number of processes, and this leads us to maximizing variety. And of course, variety was a concept that was introduced by W.R. Ashby in the Evergood regulator theorem, and he talked about how variety is necessary for control. But it also creates the conditions for adaptability, modularity, and modifiability. So we have systems that are both not purposeful, but they also have this sort of imperative for control, but also for other types of conditions in a system that allow it to adapt, be modular, and be modifiable. And so we can also add in polarity. We can have different types of effects resulting from feedback. As we talked about, if we reorder past, present, and future, that's all well and good, but this also has relevance to different types of processes that result in systems. So in complex systems, we have these different effects like avalanches, runaway feedbacks, and dampened feedback. These are nonlinearities. And we saw an example of avalanches earlier in our experimental cybernetics, and that can result from a number of feedbacks of different polarity, and this can produce unpredictable instability. We can have things like runaway feedbacks, which are basically just the product of positive feedback, and that can lead to mass instability. And we can also have something like dampened feedback, which is a negative, overly negative feedback, which sometimes makes things more controllable. And so we can have these effects that result from these processes that have a polarity that lead to these different complex systems phenomena that then lead to things that are maybe look teleological or purposeful, but they're actually just the products of complexity. And so if we kind of go back and look at like how we can model things like connectionist learning and reinforcement learning with cybernetics, we can actually take the equations of connectionism and reinforcement learning and put them into this sort of cybernetic system. So this is where, we want to take modern learning systems or artificial learning systems and understand them using cybernetic approaches and maybe apply them into these kind of CCAs. And so this is congruent with Hopefield and Sutton's alternative viewpoint, which is that the weights of a network are reinforced by the activity and selection of previous inputs. So this is where we're looking at Q learning here, and we're looking at connectionist learning, and we're looking at sort of the way the equations are structured, and we're thinking about how, we can get learning from these systems of equations. And, this is a dynamical system, as much as a learning system. So we want to understand kind of how this works. And so we started a random set of weights and lack structure due to selection. We started a random set of weights and lack of structure due to selection. We proceed to a structured set of weights and optimal policies. Unwittingly, we kind of move from a Markovian system to a non-Markovian deterministic system. And so there's a trick question here, which is how do we go from something that does not resemble purpose to something that is purposeful? And the answer is that purpose is a post hoc determination. So we can model this as habits with weights. So we have this input, we have these outputs, and we have this CCA that has polarity. And we can have habits that serve as the inputs, and the weights are the polarity. And we have non-teleological behavior in a directed graph. So this directed graph kind of moves towards the endpoints, the outputs. And so the lesson here is that purpose is basically whatever we determine these outputs to be. So when we observe a behavior is generated by these CCA graphs, we interpret the output the way we'd like to interpret it. And as I said before, we can have these different outputs that look purposeful or they look teleological. But that's just really a post hoc determination. Then we move to Weiner's alternative viewpoint. So Weiner is more of a cybernetics guy, and he also has an alternative viewpoint. And his viewpoint focuses on communication and information, which have both a control layer and a semantic layer. So again, we have to go back to the past, present, and future formulation. So instead of thinking about this in terms of polarity, we want to think about this in terms of not just the control, but the semantics as well. And so we have this past, present, and future. We have an input, which is the past. We have a future, which is the present with past feedback. We have the present. So the present goes to the past, goes to the future, but the future also moves to a present where there's a present with past and future components, and then an output. So if we run this in time, if we run this as a dynamical system, we end up with the present being sort of, it's not really additive, but it's basically you're concatenating things onto the present with information from the past, and you're informing a future trajectory. And you can actually generate alternate futures of a system from this. And so there's a control layer, a semantic layer, and this gives us information about the system, both in terms of contingencies and synergies. So connectivity and ordering provides both contingencies, which is that nodes depend on other nodes, and synergies, where nodes working together. So in this model, we can't knock out any one node and have the system work. We can't knock out the feedback and have this sort of rich a self-reference. We can only have, a feed-forward model, and we've seen that that's much less interesting. We also can't knock out the future, and we can't knock out the present. We have to kind of continue with all of our nodes. But also these nodes working together produce this synergistic trajectory that gives us rich information about time. It gives us this present, it gives us a future, but it also gives us these intermediate states where we get past feedback and we get integration of those. This stands in contrast to the imperative of purpose in teleology. Is cybernetic control and behavior purposeful, or stochastic activity tempered by recursively recombined temporal ordering? And so this is again one of the CCAs, and a CCA is also a series of steps that add recursive functionality. So sometimes if we think about this in terms of our internal model memory, this is memory with sub-referential power. So it allows us to have a memory, again, where we can reference the past of a past of a past, and it informs the future of the present and adding present into future and things like that. This creates a hierarchical system and high degrees of intentional order. So again, we can add these things together, or we can run these CCAs and we can produce this memory with sub-referential power, and the output can look very organized and hierarchical. But the thing that produced that output is not necessarily ordered, and it's not necessarily, there's no overarching goal or any other sort of information going into it. So once again, thinking about habit and purposeful behavior, we have this paper, Creatures of Habit, the Neuroscience of Habit and Purposeful Behavior. This was published in Biological Psychiatry. So this is where they talk about animal behaviors being composed of habitual and goal-directed categories. Habitual is non-teleological, while goal-directed is teleological. They provide this sort of breakdown where you have teleological versus non-teleological behaviors and deterministic versus stochastic behavior. If we think about teleological and deterministic behaviors, we get goal-directed behaviors. Those are things like reaching for a target or moving towards a goal. But of course, we know that some of these types of goal-seeking behaviors are like chemotaxis or phototaxis are stochastic. And so if we have teleological and stochasticity, we might have something like chemotaxis or phototaxis. If we have something that's non-teleological and deterministic, we have habitual work. So we have something that's habitual, it's not moving towards a goal, but it's deterministic. Something like scratching or like a reflex. If you have non-teleological and stochastic behavior, however, we know that that looks something like a random walk. So we can actually characterize these different behaviors in this way. The problem with chemotaxis, and I put a question mark in the table. So chemotaxis, for example, which is a movement along a chemical gradient, we already established that that was not teleological. The goal-directedness in that case is due to the environment, not the internal model. And so we can look to Gibsonian information, or we can look towards sort of thinking about why it's not teleological. And so, but it also doesn't resemble a random walk. So that provides us with a problem, which is where does this fit into this typology? So a clue to kind of where chemotaxis and phototaxis fits into that typology comes from this paper, Brain-like Neural Dynamics for Behavioral Control, developed through reinforcement learning. And this is from the bioRxiv from this year. Cotto et al. Test two scenarios, supervised or extant, and reinforcement or developmental learning. So we have extant and developmental learning. Only reinforcement learning produces goal-directed behavior and neural activity similar to biology. It provides robust short-term behavioral adaptations to perturbations, and it produces an emergence of policies that are not purposeful in and of themselves, but lead to things that look the part. So this is reminiscent of our CCAs. It's also reminiscent of our discussion of chemotaxis and phototaxis. Building a CCA from a small motif is a form of purposelessness, or purposelessness reinforcement learning. You build up to function and sometimes useless structures, and that's okay. Another example of non-purposeful behavior that kind of fits into our CCA model comes from fetal substrate cycles in biochemistry. And so this is the paper, Stochastic Amplification and Signaling in Enzymatic Fetal Cycles They're noise induced by stability with oscillations. This is from PNAS. So this is where we describe these feudal cycles as these feedback loops where you have an input of energy, there's an enzymatic reaction, and you get nothing that comes out except entropy or heat. So you basically don't have an output. Your output is entropy. It's heat. And of course, this is a problem because we expect there to be an output. We expect this reaction to actually do something. And in fact, it's creating heat, but it seems like that's a lot of work for just heat. So we have a biochemical pathway, which is a closed loop feedback. It does thermodynamic work for no reason. Heat is produced from an energetic input, but we don't get any biochemical products. And this seems like it's a waste of energy, that it has no purpose. But it's actually important for regulation and other processes. It produces complex higher order dynamics or amplification effects throughout a greater biochemical system. So if we go from convolution to order, we can see that the evolution of cybernetic control is a causally recursive chain of contingencies. And so here we look at the contingencies in a CCA. We go from 1 to 2 to 3, and then that's a feed-forward system. And then we can go from 1 to 2 to 3 prime to 4, which it feeds back to 2 and gives us this output 4 prime. Or we can go from 1 to 2 to 3 to 4, or 1 to 2 to 3 prime to 4 to 5 to 6 to 7, which is an output. So we have these different outputs from these different numbered boxes, and we have these resulting processes. So let's take 3 prime as an example. 3 prime is dependent on 2 and 1, and once feedback is operational, 4 and 5. So 4 and 5 actually do feedback to 3 prime, which of course is a dependency. So if you knock that dependency out, you lose your entire functionality of that part of the network. 7, on the other hand, which is another output at the top, is dependent upon 6, 5, 4, 3 prime, 2, and 1. There's no feedback from delay. So you can see the different types of order and how there's a lot of recursive chains that lead to contingencies. So again, if we think about our feudal cycle is like something at the bottom, our higher order feedback is like something at the top of this diagram, and our alternate outputs are at the right, and they are, of course, maximizing for variety. And so if we think about the evolution of cybernetic control as a causally recursive chain of contingencies, we can think about the kinematic chain, which is where we have these dependencies. So D is affected by the activities of A, B, and C. We get this chain. This is this robotic arm that extends out across 2 joints. And the activity in D with kinematic is constrained by A, B, and C. And so we can describe it in that way. If we go back to these kinds of contingencies, we know that 7 is constrained by its intermediates, and thus it is with the kinematic chain. In the kinematic chain, we can do this in a linear fashion. We can add on conditionals as the convoluted cybernetic network evolves. This restricts the system to a deterministic path. Behaviorally, this leads to interesting consequences for a developing sensory motor loop. And a kinematic chain is basically sensory motor physics with contingency. So here are examples of a kinematic chain in robotics. And we can think about embodied robotics here, where we have these control systems for these kinematic chains, maybe a CCA where we have different types of morphologies, and we can design them appropriately. We can design them appropriately. We can design behaviors that aren't purposeful, aren't teleological, but still give us behaviors that look intelligent. You can also think about purposeful behavior in 4E cognition. So our approach to purposeful behavior can be applied to 4E cognition. So we have these different types of cognition, some of them being embodied, some of them being embedded, some of them being extended, which means outside the brain, and some of them being inactive. If we put this in the framework of Rosenbluth et al.'s behavioral classification, does 4E force us to rethink that behavioral classification as we did in a number of of instances in this talk. Now, there's one insight of 4E that's interesting to us, which is that the morphology and environment of a system is more important than its internal model. So we've been talking about internal models and how these CCAs model the internal state of behavior and how that shows that in a lot of cases teleology and purpose are sort of illusory. But if morphology and environment are more important than the internal model, then maybe we need to incorporate our CCAs or recast our CCAs in terms of morphology and environment as well as an internal state. And in fact, our CCAs do that to some extent, but it's sort of a way to put this behavioral classification on its head. And so in the case of 4E, purpose is not ascribed to a mind. Feedback is diffuse and complex. Prediction in its highest orders are not teleological. They must be open-ended. We talk about this in a paper from 2023 in Royal Society Interface Focus. So what is behavior and what are its properties? So we're kind of revisiting what Rosenbluth talked about. We're looking at a number of examples from neuroscience and from psychology and from other areas, animal behavior, robotics. And we kind of break down kind of what we're looking at here. So behavior can be intentionality. It can be goal-directed and supervised. And so these are things like control systems, higher order cognition. And of course, some of those are goal-directed. Some of those are regulated complexity. Then we have rich, higher order, complex dynamics. And those are things like BZ reactions, which we talked about, and embryogenesis, which we didn't really talk about, but also qualifies in that category. So these are outputs of dynamical systems. We also have connectivity and convolution, which are things like connectionism, avalanches, and open-ended learning. And then finally, we have behaviors that are hardwired but recursive. So with our CCAs, we're modeling some hardwired behaviors in a recursive fashion. We also talked about this in terms of non-Markovian systems and habitual behavior. So we want to go beyond the standard of teleological and purposeful behavior. So a standard way of thinking about behavioral regulation is that inputs are deterministic and outputs or collective outputs should be closed-ended. So if we expand the basic closed-loop feedback model, we get an interconnected network of retrocausal ordering. So this is something that we're seeing in the CCA, where we talk about the order of causality, past, present, future. We have this basic closed-loop feedback model, but if we expand that out, we get much richer retrocausal ordering, which leads to, of course, to variety, but it also leads to these interesting paradoxes and interesting effects of higher-order feedback. Behavior is often open-ended, and this can be characterized by embodied dynamics. Unpredictable, which can be characterized by chaotic dynamics. Non-normal, which can be characterized by non-Markovian behaviors and systems, avalanches of different types, power law dynamics, and so forth. And variational, which means that it's characterized by multiple goals and redundancies. And so this requires a reassessment of Rosenbluth et al.'s typology and has wider consequences for the practice of active inference. Thank you for your attention. One of our co-authors, Jesse Parent, produced a lengthy blog post on the Rosenbluth et al. Paper, talks about its enduring insights and its context in cybernetics. And then we have two papers we talked about in the talk from our group, allostasis machines and a primer on Gibsonian information. So I thank you for your attention.
All right, welcome back. Here with Alexey Tolchinsky, a friend and colleague and collaborator on this paper, Temporal Depth in a Coherent Self and in Depersonalization Theoretical Model. So, go for it.
Well, I'd like to say hello to everyone and thank you for being with us after such a long and fruitful day at 6 p.m. on the East Coast. And I appreciate your interest. And thank you, Daniel. Thank you, Active Inference Institute, for this fantastic symposium. We'll be talking today about this paper on dissociative states, and it's a collective effort. This paper is in peer review right now. Early preprint was posted on the site, and it was work by Michael Levin, Chris Fields, Lancelot da Costa, Rachel Murphy, Daniel, who's here, David Pincus, and myself. And this is the link to the paper if you'd like to take a look at the early preprint. Perhaps some of you would like maybe to get a feel for what we're talking about, and this is not a patient's account. This is a poem from Kurt Weill and his song Pretty Pumpkin. I woke up this morning, didn't recognize the man in the mirror. Then I laughed and I said, oh, silly me, that's just me. Then I proceeded to brush some stranger's teeth, but they were my teeth and I was weightless, just quivering like some leaf come in the window of a restroom. And this poem was cited by Paul Molyneux. He's a specialist on DID in England on the Psychiatry and Psychotherapy podcast. You can also find patient's account on YouTube. I couldn't post the video here for copyright reasons. So dissociations are a spectrum, and they range from mild to severe, transient to chronic. They can be benign and pathological, and certainly they're not a bright line category. The causes vary for them as well. We call it etiology in the clinical world. They can be caused by psychological trauma, neurological conditions, substances, seizures, anesthesia, and different sleep phases. There's a subset of conditions here we call dissociative disorders. Typically, in the history of these patients, we see prolonged elevation of stress accompanied by repeated traumatic experiences in circumstances where they feel there is no escape, typically childhood abuse and neglect. And we call that complex trauma, which has a different presentation than acute trauma. And we'll touch upon why this specific pathway of etiology is important for dissociative disorders. I'd like to say why this matters, what's at stake, what's the motivation for this paper. And we have many authors and they have variable motivations, but I'm a clinician, I see patients all day. And for me, the main reason for that is these conditions are hard to diagnose. Many patients go undiagnosed for a long time. They're very hard to treat, and we're sometimes content with partial results. And the risk of self-harm or suicide is higher for these patients. And there are many, many reasons for that. We think that perhaps one of the reasons is that there is no unified theory of dissociations. We have kind of neurobiological ideas, the corticolimbic inhibition hypothesis. We have psychodynamic ideas. We have attempts to model dissociations from first principles by Anna Siunica and other colleagues. But these different attempts are not tied together, and certainly not tied together with the patient's subjective experiences. So we are trying to make steps in that direction, and we don't claim that we've built a unified theory of dissociations, but what we're doing here is we're focusing on one aspect of dissociations, one focal point, and that is a collapse of the temporal depth in any kind of dissociation, regardless of the cause. By temporal depth, we mean how far into the future the person can plan. What we're hoping for is that this focused approach has the potential to allow us to perhaps develop more accurate diagnostic procedures and to possibly help increase efficacy in therapy, with full respect to how difficult, complex, and messy this work is. Additional point of convergence is we explore multiple theoretical perspectives in the paper, and they all converge on the same points. And here is the main thesis. the collapse of the temporal depth is necessary and sufficient for the onset of a dissociative episode. So we're going a little bit further than colleagues who already mentioned a relationship between temporal depth and dissociations. Dean and Anna Siunica and others, and Karl Friston were saying it's causal, that there is no dissociation without the temporal depth collapse, and the collapse of the temporal depth will reliably lead to a dissociative episode. Further, we are saying that temporal depth collapse can be conceptualized as a common pathway for the onset of dissociative symptoms, regardless of etiology. And finally, we suggest that the focus on restoring the temporal depth can be an effective strategy in therapeutic interventions. One of the theoretical perspectives we explored in the paper is Michael Levin's TAME framework, Technological Approach to Mind Everywhere, which I think is very useful. And unfortunately, I haven't seen many attempts to use it in clinical applications. This is the title and the link to the paper. There's so much in Michael Levin's work that is useful. His paper on cancer, which is based on his experiments, is also one of the inspirations for our paper here. But here's another inspiration. If you dive into Michael Levin's work, you'll probably see what he claims, based on experiments, that all intelligences are collective intelligences. However, at our subjective level, at the level of the conscious mind, we don't feel that way. We perceive unity. All our percepts, sensations, thoughts, feelings come together in a cohesive and coherent whole, a single conscious experience in the here and now. And we will talk about this seeming paradox, if you wish, in our paper. Some of the core tenets of the TAME framework, not all of them, but some key points. Commitment to graduality. There is no bright lines. Michael suggests that intelligence is built gradually and by accumulation of complexity. Material independence. Our model is not based on neurons or central nervous system. Well, we'll talk certainly about a subset. You know, I'm a clinician, I work with human beings, so we'll talk about brain-based models, but generally the model applies to synthetic agents and cells that are not neurons. Commitment to empirical research as opposed to just exchange of opinions on the subject. Dynamics. The selves are not fixed, they're malleable and plastic. And selves can be nested and overlapping, cooperating and competing both laterally and across levels. This is an illustration of one of the key concepts in Levin's framework called a light cone. And what you see here depicted is various organisms. In the middle of the slide, you see a tick and a dog, a human being, possible AI, a compound intelligence such as an ant colony, and you see this sort of nested and embedded structure on the picture on the right. And light cone has two dimensions. There's a spatial dimension and on the horizontal plane, and the vertical dimension is temporal. And tick, for example, is not particularly concerned with things happening a mile away. It cannot recall far from the past and plan far into the future, while human beings are capable of planning things until that happen after we die, a living will. And with the use of language and culture and books, we can use things that happened before we were born. So we're capable of huge light cones. And I'm highlighting this word capable of. It doesn't mean that in our wakeful hours and alert hours, we're walking around with a significant light cones. They contract and expand depending on various circumstances, but we're certainly capable of them, while ticks are not. And the vertical dimension of a light cone is exactly what we mentioned before. That is the temporal depth. There is, of course, a perspective on the same thing in FEP, and I like this very succinct phrase by Karl Friston, who said, because consequences follow causes, the generative model acquires a temporal depth. And more formally, some agents are only capable of modeling their immediate environment and live in the here and now, while others are capable of planning actions into the future. And the generative models capable of planning are referred to as temporally deep generative models. So temporal depth under FEP is the length of the temporal horizon that is considered during planning. We're moving on to describing the, if you wish, healthy self. And we do mention that it is a materially independent structure where, you know, in principle, we can talk about the selves of synthetic agents and cell collectives. Selves depend on an organism's ability to infer. And here we will provide a viewpoint on the two clinical terms familiar to clinicians, such as derealization and depersonalization. So the organism's beliefs about the world are the inferences about the external environment, and the continuum of issues in this process we will call derealization, while the organism's beliefs about its own internal milieu, its body and mind, we will call the self, and the continuum of issues of this process we will call depersonalization. The selves are hierarchical, composite, nested, and with boundaries. So we consider a self to be a system consisting of hierarchically structured beliefs, which effectively makes it a dynamic, hierarchical generative model. And taken in its entirety, the self is informationally separated from the external environment by a Markov blanket or a near Markov blanket by a boundary. We'd like to emphasize, I apologize if this is trivial to the audience of the Active Inference Institute, that this boundary is not material like skin, it is informational, through which the self and not self interact. So to emphasize, the self, as we have defined it, is a model. It is not an organism. The organism constructs and implements it. So the self is quite literally the construction of the mind. This is an illustration of that from early work by Michael Levin. I think this was his doctoral dissertation materials. And what you see here is duck embryos that started from an oocyte, and then you have blastoderm. After cell division, you have a collection of cells. And at the top left, if nothing is done, then this blastoderm will develop into a single ducky. You see this green shrimpy-looking thing? That's a single duck. However, if you introduce a scratch in this blastoderm and the wound heals, the same exact cell collective may develop into twins or triplets. You see the red, yellow, and green duckies. Now think about that for a moment. What happened here? This collective of cells computed what is me and what is not me. And the hardware did not change. But in one case, it made a decision that this is all me and the rest of it is not me. And another one, it says there's three me's. So you can see that this is not hardware. Selves are also, as I mentioned, hierarchical, composite, nested, and they have boundaries. So now we're moving on to components of the self that are, each component is separated by their own boundary and Markov blanket. And because we're using the word hierarchical, we will define that there's a core self, a core component. If you'd like a visual metaphor that Mark Solms uses, we can think about an onion. And there's different levels of the layers of the onion, and there's a core in the middle. We will talk about that as applied to humans and mammals and rodents. So now we are in organic organisms. This term is from Effective Neuroscience, from Jaak Panksepp and Lucy Biven's book. And also, I believe Solms and Turnbull used it. So core self is non-reflexive and dominated by raw feelings, and part of purely effective core form of consciousness. So the effective homeostatic mechanisms allow an animal to problem solve in novel environments. And I'll give you an illustration from Mark Solms to maybe just bring it home. Imagine that I'm in the room full of carbon monoxide, and I've never been in that before. So I don't really know what to do, but I feel badly. I feel badly in a very specific way. There's air hunger, suffocation, distress. And let's say I'm moving around the room, but if I move to the left and I feel a little bit better, then that's information. And if I move to the right and I feel worse, that's also information. Perhaps there's a door on the left and there's a draft underneath the door and I feel better. So this compass, this internal mechanism, the homeostatic mechanism, allowed me to find out a possible solution. And we have a whole collection of these, to mention, the actual hunger for food and thirst and social homeostats such as rage and fear and panic, separation, distress, etc. So the collection of that is what Panksepp and Solms conceptualize as the core self. Therefore, the set of predictions in the core self that all the life-sustaining affects will be at or near their settling points, which means, in emotional terms, contentment. All my needs are met. I am A-okay, thank you very much, right? And that is the minimum of the variational free energy. If there are deviations from it, such as hunger or thirst or air hunger, then that would be a prediction error accompanied by a negative feeling, like in the example that I used above. In mammals, we're not putting the equal sign, but we're describing the anatomical structures that are participating in serving this function. We're talking about the upper brainstem regions, including the reticular activating system and the periaqueductal gray. They mediate the functioning of the core self. And you can see a lot more details in Mark's book, Hidden Spring, A Journey to the Source of Consciousness. So, core self is thought to be present in animals without the cortex, such as decorticated cats, that are actually more effective and not less. And the cases of human children born without a cortex, hydrancephalic children, they have emotions when, you put a brother on the girl's, chest. She smiles and she cries. So the core self does not require a functional neocortex. The higher levels of the brain structures in humans, including the cortex, mediate the higher levels of both consciousness and the self, and sometimes it's referred to as extended consciousness, which allows us to reflect on what's going on, such as to say, I feel anxious right now. There is an asymmetry in this model where the higher levels, the peripheral levels of the self and consciousness cannot exist without the core. While the reverse is not true. The core can't exist without the higher levels. One of the other illustrations of that, which Solm cites, this is based on Fisher's work in 2016, is that a tiny lesion, a 2 cubic millimeter lesion in a parabrachial nucleus, will reliably and irreversibly reduce a coma. The patient will never become conscious ever again, while you will never have anything like that happen in the cortex. This small lesion in the cortex will not result in catastrophic outcomes like that. And this is one of the reasons why neurosurgeons don't usually like to operate around the brainstem. This is too consequential, too risky. So everything was said about consciousness, the core and extended, is applied to self as well. The peripheral self components cannot function without the operational core self. And we will illustrate that with specific examples in humans later on. In addition to this on-off, where the thing is completely operational or not, we can talk about the influence, and the core self has the ability to change the regime of functioning in other, more peripheral self components by inducing phase transitions in them. And the brain mechanism for that is generalized arousal. When the higher levels of consciousness are present and functional, then we have representations such as fruit and vegetables. And, in the core self, we have raw affects such as, separation distress or hunger. But with the higher levels of consciousness presence, we are capable of thinking things like, I want an apple. Or the affect, the drive, as in Freudian language and in Solm's language, is attached to the object. And similarly, we can have these constructions about the meta objects, such as I look pale, or I am a pessimist, and I here is a mental object. And therefore, I is a metacognitive construct, an abstraction, and it only exists at the higher levels of the self, such as autobiographical self. It is not used or even needed in the core self. To reiterate, core self as a system has the capacity to detect the effective prediction errors and attempt to minimize the variational free energy through action without any I. And we're moving on to peripheral self components, and we'll describe only a few. And the terminology here is different from what you may read in a wonderful book by Neil Seth, Being You. So the first one is autobiographical self, and that's a system dynamically representing our life's history. If you, for example, remember your 10th birthday, and the cake is on the table, and mom is there, and your friends are there, and the sun is shining, and everyone's smiling, and it's Tuesday, that's an episode, that's an episodic memory. And a collection of them organized through time is our sort of life narrative. There is a bodily self, which is a system dynamically building inferences about our body and various representations and interoceptive processing. There's a social self, which is a system representing inferences about how we're seen by others and how we present ourselves and act in the social environment. Each peripheral self component, such as bodily self, for example, has its own Markov blanket, And each component is embedded into the whole self and also contains subcomponents, creating a nested architecture that you saw in the TAME light cone picture before. About the unity, that in humans, at the higher levels of the self, such as at the autobiographical self level, these levels create an impression of a unified experience, and this is just the experience of the autobiographical self, not the entire system. The autobiographical self claims to itself and others to be the entire self, while it is not. So Anil Seth refers to these things as delusion. We have a delusion of being a unified, Alexey, right? But what we're saying is that it is that system that is deluded, the autobiographical self subsystem. I'm ambivalent about using the term deluded. I think it's not the optimal one because we use it in the clinical world, and I prefer it called inference or belief that we're unified. Stated differently, we can say that a stable belief that I'm whole in the I'm complete in the autobiographical self, its generative model contributes to us feeling as a monadic self. Therefore, the subjectively perceived unity, the coherence of the self, is an inference. Related to coherence, another thing we can talk about is continuity. And nearly as a tautology stemming from the definition of Markov blanket, our self remain the same, persist in time, while all the processes or communications across its Markov blanket remain functional. And we can offer you another viewpoint on the same exact phenomenon from, if you wish, more neurobiological perspective or psychological perspective. If you recall, maybe you're at the train station or anywhere in the city and you see someone and you think you recognize them, but you're not sure. This sensation of recognition of familiar, so the familiarity novelty calculations is what we're talking about here. And depersonalization is a breakdown in that. Something that is familiar myself suddenly, abruptly becomes very novel and not recognized. But actually, these calculations neurobiologically are not bright line dichotomous categories. They are probabilistic and they are spectrum, but we coarse grain them in the mind often into yes or no, familiar or novel. So that subjective impression of, yes, I know this person or not, is just the coarse graining of the continuous variable. Representational capacity is important. The deep generative model implies that the agent is capable of planning into the future, which in turn requires an ability to generate, store, and retrieve counterfactual data. Generate, store, and retrieve is memory. So therefore, when the representational capacity is completely or partially impaired for any reason, the agent completely or partially loses an ability to infer, leading to depersonalization and derealization. If we talk about health and pathology briefly, the two key terms here are voluntary and involuntary. Again, all of us during our day, we can either sit down to plan things, for 10-year temporal horizon, which expands our temporal depth, or when we meditate or rock climb, then we can be more in the moment, in the here and now. But trauma doesn't ask permission. Perpetrators are, there's nothing voluntary about it. And so that's an involuntary collapse of the temporal depth, which usually is leading to pathological conditions. This is a perspective from the nonlinear dynamical systems. If again, I am in, adult, healthy, alert functioning, and I may have small deviations from I am me, say I'm daydreaming or something like that. And the collection of these points from which I reliably return to I am me can be described as the attractor basin, and the whole thing in terms of attractor landscape is the set point attractor regime, I am me. And I am me would be the variational free energy minimum. And that is a fairly stable system, perhaps in the autobiographical self, right? Now, in order for that system to change, some energy needs to be applied. And with external interference of sufficient power, this attractor landscape can change. When that power is applied, temporarily there's a phase transition. The attractor landscape evolves into something else. Perhaps during that transition, you have a chaotic regime. And if we are in the case of trauma, then the functioning can be chaotic for a while, but then it may settle down, so to speak, into one of the possible post-traumatic presentations. There may be multiple post-traumatic presentations. And one of the possible options is depicted here. This is not, again, universal, but it's one of the possible options. What you see here is a multiple coexisting point attractors represented by local minima of the variational free energy. And they can correspond to alters in DID. And in this example, you also see that they're surrounded by a global minimum of variational free energy. Now, also, if you look at the area, the region between the local minima, then in dynamical systems, that's called a repeller. And repellers are notoriously chaotic, so that suggests that you may not have very good predictability of how you will transition from alter X to alter Y or alter Z. To say a few more words about this, when we switch between the alters, then we are in regime of itinerancy. This is the term Karl Friston likes to use a lot, and justifiably so. Also, when we have these transitions from X, alter X to Y, that the time is disrupted. In DID, you don't have this flowing continuity of time. There's a series of disruptions. Effectively, then your coherent large light cone is broken into pieces here. Now, imagine that this patient with this condition reached out for help and they want to get better. But this attractor landscape already acquired some stability. And so, again, we need some interference to destabilize the pathological regime. The difference here would be that in therapy, in the process of healing, this destabilization of the pathological attractor landscape is voluntary, controlled and guided, ideally by a licensed and competent mental health professional. And that's the difference from the onset of acute trauma. So psychotherapy can be one such intervention, and it's the treatment of choice. We have very limited efficacy with medications, and now it's very fashionable to talk about augmentation with psychedelic treatment or perhaps neurostimulation. It's important to say that just destabilizing that landscape doesn't guarantee anything at all. So when people present this idea that you just go to and have some ayahuasca or anything, ketamine infusion, and you're better, is a myth. Because, the important part is that the patient settles back into health, and just the destabilization of this landscape doesn't lead to that. You still need therapy. You still need, to process the trauma, not just to destabilize the pathological regime. And that therapeutic process, when you destabilize the pathological attractor landscape, is another phase transition, temporarily chaotic, with the idea that eventually it leads you to a healthier functioning, either a attractor landscape corresponding to cohesive system, or at least a little more coherent system with less alters, partial improvement. Let's talk a little bit more about the phase transition. So before things happen in health, we have a nested and embedded self, and that can be described in FEP as a hierarchy of coupled interconnected attractors. Karl Friston, wrote that slower attractor can possibly control the phase transition of the faster attractor. And in our system, the core self is feeling-based, it's affective, and it's one of the components of affects of feelings is generalized arousal. And we know that the changes in generalized arousal level can lead to the phase transitions of the entire neocortex from periodic to chaotic state and back. So this is one of the possible explanations in our model how this works, the phase transitions. A few more thoughts about it. Trauma is not a guided transition. It's an affective storm. It's a flood of cortisol that is abrupt and severe, and that abrupt increase in generalized arousal leading to the destabilization of a healthy attractor landscape in the autobiographical self. But then when there's an onset of a dissociative syndrome after trauma, then the regime settles down to a lower energy, perhaps affective numbness that patients talk about. And in a psychotherapy, not immediately, but when the patient is ready, which can take a year or more, when there's active trauma work, then there is again an increase in energy level with the idea eventually to settle down to a healthier regime of functioning. A few clinical observations starting from dissociative disorders, which are conceptualized traditionally as defensive response to prolonged and inescapable trauma. Clinicians talk about, and patients report this quality of emotional flatness or deadness or numbing. Sometimes they call it freeze. So in our model, it corresponds to issues with communications between the core self and the peripheral self components. For example, that autobiographical self in this regime operates as if it is uninformed by the vital emotional informational flows that originate in the core self. One of the possible ways it can be achieved, not the only way, but one of them is the prefrontal cortex inhibiting the limbic structures. That's the cortical limbic inhibition hypothesis. And in FEP terms, that means lowering of precision associated with effective prediction error messages. We're moving on to also severe dissociations, but temporary, such as general anesthesia, propofol. And it's a very profound change in the body that influences the gap junctions between the cells. And recovery from anesthesia is a very interesting process. Michael Levin is fascinated with it. It's actually a little bit of a miracle that we come back to be the same person we have been before. And some people don't. You may wake up a pirate. And these conditions are called postoperative delirium, dissociative amnesia, postoperative cognitive dysfunction. This is also an illustration that self is computed and plastic and malleable. It's not a hard, hardware. And perhaps we get oriented with the use of our memory systems, including the episodic memories. Another severe case is a seizure, where not only autobiographical self is impaired, but also the social and the bodily self. And one of the reasons for that is the necessary resources for the functioning of these self components are not operational in seizure. Moderate dissociations in neurological cases, but permanent ones, are, for example, perhaps one of the most famous neurological patients, HM, who had a bilateral hippocampus damage. And in Britain, there's Clive Waring, and Anil Seth describes Clive Waring in his book, Being You. These patients do not have episodic memory encoding, and effectively they live in about 10 minutes of the here and now. There is no past and no future beyond that. And if you read Clive Waring's diaries, that he talks about the series of awakenings. He said, "Oh, I just woke up." And 10 minutes later, "Oh, I woke up." And then I woke up. And if you show these diaries to a clinician who's an expert in DID, they will, which I've done, I talked to Roxy Wolf, one of the fellows of the International Society for the Study of Trauma and Dissociations, and she said that, this patient looks perpetually depersonalized. There is no continuity in self. Korsakoff patients, they don't recall the past, they confabulate the past. And in Alzheimer's, in early phases, there's issue with recent autobiographical memories, but some access to the remote autobiographical memories. All of these cases are discontinuity in autobiographical self. More frequent, perhaps, cases are substances. Ketamine, high doses of THC or ayahuasca lead to depersonalization and derealization. And importantly, if you read the studies, then these patients actually report, they tell you that their sense of time is impaired. Not only that, the planning is impaired as well. If you have a alcohol blackout and the person tells you on Wednesday that they have no idea whatsoever what happened on Tuesday after 6, then this is a discontinuity, this is a gap in episodic memory. There's also something called traumatic amnesia. There's very sad cases of high school shootings where, the person literally doesn't remember, 15 minutes of what was happening in the cafeteria. What happens in acute PTSD is that, hippocampus is reaching cortisol receptors and there's a flood of cortisol. And effectively, the episodic memory of trauma, the cohesive contextual timestamp memory is not laid down in a stable fashion. You have shards of glass, you have phobic memories, semantic memories, procedural memories, but not the episodic one, which is also discontinuity in autobiographical self, and that is involuntary. And we talked about mild, benign, everyday dissociations. Next time you wake up, maybe tomorrow or the day after, try to monitor what's going on. And you may catch that phase of what Metzinger calls, a non-egoic self, where things are just flowing through your mind. but your eye is not fully on board just yet. To summarize, the level of consciousness, regime of consciousness, pathological states, and all the underlying resources necessary for the successful operation of each self-component collectively influence the complex dynamics of the system. A neurobiological perspective, briefly, the historically most famous one is cortical limbic inhibition hypothesis by Sierra and Berrios, who postulated that prefrontal cortex is inhibiting the limbic structures, including the amygdala and the anterior cingulate cortex, ACC. The subsequent studies don't fully support that hypothesis, but partially support it. I like the work by Ruth Lanius and her colleagues. And guess what? Her revision, her refinement of the cortical limbic inhibition adds dynamics, transience, context, and itinerancy. All the things we like. They talk about two regimes, even in patients with dissociative syndromes, overmodulation and undermodulation. Again, itinerancy. In not one regime, but multiple regimes. Overmodulation is indeed hypoactive amygdala and hyperactive prefrontal cortex, which is described above. But also these patients less frequently, but you can see it, are in a reverse regime where amygdala is active and PFC is less active. Overmodulation dominates in dissociative conditions. They refined the anatomical network and talked about different subregions of amygdala, the central medial amygdala, basolateral amygdala, dorsolateral periaqueductal gray, ventrolateral periaqueductal gray, thalamus, and other regions. And this network of regions collectively works to create specific post-traumatic regimes. They also described that regime where patient has access to painful memories, usually is accompanied by undermodulation, very active state with amygdala active. And when they don't have access to painful memories, they're more in a dissociative state. We can also briefly talk about what are the anatomical substrates and the neuropsychological substrates of the temporal depth collapse. And again, acute trauma, hippocampal damage, and dementia affect the episodic memory system. If there's an insula damage, then you can expect the disruption in the bodily memories. And perhaps in ketamine use, you may have a dysfunction of prefrontal cortex and frontoparietal network, which renders the working memory of the patient dysfunctional. You can imagine other circumstances when you have PFC and frontoparietal network impaired. That usually leads to a psychotic state where, it's very hard to think. We need working memory to be able to think. About dissociative disorders, again, the point made at the very beginning that prolonged, inescapable exposure to highly stressful environments can be seen as lasting stress beyond the agent's ability to manage, which results in the breakdown of TAME light cone into the components, a fragmentation, decoherence, and discontinuity when the landscape, attractor and repeller landscape corresponding to a pathological condition takes root. And in contrast to that, if you look at the single episode of ketamine intoxication, then you have transient working memory disruption leading to transient dissociation. Again, to summarize, lasting or temporary, severe or mild, dissociative experiences are accompanied by the collapse of the cell's temporal depth. And we are ready for discussion, which I very much look forward to.
Thank you, Alexey. Great presentation.
Thank you.
Okay. Where should we begin? What would be interesting or given where the work has gotten over the last few weeks, what do you feel like is most relevant?
Well, perhaps any colleagues have comments. I don't know if Jesus is with us, and he's an esteemed neuropsychiatrist, and he sees a lot of patients and perhaps neurological patients, and he can comment on some of the things we've mentioned. I had a clinical meeting with colleagues who do a lot of dissociative works, and I'm seeking feedback and critique, and so whatever people have, whatever thoughts people have.
Yeah, if there's anyone in the live chat, they can write a question. A few pieces that stuck out differently in how you presented it in comparison from working on the paper was the narrative self's role in the maintenance of the narrative of unity and about what is the experiencer of that, or is that all it can do? Why does it do that? Why does the autobiographical self have that kind of a voice or a cognitive function?
Yeah. Is audio working okay? Can we hear each other? I think why is a tricky question. It might also be a teleological question. I would say that it's probably functional, for us to have coherent selves. And I don't know why, but we are observing it. So we have descriptive level, we have observations that I feel like the same Alexey. And it's a little bit of a miracle that, as we know, that the cells in the organisms, they die and they're born, but I still feel like the same person. Even so, we change developmentally. I'm not the same person as I have been at age 5 or age 15, but I still maintain this story, if you wish, this belief that I am the same. And I also protect the internal milieu from external threats, of the same organism. And if we look at other species, say an oak tree that, grows from an acorn, it is still the same oak. It's the same organism. So perhaps in biology as well, there's a need for the system inside the Markov blanket to maintain that, saying whatever is inside the Markov blanket is the same me. But it is a belief, and I don't know if I'm answering your question. Maybe I'm just free associating to it. So, yeah.
Is that a clinically valid method? Well, it reminds me of mortal computing, and there's a lot of focus on how behavioral activities in a niche relate to the material stability. And I think you really drew carefully on Mike Levin et al.'s work to talk about the analogous dynamics on a landscape of a narrative self, and that's just that was like a trampoline, but then you also complicated that with multiple selves, like the social and the narrative. And so then there are these multiple dissociative, or like it's they each have their own unity, and yet they can be discordant and unified. Yes. And so then is there any general framework for different possibilities open-endedly of different regimes?
These are great questions, or even maybe challenges to develop it further, but I agree with you. If we look in the bodily self, right, I don't perceive my hand to be a separate entity. I feel for it to be part of the whole organism, myself, my body, right? And so in the bodily self, there's also a level of unity. I'm just saying that this is, again, a computation within that specific subsystem that my body is one whole self. And we can see how that gets perhaps distorted in somatoparaphrenia, or even rubber-handed illusion, where this hand is perceived as not, So, and so we see that the system is plastic and malleable and prone to change, but when no interference is happening, it continues to be cohesive as one body and one mind, this autobiographical. I've noticed you use the term narrative self. I think that's Anil Seth's term. And I prefer autobiographical for the reason that rats, they have episodic memories and they don't have our verbal abilities. And so they also have episodic memories, which are what, where, when, the contextual memories, right? And I think that there's the same I in all autobiographical memories, and that's the unity. Yeah,
thanks. Yeah, a few comments. It probably is more accurate to say it's a narrative cognitive capacity that encompasses autobiographical or allobiographical type narratives. And I'm reminded of NPR radio discussion from a few days ago that I listened about memoir, and about what memoir was, and could it only be written when the person did or didn't change a lot, but what or who doesn't change in every single one of these ways. So then what would that mean? Like what? So that was kind of a funny connection. And then do you have any thoughts on that, or have another active comment?
No, I'm just enjoying your comment. I don't know if I have a thought on that. Yeah.
You see many clinical memoirs and presentations of self-understandings and all of this, so there's just so many, and it gets brought out so sparsely, like, and indirectly, and it makes a lot of sense to the person who might be saying it, but that you could be too or not confident enough about that.
Interesting you brought it up. Thank you for that, Daniel. I think that, when we theorize, say in dynamic theories, then we usually think about different sub-agencies of the mind. Like Freud, for example, in his structural model, he had the id, ego, and superego, where I want pistachio ice cream is the id, and pistachio ice cream is fat and calories, that's the superego response, and pistachio ice cream is $4 and you have 3.5 is the ego. But there's a whole bunch of them. We can name a sort of sub-agency of an internal judge, which is sort of super-ego-ish, or a neutral observer, or an accountant who's running a tally, and all of this. So we all have sort of a jury there of different kind of regimes of operation, if you wish. But the patient is often surprised because when they, for example, self-criticize, and you talk about that in therapy and say, do you notice the voice of your judge? It's kind of, not very fair. I mean, there's no misdemeanor. Everything's a felony and judge is present all the time. And like, no, it's not that. It's me. I'm doing it. I screwed up. So again, the default regime is me, myself, and I, that I am bad. And when we discuss these things and we open it up and we show the different kind of we show a theater with different voices or a jury with different representations, it's usually kind of an insight. It's a surprise. But that allows a bit more control for the patient in the clinical work. So,
okay, I'll read a question in the live chat. Pablo FM wrote, "Thank you very much. I find it super interesting. I wonder why humans seek for drug experiences. Having been so decisive in human history, coffee could be a great example. Tea, tobacco, alcohol have also been very popular among civilizations."
It's a great question. I don't know if I have a good answer. It's a huge question. And there's a good paper, you can find it on Google Scholar or PubMed, by Maggie Zellner, Mark Soms, and other colleagues. I think Jaak Panksepp was alive. It's called Why Depression Feels Bad and What Do Addicts Really Want? And it's based on effective neuroscience. And what it postulates is that, of course, there are individuals who have multiple drugs that they are, using all the time. So there's an upper and the downer and other things. But there are usually some innate kind of predispositions where people who are wound up in tense, they sometimes crave alcohol because it's binding to the GABA receptors and it's sort of, sedating us a little bit. It makes you a little less kind of wired up. People who are very painfully lonely and detached, and they crave human comfort and, to feel together and loved and accepted. They may, if they discover opioids, that would be a, lock and key match. That would be a dangerous combination. And perhaps when somebody is oriented to performance and they're very bored all the time and they want to something, to do better and more, they may gravitate toward stimulants. And so there's these things, and there's some common factors among different agents, such as, I believe that multiple substances, they have the dopaminergic effect. And, a lot of motivations are subjective in individuals. I've had patients say that I'm smoking pot to slow down time. I've had patients tell me that, pot is my oldest friend. I've been doing it longer than any person that I've been with. Some people seek this state of numbness and they want to kind of not feel as acutely. They want to sort of feel desensitized. So these states of dissociation can be desired. And that's briefly, I guess, what I wanted to say about it. So,
wow, thank you. I'm reminded of a comment from Mao in the live chat earlier this morning, and she was kind of pointing to how one mode of how we've seen active inference applied in these presentations is looking like ethology at the sequences of behavior, but not really looking at the self-maintenance as a behavior. Like, especially talking about digital agents, or it's just about what do they perceive, what do they do? And it's taken as a granted or a separate question how they exist. Yet also there's this self-maintenance, self-reconstruction character that doesn't even need to have anything to do with the ethology. Its dynamics can just be like morphologically playing out, not necessarily doing some cognitive task out in the world in any particularly effective way.
Mm-hmm. Yeah. It's a very interesting thought, and for some reason, I'll allow myself the liberty to free associate again. It reminded me of Yuval Harari, who, when interviewed, he said, "You guys go to the gym, you observe your diet, and you take care of your body." And he said, "I take care of my mind. I meditate an hour a day," and he goes to silent retreat a month in a year. And the interviewer challenged him, I think he was from The Daily Show, he said, "How do you manage that?" And Harari said, "I got no kids," So, but in addition to that, he's also in therapy. So there's that idea of really maintaining the mind and not just the body with behaviors. We're all oriented to what do I do? What do I think, which are sort of verbal, virtual behaviors. But how do you feel? As my great colleague Rajiv Warrior says, we're human beings, not human doings. And we have a very tough time being. We're all about doing more. That's right. And so, and also Harari talks about informational hygiene, where a lot of stuff in the social media is noise and trash, and a lot of it is consumed, and we have pollution. But, so he doesn't do, he reads books and he thinks in millennia, but I don't know. I mean, I went sideways from your comment, but that's where my thought went. So.
Yeah. It seemed like a very relevant when people are discussing the unity or the articulation of mind and body, which is kind of what this unified promise on the cover of the textbook suggests, is what would it be to have a unified model of brain, mind, behavior, and so on, then the analogy or the connection with the physical and the cognitive is just, it has to be taken as a starting point, not like a hot take.
Yeah. But what you just said reminded me, when I read Michael Levin's work and got more familiar with it, I actually had regret. I'm like, why were we not taught that? That was a bit of a revolution in my mind. It was a big pivot, because if you go through graduate program in psychology, it's all about the unity. I am the same, cohesive and coherent. And the fact that we have intelligence at the level of individual cells, and then the cell collective, and then tissue and organ, and all of this thing that I think is one monadic Alexey is a pyramid with communications bottom up and top down and laterally is a revolution, I think, that, I wonder what models of psychology can be built with that, and they don't exist yet. It's all about one big block, and then what happens to it? I am depressed. There's no collectives. This is one big block, right? Yeah.
It's a really important insight. I think that's the kind of frictions and experiences we'll start to learn more about and see produce in different ways. Like just seeing how you connected the topics to specific quotes, translated the ontology, reworded descriptions using kind of like a translation, sometimes really just as simple as a lookup of words, just authors using one word and being able to see an active ontology term equivalent or roughly related. It's and what does that look like? Or I guess as your last comments, what do you think after the paper, after this now? Like, what are the directions towards which people would say, okay, that's applying active inference in a clinical setting?
My goal eventually, I think, is to get to therapeutics. And for example, actually, I probably will not use that example. It's a good material for the second paper that we'll follow up with. But I do think that, the question is, what do we do in therapy differently? How do we understand? How do we formulate cases differently with this information? I haven't heard it clearly said out loud in the DID literature. There's a lot of perspectives, there's a lot of endless complexity, and there's a lot of nuance. But if we can highlight a central point and say there is a temporal depth collapse, I think it allows us to do something with it in clinical work and in diagnostic work, and that's my hope. It may not materialize, but this is what I'm hoping for. So,
well, even from a researcher's ethological perspective, it's kind of like that's the transferable and the interesting research question. How could you be observing not on the inside and make some kind of inference or assessment that would matter clinically with no map territory pretense? Not that it's 100% reliability, just taking a clear look at the diagnostics available, rethinking it from dynamical systems perspective, maybe different biometrics, maybe pupil. It's just kind of, that's the open question. And then where it provides clinical utility, that's where it matters.
Mm-hmm. Yeah, thank you. Perfectly said. Yeah, I agree.
Okay. Thank you, Alexey. See you.
Thank you, Daniel. See you. Bye-bye.
All right. That has concluded the live presentations section of the symposium. I'm now going to play the pre-recorded videos. So, 1 second to rearrange, get it in position. Now we'll continue with the pre-recorded videos. Hopefully all of them concatenated into the next few hours. Okay. This talk is by Leonardo Muller-Rodriguez, Groove as the Musical Glue for Social Bonding.
Ladies and gentlemen, hello. Welcome to today's talk on Groove as a musical glue for social bonding. My name is Leonardo Muller-Rodriguez. I'm a PhD student at SIMTer, and this is a neuroscientific and cross-cultural perspective. Now, I'm a bit self-conscious by the fact that the only audio you'll be hearing today is my voice, no music. But do books sing? No, we're doing a deep dive into the scientific literature, not musical theater. Maybe musical theater in the future of my active inference. Well, my name is Leonardo Muller-Rodriguez. I'm a PhD student at the Cambridge Institute for Music Therapy Research, SIMTer, and my focus is on sleep music for dementias. And if you're curious, how does this tie in with danceability, where it relates to musical entrainment, more specifically slow beats. I'm also a composer, music producer, and musician. So how does groove foster social bonding? There's a little outline of today's presentation, groove and its relationship to Spotify's danceability, the neuroscience of it, the social bonding, the cross-cultural aspect, flow states in music, what musical features define groove, an active inference application of groove, and a little update to Spotify suggestion. So what is groove? In essence, it's the apex of an inverted U-shaped relationship between rhythmic complexity and grooviness, and pleasure if you wish. Grooviness is at a moderate level of rhythmic complexity, which is rhythmic complexity is, if you use the musical term, syncopation is the amount to which the rhythm deviates from the meter or the beat, or alternatively you can think of the tempo, and the beat is a tempo, and it relates to how certain you are of your predictions of that rhythm. So groove is a pleasurable sensation of wanting to move the body to music, driven by rhythmic patterns that balance predictability and surprise. Here's another study looking at the same thing, and we'll see into the neuroscience in a bit that proves this. Now, Spotify's danceability is a measure they use, and they define it as so. We don't have the actual computation that they do. It's the suitability of a track for dancing, based on a combination, unknown combination, unless you work at Spotify, of tempo, rhythm stability, beat strength, or pulse clarity, and overall regularity. And this data sets, someone put this on Reddit, and they've looked at 1 million tracks, and I was like, okay, you beat me in terms of data sets. And so they've categorized all the musical genres, several musical genres, in terms of as a function of danceability. And based on the discussion, and it makes sense, on Reddit, it's more about rhythmic simplicity, it seems to analyze, because it's the more danceable music is techno, deep house, and then you have salsa music, which is lower, and people in the comments who are salsa dancers like, well, what is going on? And especially metal, heavy rock, or hard, metal fans that were thinking like, wait, is comedy more danceable than my favorite genre? So they're a bit offended with that. At least sleep music makes sense that it's kind of low. So it lacks this relationship between the complexity and predictability. Fun fact, if you listen to all the 1 million tracks, it will take you 7 years and 9 months if you listen to it on a 24/7 basis. Here's my data set. I compared sleep soundtracks, sleep playlists that are either very popular on YouTube or that I've created my own self, or playlists that I have millions of subscribers on Spotify, to high energy music such as gym music that has this beast mode playlist has 11 million subscribers, or this reggaeton music. With reggaeton is a Latin popular dance music, very popular here, 11 million, and this has about 5 million. And you see the danceability is in general higher for this higher energy music compared to sleep music. And here I compared valence, and high energy music is also more positive. Apparently sleep music is more negative. Anyway, let's dive into the neuroscience of it. And here, the main thing I want you to focus on is the fact that beat perception is present in the brain, and frequencies increase their strength at the onset of the pulse. Here there are different tempos that were used, or different speeds between pulses, and as you see, there's always an increase just after the pulse, regardless of the tempo. It happens all the time, and it happens at the level of beta and alpha brain waves and gamma brain waves, these higher brain frequencies, and it activates these brain regions here, and we'll go a bit more in detail, but it's quite wide range. And it turns out that we can call these the musical rhythm brain network, because it makes use of the dopaminergic and the dopaminergic reward system in the brain for beat perception and positive affect of groovy music. And this involves the supplementary motor area, premotor area nearby, the putamen, as well as for pleasure and the urge to move to the music, is the nucleus accumbens and this connection to the medial orbital frontal cortex. Because we're talking about an auditory stimulus, auditory regions must be involved. And the cerebellum also from fine motor movements. Turns out that musical rhythm predictions and surprises are measurable in the brain in two forms. So the first one is about short-term habituation to a rhythm via repetition of a certain rhythm, and then the deviation from that, the surprising change to that rhythm, is seen here in this paper, where there's this measure called the mismatch negativity, which measures prediction errors in relation to rhythm deviations, changes, or omission. There you don't have that note that used to be in that rhythm. And the other form of surprises and predictions is by the recruitment of long-term memory. Or we can talk about it in terms of implicit music theory syntactic knowledge, where here, regardless of you being told in advance that there will be a non-traditional chord sequence that will be played, you will have this sort of mismatch negativity, which is more specific because it recruits long-term memory. Here is called the electric response in the auditory nerve area. And yes, that's an interesting aspect. By traditionally, I mean traditional music, Western music theory for harmonies. Here again, we're just looking a bit deeper into this, whereby beta waves we saw earlier and gamma waves, the high frequency waves we saw earlier in terms of beat perception, are responsible for top-down, so the beliefs, the predictions, beta, and the updating, the surprises through the gamma high frequency activity in the brain. So, another aspect of music is that it's usually done in groups, such as musical performance, appreciation, music therapy, or learning about music. And it turns out that music in groups synchronizes brains. And this is called interpersonal brain synchrony. And in addition, it recruits the same musical rhythm network that we just saw, with a bit more broadening of it. It has the amygdala insula, which is usually involved in visceral activity, and more generally the prefrontal cortex, the motor areas. It could involve actually moving if you're performing, and the basal ganglia in general, which incorporates all the dopaminergic reward system, which nucleus accumbens and dopaminergic system, etc. Putamen, correct. We saw that earlier. Now, music. The real function of music, beyond the auditory cheesecake that Steven Pinker says, is not just pleasure, not just reward systems. It has to do with social bonding and building trust. Music is a participatory activity, and dancing, actually, is a way to participate without any musical virtuosity or even familiarity to the music. This is why I call it embodied democratic music participation open tool. And it fosters joy and social bonding. And music strengthens this interactive rituals. You can talk about it in terms of ritual. And it's a social tool for enhancing groups. So as you can see here, you start to predict the beat, you see repetitive motions, this induces groove, induces dancing to it, and this enhances social bonding. Within this sort of, you can frame it within an agent environment system. Moreover, seeing others dance and move encourages dancing. So this reinforces the social bonding aspect. And this was exemplified here, where eyes open with low tempo, high tempo, high groove actually increases the collective movement in a group of people listening to music. And this is what they were measuring here with this cross wavelet. And dance promotes also, here, interpersonal movement interaction, promotes self-other integration. It enhances social cohesion through synchronized movements. And more specifically, moderate syncopation, and low as well, for also there's an implication for Parkinson's disease. Low and moderate syncopation, which is groovy music, does so as well. It encourages self-other inclusion with social bonding. And we're talking about music, the groove, and is it applicable to a cross-cultural definition of music? Well, first, there has been, this is with Japanese music actually, there has been an optimal groove tempo range identified, which seems to be not only a inverted U-shaped relationship, non-linear relationship with tempo. This seems to be from 107 to 126 BPM, beats per minute tempo. And the evolutionary interpretation for this is the fact that it's near 120 BPM, which is the optimal tempo for walking and dancing. So this is where groove might come into. Sensory motor synchronization is most optimal in that around 120 BPM. And there are also universals, cross-cultural universals of music, which has been identified using statistics. And the main aspects that are cross-cultural is beat, dancing, making music in group, percussion, repetitive melodic sequences. These are musical features that are universal. Just going a bit deeper into this, they used music for all around these spots. It's quite a geographically varied data set, although only 304 recordings. You know, there's millions of music. But I think it's a nice generalization we can make based on the black box. So the black box here are musical features that are at least 50% shared in globally. And the most, which are the most, you know, the whitenesses is shared. The most shared are beat, subdivisions by binary ternary subdivisions, or scales that have up to 7 notes. So this is interesting. And this was controlled phylogenetically, meaning that this ensured that these musical patterns and associations are not solely due to shared cultural or evolutionary histories. Another aspect that is cross-cultural are musical bodily sensations and emotions. What I want you to focus on here is this correlation. They asked Asian participants, 500 people, and Western participants, 500 people, to associate emotional labels to musical features. And there's a very strong correlation, 0.94. Between these. So there's a sort of cross-cultural aspect here. Obviously, it's not all cultures, maybe African, Latin, and Middle Eastern cultures do feel differently. But here's just a Latin influence that's indeed instrumental syncing in syncopated music, which is groovy music, which here was samba, encourages the urge to dance. So groove at least is present in Latin American music. Now, musical flow is not restricted to groove. What is flow? Flow is a state of absorption, total absorption in an activity. In other words, the feeling of losing yourself in the moment. Flow state is usually characterized as a state of emotional resilience against trauma. And here, emotional expressivity is one of those not groove musical features that induces musical flow. And here, the two main things I want you to focus on is the blue histograms, which are states of flow. Here were performers, piano performers, and this is a musical feature. And so there was higher flow during swelling dynamics, so crescendos, decrescendos, which is volume fluctuations, as well as repetition of melodies, and not only just any melodies, but stepwise melodies that are not too far apart in terms of distance on the keyboard, or in terms of notes. So the closer they are, blue is again flow states. The closer they are, the melodies, the more flow inducing they provoke. Another musical element that provokes flow, that is not groove, is the narrative arc, storytelling, emotional journeys in music. And this interesting paper by colleague Annie Heideschet identified stages, emotional stages of the hero's journey, which is a narrative arc found in myths, films, popular films, and stories, narratives in general. They've identified emotional stages of the hero's journey in patients and clients specifically in this case was eating disorders, but applying to just more generally, undergoing music therapy. So they were doing guided imagery with music, which is a type of music therapy, and depending on what they're saying, the clients, these themes were identifiable within this the hero's journey narrative arc. So that's very interesting, and this is very important for music therapists because this informs further the scanning aspect that they usually do in GIM, which is that they try to identify using the music where is the emotional stage that the client and the therapist should start their emotional work. And so this is actually emotional journeys are actually a concept that is applied by DJs. They usually talk about energy arcs for their DJ sets, and it's also very prevalent in film soundtracks. Film soundtracks are so music is being used to guide the emotional journey of the audience. Now, flow as neural entrainment. I think neural entrainment is evident for beat perception. We've seen it several times. Here's more evidence, like accurate beat perception increases neural entrainment. Here it's just saying that beat sensitivity, there's a sort of temporal range where this sensory motor synchronization decreases with very slow tempi. But here again, beat perception, the beat is being identified in a neural activity, and even if you imagine certain rhythms, these frequencies appear also in the brain activity. So neural entrainment with beat perception is clear. But how about for emotional expressivity and emotional journeys? Well, this study reconstructed the music that was listened to by the participants from their neural patterns. It was a combination of EEG and fMRI, a technique that made use of EEG and fMRI and deep neural networks to reconstruct the music based on the neural activity. And you can see that not only very impressively resembles quite a lot in terms of spectrogram information, but obviously there's not just rhythm activity or rhythm information that's being displayed. There's more, there's frequency activity. So this takes us to this study that demonstrated that spectral flux is actually the most accurate measure for neural entrainment to music. And you can see this with this red line. It's the highest correlation with neural entrainment. And in addition, they've demonstrated that it is a metric that encompasses amplitude, envelope, as well as beats. They have mutual information here. And spectral flux, or spectral novelty is called, is a measure of novel energy increases in the frequency spectrum. So this is an interesting aspect. Now, nevertheless, as you can see, other strong neural synchronization musical features, in addition to spectral flux, are temporal range. So roughly, as you can see here with the orange line, 60 to 120 BPM. High familiarity with the music, and pulse clarity, easy to perceive the beats. So let's keep it simple. What are the groove's musical features? Two things: moderate rhythmic complexity within an optimal range of around the walking tempo of humans. These two encompass most of these characteristics: syncopation, tempo, microtiming, event density. This has to do with, and even beat salience has to do with rhythmic complexity. Slope of attack is a variant of beat saliency. Low frequency band, as the bass enhances dancing. Volume, and then this is the chord progression and that. Now, keep in mind that sensory motor synchronization is not limited to this groove tempo range. The sensory motor synchronization tempo range is shown to be between 60 to 180 BPM. Below and above this, the sensory motor synchronization, which is usually finger tapping or dancing to the beat, decreases which is probably linked to biomechanical reasons. However, probably training increases your capacity to do so, to synchronize. However, the beat perception still can occur beyond those this tempo range. I recommend watching this YouTube video by Ada Neely, which goes into this the extremes of beat perception. Let's apply active inference into Groove. But first, before we do that, we need to understand that the brain is constantly generating predictions about how the world works in order to minimize the uncertainty about how the world works. 2. The brain is a layered thing, and it balances top-down and bottom-up influences, where higher layers send beliefs about the world down to lower sensory layers, which these sensory layers, as we can see here, actually send back up sensory stimuli to adjust the beliefs through the mechanism of minimization of prediction errors or minimization of free energy. Now, talk about Groove. Groove balances confident predictions with surprise about the rhythm. Just reminding you, it is an optimal playing with belief updating about musical rhythms. Now, listening to Groove is accessible to groups of people, and therefore can become a shared stimulus for motor and emotional synchrony, and therefore, under the active inference framework, generates generalized synchrony, which means that people have shared world models, the listeners have shared world models. And this is depicted here with this quote. It says, "Neither a model of my behavior or your behavior, but a model of our behavior," quote by Friston. And generalized synchrony actually requires flexibility in terms of your higher beliefs. Because you're trying to model flexibly your collective identity and collective behavior. And because of this and the social bonding aspect, I place musical groove on the spectrum of the rebus hypothesis, which is a relaxed belief under psychedelics. Meaning that it's not as the flattening of the free energy landscape is not as extreme as psychedelics are supposed to do, but musical groove can achieve this through the social bonding. So dancing to the same music not only increases trust and social bonding, but it also allows for individual creativity. Compare an expert dancer and a novel dancer. A novice dancer and an expert won't be having motor mimicry, but they will be sharing emotional synchrony. And this provides the mechanism for trust and bonding while considering creativity of individuals. And you can make use of a federated belief multi-person system to model groove as the shared marginal likelihood that people non-verbally communicate. So because idiosyncratic dance moves have been shown to even increase more the social bonding and trust, I encourage you next time to take the risk and bust on some moves on the on the dance floor. All right. So what I want you to consider right now is the current models of the context that encourages dancing. Yes, they say musical properties. They have temporal predictions that you can do. It induces pleasure, induces arousal, and this, together with regularity, creates the urge to move to the music. And this will generate motor planning or policy generation under the active inference framework. And this desire to move and in training the body movements creates social connection. But I'd like to add a bit more to this in terms of contextual factors based on the literature review we're presenting today. This is a hypothetical contextual factor framework for danceability. Basically, groove is the mechanism for dancing. But there are several contextual layers that individuals might need to cover before starting to dance. For instance, I have two example individuals, a white individual here, this white arrow, who requires seeing other people, seeing their friends before starting to move. Whereas this red individual just requires to feel a change in emotions to start wanting to move. And these layers have a non-linear relationship with the groove, meaning that your contextual entry level to start dancing might be seeing a friend starting to dance, and you might not need familiarity with the music to start dancing, to start connecting to the groove. Whereas DJs sometimes make use of familiar music in their DJ sets to encourage people to start dancing. They say getting those first 3 people to dance is always the most difficult part, and once you have them, the crowd joins and you have a crowd dancing. So this was modeled with a reduction of entropy, to do relatively simply, whereby depending on the distance to the groove, there's a higher entropy level that has a non-linear relationship with grooving. And K is based on personality and the relationship between each layer. There's another way of conceptualizing this as the gravity of groove. The layers are done like this. So, implications for Spotify's danceability. We saw that it's more likely has to do with rhythmic complexity. Comedy is more danceable than blues, apparently, or heavy metal. Headbanging is not as dancing as laughing. Valence as well. The most joyful music seems to be salsa, and the less joyful music is sleep. Maybe Spotify is inspired by the rapper Nas, who has a lyric saying, "Sleep is a cousin of death." So let's go beyond this and beyond rhythm and tempo, and incorporate what we've been seeing today into danceability. So if we want to generate a formula that goes beyond danceability, unknown equation, which is most likely rhythmic simplicity, we convert. First, I want to point you to this study which asked musicians to perform groovy music with simple and complex melodies, and they showed that there's about 30% occurrence of fast notes, specifically 16th notes, when people perform groovy music. And this was also confirmed in terms of listeners saying, yeah, that's groovy. And so here I've just used the optimal groove range and transformed it into seconds, so you can have an idea. And too quick for Spotify. They can't. No, I'm just kidding. You get to see the equation. So what I've done is I made use of spectral flux, which is this spectral novelty, makes use of Fourier transform, and then logarithmic compression to enhance weakened spectral components, and then you compute the difference between time frames in terms of positive energy increases. And so it measures positive increases in energy. Event density is another measure that's been used in these studies, and it's a number of events, onsets, per time window. So here's a groove formula I suggest, which is open to your feedback, which is 30% of energy onsets that is in the 16th of a note time window, divided by a measure that's dependent on the tempo. And a measure is 4 times the beat, because most music is on 4x4 meter music. So I want to give you this quote: "Dance is an energetic mode of participation for a large population, regardless of age, familiarity with music, or instrumental singing virtuosity." To summarize, we found that groove is a musical mechanism for social bonding through movement, and therefore through movement is danceability, right? And we can make use of the active inference to model groove as a musical mechanism for generalized synchrony, even as federated beliefs to model individual creativity. Further works would encourage the usage of other social bonding metrics in music, such as group singing. Chanting is seen around rituals around the world, and this has implications for group music therapy, live performances, and team building, music recommender systems, etc. So please do contact me. I'm open to collaborate for this Groove project and discuss any of your ideas. We could discuss about musical exchange music if you want. And I just want to show here my YouTube channel, which explores. Thanks to the YouTube channel, I've actually learned how active inference works. They say teaching is the best way of memorizing. And in here, for instance, I explored Chris Field's work in active inference with the holographic boundary for social interactions, which could also be a further direction of trying to conceptualize musical groove in that manner. But shared marginal likelihood is probably very effective as well. Thank you so much. Please do ask me for the references. I will send them. They have been sent. Yeah. I should be on the chat, by the way, answering some questions. Thank you very much for your time. See you very soon. Bye-bye. Thanks.
All right, I'm going to play next a short video from Anna Pereira, an Active Inference Institute Research Fellow.
Hey, Anna Pereira here. I was disappointed that there was an irresolvable conflict during the time of the symposium, but wanted to share or contribute a small update nonetheless. For those of you who haven't had a chance to hear from me before, we've been looking at accelerating and disseminating active inference for the humanities. We're actually just starting to call it AIH. And we continue to make progress and quietly incubate in the background. We're not really at a point to do a large, more solid update. But we want to quickly say hello and say that we are incubating. We continue to be available for collaborations or conversations others find useful. And also to provide an update that we've been really grateful for the opportunity to incubate within the larger AII structure. This has provided several mutualistic affordances, has been a really great construct within the larger AII space. So we look forward to being in touch at future conferences and symposiums and available for conversations. In the meantime, wishing you a great symposium and be well. Ciao.
All right. The next talk is by Aswin Paul, Bridging Biology and AI, Active Inference for Biologically Plausible Decision-Making Models. This is a 15-minute video.
Hello, everyone. My name is Aswin Paul. I recently finished my PhD from Monash University in Australia and is currently working as a machine learning researcher in Versus AI. So today I'm here to talk about using active inference to model biologically plausible decision making. And thank you, Active Inference Institute, for organizing this symposium. Let us start by mentioning a recent cutting edge experiment that was developed by Cortical Labs in Melbourne. So what they managed to do is they developed a chip, a silicon chip, and they cultured real biological neurons like mice cortical culture and human cortical culture. And they managed to couple this chip with a computer game like the game of Pong that you see on the screen right now. So the experimental result is that given meaningful feedback, these neural cultures actually demonstrate relative improvement over time in playing this game, as you can see from this graph, right? Like the MCC and SCC neurons actually demonstrate that they can actually improve in game play when compared to baseline groups like the in silico agent or the control groups. So given such advancements in experiments, from a theoretical perspective, active inference is a great candidate to model such experiments and biologically plausible decision making. So we have emerging literature and a lot of evidence suggesting this. So when we actually try and do modeling, there is a clear need of scalability in the active inference literature, where we are used to modeling very small environments with very low number of states and very low number of actions, etc. So in order to actually use active inference in such scenarios, we have to scale up the existing active inference algorithms. And in the first part of the talk, I will be talking about some algorithms and techniques that we can use to scale up modeling decision making in active inference. And in the second half, I will talk about using these algorithms to actually model the particular experiment that we saw earlier. So when we talk about scaling up active inference or scaling up decision making in active inference, the first technique I want to talk about is evaluating decision making backwards in time and not forward in time, as we usually see in the active inference literature. So when we define the expected free energy and compute which action should be taken given a particular observation, rather than evaluating expected free energy or computing it forward in time, as we see in techniques like sophisticated inference, we can actually use dynamic programming and model decision making backwards in time. And this result is actually published in paper in this particular paper, if you are interested in this particular algorithm. And a more general version of this algorithm was recently published as the inductive inference algorithm by our colleagues in Versus AI. And in that paper, we note that inductive inference algorithms scale up decision making drastically and can be applied to bigger generative models. Another technique that we can employ in this regard is to actually learn prior preferences. And in order to do that, we actually take inspiration from the optimal control literature and this particular paper. And this particular paper introduces an algorithm called SED learning that improves scalability and efficiently computes the optimal action when compared to cutting edge algorithms like the Q-learning algorithm. And a particular matrix in this algorithm called the SED matrix is actually very similar to the prior preferences in active inference. And we can actually learn this SED matrix orders of magnitude more efficient than classic reinforcement learning algorithms. And what we do in this paper is that we show that we can actually learn prior preferences using a similar learning rule. And once we learn this prior preferences, then decision making is really easy because we don't really have to plan a lot forward in time. And we also demonstrate that learning is robust in this particular algorithm. And talking about computational complexity, both these methods, one is DPFE method that computes expected free energy backwards in time, and the other one that learns prior preferences are actually orders of magnitude more efficient than the classical active inference we see in the literature or the recent sophisticated inference. And both these methods actually learn or scales linearly with time against the exponential computational complexity of decision making that we see in the active inference literature. So we tested these two algorithms in terms of its scalability and adaptability in state spaces as high as 900. And what we saw is that when we actually introduce stochasticity into the grid, these algorithms are more adaptable than cutting-edge reinforcement learning algorithms like DynaQ. And we demonstrate that these algorithms are scalable, which gives us confidence to go ahead and model experiments like this. And when it comes to modeling neuronal dynamics, we already have existing active inference algorithms that model neuronal dynamics, that is from CBS Riken, developed by Professor Isamura and colleagues. And in one of their works, they actually talk about a similar experiment where neural cultures are actually performing a perception task, which is called blind source separation. And in a more recent work, they also talk about decision making in neural cultures and develop a decision making model that can be equated to neuronal dynamics. So going into details, we have this algorithm called counterfactual learning algorithm, and they develop a version of the variation free energy that is term to term equivalent to a neural network cost function. And this is valid for a particular class of neural network, and more details can be found in this particular paper. And there are two terms of interest in this algorithm. One is a time-dependent risk parameter and a time-dependent state action mapping that this particular agent uses for decision making. And because of how it is developed, it is biologically plausible and can be shown that every term is one-on-one related with the cost function that a particular class of neuronal networks actually minimize. So in one of our recent works, we generalized this algorithm to have memory, and we tested it in a similar control task like the cart-pole game that we see on the screen. And we can actually draw comparison with the cart-pole game and the Pong game, because both of them are reactive tasks where the agent is supposed to actually react to the environment and take decisions quickly to balance this pole or to deflect the ball back. So we observe that compared to planning-based algorithms like DynaQ and DPFE, the counterfactual learning algorithms perform really well in this particular task, and gives us confidence to go ahead and model the biological neurons or the kind of experiments that we saw earlier, right? And in addition to being able to model this, we also have the advantage of explainability in these algorithms, unlike deep learning algorithms that are black boxes. So if we actually perturb the environment, say in a particular episode, we can actually see that the risk term is shooting up in that episode, and this particular term captures changes in behavior of the counterfactual learning agent, and we can actually try to explain how decisions are being taken at every time point, unlike black box approaches. So given these several algorithms that we have, can we use them to actually model the manifestation of natural intelligence in experiments like dish brain, right? So for that, we actually develop an experimental based generative model that is based on this particular experiment. So for example, this is the Pong game environment that they use in the experiment precisely. So for example, we have the X coordinate of the ball that being communicated to the dish brain chip through 38 distinct frequencies in the experiment, and the Y coordinate of the paddle and the ball being communicated through 8 different voltage levels in the experiment. So for example, like we have 3 observation modalities in this experiment, and we note that these are the number of states and the ways of communicating that to the agent. And we enumerate the state space of our generative model using this experimental details and match our generative model to be exactly like the experimental generative process. And we also have like the active inference parameters in our generative model, like the transition dynamics of a POMDP and counterfactual learning based state action mapping, the risk term and the prior preference distribution, etc., that we discussed in the talk earlier. And given that we have this experimental based generative model, we can model decision making of in silico active inference agent and hope to compare them with the experimental result to draw insights and so on, right? So first of all, we perform simulations using the counterfactual learning agent. And we can see that counterfactual learning agent with memory horizon as low as 2 is actually performing at par with the HCC group in terms of performance. So here CFL T stands for CFL memory horizon T. So as expected, with more memory horizon, it performs better. And we can actually look at which memory horizon is performing similar to the experimental group and so on. And in one of our recent works, we note that the active inference agents are incredibly data efficient compared to deep learning methods. And it is only the active inference based model, that is counterfactual learning method, that demonstrate data efficiency at par with the biological neurons when compared to deep reinforcement learning algorithms like A2C and PPO, if you are familiar with the deep reinforcement learning literature. So we also compare the planning based methods that we mentioned earlier, like the dynamic programming method. So in this particular task or the Pong game, planning is not really useful. So with increasing horizon of planning, we don't really see improvement. And planning horizon of 5 performs as good as HCC neurons. And planning beyond a point is not useful in this particular task because of the nature of the task. And we also note the explainability of our models. For example, if we look at the average risk in the counterfactual learning method, we see that the risk is actually only reducing significantly with a memory horizon of 4, and this can also be correlated with the performance improvement that we saw in the results graph, where with memory horizon 4, there was a significant jump in performance. And these kind of explainable insights that can be drawn from our models is a clear advantage over black box methods like deep reinforcement learning. And we can also look at the entropy of the CL parameters, and we see that the entropy is decreasing over time. That is the evidence in learning. And parameters reveal differences in behavior of different agents, and that is a clear advantage here. And to summarize, we actually developed an experimentally informed generative model and simulated decision making in the particular environment. We tested different active inference based algorithms in this setting, and we also noted the similarity of memory augmented counterfactual learning method to the biological neurons, and we are interested in investigating similarities of the memory based CFL method more to the biological neurons. And also insights like this can inspire more experiments where aspects like memory can be studied well. There are several limitations to this work where we haven't conducted a really involved statistical analysis in comparing these agents. We are right now qualitatively comparing them with average parameters, but we would like to do more statistical analysis. And we would also like to inspire experiments from our theoretical predictions in our future work. So I thank all my collaborators in this work. And if you're interested in this particular work and the algorithms that I discussed, you can actually get access to all the papers here. And feel free to contact me if you have suggestions or more questions about this work. So thank you for your time. And I look forward to meeting you all when I have a chance next. Thank you so much.
All right. The next talk is by Bert Burgers, Towards Autonomous Urban Digital Twins. This is a 20-minute video.
For the next 20 minutes, I will talk about transport policy planning and how active inference could be applied through digital twins. Urban planning is a very broad field, encompassing everything that occurs in urban regions. from the design and operation of infrastructure to social programs. To scope this, I will focus on the transport system, giving a rough sketch of what active inference may entail for this domain. Modeling the transport system relies on operationalizing decision making. Many individual choices lead to busy roads. Therefore, the main storyline focuses on the difference between active and passive decision making. The presentation is structured in 3 parts. First is the context, giving an outline of urban digital twins. I will focus on livability, as it is an objective of transport policy. Next, I will present some domain-specific building blocks, which are then combined in the final part. Finally, I hypothesize that renormalizing generative models can be used as transport models. Concluding that active inference-based modeling might require a new perspective on transport planning. First, I will give some context in order to frame how active inference, transport planning, and digital twins come together. The field of transport planning is moving towards the development of digital twins. These twins enable quick calculation of effects given an intervention. Rather than performing a comprehensive study per project, which can take months, a digital twin can be reused many times. An example application would be the construction of a new neighborhood. What are the effects on congestion, air quality, and inundation risk? There are roughly 5 levels. The first introduces a compelling visual interface, often involving a 3D representation of the real urban region. Next is the addition of information on top of the visualization. Any geographic data works. The third step not only maps data, but incorporates different physics-based models. Hence, it is called predictive. Transport models are one example, others are airflow or water simulations. High-performance computing speeds up the scope of parameters which can be tested. The fourth level builds on top of the predictive models by adding an interpretive layer. The added value is scenario-based planning, where a range of outcomes is calculated for a hypothetical intervention. Instead of configuring parameters exactly, you could propose a preferred outcome to the computer, and it would only simulate what is necessary, as it understands relations between models. The last level introduces autonomy. Not only are physics-based models configured intelligently, as in step 4, but the twin actively goes out to construct its niche. Transport policy evaluation is going through somewhat of a change. In decades before, the development of transport models allowed the paradigm of predict and provide. We could forecast traffic flows and accordingly invest in infrastructure to prevent congestion. More recently, the field has acknowledged that models trained on past data are inherently flawed in predicting uncertain futures. As such, it is moving towards scenario-based planning, sometimes described as decide and provide. Along with this change comes a reflection on the philosophical context. For simplicity, I rely on 2 frameworks. The first is utilitarianism. It relies on the assumption of rational choice, enabling the quantification of benefits and costs in terms of utility and disutility. Between every origin and destination, there are several alternative routes. Each has attributes such as the distance traveled and the cost. Combined with preferences, we get generalized travel cost. The rational choice assumption enables fungibility. This allows us to take the ratio of estimated beta parameters in utility functions. These ratios can then be used to calculate, for example, the monetary value of travel time. In practice, we always use monetary value as the final measure, so that we can compare the cost of implementation against the benefits experienced. Finally, utilitarianism leads to aggregate increases in welfare at the ignorance of the distribution. Not only does this apply to wealth, but accessibility too. Take, for example, the discrepancy in infrastructure spending between core cities and the periphery. To address these concerns, contemporary policy evaluation attempts to move away from utilitarianism. Instead of attempting to relate all preferences to monetary value, we leave them separate. Not only do we reject the fungibility of indicators, but we also consider many more than before, shown in this wheel, spanning from living environment, accessibility, health, and safety. Finally, the distribution of costs and benefits is explicitly considered, and much work is now spent on reworking existing modeling frameworks to make these distributions explicit. There are three main objectives in planning infrastructure: accessibility, safety, and livability. Capturing livability is much more difficult than accessibility and safety. Livability is generally defined as the fit in an ecological relationship between resident and the living environment. With regard to the spatio-temporal scale of this relationship, livability is local and sustainability is global. For practical reasons, fit is operationalized through valuation. The more an environment can satisfy one's preferences, the greater the fit. Theoretically, it has been long known that fit could also be operationalized as a continuous transactional process. However, little progress has been made, and this is where active inference comes in. These two approaches to livability are best defined by contrasting them to each other. On the one hand, we have the static approach, which is concerned with measurable outcomes. On the other hand, there is the dynamic approach, in which livability is viewed as the hidden driving force behind that which is measurable. By framing livability as comprised of three components, indicators, percepts, and needs desires, I can show that the location of fit determines which is which. Either it is a weighted function between percepts and our preferences through valuation, or livability is a weighted function between indicators and percepts, which are biased towards our preferences. Finally, these two approaches might be complementary, and this might be useful for modeling purposes. There are many different transport models. When it comes to those used for urban planning, these can be distinguished into micro and macro simulations. The micro scale simulates individual vehicles and their interactions. Meanwhile, the macro scale applies constraint optimization over a network. Preferences constrain this optimization. Here I will focus on macro models, which combine transport and land use patterns. Fundamentally, we rely on seeing the transport system as a market. Travelers generate demand, while the network provides supply. The four-step model forms the backbone of microscopic transport modeling, and I will go over each step. First is trip generation. This step determines how many trips start end to end in each zone. It is about determining the row and column sums. See also the top right figure. For trip production, we look at residential zones and use socio-demographic factors like household size, car ownership, and income levels. For trip attraction, we look at the number of jobs, shops, or school capacity. Trip distribution iteratively balances row and column sums to fill the origin-destination matrix. Balancing is done using a gravity model, where the number of trips increases with their mass, but decreases with the travel resistance. With the full origin-destination matrix, we can split these flows per travel mode used. The utility of each mode can be weighed against our other in the choice set. Logit models can be estimated for different segments of the population. That is the figure in the equation at the bottom right. Finally, we assign trips to links in the network. According to Wardrop's first principle, travelers select routes to minimize their travel time, leading to an equilibrium where no user can reduce their travel time by changing. The entire workflow is iterative because assignment affects travel resistances due to congestion. Not shown here is the modeling of land use, which affects zonal data. Next, I will outline three conceptual building blocks which will be combined in the synthesis. As we just saw, modeling transport networks requires a representation, for example, the travel time per link. Additionally, we would like to approximate human perception, for example, by using images or sounds. The field of urban representation learning attempts to automatically capture the content and structure of cities. Luckily, there is a strong inductive prior from geography. Similar things are closer together. As such, major design choices revolve around which measures of distance to include. Examples are Euclidean distance, travel volumes, or accessibility. Generally, an application of urban representation learning relies on three choices. First is the need to discretize the urban region into spatial units. Each acts as a class. The figures on the right use hexagons. Secondly is the type of data used. Where traditional transport models only use tabular data, we can now also use street view images and text. Last but not least is the way in which parameters are structured and learned. Graph neural networks are widely used as they naturally represent the transport network. Additionally, the loss function can be used to steer training. Accessibility is a major field of study in transport planning that connects well with active inference concepts. In urban representation learning, we aim to capture spatial similarity in embeddings. Accessibility provides a theoretical foundation for which similarities to capture. Intuitively, accessibility is akin to landscapes of affordances, which are shared by everybody living in an urban region. Location-based accessibility is derived from constrained maximum entropy and can be configured to equal utility-based accessibility. The calculation is straightforward. For each zone, we sum the product of destination attractiveness and the deterrence function based on generalized travel cost. The deterrence function captures how travel cost relates to similarity. As shown in the maps, accessibility patterns differ significantly between bike and car networks. Hierarchy is a well-established element of transport networks. Think of how local streets feed into arterials and highways, each operating at different speeds and distances. Where local streets facilitate access, main roads enable throughput. To capture this hierarchy in urban representations, we start by defining the study area, creating columns of coarse hexagons and then mapping them to the finer resolutions. I have used a UNet to capture both bottom-up and top-down information. Each block in this net is a graph convolutional neural network. A pre-computed accessibility graph sparsely connects centroids of hexagons, where the edges are the accessibility value. Reconstruction loss ensures we capture input data, while consistency loss ensures columns of hexagons are integrated. Combining context and building blocks, I will now go over the synthesis. We started by discussing digital twins and two approaches to livability, static and dynamic. The dynamic approach frames livability as niche construction. When it comes to policy, the problem boils down to the objective function used. Could free energy act as an objective function for policy evaluation? Unlike utility, free energy cannot be summed across decision makers. Perception itself is subjective. Meanwhile, with utility, we all live in the same fully observed world. If urban regions engage in niche construction, perhaps we can create digital twins that embody their niche construction process. Autonomy then becomes about influencing an existing process rather than creating something from scratch. There are three potential approaches. Agent-based models on a hex grid simulating individual travelers, simulating each hexagon as a cell with the expectation of emergent behavior, or use a renormalizing generative model with a fixed hierarchy. The third option is the most promising, as it requires a single model rather than the combination of many smaller ones. In line with this third approach, I want to consider a fixed hierarchy, and renormalizing generative models are perfectly suited to this purpose. The idea is that these might already be transport models, as they map origins to destinations using cost functions. Sticking with the notion of a market equilibrium, there is a demand and a supply side to the operation of renormalizing generative models. Just like in a four-step transport model, the demand side determines the landscape of afforded embeddings, and these embeddings capture the spatial similarity. The supply side aims to calculate the distribution of flows through the network. It is just that here, the network is a hierarchical structure, not the physical transport network. On the demand side, the landscape of affordances, or the landscape of afforded embeddings, is perceived through the combination of top-down prior and bottom-up data. From the top-down, we impose our cost function on traversing the lateral accessibility graph. Attributes on edges are valued against each other. For example, travel time and the price of petrol. We also impose our preferences in terms of the content we wish to see. So the content of the embeddings. For example, the concentration of emissions in the air. From the bottom up, we receive information for this lateral accessibility graph, like the travel time at this moment, as well as the content of discrete spatial units. And this content is in the form of embeddings inferred from high-dimensional data using neural networks, so that this process can be automated. On the supply side, we have a landscape of affordances at each layer in the hierarchy, and we need to pass messages between them. Supply is about narratives of attention, either about errors flowing up or predictions moving down. To move laterally, you have to go up and over. In doing so, carve the transport system at its joints. For example, when you need to do groceries, you probably do not zoom out to the causes layer. Instead, you will find grip much more quickly and walk a few blocks. Using active inference as a framework to understand decision making in urban regions is still speculative. The standard workflow of ex ante evaluation to study the benefits of a project might not be applicable anymore, as the digital twin goes out to construct its niche on its own. The separation between technical calculations and political motivations in planning becomes blurred. How do we capture both travel choice and policy objectives in one model? Accessibility is already a central topic, yet it has now gained additional consideration due to the reframing into landscapes of affordances. These affordances may not only be in terms of tabular data, but can be high-dimensional, like images. Accessibility heavily draws upon constrained maximum entropy. Bayesian mechanics treats this the same as free energy minimization. It therefore seems worthwhile to reframe accessibility in this way too. Active inference is useful not only for autonomous urban digital twins, but also for level 4 twins. To refresh, level 4 twins use physics-based models with the addition of an interpretive layer. And this additional layer contains an understanding of the sensitivities between models, which allows an urban planner to quickly converge on a set of designs rather than simulate thousands of alternatives. Therefore, a practical starting point would be to take level 3 digital twins and upgrade them with an active inference module to explore the parameter space efficiently. The apparent complementarity of static and dynamic approaches of livability suggests that we could use representations learned through valuation, so a supervised way of learning urban representations, to then use them in learning the structure of an active inference model. In sum, it is fair to say that autonomous urban digital twins still need a lot of work. Regardless, considering free energy as an alternative to utility is a valuable exercise in understanding decision-making in urban regions. Lastly, I would like to thank the team of symposium organizers for the time and effort.
All right. The next video is 23 minutes long. Ines Hippolito, Dysfunctional Markov Blankets, From Stuck States to Adaptation.
Hi, everyone. I'll be presenting today Dysfunctional Markov Blankets, From Stuck States to Adaptation. This is a paper that has been in progress for quite some time, and it is a collaboration with Mahault, Albarracin, Alex Kiefer, and Daniel Friedman. So I want to start by highlighting that there are stuck systems or stuck states all around us, and that we find that example in neural cognitive levels, such as in OCD patterns, in PTSD trauma cycles, or in addiction circuits. Then on the social or ecological scale, we find it, for example, in poverty traps, in echo chambers and market monopolies and climate tipping points. Then in AI, we also find them, for example, in large language models loops. Who hasn't been stuck in a I apologize kind of cycle? Then in reinforcement learning local minima, in recommendation filter bubbles, and in neural networks training fails. So what these kinds of systems share is that they are some sort of critical threshold. They have or present self-reinforcing loops, and they have this persistence to change. So they tend to remain in the same state, hence why they are stuck. So then the core problem is going to be a sort of a paradox. So the view is that systems, adaptive or complex systems, coupled with the environment, they should adapt, but sometimes they don't. So then from this perspective, a few questions become salient. Why do flexible systems become so rigid and do not have that flexibility to adapt to the environment? How do these adaptive boundaries between the system and the environment break down? And what maintains that dysfunctional state? What is there that it must be so strong that the system cannot change to a different or look for or act for to attain a different, more preferable kind of state? So then, of course, that these are presented as challenges because there is an ever-changing world and the system that needs to adapt to that ever-changing world. And it seems like existing approaches, such as dynamical systems theory and network science, still have some limitations to quantify and address this kind of phenomenon that we call a dysfunction. So then, from our perspective, we need a framework that unifies this explanation. So we need three things. First, we need to identify and characterize dysfunctional states. Then we need to provide a mechanistic explanation for the stuck states. And finally, we need to offer a principled approach to designing these kinds of interventions. And that's what we set up to do in this paper, and that I'll be presenting to you. So our framework bridges theoretical frameworks from complex systems theory and the free energy principle. the main or core concepts that are going to be useful are notions such as emergence, self-organization, and adaptation from complex systems theory, and coupling, self-maintenance, and free energy from the free energy principle. By utilizing these two frameworks, we developed what a construct that we defined as dysfunctional Markov blankets. And with that, we hope that we will offer a formal theory of systems dysfunction. And we hope to develop quantifiable measures for this phenomenon of stuckness. And finally, practical recovery strategies so that we can act upon the system that is stuck in a therapeutic way, and we hope to kick the system out of that stuck state into a healthy state. Okay, so as to adaptive systems, we all know that they are comprised by components which interact, and from that interaction we observe some sort of emergence. For example, in the case of an immune response, we have different immune cells, each one with a specific role, and they interact in the form of cell signaling, recognition of events, and that interaction then gives rise to emergence that we observe in the form of coordinated defense or system-level memory. Then, from the free energy principle, which we are very acquainted with in this conference, we learn that systems that exist act to minimize their free energy. And further to that, the understanding or the insight is that systems are coupled with the environment and they act upon the environment to precisely attain or look for more preferable states for their self-maintenance. And we can explain that behavior through active inference. Then another very useful construct is Markov blankets. Of course, the framework is dysfunctional Markov blankets. And the Markov blanket, as we all know, is a statistical boundary between what is inside of the system and what is outside. But further to that, an important insight is the conditional independence between internal and external states, which give the system sort of a very important boundary to have a distinction between the self and the no self. And that can be seen also through the notion of it's an operationally closed system, a system that self-organizes and maintains itself. For that maintenance, it's also quite important that it is thermodynamically open. It is an open system. It's not a closed system. And that's what allows them to remain alive by adjusting to the environment. And here you see, for example, we have neurons in the form of internal states that could be part of a network. So a key innovation concept that we bring in is the notion of selectability. And selectability is a system's capacity to explore, navigate, and select among possible states. These can also be seen as the system having multi-stability, many points that are afforded to the system in the environment such that the system can be healthy in that navigation. So you can see that, for example, that comes represented here in the form of state A, B, C, or D. Different points that the system can explore within the environment and select the most preferable ones. And the notion of selectability allows us to think about state space accessibility or affordances, the adaptation capacity, and the boundary flexibility to adapt rather than being rigid and stuck in a particular state. So then within the free energy principle, we can think through that paradox. It becomes if systems minimize free energy, if they accord to the principle, why would they get stuck? Does the principle not work, or is it the system that is not in a stuck state? So then what we realize is that what is really within the paradox is that we cannot explain these persistent maladaptive states, and there is not really a formal treatment of the dysfunction. So then there is a missing link between theory and intervention. And our solution is the dysfunctional Markov blankets. There are two types of boundary dysfunction that we can observe in these systems that are not adjusted, attuned, adapt to the environment. So they can come in the form of stuck states or blanket breakdown. And stuck states, I mentioned this in the first slide. And for example, in the case of depression, what we observe is rigid kinds of thought patterns, reduced emotional flexibility, impaired social information processing, and shortcuts bypassing healthy emotional regulation. And in a more general way, we can define these stuck states as the self-reinforcing kind of cycles, being trapped in deep energy wells and being resistant to environmental perturbation. Then on the other hand, we have blanket breakdown. And an example of this is the immune system, when the immune system attacks its own tissue. And what happens here is a very interesting phenomenon of excessive permeability on the boundary of the blanket, right? Loss of system integrity. So the no self distinction. The system doesn't know what's self and what is not self. That's the loss of system integrity because of the boundary dissolution. Okay, so then we arrive at the definition of the dysfunctional Markov blankets. And this is a statistical boundary that contrastingly has lost its adaptive capacity for effective mediation between internal and external states. And the key characteristics of the dysfunctional Markov blankets are that the system is persistent in high free energy despite adaptation attempts. And what we observe is the breakdown in information processing and the loss of effective environmental coupling. I will unpack this further, but let me just situate us for a moment. So we will go from the framework to practical tools to cross-scale applications. That's where we would like to go. So to do that, we need to first define quantifiable measures, then identify a dysfunction index, and finally, the recovery metrics. Then as to practical tools, we need adaptive perturbations in order to kick the system out of the valley, and recovery strategies. And this is on a more therapeutic kind of side. And hopefully we'll be able to apply these across scales. So now looking at the framework itself, the first thing that we need to do is to find that dysfunction index. And what that is going to help us do is to measure and identify and delineate the dysfunction. It will measure the information flowing through the wrong channels, like a diagnostic kind of tool that spots the system bypass. And the higher the value, the more dysfunction. For example, like a cell with a compromised membrane. Then we will need also a recovery metric. And this will be a progress kind of indicator for us. So it shows a dysfunction reduction. And the thought here is that we ask ourselves, are we fixing the bypass problem? So then we will need in order to advance with that, we need the landscape reshaping, kind of like bringing out a new geography of points that are afforded to the system, making sure that we don't get stuck again. And hopefully we'll attain the system's adaptability, where we find the question, can it explore and respond flexibly to the environment? So why are these two measures relevant? Well, they will serve the role of being universal tools across scales. We will be able to apply them to all scales from cells to ecosystems, and they will help us diagnose and track recovery and guide our next stage, which is the intervention design. Okay, so now moving to practical tools, adaptive perturbations, and recovery strategies. We have adaptive perturbations here playing a crucial role, and an adaptive perturbation is going to be a controlled intervention that temporarily disrupts a system state to facilitate adaptive change. And what we mean by this, or our goal, is not simply to push a system out of being stuck, but it is to help it to become more resilient, precisely to make sure that it doesn't come back to the stuck state, as you can see an illustration here on the graph below. So we define the adaptive perturbation design as, in the first term, as traditional intervention approach, where we would like to nudge the system towards these better states, such that it adapts based on the system's response. Then with the middle term, we can reshape the energy landscape, have a different sort of more flexible geography that makes it harder to get stuck. Again, like smoothing out the deep valleys. And then finally, we can promote exploration, and that means help the system discover new affordances, new possibilities, hence enhance adaptability. There are kind of like two examples of adaptive perturbations that I just want to mention, and one is by the parameter changes, where, for example, you can think of that as a temperature modification in cellular environments. And the other one is the external force or input. An example of that is transcranial magnetic stimulation. So why is this adaptive perturbation relevant? Well, it combines three intervention strategies: self-adjusting, all parameters will adapt over time, and it includes a balance between immediate improvement, long-term prevention, and future adaptability. The practical impact of an adaptive perturbation is that it will help us guide for designing interventions and work across different scales and prevent the kind of, so to speak, band-aid solutions. Right, so then why do perturbations matter in the end? Well, for the stuck states, they're going to be very relevant to help us overcome energy barriers, break self-reinforcing cycles, and enable the system to have more states and the capacity to navigate and explore the environment and select the states that are going to be much more preferable to the continuation and maintenance and self-maintenance and self-organization of the system itself. In the case of the blanket breakdown, this is the case of, for example, the immune system that has lost the capacity to differentiate between what is self and what is no self and attacks its own tissue, then utilizing an adaptive perturbation will be useful to restore boundary function, to stabilize information flow, and to reset system dynamics, and therefore repair the capacity of the system ultimately to recognize what's self and what is no self, what is internal states, what is external states. Okay, so I will recap the journey now from the dysfunction to the recovery. So first, we need to measure the dysfunction. Then we need to track the recovery. Then we will need to design interventions, and we do that through the adaptive perturbation to implement the recovery. Finally, we need to monitor that kind of recovery such that we now have been able to get the system to be adapted to the environment rather than just in a very short term. So key relationships that come up within this journey include going from higher dysfunction to stronger perturbation that is required, going to better recovery to reduced intervention strength, and going from more selectability to greater adaptation capacity. Future directions where we need to go is to extend this mathematical formalism to non-ergodic systems, to multiple timescale dynamics, and coupled systems interactions. In order to do that, we also need to develop measurement tools such as real-time dysfunction metrics, early warning indicators that can predict a tipping point or a point of no return, and then we can apply a preventive measure, and cross-scale validity tests. Some of the implementation challenges that we can see include, of course, measurement, intervention, validation, and scaling up. And in order to address them, we will need better tools, more precise tools, standard tests, and infrastructure. The potential impact of this framework is, like I said, across scales. In healthcare, for example, we can look into therapeutics for any sort of disease kind of cycles. It includes mental health and aging patterns. In climate action, we can apply this framework to tipping points as a preventive measure and to restoration. In AI, we can apply to develop more robust AI. We can also apply it to make more smoother ethical and governance measures for safety in AI, as well as can help us design bio-inspired AI such that it's a system that is more adapted and hence more effective. Finally, in social systems, we can also apply this framework for policy design, for economical stability and social cohesion. And coming to the end, call for action. Research priorities include developing standardized metrics and build shared data sets, create open source tools, and establish cross-disciplinary teams. So please join us in theory development, tool creation, application testing, and knowledge sharing. Conclusion and takeaways. So we went in this journey from dysfunctional systems that we observe that are stuck in a local minimum, and we want to develop a perturbation in order to help the system become more resilient and adapt to the environment out of the stuck state, and hence a full recovery in the long term. So then key takeaways are that we hope that we have developed the foundations for a formal theory of system dysfunction, quantifiable measures for the stuckness phenomenon, and a practical recovery strategy that can be applied, that can be further in the future applied to different scales. Thank you so much for your time. Please do not hesitate to contact myself or any of the authors if you'd like to engage or learn more about this work.
All right, keeping with the co-authorship theme, next talk is a 25-minute recorded talk by Alex Kiefer, Resilience and Active Inference 2024.
This is Alex Kiefer. This is Alex Kiefer. I'm here to present some ideas on resilience and active inference. So this is largely just a unpacking in a careful way of some concepts from this paper from 2022 that I was involved in, but also we'll explore some novel directions that this thinking has taken since then. So the concept of resilience, really, if you look at the etymology, it means like the capacity to recoil, essentially, or to bounce back, or just to survive through hardship and change. So obviously this concept is sort of a fundamental one if you're looking at life forms, dynamical systems more generally, in the context of like ecosystems and sustainability. It's an important concept. So that's why we're interested in this. It's actually also sort of a fundamental concept in materials science. So since this paper has come out, I've been approached a couple of times by journals of materials science for follow-ups and such. So as I said, the fundamental concept has to do with recoiling or bouncing back. But there's there are some peripheral sort of different facets of this meaning, and we explored all of these in this paper. So roughly speaking, you can think of resilience in sort of three ways. So first, there's inertia. So inertia, I mean, I guess literally just means really sort of not changing. So persistence. But you can also think of it as resistance in the sense that, right, unless you're exist in a vacuum, then you're a system that's embedded in some broader system, and inertia is basically continuing on your way despite changes that might occur, or interactions with that broader system. So if you think of the red arrow as representing the path of a subsystem or an agent through its state space, and the black arrow is some kind of potential disturbance, then the top diagram here illustrates inertia. The central meaning, again, of resilience arguably is elasticity, or the ability to bounce back. So in that case, you undergo some perturbation or change, and you end up recovering your initial, it doesn't have to be that you recover your exact initial position, but the point is you make your way back to a reasonable state in terms of the kind of system that you are. Then there's also this sort of third thing we call plasticity, or adaptation. So in this case, you begin in one configuration, the red arrow at the beginning here, and after the perturbation or disturbance, you end up in a slightly different configuration. So that should be read not as just that you change your state, like you update your beliefs on the timescale of inference or something, but that you actually wind up somewhat adjusting your model in response to this change. So this is more like something like allostasis, whereas elasticity is returning to the same state. So I'd say there are some close relationships, just to get into some philosophical conceptual analysis for a second here. The first thing, inertia, probably doesn't really exist in its pure form, right, in nature in a way. If it does, it reduces to sort of elasticity. So I mean, presumably if you perturb a system, then you have to cause some change in the system, however slight. Otherwise, there hasn't been a physical interaction, right? And inertia is going to look in practice just like the capacity to sort of instantly recover from that tiny change. There is, in the limit case, there is sort of a different meaning here, because again, there might just not be a change, but I think in the context of realistic systems, there will always be some interaction. But arguably, these two concepts are very close. Plasticity seems like, on the face of it, like a different thing, because, first of all, the ability to be plastic in this sense sort of explains how you could come to have this property of elasticity. So if you look at the example of neuroplasticity, for example, it's the ability to adapt to change and to basically update your synaptic weights to arrive at a new model that allows you to be, in part, allows you to be resilient in these first two senses. But there's another sense in which, if you just assume that there's some property of the system that doesn't change through this process, which I think is a reasonable assumption in the case of biological systems, then there's going to be some kernel of the system that survives through change, and then you're back to your sort of original definition. Okay, so if we look at this concept through the lens of the free energy principle, I mean, first of all, it turns out to be a very fundamental, as is often the case when you try to unpack fundamental properties of systems in nature in terms of the FEP and active inference, you find that there's a fairly direct mapping from the properties that the FEP attributes to systems, or the types of systems that are well described by the FEP, and this concept of resilience. So, I mean, Karl Friston has said in discussions of this that essentially systems well described by the FEP are resilient, full stop. So, but we can look at the three facets of the meaning of resilience here. So, certainly systems described by the FEP they have this property of inertia, in the sense that by definition, right, they're things that have managed to persist, so they limit their exposure to unlikely states, unlikely observations. But they're also sort of by definition elastic systems, because they have this attracting set. So having an attracting set of states means that of course there might be changes or perturbations that are sort of catastrophic that destroy the system, but as long as the system is not destroyed, then by definition it's going to make its way back to this attracting set of states. So resilience in the core sense is really almost a defining feature of systems that are described by the FEP. And then finally, plasticity you can think of as something like Bayesian model selection on some time scale. And so that might seem like something extra, but it's only extra if the multi-scale aspect of the FEP is extra, and I would argue that it really isn't, because at its heart the FEP is a scale-free description of things, and this multi-scale and scale-free are sort of connected notions. So that's plasticity. Okay, but so most of the interest, I'd say, of this lies in the mapping of resilience onto this formalism of active inference. So a key concept in this analysis is the notion of degeneracy, and this is a somewhat technical term. Here we mainly follow in the definition of and in fact the analysis of degeneracy in terms of active inference in Psy.D et al. 2020. This is a great paper on this topic. So here we have just the expression for variational free energy. In the top row is a expression in terms of basically a Helmholtz free energy, so it's an energy term minus an entropy term. So if you just look at that for a second, we've identified, again, following this paper from 2020, we've identified degeneracy with the entropy term. So we'll get into why that is in a second. But basically, the concept of degeneracy is useful redundancy. So this, you can think of this as like complexity that earns its keep, or that's worth having. So complexity in this bottom breakdown of variational free energy, you analyze it in terms of complexity, which is the difference, the KL divergence between the prior belief over states, the generative density over states, and the approximate posterior. So this is kind of like how difficult is it, or how much change does the system have to undergo in order to represent the states that are inferred from some observations? What's the departure between that posterior distribution and the prior distribution over states? That's complexity minus accuracy, the expected log probability of observations given states. So what's the connection between complexity and this idea of useful redundancy? Of just redundancy. There's a assumption here that complexity and redundancy are closely related. I think the basic idea is that redundancy in this context is quite literally just duplication of states. I'd say the classic example is like an error correcting code. So if you're trying to transmit a bit of information over a channel, you might send 10 copies of a bit in case some of those bits get flipped or corrupted, and you want to make sure that the message gets transmitted. So that's redundancy. It increases the complexity because, one way of looking at it is that it increases the description length, right? This KL divergence is like how much more do you have to say in order to communicate that an event drawn from this Q distribution has occurred, given that you assume this P distribution. So you can think of it as, well, what these extra bits are the redundant bits. So there's a sort of conceptual connection between complexity and redundancy. And then degeneracy, on this first definition, is just the complexity that serves some purpose, and we'll get into that in a moment. It's just also important to note that there's this definition of degeneracy as partial redundancy in the literature, and this is partial overlap in function. So the idea is that redundancy exists in a system. Degeneracy exists to the extent that multiple states in the system serve some function in common, but then those states also have otherwise have distinct or disjoint sets of functions. And in practice, I think these two almost always line up. So there might be sort of limit edge cases in which they're different, but in practice, right, if you have multiple states, they'll always have some different properties and therefore perform some different functions. Okay, so this is one of the core things that we pointed out in this paper of ours. So this breakdown is from the Psy.D et al. 2020 paper, but we sort of have a different gloss on this center term here. So this is the complexity term and the variational free energy. You can break this down in terms of further break this down in terms of this expectation under Q of the negative log probability of states under the generative model. So this is called a cost term in the 2020 paper. We describe this in epistemic terms as an uncertainty term. So this is basically you can read this as the Shannon minimum description length of the states given the generative density, but it's sort of the expected surprise. How surprising are these states that I infer using the variational posterior under my generative model. So that's an uncertainty term, and then we subtract this degeneracy or the entropy over the variational posterior over states. So, I mean, first of all, sorry, I realized that I didn't quite make the link here between degeneracy and entropy. So why is this the case? Why do we identify these? It's because this means if this Q distribution over states is higher in entropy, it means that there's a degenerate mapping in the likelihood from states to observations, right? So meaning for multiple states, you can get the same observation. And so then when you invert that likelihood mapping in order to recover this posterior, this means that for one observation, you might have several different states, and the spread of the distribution over states, of course, is just the entropy. So that's the link to degeneracy there. So this complexity term is uncertainty minus degeneracy. One reason that's interesting is that when this complexity is 0, it's not as if the system is completely certain of what's going on. The uncertainty term actually remains. It's just balanced by this degeneracy. In other words, all of the uncertainty in this ideal case is useful. And so I think this really captures what degeneracy in this context amounts to. It's uncertainty that's useful, and it's useful precisely because there's some amount of uncertainty that's inherent in the source of the information you're trying to model, right? So here P is in this context is the generative model that the system has of it's the sort of internal generative model of the external states. And so there'll be some entropy, some source entropy associated with that system that you're trying to model. And so long as you match, your variational posterior matches that degree of uncertainty, then you're in sort of an optimal model. So in other words, for maximum model goodness, try to ensure that P equals Q. This ties nicely into the idea of plasticity. Resilience is plasticity. So your goal here is to adjust the posterior to match the generative model, essentially. So you can do that, in like perceptual inference. You can try to infer a state, a Q distribution. This is, again, an approximation to the posterior, the true posterior over those states under the generative model. But equally, you can adjust the generative model in a multi-scale setting. You can learn or update the parameters of the generative density in order to match what's in the external world. Right, this complexity term is affected by changes to P as well as changes in Q. And so I think the fundamental idea that I had here was that in an ideal sort of optimal system under the free energy principle, you should expect, first of all, P will be adjusted so as to model the environment for sort of basic, free energy principle / good regulator theorem types of reasons. And then Q will also be adjusted to match P. So this involves this cybernetic principle called the law of requisite variety, which is sort of it's closely related to the good regulator theorem, but basically it just says that if you're trying to regulate or control some states, then you need at least as much variety, or in probabilistic terms that translates to variance or entropy. You need as much variety in the controller as you have in the environment, and so it's a fairly intuitive thing because you basically need sufficiently many degrees of freedom in the controller to be able to model what's in the environment. So you can see this degeneracy property of resilient systems, or just any system under the FEP, as an instance of this law of requisite variety. It's also clearly, by the way, an obvious case of constrained maximum entropy. So there's work showing that many lines of thought really showing that the active inference, the free energy principle is equivalent to a principle of constrained maximum entropy. So here the constraint is this. You can think of this as constrained by accuracy, but you basically maximize this entropy term subject to that constraint, subject to the generative model. Okay, so looking just a bit more closely at this notion of degeneracy. So I've said that it's central. One pointed question you might ask here is, well, do all resilient systems have this degeneracy property? And so I want to say the answer is yes. So the type of degeneracy that we've already talked about is this degeneracy in the likelihood mapping. So this is multiple states mapping to the same observation. And again, that can be cast as you'd expect to see that given that you're performing maximum entropy inference. So that is crucial, but equally important, I'd say, is degeneracy in the dynamics. So this characterizes just systems that have an attracting set of states. So if these STs are states at a given time, and then ST+1 is the state or set of states at the next time step. So this, in order for a system to be resilient, it really has to be the case that this transition, that these transition probabilities or the dynamics of the system are such that that mapping itself is degenerate. So this means that basically you can perturb the system in several different ways, and you'll still end up at the same state or set of attracting states. Obviously, if the perturbation is too large, then that might not be the case. The system will diverge, and you'll destroy it. But by definition, the systems that survive through change are the ones that have this property. So there is a very deep link between resilience and degeneracy if you consider dynamics as well. Just a couple more points here. One is something that I've recently been thinking about. It's actually a theme that's been on my mind for some time, but I've recently written about it in some other work. And this is what does the principle of requisite variety and what do these concepts of degeneracy and resilience look like in the context of multi-scale active inference? But specifically here, I don't just mean the fact that excuse me, the fact that model parameters as well as states can change, but I mean multi-scale active inference in the sense that you've got potentially higher level agents that are composed of lower level agents. So in that kind of setting, requisite variety ends up looking like the property of higher level agents, that they're composed of a variety of different types of lower level agents. So, I mean, I would argue that if you combine this law of requisite variety with multi-scale active inference in this sense, then you really sort of automatically have something like a diverse ecosystem in which there are many different types of agents that participate. So here in this diagram, we're illustrating, first of all, just the same degenerate state observation mapping that we saw in the previous slides. But here, the nodes are individual agents that compose this higher level agent. Also, as pointed out in this paper by Karl Friston and Daniel Friedman et al., in this kind of context, different agents can be expected to, and I think empirically in some simulations are shown, to take on the roles of these different types of states. So, of course, the breakdown here is in terms of active sensory and internal states. So here you've got active sensory and internal agents, and that's one instance, I would argue, of this application of the law of requisite variety to this higher level system. I also show here the policy selection based on expected free energy for completeness, but that's sort of the main point is this specialization and diversification of agents in this setting. In terms of the second definition of degeneracy, you can also think of these agents as playing somewhat distinct but partially overlapping roles. And there's some lots of interesting work on that sort of multi-agent perspective from the point of view of active inference. So that's really it. I'm just going to conclude with sort of a philosophical question that I think is kind of important for tying this together and sort of checking that it just makes sense. So I've said earlier that any system well described by the FEP is resilient. So hold on a second. Not all systems are equally resilient, though, right? Teacups are sort of the paradigm of a fragile as opposed to resilient object. So since the FEP describes things in general, doesn't it mean that all things are resilient? And doesn't that contradict this obvious fact? So I think the answer here is that it's a matter of scale. So yes, all things are resilient, all things, that is, things that are re-identifiable over time and that persist through change. All such things are resilient, but it's a matter of scale. So if you introduce a very slight perturbation to this teacup, very slight, relative to a certain reference frame or a certain scale, but large enough, right, relative to the scale on which that system is resilient, then by definition it will survive, right? And so obviously, again, in a real universe in which there are interactions, and you're always interacting in some way, dealing with some sort of random fluctuations, then yes, for the system to persist through time, to be inert and elastic, it has some, right, the material has some coherence that allows it to persist through those changes. So it is a resilient system. It's just that if you introduce a change that's on a scale that's too great for the system to handle, then it'll be destroyed. But sort of just the basic coherence as a spatiotemporal object of this teacup is itself a form of resilience. And then when we get into more complex forms of life, more complex generative models, that's when we begin to see more impressive forms of resilience and shading it even into plasticity and the ability to really survive through more significant changes. So thanks for listening / watching. I'm happy to participate in this symposium. Thanks to all the other the co-authors of this paper by Mark Muller et al. In 2022. That was the departure point for this work. Yeah, thank you.
All right. The next video is going to be 28 minutes long. It's from Mahault Albarracin, Sustainability under Active Inference.
Hey everyone, my name is Mahault Albarracin, a PhD candidate at the Université du Québec à Montréal and Director of Research Strategy at Verses. Today, I'm going to be talking to you about budding work on sustainability under Active Inference, which we had started with multiple authors that I listed down below, starting from the core components and scaling up to a computational model. We are pursuing this research and multiple collaborations at Verses around sustainability. Ultimately, this is meant to charter a path to much larger projects, so feel free to reach out if you want to collaborate. So let's begin with the most fundamental aspect of sustainability, namely resilience. Resilience refers to an agent or system's ability to persist and adapt in the face of challenges or perturbations. Under Active Inference, resilience is a multifaceted concept involving different strategies that allow a system to maintain or recover functional stability. Resilience can be broken down into three core components: inertia, elasticity, and plasticity. So let's start by defining inertia. It describes an agent's capacity to resist change when subjected to external disturbances. It really is the stability and robustness of a system. In Active Inference, inertia is represented by high precision beliefs, which can be thought of as highly confident, low entropy beliefs about the system's current state. Inertia is reflected in the precision weighing of prediction errors. Higher precision implies stronger resistance to updating beliefs. Maintaining a stable state means that precision is implemented as a scaling factor. So here, higher precision really implies increased resistance to change. The problem is that inertia alone makes systems brittle to errors. They cannot adapt. So then we move to the second component, elasticity. Elasticity describes the system's ability to return to characteristic or attractor states after a perturbation. It corresponds to the concept of homeostasis, so the capacity to adaptively recover. In Active Inference, elasticity is expressed in terms of an agent's ability to minimize free energy and seek stable states. It can be mapped onto the relaxation back to attractor states, which is driven by minimizing free energy as the system follows a trajectory. In doing so, it restores the system to a preferred state, analogous to returning to an attractor point. So for example, in nature, biological systems really exhibit elasticity through homeostatic feedback mechanisms like temperature regulation or blood glucose balance. These systems have the ability to change, but they ultimately return to where they were without necessarily learning. And this may yield the same errors and ultimately can crack under pressure, much like a rubber band pulled too hard. So let's move on to the third component, plasticity. It refers to the expansion of an agent's repertoire of adaptive states. It allows systems to adapt not only by returning to previous states, but also by exploring new states, enhancing robustness. So in Active Inference, plasticity is related to functional redundancy and structural degeneracy, having multiple pathways to achieve the same outcome. Structural degeneracy means that you have different components perform overlapping roles, allowing the system to adapt to novel challenges, but we will dig into this a little later. So here, plasticity is captured through posterior beliefs that can change flexibly based on new sensory input or structure learning if you actually add a new state. We can use the variational density such that the agent can represent a diverse range of potential states, maintaining a dynamic model of its environment. Think, for example, of neural plasticity, where different neural circuits can adapt to perform similar function after damage. To understand how plasticity comes into play, we really have to hone in on certain key concept underlying it. So complexity refers to the uncertainty or diversity of system dynamics. In active inference, complexity is associated with the range of possible states an agent must consider. Complexity is linked to entropy of the system state distribution. Higher entropy reflects greater uncertainty and the number of potential states the agent must account for. Variational free energy is a way of balancing two important things: how complex our beliefs are and how accurately they match what we observe. And so we can balance this in a formula that goes F equals the difference between the complexity of updating our beliefs and how accurately these beliefs predict what we observe. So in this formula, the first part, DKL, measures the complexity or the cost of updating our beliefs to align with reality. The second part, written as EQ, represents how well our current beliefs can predict the observations we make. So we said we were going to turn to degeneracy and redundancy, and I'm obviously here leveraging work by Noor and Karl Friston. For degeneracy, what we're considering is that the presence of different components are capable of fulfilling similar roles within a system. In her paper, they talked about, for example, left hand, right hand. And redundancy means that you have similar components performing the same function, which enhances robustness against failure. The redundancy here involves overlapping functions in state transition matrices B, which indicates similar transitions across different states. And degeneracy can be quantified by the entropy of the posterior distribution, which represents the number of alternative configurations that lead to similar outcomes. And so managing complexity through diverse beliefs really means that the agents can adapt to changing conditions. Degeneracy means the agent can switch strategy when one pathway becomes unavailable, which promotes adaptation. And redundancy ensures the continuity of function when certain components fail, which adds resilience to the system. So degeneracy here helps reduce the complexity cost by distributing probabilities across multiple states, thus maintaining low free energy and supporting robustness in diverse conditions. But while resilience is really critical for maintaining stability, it doesn't fully capture the dynamic interaction between systems and their environments. Resilience focuses on an agent's ability to withstand or recover from perturbations, but it lacks insight into the broader system dynamics. Without considering systemic interdependencies, focusing solely on resilience can lead to short-term adaptation without promoting long-term stability. This is work that Mark Miller and Ines Cipolito have written a lot about. So for sustainability, we really need that systems not only adapt, but also ensure the long-term viability of their environment and resource base. We can, through active inference, integrate resilience and sustainability and show the need for system-wide coordination for harmonious interaction. As Karl likes to say, active inference really is just the story of resilient and sustainable systems. So let's define sustainability a little more. Sustainability is defined as the enduring capacity to meet needs without depleting crucial resources. And here resources is taken a little more liberally. We can expand beyond material resources and encompass social, ecological, and system dynamics. Sustainable systems are those that persist over time and do so in a manner that promotes stability and health across all dimensions: environmental, economic, and social. We achieve this under active inference by enhancing long-term adaptability and interconnectedness across multiple scales. Sustainability emphasizes the creation of conditions that allow for continued adaptation without exhausting resources, effectively ensuring that all parts of the system work cohesively to support resource renewal and plasticity. So, sustainability can be framed as optimizing the expected free energy over deep temporal scales, which is work that Caspar Hesp has pioneered. Balancing immediate needs with long-term system viability. So, the optimization of expected free energy can be represented as f of expected S and A equals the risk plus the ambiguity of x of f expected S and A. So risk quantifies the divergence between the predicted paths, i.e. the future states of the system, given an action sequence and past observations, and the preferred paths, which are ideally sustainable and align with long-term goals. This encourages the system to pursue states that meet its sustainability preferences over time. Ambiguity measures the expected uncertainty in mapping states to observations, and it ensures that the system continuously learns about its own dynamics and the environment. This helps the system reduce uncertainty and improve its predictive dynamics over time. The components of expected free energy balance the drive to fulfill preferences with the need to minimize uncertainty. And so this balance supports plastic responses that enable the system to adapt to change, but also actively guide itself towards more sustainable and self-organizing configurations over extended timescales, ensuring resilience at both individual and collective levels. But sustainability isn't just about survival, or at least it's not a simple story. It must incorporate eudaimonic well-being focused on growth, fulfillment, and development, and hedonic well-being, which captures immediate satisfaction. So in active inference, this means that the system should balance present experiences with long-term strategies that enhance overall capacity for adaptive growth. So when we talk about eudaimonic well-being, we represent growth and the system's ability to find diverse, beneficial states. And it aligns with long-term sustainability by ensuring that agents survive and thrive through extended adaptability and resource renewal. It represents the growth and system's ability to achieve its long-term goals. This concept aligns with active inference because it emphasizes long-term sustainability by optimizing internal models that allow agents to find those beneficial states. And so within active inference, agents act to minimize expected free energy, which involves the balance, as we saw, between risk minimization, which means that the outcomes are aligned with the agent's preferences, and ambiguity minimization, which ensures that the learning continuously happens. So that's what enables the agent to grow and thrive. And so eudaimonic well-being can be conceptualized as the successful maintenance of favorable states and the expansion of the system's potential, allowing it to reach higher order goals over extended time horizons. And so this behavior reflects structured learning, wherein agents adapt to changes in the environment by restructuring their internal models, which lead to growth and a diverse set of beneficial states. Now, hedonic well-being involves immediate moment-to-moment satisfaction, which is necessary to maintain ongoing motivation and effective response to environmental demands. It focuses on immediate satisfaction. And so the agent's capacity to respond adaptively to current needs, it can be seen in active inference as the system's ability to reduce momentary free energy and maximize instantaneous reward. So we can see this at the lower levels, say, of hierarchical models. So you minimize prediction errors in the present. You seek sensory states that satisfy immediate needs or preferences, like finding food to satisfy hunger. And this corresponds to reducing free energy associated with specific observations. The internal reward or momentary satisfaction that the agent achieves after fulfilling immediate needs corresponds to the agent reaching a preferred state as predicted by its internal model. This is crucial for maintaining motivation and ensuring effective responses to environmental demand. Here, we also have to factor interdependencies within the system. These interdependencies can be represented through mutual information equations, which ultimately quantify the connections between different components. The plasticity at individual levels translate to the sustainability of the entire system, aligning short-term actions with long-term goals. So sustainability is an emergent property that depends on the balance between all elements in a system. This really involves presenting resource depletion, maintaining well-being, and promoting resilience through self-organization and learning. So it's a continuous effort to increase resource redundancy and avoid overexploitation, thereby ensuring sustainable practices over time. You can think of it as avoiding the local minimum. The sustainability of a system depends on harmonious interactions among its different components, which range from individual agents to the broader collective. This means that the system must align both internal and external goals to ensure stability over extended periods, enhancing resilience and sustainability. And so, for example, the resilience components of inertia, elasticity, and plasticity will work synergistically to support adaptive actions that contribute to sustainable outcomes. The emergent stability is promoted through decentralized interactions where each component of the system self-organizes and responds to environmental feedback, which reduces the complexity and increases adaptive capacity and allows the system to maintain a dynamic but stable equilibrium, also sometimes referred to as homeostasis. So we can think of attractor states which emerge as agents minimize their variational free energy over time. And this process supports the alignment of internal models with the environmental demands, ensuring that agents remain adaptive while reinforcing the renewal of resources and overall system well-being. So these are all nice ideas, and we think they hold up mathematically, but we wanted to test them out. And obviously this is the beginning of the journey. So we built a small and very simple agent-based models to illustrate sustainability under active inference at the level of one single agent within one environment. This is extremely simple, and the following studies will cover more. So the model here simulates an agent managing food consumption in different environments to ensure long-term resource availability. Our objective was to show that the agent's goal is to maximize well-being while ensuring resource sustainability over time. And this involves balancing immediate needs with future availability of resources. So we started with a validation case. In this case, the agent makes decisions based on current food availability without affecting future availability. And so the agent observes food and decides whether to consume or not based on its current state and prior preferences. So we have the generative model, we have hidden states representing food availability and satiety, and the preference C, which encoded a strong preference for satiety while maintaining food availability. As you can see, these two preferences are technically contradicting. And so in a static environment, which was the first case, the agent's decisions are really straightforward. They just maximize short-term well-being without needing to manage resource dynamics. So as you can see in the tiny little plots here, we can see that the agent's behavior, specifically whether the agent chooses to eat or not over a series of time steps. And so the middle plot shows that the amount of food over time, which is represented as food left. And the last bottom plot shows that you represent the agent's level of satiety, or how satisfied or full the agent feels over time. Higher values indicate higher levels of satiety. And so the agent has a strong preference for high satiety. Since food is continuously available, the agent keeps eating at the beginning, which increases its satiety level. And since the environment is static, the food remains available indefinitely. And so the agent successfully increases its satiety. We then wanted to show whether or not what we did was just an artifact of the simplicity of the model. So we screwed with its matrices. And so incorrect matrices cause the agent to misjudge the effect of eating, which leads to an unstable satiety level. And so we showed how errors in perception and action models can significantly impact the ability of an agent to achieve stable and desirable states, even in an extremely simple setup. So then we tried something a little more complicated, which is a dynamic environment where the strategies have to change. So the environment changes based on the agent's actions, so resources deplete when consumed, but replenish over time when not used. And so the agent's challenge was that it had to learn to balance consumption with replenishment, which effectively had to demonstrate some degree of sustainable behavior. So the model includes the transition matrix that maps the state of food available based on the agent's actions, and expected free energy here, minimization, guides the agent to consider future state and ensure resource availability. So this was the case. As you can see, it hasn't changed much. The only thing that has changed is the dynamics of the environment and the ability for the agent to ultimately learn those dynamics. So the agent had to adopt adaptive strategies that balanced immediate rewards with long-term stability. And this was showing us how active inference can foster sustainable behaviors in fluctuating environments. So when we look at this plot, we can see that the agent has learning turned on or not. And we wanted to see whether an agent that didn't learn did just as well as an agent who learned, just to see again whether it was an artifact of the simplicity of our model. And also, the agent can die. If the resources are depleted and it has high and is not satiated, over time it dies, which, ethically might not have been the best thing to do, but whatever. So agents that have learning quickly improve their survival times by refining their internal models and strategies. And so the rapid improvement really shows that learning enables them to find efficient and sustainable ways to interact with their environment. Without learning, there's no significant increase in survival time as they are unable to really adapt their behavior based on past experiences. So they end up in suboptimal decision loops, leading to a lower average survival. So we can really show that learning is crucial for agents' ability to adapt, which in turn allows for longer, more sustainable presence in the environment, and ultimately, also the environment's ability to actually be sustainable in itself. The agent overcomes initial limitations and eventually converges to strategies that maximize their survival, which really shows the power of dynamic adaptation in uncertain environments. So we saw that the agent's behavior in both static and dynamic environments really shows how well-being can be optimized while maintaining resource availability. And in the dynamic environment, the agent learns to moderate consumption. it is able to understand the trade-off between immediate satisfaction and future resource sustainability. The agent has the ability to create adaptive strategies that align with the principles of resilience and sustainability. And so here, our model illustrates in a very, very minimal way how minimizing free energy can lead to behaviors that promote long-term viability rather than short-term gains. And so these simple models are just laying the groundwork for modeling more complex systems, such as ecosystems or urban environments, where sustainability requires coordinated interactions between multiple agents and resources. So to recap, we started by understanding resilience within active inference. We broke it down to inertia, elasticity, and plasticity. We then explored sustainability, building on resilience, and we incorporated well-being as a critical component. We demonstrated how agents can balance immediate needs and future viability, achieving sustainability, again, all through active inference. And so it maps systems that can adapt, sustain, and thrive by balancing short-term adaptation with long-term sustainability. But we still need to show how active inference can effectively be scaled to real-world applications, involving multiple interacting agents and resources, involving the ability for the environment to fully deplete, and therefore how to actually manage such possible patterns and how agents might learn over different areas. We have to transition from theoretical models to more practical implications that involve challenges in data acquisition, model complexity, computational scalability. We also need to factor mutual interactions and the effects of each subsystem on each other and the larger system such that they promote more resilience and plasticity. So all of this is extremely seminal. We have to move further and actually demonstrate in much larger scale and more complex simulations these ideas. But it has critical potential applications. Achieving all this, we can use active inference to model and predict adaptive strategies for mitigating climate impacts at different scales, or improve decision-making processes in organizations, enhancing resilience and sustainability in economic and social contexts. So active inference can be extended to other complex adaptive systems, and we can support initiatives aimed at fostering sustainability in healthcare, agriculture, and urban planning, which is work that, again, Mark Miller and Ben White, Ineshti Polito are really pushing forward. So thank you for listening, and I hope you enjoyed.
All right. The next recorded talk is 50 minutes long by Jager Raman, Humanity's Story, A Search for Moral Clarity.
Hi, everybody. So I'll be going over what I'm calling Humanity's Story, A Search for Moral Clarity. And I'll get into kind of what that cheeky title means, going over kind of myth, morality, narrative, self-understanding, and the meaning of life. And no, that one was too far, but I guess not too much farther than what I'm claiming. So yeah, before we get started, I just want to give a big thank you to the Active Inference Institute, for overall the work they do. It's been super rewarding and engaging to be a part of. I put my information here, so feel free to reach out if anything piques your interest or bothers you, or you have to correct anything. Feel free to give me a shout. So we'll be discussing a few things, as I mentioned. So one of the big roles that I feel active inference can, one of the ways that it can at least intuitively scale into human culture, first of all, is through our use of symbols, kind of what makes us unique as a species can be understood semiotically or through symbols. And the road there, as I make the case in Myth of Objectivity, is through morality, largely through by codifying norms and expectations, which again ties very nicely into active inference, I believe. The last way is through narrative. And specifically, I'll be talking about kind of at a meta level, the narrative of modern narrative. And why are we doing this? It's epistemic reasons, interesting as it is, but also I think that kind of applying a rigorous framework to humanity specifically, particularly as we get into narrative, we'll see it more broadly tackle some other areas of humanity. And this is necessary, I feel, for cultural cohesion, something generally lacking these days, with partisan and polarizing the nature of our culture at the moment and our politics. And so it'll achieve, hopefully, or at least understand the outlines for cultural cohesion and things like social and personal integration. And I'll do this by, as I mentioned, by expanding upon my myth of objectivity hypothesis. Right? And so my own road to becoming interested in the free energy principle and active inference was being disillusioned with the economics paradigm, finding it to be, as I'm sure other folks were, insufficient to describing human behavior, even through the kind of quote-unquote narrow lens of the marketplace, conceiving people as the neoclassical framework does as utility maximizing individual agents who are well versed in what their own preferences and interests are. It's kind of quite unrealistic, to say the least. Not only that, but behavioral economics didn't really do it for me either. It also held up this idea, this neoclassical idea of rationality, as the kind of gold standard. And you can see that with some of the recommendations, the way we should constantly default to 401ks. Maybe that makes sense, but it comes up with that advice, it justifies that advice using this kind of principle of stationarity, meaning an agent's preferences should not change over their lifetime, which of course is not realistic. And so kind of speaking of behavioral paradigms that are lacking, at first I thought, well, the neoclassical model on its own isn't interesting. Maybe we can marry that with some views of moral philosophy, because I'm sure moral philosophers have a much better view of humanity. Well, that's what I thought. So here are a few different moral philosophies that maybe some of you folks are aware of, maybe others not. But kind of briefly, deontology, utilitarianism are traditional from the Enlightenment era, going back to Kant and Stuart Mill, paradigms of moral philosophy. Interpretivism is a bit more recent, but I think it's still been around for quite some time. And the last one is just a couple examples of some Eastern philosophy. And so when we think about, I guess the question I'll pose to those listening is, what type of thermodynamic systems in terms of their adaptability, how do we characterize these various different systems? Are they single equilibria? Are they steady states? Are they maybe chaotic? Maybe they don't reach any equilibria. How do we think about these? So firstly, deontology and utilitarianism. And if you're not familiar with them, don't worry about it, I'll kind of explain it. But deontology and utilitarianism I view as single equilibrium, even though they are different. They seem to have one kind of one unifying mistake, which is the environment or kind of context doesn't change, or in other words, there is no uncertainty in these systems that they assume by their prescriptions of morality and moral philosophy. So deontology assumes that there are a certain set of rules that you should never violate, that never change over time. So you maybe thou shalt not kill, thou shalt not steal, etc., etc. There's no conditions under which those should be violated. And utilitarianism, this is all of your actions are based, their morality at least is evaluated based upon the impact that they'll have on the aggregate welfare of others. Right. So, this is kind of featured, for instance, in The Good Place for those watched it. But the problem with both of these is that, in a word, it's uncertainty. Right. There's no epistemic foraging. There's no model for how agents come to learn. Okay, what are the rules? Maybe the deontic rules that I should follow. What are the ways that my actions impact others? Like, what is that process of socialization, that kind of awareness, those, the empathy, all the things that, should I read a book? Should I read fiction? How should I speak to people? All these are essentially epistemic tasks, kind of learning tasks that are not featured into these twin systems, and I'll get into perhaps what this reveals about Western society. Kind of spoiler, but this is the kind of analytical bias of Western society, I think, revealing itself in deontology and utilitarianism specifically. So interpretivism, this comes out of postmodernism, I believe, or at least it was re-brought into the dialogue following modernism, into postmodernism, Jacques Derrida, etc. So it says essentially kind of rejecting these analytical reduction single equilibrium, as I've presented it here, frames of moral philosophy, and says that, well, it's based on the agent's interpretation of their behavior. What are the contexts for their actions? Also, how do they interpret their actions, etc., etc. Well, of course, it's an important element of morality. The kind of classification that at least I would label is chaotic, right? So if we're just saying it's up to someone's interpretation, well, how should they interpret it? Should everyone interpret it differently? Is everyone's interpretations equally accurate? How should we, yada, yada, yada. And the point is that it's not super helpful for society to, as a approach to morality. All right, so final two, Confucianism and Taoism. I see them as being adaptive and being steady state, focused on the kind of rituals and behaviors, not content specifically, not focused on particular deontics, and not kind of hyper focused on the impacts of behaviors to others. Although that can be a component, as can interpretation, but it's really about the emphasis of these two paradigms, kind of inherently acknowledging that the world is changing, that society is changing, and yet the goal of morality at both personal and social level is to find coherence. So it's kind of still privileging some kind of equilibria, some kind of harmony, but not kind of how you get there. And I'll get into how it does that with active inference. So, before active inference, what I would say is that of Taoism and Confucianism, they come from a tradition that Carl Jung would label as the mythological construct of the cosmic human or cosmic man, aka the symbolic self, which is the term I'll use for kind of going forward, because it kind of ties into my theme of symbolic agents, etc. So the point is that Carl Jung, after surveying, doing a cross-cultural analysis of various different mythologies and traditions, found that this particular, what he called archetype, reemerged. And essentially, the cosmic human was the perspective that we're all kind of connected to one another, not only to other people, but to the cosmos and to the world in general. And our actions do have consequences because of that inherent interconnections. Moreover, we do have a certain responsibility to the world as a whole, to other people, because of our place as a kind of a node in this hierarchy. I'm signaling where I'm going with this. But it allows, as you can see, an area both for the kind of characteristic state, so the ways to minimize uncertainty, kind of using both that epistemic and exploitative paradigm of active inference. but it kind of does so specifically by conceiving this kind of broad view of the self, right? And so here, of course, is how it connects to active inference. So active inference, unlike the neoclassical framework and unlike other single equilibrium approaches to social science and to science in general, it allows nodes to communicate both with spatially and temporally. And so kind of over time, an individual passes information to itself or to kind of quote unquote its future self, and in some ways it's its past self in terms of goals. But the self is not a stationary construct. It is something that is constantly seeking what other nodes are kind of included in my hierarchy, what other selves are included in kind of myself, and the symbolic self is an example of our ability to explicate all these different nested nodes. So the result of us being a symbolic agent is that every time we meet someone, say, who says they're Canadian, well, if we haven't met this person before, our model of what it means to be Canadian now includes that person. We now have a instance of the general concept of a Canadian, of that kind of general archetype. So that means that the model we have of Canadian, whether or not we are Canadian, we have the ability to constantly compute what the self is, and by virtue, what the other is. And so the kind of road, the trajectory that I outline that kind of brought us to here, and what it means and all that, I draw from our social bias. So what are kind of some instinctual impulsive elements that first started to see human society expand kind of outward laterally, or even over time? Well, at least laterally, at least kind of within a specific time. I make the case that it's social bias, something that we are inherently born with. Although we are not, born racist per se, we are born with a specific bias, and that's accent bias or shibboleth. It does seem to be something that emerges in utero, and we have preference for pronunciations, for vocal accents over others, those we are more familiar with. And while that's often negative, it does have clear biological benefits. Of course, that's why it exists, and that's why it persists today. And secondly, what do we do with a society that's based on people with the same accents? Well, that's an inherently unstable one that's not super adaptive, although is extensive and allows for greater cooperation. It's unstable because it allows for deviance, free riding, things like that. Okay, so enter morality, enter morals. And so here now we're connected in this symbolic node way by codifying those expectations, by minimizing surprise, using morality. Right. So this is my kind of myth of objectivity. You're supposed to behave cooperatively. You're supposed to follow these norms by virtue of where you've grown up. That is social bias. That is shibboleth. Evidently, you are not doing that. So how do I deal with that surprise? Well, over time, of course, that model you have, the shared model you have of that's based on identifying with those like you, starts to wear thin, starts to break down. And so in comes morality as a way to stabilize, to offer kind of a hood that you place on deviance, and that you can then use to shame and guilt into aligning with the shared model. Or of course there's punishment and ostracization and other things, right? But that's what the tool that morality probably had in the Pleistocene and continues to have with us today. All right. Okay. That third leg is, okay. So if this is the self, what are we modeling off of? Right. So we have the internal model, active inference. We have the Markov blanket that screen between us and the world. So then we have the external states. So once we have kind of symbolized the self, what is the world? What exactly are we modeling off of? Sometimes it's the world, you can say. Okay, well, think about farming. Think about, someone who's born and raised as a farmer. The land will feature very prominently in their model of the world. Think about a hunter. The land will figure, the world itself, the physical world will mean something. However, it won't mean everything. So what are some other things that will constitute the world? Probably the other. Right? So social bias, of course, works into that. There's those who sound like you. There's those who's not, or those not like you. So by virtue of having a bias means that you're biased away from other people, and that's why we don't like to admit that we have biases. And that's why we were troubled when people tell us that we're biased. So that's one example. Over the trouble with the other, and you can think about the Cold War. Think about any time that a country is under attack, the other becomes prominent, becomes salient. The in-group binds together, and for a while, whether it's 9/11 or whether it's during World War II, there's kind of great social cohesion. Trouble, wars end, enemies become salient, and then what happens? Well, this is how we have this is enter kind of mythology. Not that these things are entirely separable. There's a lot of overlap, but for our purposes, if we think of mythology and we start to think of narrative, what we're talking about is in the language of like Levin and Chris Fields, we're explicating the reference frame. We're explicating the measure, the kind of yardstick of what's good, what's bad. Whereas, according to Michael Levin, the frame of reference that allows agents, whether bacteria or complex organisms, to judge whether they should approach something, whether they should avoid it, is an internalized coordinate plane or frame of reference. What we're doing eventually, once we get to myth, once we get to explicit morality, once we get to narrative, is we're explicating that frame of reference. We're saying, okay, these group of people say are evil. We're all descended from this ancestor, from Hercules, from Beowulf, from this kind of half man, half god. We're explicating these reference frames to gain cultural solidarity, to gain cultural cohesion. Right? And so I mentioned this. This is kind of more going into my myth of objectivity hypothesis, but I'll just kind of briefly show it because I would love to get some feedback from the folks listening to this. So this is how I have. I hope to formalize, how we, became symbolically literate, if you will. So that kind of path from shibboleth to morals to full symbolic agent. And so I just have kind of an agent here, assuming that another agent B has a fellow accent, therefore shares the model of the world, has some error. The error reaches some threshold, and then suddenly, if then else, you end up with a new model that eventually leads you to modeling the prediction error. So we have a somewhat familiar equation, but kind of modified, but instead of taking where the posterior is kind of conditional on traditionally conditional on the model, here in place of that I have an objectified error. So the point is that you have these categories of, whereas typically the prediction error will just be whatever kind of noise that you experience that are not in line with the prediction, and either you'll select a different prediction model, a different model at that point, or you just assume it away as noise. In this case, there is an explicit model of error. So when someone decides to steal food, when someone decides to not help with child rearing when someone decides I can't think of any moral deviations. But the point is that there is a specific set of deviations from the typical predictions versus just being surprised generically. So it's a modeled version of error that then allows an agent A to view a given agent as possessing the ability to select between adherence to a higher level or superordinate model, now an objective model of the group, or a narrow one, so they can comply or they can deviate. That's a C and D subscript. And the point is that, or I guess one takeaway is that, okay, this is metacognition, that kind of upper level superordinate G, and this is transjective, meaning that it's not purely objective. It's framed as objective from the point of view of the agent, but that only means that they're transcending their own subjectivity and the subjectivity of the agent by conceiving that they have the ability to select between a higher level or a lower level model. And so in this kind of simple way, at least at this level of explanation, we can see how, from an active inference point of view, we could have gotten to something like objective morality, and more importantly, something like free will. And of course, the various different significance. And so just, again, a couple, I view this as the kind of a hypothesis hiding in plain sight. Why? Because morality is something that we're so impulsive about, something we have so many emotional ties to. For instance, we're constantly looking for we're constantly claiming to be the victim. We're constantly looking for people who victimize, and yet we can't really agree on what the specific contents of morality should be. Even though, when I mentioned deontology, I'm sure there was folks listening who had ideas of what could be deontic, meaning forever there. So I went over some of this. There's social biasing, morality. There's an impulse to do this, and there's some kind of research that I've done. In the economics, going back to that neoclassical paradigm, although I was kind of dumping on it earlier, what these single equilibrium analyses allow for is the ability to say, okay, well, where does this model break down? Where does this model fall? So you might say it falls down everywhere. Well, it's not quite true. People are selfish. They do have stationary preferences, at least for a long enough time for that model to be useful. However, it does fall down in certain interesting ways. One interesting failure of the single equilibrium economics paradigm is the need for social trust. And so social trust means that we have certain expectations. We have expectations that a company selling something sells what they promise to sell. It means that you can trust the market system, trust the institutions in the market that you inhabit, and engage in economic activity. So you think about this at all levels, you essentially need it. You essentially need to take medicine and understand that, hope that the people are so ethically inclined, because of course if they do something bad, they might not get caught for it, yada yada. The point is that there needs to be some sort of agreement on social trust. So it's an example of how kind of morality seeps its way into something, even as intended to surgically remove all kind of humanity from the paradigm, all morality, all essence of morality from the study of economics. Social trust and morality seeps back into it. The same thing with linguistics. won't get into this one too much now, but the idea of transcendental signified. So it's a way of structuring an otherwise kind of elusive set of symbols, linguistic systems. We always have something. There's always, as I mentioned, there's always God. There's always some sort of myth that's tying everything together. Even in secular society, we have not, we don't have kind of uppercase God, G God, the way you might have in the past. There's a lot of different religions, there's a lot of institutions, and probably agnosticism and secularism is kind of increasingly dominant. So what do we have in this case? Well, we have democracy, we have science, we have kind of other essentially kind of mantras, if you will, that require this kind of shared belief element, which kind of has very moral characteristics, but is kind of tied back into a kind of shared belief system that then tethers our norms and expectations to, and allows for us to kind of have social and political dialogue. I spent a bit of time on the myth of objectivity hypothesis. Quickly, I don't know if I'll have time for this entire run through, but once we have established that we achieved a symbolic capacity of what is the next step, do we just kind of walk around shouting symbols? No, we have kind of narratives that attach to our symbols. It's the way we kind of piece them together. It's how we connect one symbol to another at a very kind of crude way of describing this. There was a recent paper on narrative theory and active inference, which I encourage folks to go out there and seek. It covers episodic memory, it covers narrative identity, so some interesting topics throughout on narrative. The one thing that I wanted to add is it makes the claim that narrative is for the future, it's for prediction, just as many things in active inference are. However, I think that you could equally say that in order to establish a productive prediction, we write narratives about our past. So we can separate, the person who we were in high school, the person we were, in our 20s, our 30s. So we tell stories about that, about our last job, in order to draw a boundary between us and that person. So it's a way of kind of inheriting inhabiting various selves, but not over-identifying with the past one. So I just want to add that because I don't think it was covered in the in that paper. And so here I have a couple different of the core elements of narrative and why I think that it thinks so well in the narrative paradigm. So I think the story describes the set of the underlying events. So it's not explicitly what's in the narrative. So if we read a novel, and the novel is a short story about Harry Potter, it's exactly what's happening in that version of Harry Potter. Maybe he's already at school, doesn't kind of go into his backstory necessarily. But the story is all the things, all the underlying events that happen that are related, that are necessarily depicted in that narrative. And so this is essentially the generative process, right? So it's the outside world that's that's being modeled in the narrative and in the kind of causal chain that is the plot. So the point is that I remember kind of quickly, but the point is that when discussing or when kind of analyzing analytically the core elements of narrative, a lot of the themes that emerge are kind of similar to at least some of the key elements of active inference. Yeah. I'll skip this one for now. So one thing I think it's important to notice is that there is implicit versus kind of explicit narratives, and so there's the idea of feature placing. So this is essentially how vocalizations emerge prior to symbolic cues. So other animals have verbal expressions, but they're non-symbolic. A feature placement is kind of one single verbalization that might be some way that we can think about how language began. And so essentially kind of going back, okay, concepts need context. If we just shout fire, what does this mean? Does it mean that I'm fired from a job? Does it mean that something is burning? Or does it mean that, I'm just, someone said something was really cool and I'm just saying fire in that kind of slang context. So explaining the explicit. So here, I just wanted to raise the instance of where creating narratives, although everything can be narrated, not everything is narrated. So there could be unconscious events that happen in your past or childhood, or even during the day that you hadn't really thought about. So various different therapeutic techniques address that. So internal failing systems is one where you address different emotional states or different psychological states and try to personify those and try to kind of give them abstract structure in your mind by engaging with them through journaling or through dialogue with a therapist. So that's internal family systems. There's also expressive writing similarly. And so if we think about one of the impacts that narrative can have, that's one. And sometimes it's good to, not, sometimes it's good or sometimes it's just a fact that we don't have narratives, like we don't have narratives on all of our feelings every day. I don't think we would be able to kind of narrate everything that's happening to us. If we think about meditation and mantras, the idea there is that, for a time at least, we shouldn't narrate everything, or at least we shouldn't accept the first kind of order narration. Which we think about mindful meditation and kind of focusing on the breath as opposed to following our thoughts. For anyone who's practiced meditation, you'll know that sometimes we should just be quiet and not listen to the narratives that show up in our brain. We're going to have a couple different, obviously, examples. All right, so here what I'm talking about is, and as I mentioned on the previous slide, or I had it written down, I don't know if I spoke to it, but what we're talking about here is the problem of promise of cultural narratives. This is most known as master narrative or grand narratives that traditionally would have been the purview of mythology and religion. In more modern times, is kind of constructed in other ways. And so, as I mentioned, from our nomadic multi-band past to even agrarian societies, and then kind of coming into the universal age, these started from these fully integrated narratives where a particular nomadic hunter-gatherer tribe would have a single kind of master cultural narrative, or at least that's what we understand. And so our kind of best guess is that this was the case or wasn't. Which religion am I part of? I'm part of my tribe's religion. Why did we catch food today and not yesterday? There was an answer from the shaman for that. It was fully integrated. The second kind of epoch was the leading up to kind of the axial age, when the universalizing religion, setting the stage for Christianity, Hinduism, Taoism that I mentioned. So for a very long time, this is kind of following from 10,000 years ago when we started farming, perhaps up until recently, we had these dominant religions that essentially kind of took over the cultural sphere. Those are the universal narratives, religious narratives that I'm sure folks are aware of. And most recently in weird societies or Western societies, is kind of Western educated, industrialized, rich, and democratic. That's the acronym for weird there. And my case here is that these are, we're largely in a culturally fragmented environment. So earlier when I mentioned single equilibrium analysis, neoclassical economics, but specifically deontology and utilitarianism, those are all examples of, from I think a thermodynamic systems point of view, from an active inference point of view, this would be kind of a very single equilibrium, kind of ways of looking at the world. And why are they? Well, according to Joseph Enrique, and I think according to some similar analysis from Ian McGilchrist, this is because Western people are distinctly individualistic. They're a bit more left brain centered than at least the axial age portion of society. So those traditionally kind of settled societies that are more gestalt and more right brain oriented would think of things a bit more holistically rather than as kind of reductive. So the good, of course, there's many benefits for left brain thinking. It's more individual, it's more analytical, and it'll be a bit more geared towards science versus more mythology versus stories and narrative. But what is it missing? Well, it can make a lot of mistakes, and not kind of random mistakes, a specific type of mistake, which is leads to kind of reductionism, and which is how we kind of ended up with, which might be, according to these views, how we kind of ended up with some of the paradigms that we did. Yeah. And so the fragmentation we can understand along kind of these three different dimensions, right? And so one is aesthetic, the next is kind of institutional, and the last is kind of objective. And so this is essentially how I see our master narrative currently broken down. And of course, there could be additional ways, but here's kind of three ways as a starting point to understand the kind of cultural narrative, and how specifically it's fragmented. So aesthetic, we have the kind of modern era, the postmodern era, and now what some people are calling the meta-modern era. It's maybe a bit too soon to turn on it. However, I do think it's super interesting, especially in the light of the free energy principle, which I'll hopefully have time at the end to kind of touch on. The second one is our institutional narrative. So the economic framework, how we should distribute wealth. What does that say about us, and kind of what's the most quote unquote efficient way? But what are the narratives around our economics? What's our narratives around our politics? And finally, there's this idea of objectivity still kind of creeping in. So what are the kind of quote unquote true narratives out there? And so, a reasonable question is, okay, this is, we all have kind of our own stories. Perhaps there's still vague senses of a master narrative, and I think there always are. There always kind of might be at least some emergent master narratives by virtue of us kind of all occupying the same, at least digital space, the same kind of time. We'll all converge on some things. However, without a kind of coherent or a more of like a religious story that we perspective that we had in the past, where the narrative is not just okay, we're this third rock from the sun, we're revolving around revolve around space, and we're victim to laws, and this is what happens to be happening with society. What we lose with the kind of grand cosmic narratives of the past is a type of psychological coherence. So where do we fit into this world? The idea of going back to kind of cosmic band, where is our place in the universe? What is the kind of personal meaning for me? That's where a tighter narrative, kind of more intentional master narrative, comes into play. So our current fragmentation leads to personal anxiety, it can lead to social anxiety, and it can lead to kind of the polarization and partisanship and the results of fragmentation. So institutional misalignment, so whether the company you're working for shares your values, whether they're working on something that is you find deeply meaningful, that is deeply meaningful for your identity and your values. That's what do you mean there by misalignment? Okay, so in terms of aesthetics, as I mentioned, the period owner is sometimes called metamodernism, and so that kind of gets into the idea of genres, meaning that we have kind of plenty of good, television, so we have plenty of good narratives available for us to consume. That does include kind of classic genres, but the problem is that they're all genres. So we're all kind of consuming different content. We're all consuming it through different media. Even in times past, not even too far past, we would watch TV at the same time. You watch the same movies because they're in the movie theater. That's where that's the only place you could watch them up until recently. Now we're watching movies at different times, moving from movies from 20, 30 years back, from 50 years back. And essentially the fragmentation has gone up exponentially. As I mentioned, there's an analytical orientation. And so here, I think it's worth noting that along with the fragmentation that has occurred in weird societies, along kind of side that kind of loneliness that happens with the rise of the analytical world is some great literature. And so one of the reasons I argue that this came about was specifically because once mythology, once religion stopped serving the role that it did, that left in particular artists, in particular those kind of aesthetically inclined, to seek out art, to create art in some cases, to fill those gaps for offering a narrative, for answering the questions, the big questions that were typically answered by those institutions. Yeah. And so kind of going back to my quest, what we're kind of after here is we're looking for greater cultural cohesion. We're aiming for better personal and social integration. So I argue that these pieces are connected. And I'd argue that if the free energy principle has told us one thing, that agents minimize uncertainty. However, if it tells us another thing, is that one way to verify kind of any claim about a self-organizing system, it's to not look at one paradigm in science, it's to synthesize various different views. So what we can glean from that is essentially a meta-modern approach, which is to not necessarily ensure that everyone in culture, everyone in a particular society is consuming the same content or media, but it's to highlight certain aspects of it that each person can find meaning and the right type of meaning in their own content. And even if we achieve that through different areas, we'll all be experiencing something similar with each of our traditions that we're interested in. And once we've identified the certain components or make the case for certain components that answer maybe some important questions from an active inference point of view, can allow greater visibility into that uncertainty minimizing process at a cultural scale. So here, I think poetry is a great example, and because of its, it reaches everything from the senses, from its sounds to its visuals, to its more deeper symbolic meaning. And I think a great example of that is T.S. Eliot, the great many references he makes in his work, and also the kind of poetic conventions he adheres to, makes it just a kind of very, in some cases, accessible works that he offers. And so, whether it's T.S. Eliot or Kendrick Lamar, in each case, what these artists are constructing is a explicated symbolic self, an explicated number of different nodes in a hierarchy that are connected with all these various references in a particular song. That can be made clear. For instance, in this website, it's Genius, so you can see where the different lines, in this case, Kendrick Lamar has, and what the references were. And so, in a sense, what you experience when we read poetry or we read a work of fiction that has deep references, deep cultural references like this, it's constructing an extensive self, bringing coherence to it and to everyone who listens to it. And by kind of calling it out, you're able to share in it almost as if it's something, it's a greater work of literature in the past, as folks would. And so that, I think, is kind of a few examples of ways we can start to apply a rigorous framework to the humanities. It tells what kind of literature does for us, why it does what it does for us, and parse through some of the components that make it meaningful to us and kind of allow us to use literature in ways that I think it was originally intended to, and in past times has. So I'll leave it there, and once again, feel free to reach out to me with my contact information, and please follow my Substack and let me know if anyone has any feedback. And I just want to thank Daniel Friedman again, and all the folks at Active Inference Institute and Karl Friston for this content and the discussions here. So thanks again.
All right. The next recorded talk, the penultimate recorded talk, is by Bradley Alicea. Earlier, Bradley gave a talk on Purposefully Nonstandard Cybernetics, and this talk is going to be an overview of open source and open science. So that's really cool, and thanks for bringing this important complementary topic to the symposium for all who are working on this. Okay, it's 51 minutes long.
Hello, my name is Dr. Bradley Alicea, and I'm a member of the Active Inference Institute Scientific Advisory Board. Today I'm going to give you an overview of open source and open science. My home institution is the Orthogonal Research and Education Lab. I'm also affiliated with the Open Worm Foundation and the University of Illinois Urbana-Champaign. I'm also of particular interest in the Orthogonal Research and Education Lab as our open source interest group, and I'll talk about that throughout this talk. This starts with a question. What can we do with open source and open science? And I pair these together because sometimes we're building software, sometimes we're doing scientific discovery, which kind of relies on the open source software. And so if we're doing both, we can actually build systems that can sort of help us do better software engineering and science. So they're kind of grouped together. So in terms of open source, it's maybe a truism that open source is about software and putting it out into the world, but that's not enough. And you really what you want to do instead of just putting software into the world is building a community around technical standards and code. And this is true if you want to build a community of users or an open source community that helps build the software, because you need to have some interaction with the software to make it sustainable. You also want to have good technical standards. And with academic software, as we see, that's been lacking. This also allows us to open up the organization's processes and products. So having these communities and having these technical standards are not only good from just the standpoint of sharing software, but it also opens up our processes and products and allows us to serve our communities better, our academic communities. Open science is where we share data, share results, share research artifacts with the public. So we do a lot of sort of transparency related things. We give people our results and our data and it's software and papers and presentations, and we're very open about it. We can give them access to these things. So when I say open science, I also kind of mean open access, and they're kind of in the same bucket. Open science in general allows us to open up our organization's research capabilities so that people can benefit from our discoveries and we can benefit from their feedback. So a lot of organizations have proposed different sort of roadmaps or statements on open science and what that involves. So not every organization's view of this is going to be the same. But I'm using the Young European Research Universities Network statement on open science at the link below. And to them, they have a very strong emphasis on collaboration and citizen science. So this is where you have collaboration around the world, around the scientific community, and also involving, say, citizen science, where people just want to contribute their own analyses. Sometimes it's data, sometimes it's observations, things like that. There's also visibility and idea sharing, so being able to get to the outputs and read them and understand them is important. Open education is important. Idea sharing, because you need to have focus on collaboration. Alternative models of publishing, you need to be able to publish the work to get it out there into people's hands. Incentives, assessments, and research integrity. So those are all kind of part of this open science tree. Now again, every organization who champions open science will have a different view of this. We don't really have a formalized view in the orthogonal lab, but it follows this kind of outline quite closely. And so if you want to know more about where the orthogonal research lab is coming from, you can read this paper, and I put this out in 2020 and it needs to be updated, but it's a good overview. And this is building a distributed virtual laboratory adjacent to academia. And so there are a number of things in this paper. It's just basically, it's very similar to the model that the Active Inference Lab uses. We're much more focused on sort of educational opportunities and opportunities for people to sort of pick up the load and build research artifacts, and having students come in and do short-term projects. But it's a very similar process. So one of the processes, or one of our goals, is to integrate open access and open source practices for advancing distributed research projects. So we want to be able to help people make these things open, help them build research projects. The other thing is that we want to encourage practice and open working through the creation of digital research artifacts. It's like papers or presentations. And when I say open working, I mean, I borrow this term from the Mozilla Foundation. And their approach to this whole enterprise is basically working open. So it's working in these collaborative distributed groups and how to make the most of that kind of experience. You know, things like note-taking and meetings and managing sort of the human capital. So that's also part of it. Open source and open science is managing the human capital, managing these work groups. So one of the other big things about open source and open science is this idea of practice. And so, you know, it's very practice driven as opposed to sort of theoretical or philosophically driven. And so, you know, practice means that you need to establish practices, procedures, routines, workflows, and technical solutions for working open. So this means you need to adopt open practices. It could be community review of code, releasing code under a license, preprinting manuscripts, and generating open data sets. So these are all things that involve, you know, planning, but also practice and being able to produce something at the end. Related to that are what we call open workflows. So when we want to release an open data set, we can't just pop data out onto the internet. We have to put open data sets into a production line model where we, you know, clean the data, we analyze the data, we produce metadata, and then we publish that formally in a repository with metadata attached. We also want to have community standards for open participation. So we can't just expect people to pick things up and run with them without giving them some standards for working. So, usually in academic work, you're trained a certain number of years, and it becomes kind of intuitive to you what to do. But a lot of people, especially students, undergraduates, they come in and they don't know what to do. They don't have like those standards ingrained, and so you have to have community standards. But also because sometimes the incentives aren't there for people to follow long, lengthy procedures, and so they don't. In any case, this helps you standardize these efforts. Then we have open technical solutions. So open source and open science are built or enabled by technical solutions. You couldn't really have open source and open science without having open technical solutions like GitHub, live streaming tools, and bibliographic tools. And of course, those things don't make something open source or open science by themselves, but they enable those practices. So this is a nice graph where I kind of talk about vision of sustainable open science. And so I have a couple of categories here to the left and to the right, which are sort of suboptimal areas. And then where we want to go is we want to go to this zone, this elusive zone in the red box. So the elusive zone in the red box are the set of tools that would allow us to do sustainable open science and open access. And the stuff to the left and the right are kind of like things that we do now that are suboptimal. So we start with the suboptimal and we talk about black open access, which is kind of a fancy word for piracy or informal sharing. And so each of these types of open access are colored. Black just means it's kind of related to under the table or, piracy or something. So one of the examples is Scilab, where, my position on piracy is it's justified given the incentive structure in science. But, you have systems where you can just get access to things. And then, of course, sometimes we share PDFs by sending emails to our colleagues and sending them the paper. And that's all black open access because it's very informal and it's not really sustainable because you're relying on people to have, someone has to get access to these and then share it with someone else. Then you go over to the other side, and you have two other areas of open access. You have gold open access and diamond platinum open access. So gold open access is where typically an author will pay an APC fee, which is a publication fee. It's usually a fairly decent sum of money to a publisher to make a paper open access to all. A lot of times journals will restrict access to paying customers. If you are a member of an academic library, you can get access, but if you're not, then you don't have access. And that's one of the things about like places like the Active Inference Institute or the orthogonal lab is not everyone has that academic library access. And so it's really hard to get access to papers and things that you need. So this becomes a very important set of points here. Gold open access then, of course, is beneficial to the publishers, but not to the authors. Diamond platinum open access is more beneficial to the authors. There's no APC fee, but someone has to take that fee and, they have to absorb that fee. So that's not optimal either. So this elusive zone is a way to sort of build on sort of the low cost, but still sufficient resources we need to provide access to our work. We need to open it up, give everyone access to it, and allow them to interact with the work in a way we couldn't even do with any of these other types of open access. So the first thing we have is green open access, which is preprinting. So this is where it's like not the gold standard, but it's also, you can post a paper on a preprint server. There's a preprint server that gets funded through like a foundation, and that makes it open to everyone. They're, formal sort of, there's a DOI, which is a formal link. It's a permanent link. So your work is in a place that has, some level of reputation with a mark of approval on it. You can also take that preprint and go through what's called open peer review, where you open up your paper to peer review, not to like 3 referees you've never met, but to the entire community. And the thing about peer review, and I won't get into this any more than what I'll talk about here, but if we do peer review with like 3 people and an editor, you pick the people who are maybe the most available, or maybe the most visible people in the field, or maybe people with the most time, and they have certain opinions about what you should do, what you should add on to a paper to make it publishable. And sometimes it's not in the best interests of the science. Furthermore, given that, they still don't really have a very good handle on detecting things like mistakes or even fraud. So you can have a paper that goes through 3 reviewers and an editor and still be retracted for mistakes or fraud. So that's not good either. Open peer review allows us to have many eyes on the paper, many comments. You can incorporate the comments by generating a new version of the preprint, and you have this continual feedback of your work. And you can eventually maybe publish it somewhere, but you can also update the preprint continually and have that process going. So that's, green open access and open peer review. Now, a lot of papers also have data, and we can include open data management in this elusive zone because we also want to have a strategy for managing and sharing data. And this goes along with the peer review and the access to the preprint. That's the link to it, and that the data can then be reviewed and worked with independently of the preprint, but also, it's transparent, and people can actually work with it far beyond the lifespan of a single paper. Then we have overlay journals. So we can have preprints, but that sits on a preprint server. We can have multiple versions, but sometimes we want to build our own journals because we want to narrow the focus of the preprints, funnel them down into things of interest for certain fields. So say, for example, we had an active inference overlay journal. It would take preprints in the active inference area, only those preprints, and present them as journal content. So what journals do, besides conferring status on people, is they give you this curation of the literature, of research. So that's what overlay journals can do, but without the overhead of a journal. So you can have like your preprints, you put them on this with the skin over the top. That gives us this imprimatur of, what a journal would give you. So that's the elusive zone of open access. And I just wanted to point that out because I think it's, a good way to think about sort of the production of science and the production of academic work. I posted a blog post for Open Access Week 2024, and it's kind of a critique of open access as it exists. And this is why I kind of went through this. And basically I argue in this post that open access has essentially failed, at least up to this point, that we don't have the right incentive structures. We don't have the right intrinsic and extrinsic incentives to do open science correctly, open access. And so we need to change those. And so you can read that post on my blog, Synthetic Daisies. So in that blog post, I talk about the intrinsic and extrinsic motivators for doing open access sustainable. So this, you can think of this as more generally as a reinforcement learning of working open or reinforcement learning of open. So when I talk about intrinsic motivators, I talk about the internal drive to do something. So, the idea is that you would do things that are meaningful to yourself. That's an intrinsic motivator. Or what motivates me in terms of a scientific question? What motivates me in terms of how I can contribute to the field? And then how can I benefit from or contribute to a team? These are all intrinsic drives. These are things that sort of you would generate and you interact with a group based on those things. By contrast, extrinsic motivation is the external encouragement to do something. So this could be money, paying people. This could be cost and benefits. So if there's a cost to opening my data set, I will do it. If there's a benefit to opening my data set, I will do it. And that leads to an inequality within the scientific community. And then, of course, prestige, which is, of course, if something is prestigious, I'll do it. But if something isn't prestigious, I may not do it. So it interacts with intrinsic motivation, but it also is this external force that sort of is encouraging people. It's like a reinforcement mechanism. Extrinsic motivations can also be where things tie into existing activities. So one example is where a lot of funding agencies and journals will mandate that people share their data. If you want to publish a paper, you have to share your data. So this is like tying data sharing and doing this to publishing. The problem is there's no intrinsic motivation to do this. It's not meaningful to everyone. And so people will do it to differing degrees of completeness or of usefulness. So if you're forcing people to do something versus it's something that people want to do and think is a good idea, it becomes uneven and you don't have the same quality everywhere. Sometimes there's, of course, there are other types of mandates and other things. And there's been in general an overemphasis, I think, on mandates and sort of top-down motivation to do things in open science and open access, trying to get people to adhere to certain standards or trying to enforce mores that may or may not fit the situation. So this is a problem in open science, open access, and even open source, where people, you have to kind of figure out the psychology of the people doing and enabling a lot of these open practices. So if we look at this graph, we see that there are intrinsic motivations and extrinsic motivations that interact. So at the middle of this, in the gray box, you have intrinsic motivations. Things like, I want to do science, I have theory building goals, I need to create tools. And these things feed into extrinsic motivations, such as funding, community building, adhering to the standards of the field, and adhering to standards of rigor. So this is all kind of these intrinsic and extrinsic motivations interact and then contribute to how you carry out your open science, open access, and eventually open science. So now I'm going to shift to sort of how we approach this in open source. And so this paper from Neuron, it was published in 2017. It's called A Commitment to Open Science and Open Source. It's called A Commitment to Open Source in Neuroscience. And Corey Gleason, Andrew Davison, R. Angus Silver, and Giorgio Ascoli were the authors. They're involved in an organization called INCF, which is the International Neuroinformatics Core. And they've all kind of done work in this area, and they're contributing to a project I'll talk about in a little bit that's open source. It sort of solves a lot of problems in neuroimaging and how to do that. So one thing that they point out in this paper is that code sharing is useful for a number of things in science, but they make a claim that releasing code can be used to replicate results. So one reason why we do code sharing is so we can replicate our results. We can be confident that those results can be replicated because we have the code and everything is, perfect. Which is not always the case, but this is the claim. This is the motivator that they're talking about. And so sometimes you have to be strategic about how you release your code. Sometimes, you just release your code as a matter of, requirement. But sometimes you can actually benefit from releasing your code. And in this case, in the paper, they talk about releasing core scripts and libraries before publication to offer early feedback from the community. So you can release your code just as a matter of sort of requirement, or you can benefit from it by releasing your scripts and libraries early so people can debug them and help you if there are any problems with them or whatever. And so you end up with this nice optimal situation. Another paper that I'd like to highlight here is this paper from Nature Technology, a technology feature in the journal Nature, called 6 Tips for Going Public with Your Lab Software. So, it's not enough to just write the best quality programs and to sort of put it out there. You need to really kind of think about a lot of other things going on under the hood. So one of those things is that you need to sort of carve out some time for maintenance. So if you put software out into the world, one of the reasons you're doing so is to sort of serve your community. Sometimes you want to be the standard in the community. Other times you want to gift this to other researchers so that they do better research. Sometimes you want the prestige of having like the top software in your field. But whatever the reason, you want to be able to maintain the software so that it has a longevity. And so different sources that they talk about in this paper estimate anywhere from 5 to 15 hours a week to 20 to 30% of the time of the project to be spent on maintenance, maintaining the software. Now, as you might guess, there isn't a lot of motivation for that unless, your software is really successful. And so it can be a problem if you, take the leap into putting your software out there, but don't devote the time to maintenance. It ends up hurting you later. Another problem is that you need to simplify runtime. So a lot of times you'll release software and people will try to install it and fail because they don't have the right dependencies. They don't know how to run the software. And especially with a lot of academic software, we kind of build a kludge of plugins and other types of software on top of software. So that's not ideal. And that's a problem that can't be solved necessarily by incentives and motivations. Some of it is going to depend on how we implement the software, and I'll talk about that in a little bit. You also maybe want to spend time in interface design, automated testing, and documentation to help users who, when you're in your own research group, you're sort of in a bubble where you understand what you're doing, you've used the software, you understand the specific problem for which your software is written, but when you release it into the public, you might get people who are not as experienced or simply don't understand, what some of the variables are or whatever. And so there are a lot of ways that, making this easy to use is an imperative. And then a need for transparency and community building. So if you release software, you need to have users to make it worth your while. And if you have users, you want to build a community around that so that you can do things like have have a user base, but also have a community where, you can solve problems collectively and address open scientific problems and really for everyone to benefit. But also transparency, because we need to understand everyone's methods and we don't want to make it, obtuse for people when they use the software to understand the methods that went into generating the result that they're getting. So you need to think about all these things when you open up your software, when you go open source, with academic software especially. This brings us to another point, which is the need for research software engineers. So in academia, we usually homebrew software. We end up putting it out there, and we maybe find time to maintain it, we find time to build a community, but the software is not up to the standards of, say, professionally designed software. And so one of the things we don't have is our research software engineering skills in academia. A lot of academics know the technicals matter, but they don't know how to build software. So software needs to be maintained and needs to undergo quality control. And so those things are, separate skills. So the problem, of course, is that in academia, we tend to have graduate students or open source contributors build packages or whole software platforms, and their contributions are well appreciated, but their involvement is itinerant. So that means that they might build something and then leave the lab in 2 years, where they may contribute to an open source project and you may never see them again. And so they built something with no documentation and obviously no maintenance, and it just kind of sits there and withers. So I've seen this a lot in my career where people will build software for one purpose, one use, or like for a single paper, and then it goes away because it's not maintained. I mean, there's a lot of code I've written when I was a graduate student, say, where that was the case. And I wish that we could recover that software and maintain it, but who has the time? So really what you need to do is you need to include research software engineer roles in your organization, in your academic organization. And sometimes open source projects will have this expertise, but sometimes they don't because there's no requirement for it. But it's also a different skill set than, say, like the academic skill set that people building the software might have. So this is something where you can either cross-train people, and there are programs where you can cross-train research software engineers. But more often than not, you just have to help people acquire those skills. And so there are all sorts of roles for RSEs in different, academic and open source organizations. Things like intentional software design, continuous integration, release cycles, bug fixes, and maintenance strategies. And those are all things that are separate skills from the academic world, separate skills even from even if you're a computer science researcher, you're not necessarily a software engineer. So you have to have that set of skills, or at least, have a way for people to acquire them. Okay, now we talk about open data. So open data is also a part of open science, and as well as a part of open access. So Wikipedia defines open data as openly accessible, exploitable, editable, and shared by anyone for any purpose. So it's a data set that you can access, you can exploit or change, you do analyses on or whatever. You can edit it and even share it. And so anyone should be able to do this. Now, when they say any purpose, they mean that it's licensed under an open license. So an open license is a permissive type of liability protection and copyright for people who put these things out there that they work on and they want to benefit from in some way, but they also want others to benefit from as well. So it's a legal regime to maintain, to manage liability, but also to manage the social relationship between the person making the data set, producing the data set, and the person using it. Open data allows for data to be easily shared and reused, but requires governance, issues of ownership, and adherence to community standards. So this, part of this is, open data is in sort of producing data sets for public consumption. The other part is working on what they call an open data stack. So an open data stack is a management strategy that is needed for sharing, reusing, and archiving data. So we typically start at the bottom with some sort of interactive interface for working with data. We need a metadata format. We need a cloud server to host our files on, to host our data. And we also need standards. So we can have these higher level standards for data production, for open science production in general. Things need to be findable, accessible, interoperable, and reusable. So we need to have those 4 principles embedded in our workflow. And then we need to have a strategy for archiving data. And for that, we might use something like Dryad, which is a data repository. So we have this technology layer, a standards layer, cloud and security access layer, and an archival layer. So put together, that's called a data stack. And you want to build a data stack that's, with tools that you know how to use and standards that you know how to adhere to, but also things that will last. You don't want to pick something that will last a year and then you have to migrate to something else. So you want a sustainable data stack with sustainable tools, with things that are easy for your team to use. And so this also holds true for our open access publishing strategy. We don't want to pick a strategy that isn't sustainable because we'll stop doing it. Now, in the C. elegans community, and this involves my work with the Open Room Foundation, you're fortunate in that you have many open databases. So the nematode C. elegans is often used in biomedical research, and there's some basic research on it as well. And it's a tight-knit community where there are many, many open data sets, meaning people produce data, they share them with the community, and they have tools that are curating a lot of these data sets and papers and things like that. So we have all sorts of data sets available for all sorts of modes of investigating C. elegans biology and behavior. So we have a number of open databases covering anatomy, genetics, gene expression, regulatory elements, behavior, connectomics. So this includes like the worm wearing site, which includes data on nematode connectomics. So we know in C. elegans, we know all of the neurons in the connectome. We know a lot of their connections, either through gap junctions or through synapses. And we have worm wiring diagrams for both the male and the hermaphrodite. So we have very rich data on worm brains. We also have Worm Atlas, which is an atlas of structural anatomy. So on top of the connectome data, you can fit structural anatomy data. And that's at wormatlas.org. The C. elegans database run by MDC in Berlin features a lot of data on proteomics and RNA. And so this is another database that we have available. CenGen is a database of gene expression in C. elegans in the nervous system. So we can, build a model of the connectome. We can have the worm wearing data set, CenGen data, the Worm Atlas, the MDC C. elegans database, and we can actually, produce a study from that. So we have all those layers of data that we can include in, say, a model or in an analysis. We also have this resource Wormbase, which is where we can explore the world of C. elegans defined mutants. So C. elegans has a number of defined mutants for specific genes. There are specific mutations that we can backcross. And so if we have a strain of, say, some defined mutant, we have this worm that has a certain mutation that might be expressed in some behavioral or anatomical deficit. And so we can compare that to the wild type and say things about mutations of function. And so this is a really useful resource both for experimental work and for looking at the C. elegans genome and finding, like alignments and other types of data. Like in one of the papers we recently did, we found we aligned different open reading frames within genes. So it's really a good resource. And then, of course, Nature Methods, this paper by people in the Open Worm Foundation. And this is called an open source platform for analyzing and sharing worm behavior data. And this is on something called the TERPC tracker, which is a movement tracker. So they can actually take microscopy images of C. elegans. They can track the worm's movement and they can characterize different movements. They're stereotypical movements that worms make, and they can actually track the behavior of the worms and classify it. So that's the kind of data that's available on C. elegans. And so if you think about the active inference community, what kinds of data sets and what kinds of resources could be built around things involving active inference. So you might, for example, think about, and some of these resources are just more general resources that you could bring to bear. So you might say, for example, go to a neuroimaging resource and then go to a behavioral resource or build a behavioral resource. There are all sorts of ways that you can build these open data repositories to help the community, aid the community in solving problems and answering questions. So this is a talk by EcoFried. This is called Open Science as an Antidote to Poor Practice / Cynicism. So one of the things he advocates for in this video is to use open science as a way to combat poor practice. Like we said, open science is about reinforcing practice. And when you reinforce practice of open science, you reinforce good scientific practice in general, because you're focusing on the process. You're focusing on, cross checks and other things that involve teamwork. And so there's a lot of this sort of advocacy for helping science through open science, but also combating cynicism, where when we see poor science, we often think, well, this is just the state of science, that it's actually failing or that it's bad. And so you can fight disinformation as well with open science. This is a nice set of views here. So in the orthogonal lab, we have done a lot of work modeling open source communities and their sustainability. So I talked earlier about open access sustainability. Now I'm going to talk about open source sustainability. And so we've done a lot of work with modeling frameworks to understand this problem. So why is sustainability important? Well, in the case of open source, many projects fail for a host of reasons. Sometimes they're related to people's projects, not being of good scope, where they weren't asking very good questions. Sometimes the team falls apart, the team is dysfunctional. Sometimes the project runs out of money. So there are a lot of reasons why projects fail. And sometimes open source projects especially have problems with maintainers, problems with people contributing, so they fail for those reasons as well. So you can have things like poor scoping of a project. We were trying to do too many things. We were trying to do too few things. We might have bad management or a lack of participation, or we might have no resources in terms of time or money. So these are all things that we want to be able to figure out how to manage at a reasonable level. And to do that, we have to understand sustainability. So in these models that we've built, we use different methods, including active inference, reinforcement learning, and large language models, to model open source communities and understand what makes a project sustainable. So the first one is this preprint that kind of includes a lot of the work that we've done, especially in terms of reinforcement learning models and active inference models. This is on ResearchGate. And then there's this newer work on combining agent-based models and large language models. This is Sarah Bostawala's Google Summer of Code project from this past year. So she actually presented in front of the Google Summer of Code symposium, and she presented her project there. And so this work on large language models involved using large language models to generate issues and then generate agents that could then solve those issues and see which kinds of, almost create fake projects and then create issues to solve and then see how the agents were able to solve them. And so, we used a combination of agent-based techniques and large language model techniques to sort of work this out. It's a very exciting project. Another approach is to take the multi-agent reinforcement learning route. And so you see this grid down here in this figure and all these dots, and they represent agents that are doing different things. Sometimes they have different statuses in the open source community. Sometimes they're have a different level of competency. And you can actually run these agent-based models. You can implement them in MESA, which is a Python package, and run these agent-based models, and then use reinforcement learning algorithms to sort of optimize the strategies that they're using. So this is, again, where you're using these sets, you're creating these projects, you're using these sets of issues, and you're measuring their ability or their competence to solve those problems. And so Shubham Soni, R.V. Rajagopalan, and Himanshu Shogul were all involved in this work. Over the past several years, we've been doing these kind of reinforcement learning models for understanding open source sustainability. And then we've done this work on collective cognition for AI ethics. This is where I actually applied active inference. And we modeled agent behavior in terms of active inference using a package called Interactively. And this is the GitHub repo here, Interactively. This applies a partially observed Markov decision process, or a PYMDP model, to the problem. We also used a multi-arm bandit approach to model explore and exploit behaviors. So explore and exploit is sort of this trade-off that agents make between exploring a project, exploring issues to be solved, and exploiting specific issues and solving them. So it's like coordinating agent behaviors and then figuring out what strategy they're going to use and modeling all of that. So it's a very interesting project. It needs more work on it. So if people in this group in the Active Inference Institute are interested in following up on it, that would be welcome. And so there are a number of issues about maintenance that are very important to sustainability. And this is especially true in the academic sphere, because academic organizations and open source typically don't have the resources that private organizations might. So maintenance and sustainability issues are a multitude in open source. So I'll talk about a couple of them here. So the first one is Log4j, and this happened a couple of years ago, where there were a number of open source projects that got hit with the security threat, and it was because their security fell out of sync with the current state of the art. So in open source, we don't maintain things as well as, say, like commercial products. So you have these holes that can be exploited by malicious actors. So Log4j was so serious that they had to consult with the US government to try to help fix this problem. And so this was a big problem with just kind of maintaining the security of the software, but also it exposed a big hole in the open source model. And so this is still something that probably requires meta governance, some organization between like the federal government and open source organizations to solve. The second is called the maker-taker problem, which is basically where some organizations make open source software and other organizations fork or copy the software for their own purposes, thus being a taker. And the problem here is where that relationship is not reciprocal. That, the makers will develop systems that encourage forks, and then the open source contributors or the takers are expected to contribute back to the makers some sort of, maintenance or something like that, but they fail to do so. And so this is the problem where you need to coordinate this reciprocal relationship. And so an example of this is the WordPress fork controversy. So WordPress is the maker in this case, and I think it's WP Engine is the taker in this case. WP Engine was forked from WordPress, and it resulted in a fight between the two organizations, one being the maker and one being the fork or the taker, and they've been fighting over commercial issues and fair use issues that have served to break the norms of open source. So there's this primary issue of maintaining sort of a reciprocal relationship between organizations that basically rely on each other to survive. But you can have all sorts of, fights and disagreements about different ways that the software can be used commercially and other types of use that, although are stated in the license, sometimes evolve away from the license, and they're practical concerns that, isn't going to be solved by just some sort of reciprocal relationship or even intrinsic and extrinsic motivations. And then finally, the final example is XZ backdoor /auto tools. This was an exploit that was made in an open source repository where it resulted from a lack of maintainer vigilance. So this maintainer, in this particular case, was burnt out, and they didn't feel like really kind of closely inspecting every pull request, which is where a contributor will submit a change or a contribution to an open source organization. And so malicious actor was able to get exploits into the software, and it became a huge security problem. It's kind of like Log4j. And the problem here is that it's, the failure here is at the level of maintainer. And it wasn't the maintainer's fault necessarily. It's that sometimes people in open source organizations, as well as open access organizations, open science, have become burnt out. Especially when you have to do all of these things, all these practice-oriented things to realize the open vision. And, also you have disincentives that lead to problems. So if you're not paying your maintainers enough, or if you're not, if they don't have that intrinsic motivation high enough, they can't do the job that they need to do to make things work. Or the extrinsic motivations aren't good enough. You don't really pay your maintainer very much, and therefore they're disincentivized to snip out exploits. And so these are all problems with maintaining open source, especially in an academic environment. This is a second YouTube video I wanted to point out. This is behind the screen. There's a wordplay here, which is open source software as both a tool and topic for research. This is from William Schuller at Santa Fe Institute. And he talks about sort of the history of software and how, you can research open source software, but also use it as a tool. It has a lot of interesting issues in here, so I recommend watching this video. Now I'm going to talk about how to sort of implement open software for like a purpose-run organization. So we talked about, one of these points about distributing open academic software is being able to run it properly, or run it in a way that doesn't rely on too many dependencies. And so this is where we can use something like Linux, or some flavor of Linux, to package data analysis tools so that people can use them in an environment where they don't have to worry about dependencies, they don't have to worry about having the proper software requirements. So there are two examples of where we can use a Linux distro to package data analysis tools and present them to people in the community, sometimes with fairly low technical standards. So the first is NeuroFedora. And so this was created as free and open source software. This is where we have a version of the Fedora distro of Linux. And in Fedora, you package a bunch of neuroimaging analysis tools, and you put them in, and you just give people the package. They install it on their machine, and then they can run those tools without worrying about dependencies or getting the thing to run on Windows or Mac or whatever. The other example is NeuroDebian. This is run by INCF. This is the group led by Poré Gleason and Angus, run by Poré Gleason and colleagues. And this is where they have a Debian distro of Linux, and they have these neuroimaging tools in Debian. So you have Fedora and Debian. You can choose between the two distros, and you can run these neuroimaging tools in these environments. And that makes it easier, I think, for neuroscientists to do this kind of work, to work with these packages. A similar thing could be done for Active Inference, and especially in Fedora, you have these different flavors of Fedora, like for artists or for musicians, where you can package tools for those professions, and they can just, use it out of the box. So focusing on the NeuroFedora project, this is a special interest group whose goal is to provide neuroscience researchers and enthusiasts with a strong, easy-to-use, ready-made, free and open source software platform for their work. And Ankur Sinha has taken the lead on NeuroFedora. Morgan Huff, who's part of the Orthogonal Lab, has also worked on this as well. Then we have NeuroDesk. So NeuroDesk is not an operating system, but it's a virtual machine. It's a virtualization or a containerized environment where you have basically a virtual machine on your existing computer, and you run everything inside of that. And it really paves over a lot of the operating system differences and system requirement differences that you might find trying to install open source software on your home computer. So this is where you've basically created a controlled environment for the software. So it really helps people run it when they have very little technical expertise, and just get it to run. That's all you need to do. So NeuroDesk is a containerized data analysis environment specialized for neuroimaging research, and this is something that you can easily do with the Active Inference. It's where you package the software code with the operating system, libraries, and dependencies required to run the code in a single lightweight executable. So this is platform agnostic. It's just you open up the container, you run it, and you can do everything inside of there. So thank you for your attention. I especially want to thank the members of the open source interest group, Bradley Alicea, Jesse Parent, Morgan Huff, Sarah Bastawala, Brian McCorkle, Himanshu Shogul, RV Rajagopalan, and Shubham Shoni. We have other people who cycle through the group from time to time, and you're welcome to join us. Please join the Orthogonal Research Lab, and then be on the lookout for our open source activities. We usually do the interest group in the summer. If you're interested, get in touch. Otherwise, happy active inferring.
All right. That was a great presentation. This will be the last of the recorded presentations for the symposium and last video on this part 1 stream. We have J.F. Cloutier, an experiment in artificial agency.
An experiment in artificial agency. I'm Jean-François Cloutier. I'm a research fellow at the Active Inference Institute, and I do research in cognitive robotics. One of the principal questions I ask myself is, what does it take at a minimum for an autonomous robot to learn to survive in a world it knows initially almost nothing about? Other questions which follow are, can a robot act for its own reasons? Does it have agency? Can its agency be programmed? And would such a robot be an active inference agent? The one way to find out is to actually build an artificial agent. And by artificial agent, I mean a sense-making, adaptive, and self-directed robot. So this project is a continuation of a personal project that I started quite a few years ago. And 3 years ago, here's where I was. I had a Lego robot with quite a few sensors, like ultrasonic sensors, infrared sensor, a color sensor, luminance sensor, motors of different types. All this running from a Raspberry Pi with a board that provides an interface between the Raspberry Pi and the various Lego motors and sensors. And the robot also had a 360-degree beacon that allowed one robot to see another through the other robot's 360-degree beacon seeker. So let's look at them in action. I named them Karl and Andy for, I think, quite obvious reasons. Karl had gone through quite a lot of training runs, so it was better at finding the food, which is the piece of paper on the floor, with a beacon, infrared beacon, providing the scent, the attractive scent. We can see that Andy is having a bit of a hard time, and they see each other, so that if one robot starts acting panicky, which they do if they collide too often, the other will notice the pattern of movement. And if one robot makes a beeline, then the other robot will perceive that and say, aha, that's where the food is, and try to move in the same direction. But we see them moving about and trying to get at the food and eating the food. And Karl is clearly more apt at this task than Andy. And what they've learned through various trials are the policies that are most successful at finding the food. So that's where I was 3 years ago. The way I implemented the cognitive capabilities, quote unquote, of these robots was based on a architectural model described by Marvin Minsky in his book, The Society of Mind. This architecture posits that interesting behaviors emerge from many simple actors that interact in simple ways. So we're looking at cognition as a collective intelligence. The implementation was a hierarchy of these simple processes. I call them cognition actors. And they formed an abstraction hierarchy with at the very bottom cognition actors that simply wrap sensors and effectors, motors. And then at the very bottom, we have cognition actors that care about very simple things like the location of food. Then at a higher level, information obtained from the food location cognition actor feeds into the food approach cognition actor. And this one tries to figure out, am I getting closer to the food? And so forth and so on. Other cognition actors are concerned with avoiding collisions and avoiding dark places. Now, each cognition actor, as I said, is a separate process. And each such process does very simple things. It makes predictions about what it will observe next. It then updates its beliefs based on predictions that were successful or prediction errors received, and then selects a policy randomly in the beginning, but then based on what was successful in the past, and applies that policy, acts, and then decides, okay, and then predicts what the next incoming sensations will be, and so forth and so on, essentially implementing an OODA loop. Observe, orient, decide, and act. There's one big problem, though, that this society of mind, this hierarchy of cognition actors, is predefined. It's hard-coded. For each robot, it's the same. The only thing that's learned is what policy is more effective over time, based on experience. So the robot acted for my reasons, for the programmer's reasons, not its own. The robots had autonomy, but no agency. In 2022, I joined the Active Inference Institute and continued this project under the Symbolic Cognitive Robotics tag. And I asked myself, what if a robot started with only a rudimentary society of mind? What if it didn't have that pre-built society of mind, this hierarchy of cognition actors? It started only with the most basic ones, the ones that wrap sensors and motors. Then the society of mind would grow from experiencing autonomous engagement. So the robot would start and with all these very basic prior cognition actors for sensing and affecting, and then would create new cognition actors. And these cognition actors would be very simple in the sense that they would take their sensations from the sensors themselves and would act by engaging the motors, and then observe how it changes its perceptions of, say, color or distance and whatnot, etc. So cognition actors would be added to the society of mind, bottom up, to make sense of observations and actions. Now, each new cognition actor would select an Umwelt composed of cognition actors one level below. And how do we know that a particular level of cognition actors in this growing hierarchy is complete? It's when all cognition actors one level below belong to an Umwelt. Now, it would not only grow, but it would also shrink, because whenever cognition actors were recognized to be hopelessly ineffective, they would eventually be removed, and new cognition actors would take their place. And the hope would be that as this cognition hierarchy grows, becomes more competent, we would have a robot that starts acting intelligently and in survivable ways. So the society of mind would grow, shrink, and evolve as needed to survive. Now that's a key point here. This is an implementation of a form of mortal computing. Obviously, the robot is physically, the wheels, the sensors themselves are not mortal. They're like a computer on wheels. You turn it off, you turn it on, it's still alive. It hasn't died from having been turned off. However, the society of mind itself is mortal. It grows, it evolves in such that the robot will be competent at finding the food it needs to keep the society of mind alive. So what we have here is a mortal society of life, of mind, trying to achieve a sufficient level of competency to maintain itself. This is a work in progress. This is a system that I'm in the process of building, and it's composed of these subsystems, agency, where the smarts are for growing, shaping, and evolving a society of mind. There's another subsystem that it runs on the robot itself, which I call body, which provides an interface to activate motors and to read the sensors. There's also a version of the body subsystem which will run in a simulated world, and the subsystem world implements that simulated environment. It will also animate a real environment. And then there's a subsystem that I call observer, which provides me or any other human being with a window into what's going on within the society of mind of the robot. The agency subsystem runs on a powerful computer. The body subsystem, the physical one, runs on the brick Pi, which is powerful enough to run the significantly complex programs, but not too computationally intensive ones. And world and observer and body simulated run on a separate computer. The Karma body subsystem, as I said, gives access to real and virtual sensors and effectors. And here I have all the sensors I want to use and the motors removed from the robot, just like connected directly to the brick Pi. And they can be activated, they can be reached via a REST API, which is essentially they exposed a web interface to the agency subsystem. The Karma world subsystem, here we see the simulated environment. It's a grid world. The gray tiles represent just the surface, and with brown tiles representing obstacles. So the robot will bump into these obstacles and will perceive them with its simulated distance sensors. The green patch represents a food patch, and the robot needs to find food in order to consume the food and replenish its resources. If it runs out, then it dies. We can see that some tiles are darker, others lighter, and this gradient, this luminance gradient, corresponds to a scent gradient. So the closer the robot is to the food, the lighter the tiles are. There will also be poison patches, which will be red, so detectable as a red surface on the simulated floor. The robot must learn to avoid poison food because that will harm it, and if it's excessively harmed, then it will also die. When a robot spends enough time over the food is consumed, and another food patch appears somewhere else. So the environment is dynamic, and it changes with its interactions with the robot. That's an important element here. Now, the karma agency subsystem is the most complex and the key subsystem, and it implements a generative cognitive architecture for the robot implementing agency. So it's going to implement cognition actors, as we've mentioned already. It will implement something I call metacognition actors, a very limited understanding of the concept of metacognition. One metacognition actor per level in the hierarchy, and the cognition actors are responsible for adding, removing cognition actors as needed, as required. Then very, very importantly, we'll have well-being actors, and these actors represent the homeostatic values that the society of mind must keep within acceptable bounds in order to survive. We have fullness, integrity, and engagement. We'll talk in more details about what they are later. And then, very importantly, there's an apperception engine actor. Last year at the symposium, I presented my implementation of an apperception engine, and this is a very important part of a component of the society of mind. It is responsible for making sense of observations in order to be able to make predictions. We'll go into more details as well. Now, let's go and look at these well-being actors. They implement homeostatic states, and I have three. One is fullness, which represents how much energy the agent as a whole, the robot, has available to do things. That could be computing, doing some expensive computation, or just moving about. So there's an energy budget that gets depleted and also gets replenished when the robot finds food and spends enough time in a food patch. There's also the integrity well-being actor, and that represents the health of the agent. If the agent, the robot, suffers too many collisions, then integrity goes down, and integrity is recovered over time. Think about lives in a video game. That's pretty much the same concept. And finally, a little bit more abstract well-being actor is engagement, and it represents to what degree the robot is engaging its environment. We want to avoid the dark room situation where the robot stops doing anything stops moving, engaging its environment, it feels, quote unquote, an imperative to engage its environment. Now, the agent as a whole, meaning the society of mind of the agent, strives to maximize well-being for the entire society of mind. Now, low well-being levels will signal risk to the survival of the society of mind, so that information will be available to each individual cognition actor and to the metacognition actors, and will modify, constrain what they do. Key concept here is that well-being imparts normativity to beliefs. Beliefs acquired in the context of a low fullness or low integrity becomes a unpleasant, undesirable belief. Now, this normativity associated to beliefs will focus attention and motivate action, as we'll see later on. So, well-being actors aggregate metrics received from the various cognition actors, and then aggregate these metrics and broadcast wellness events back to the cognition actors, essentially informing them of the homeostatic state of the agent as a whole. Now, these metrics include the work that's been done, the food that's been consumed. These two will impact the fullness metrics values. Then poison consumed, collision count will impact the integrity, overall integrity of the agent. And then predictions made, predictions received, prediction errors sent, policies executed. We'll see that in more detail later. All these are indicative of the society of mind engaging its environment. Now, metacognition actors. Their role is pretty straightforward. They're responsible for adding cognition actors that are missing and to remove underperforming cognition actors. Each cognition actor is assigned one level in the abstraction hierarchy, and it looks at the cognition actors under its supervision and determines if all the cognition actors below them are part of one or the other's Umwelt. So the notion of Umwelt here. A cognition actor can only observe or act within its Umwelt. And what is the Umwelt of a cognition actor? It's other cognition actors of a lower level of abstraction. So at the first level of cognition actors, the prior level, where we have where they wrap sensors and motors, they don't have an Umwelt. Well, they do. It's the actual external environment of the robot. They don't have an internal Umwelt. Anything above this level, the cognition actors have, as part of their Umwelt, other cognition actors, and they constitute essentially the internal Umwelt of within the society of mind. So if a one layer of the society of mind is complete, it covers all the cognition actors below, then it's time to create a cognition actor at the level above, create a new layer of the society of mind. And when you create a cognition actor, you give it, or the metacognition actor gives it, its Umwelt. Mostly randomly, with the constraint that there's going to be overlap between Umwelts of various cognition actors, and making sure that they have access to the motors directly or indirectly. Now, when well-being is low within the society of mind when the well-being actors are reporting low well-being levels. This might accelerate the removal of cognition actors. The metacognition actors, being aware that we're not doing well now, will say, okay, which cognition actors are underperforming our expectations, and let's remove them in order for them to be replaced with new cognition actors, which hopefully will do better. And if well-being is low, this will also slow down adding new cognition actors. So there's an influence of well-being on the actions of the metacognition actors. Now, I want to say adding and removing. It's important to understand that adding is bottom up and removing is top down. For example, if I have if I have a cognition actor that has, let's say, two other cognition actors in its umwelt, I cannot remove a cognition actor in its umwelt because it depends on it. But I can remove a cognition actor that is not in any other's umwelt, so that removal will be from the top to bottom, and addition will be from the bottom to top. What does a cognition actor do? Well, a cognition actor observes its umwelt of other cognition actors. It generates beliefs from analyzing its observations, and then it generates policies in order to modify or validate its beliefs. And it does this observe, believe, and act always within its umwelt and one time frame at a time. So each cognition actor goes through its more or less OODA loop, one time frame at a time. Now, the lower a cognition actor is in the society of mind, the more concrete it is, the less abstract it is, the shorter this time frame will be. It will cycle faster. It's important also to realize that there's no synchronization between cognition actors. Each starts its time frame independently of other cognition actors, and so that they may overlap, but they don't coincide. They don't overlap completely. And the more abstract the cognition actor is, the higher up it is in the hierarchy of cognition actors within the society of mind, the longer its time frame will be. Which means that very abstract cognition actors will update their beliefs more slowly and will take actions not as quickly as a more concrete low-level cognition actor. So we can see here the cognition actor, the large one, surrounded by its low-level cognition actors. What does it observe? What does the cognition actor observe in its umwelt? Well, it observes the beliefs of the cognition actors in its umwelt. So, as a more abstract cognition actor, I observe the beliefs of the more concrete cognition actors in my umwelt. Then, based on these beliefs, and as we'll see, based on the normativity associated to the beliefs, are they good beliefs, are they bad beliefs, the cognition actor will decide on what its goals are in this current time frame. The goals would be modifying a particular belief or validating a particular belief. Then it will generate policies to attain this goal, and then emit this policy to its umwelt and say, okay, do what I want. And we'll see in more details what do what I want means. So within each time frame, a cognition actor will predict its umwelt after having made sense of it. That's a key aspect that we'll go into more details. It will update its beliefs by analyzing past and present observations. So a cognition actor has a memory of the current observations, and this is the current time frame, and observations made in previous time frames, and it will update its beliefs but from analyzing current observations and past observations. Then it will select a goal, affecting a belief it intends to impact, and construct a policy and recruit its umwelt to realize it. So if you look at the little redesigned OODA loop here, first there's predict, make predictions about beliefs of other cognition actors in my umwelt. In order to predict, I need to have a causal model of my observations. That's what apperception will do. We'll see in more details. Then, as a cognition actor, update my beliefs, select goals, act, and back to predicting in the next time frame. Apperception is defined here as the process of assimilating sensory information into a coherent, unified whole. Let's look at predicting. What are the observations of a cognition actor? Observations are predictions it makes about the beliefs of other cognition actors which are in its umwelt, plus prediction errors. So it makes predictions of its umwelt, of cognition actors in its umwelt about their beliefs, and the umwelt cognition actors receive that prediction, look at it, does it correspond to my current beliefs? If yes, not saying anything, I'm not contesting the prediction. If it doesn't match, then I emit a prediction error. And the cognition actor accumulates these predictions that are uncontested and the prediction errors, and together they constitute the cognition actor's current observations. So we'll see that not all observations receive the same attention, that they're not equally subject to prediction. There's a prioritization, there's a notion of attention. We'll see that a little bit later. Attention. Attention prioritizes which observations to update. So the cognition actor starts a time frame with observations made in previous time frame, and it wants to make those observations current to the current time frame, as many of them as possible. But there's a limited amount of time in which to update these observations. So the cognition actor will need to prioritize which observations from the previous time frame to update into the more current observations. So which one will it try to update first? Well, it will look at the predictions that were made by higher level cognition actors about its beliefs, and knowing which observations support the beliefs will say, these are the observations that more abstract, more important cognition actors are making about me, my state, my beliefs. So I'm gonna try to make sure that I have up-to-date observations that are of interest to my parent, my parent cognition actors. So that's the first one I care about, the first observations I care about, the ones that are of interest to my parent cognition actors. The second most important observations in terms of updates are the observations that support the strongest desirable and undesirable beliefs. Remember that beliefs are the result of analyzing observations, current and past. If I have very strong desirable or very strong undesirable beliefs, then I will want to verify that those observations are still current. So there will be the next observations that I will try to update. Then finally, the observations that support weak or neutral beliefs, and then whatever remaining observations they are. So the cognition actor will prioritize the observations that existed from the previous time frame and say, okay, I'm going to now make predictions that these observations are still valid or not valid. And if there are prediction errors, then the observations are updated to the prediction error. And if the observation is not contested, then the observation is the one that is current. This implements a predictive processing architecture because, as you can imagine, a high-level cognition actor will make predictions about beliefs of its children cognition actors. This will trigger predictions about the observations supporting these beliefs, one level down to the cognition actors in the layer below and all the way down. So predictions flow down and prediction errors flow up through the entire hierarchy of the cognition actors in the society of mind. Now, in order to make predictions, we need to have made sense of observations. That's what apperception does. So we need to make sense of observations in order to predict them. Now, in order to explain the concept of apperception, in which in last year's presentation I went into quite a lot of details, but just I want to give an overall understanding here. Let's take the example of observing two lights, light A and light B, and the light can either be on or off. And at different steps in time, the lights may change their state from on to off, off to on, or not. So here we have a set of observations of light A and B over time, and sometimes we may not be able to observe a light, like light A in the fourth state is a gray rectangle. We don't know. But we have a good enough set of observations, and now the goal of the apperception engine is to find a causal theory that explains how the observations change over time. Why are we seeing some light A turn on after having been off, or etc. In order to formulate a causal theory, kind of a little program that when run recreates what we've observed, the apperception engine may need to imagine another light. It might need to imagine some kind of connection between the lights. So the apperception engine will, in formulating a causal theory, will do some abduction, some imagining of unobserved latent objects. So we have a number of observations that are remembered from previous time frames. We don't accumulate all observations forever. We forget the older ones. And then we feed these observations into the apperception engine. Out of that comes a little program, a causal theory, that when applied to the latest observation will produce the next incoming expected observations. So that's a way of making predictions of incoming observations from current and past observations, from the current observations given a causal theory. So you feed the latest observation, you feed all the observations into the apperception engine. It gives you a causal theory. You feed the latest observation into the causal theory as input. The output is incoming predicted observation. So an apperception means finding a causal theory. that explains all the rules of the theory and predicts observations. So a cognition actor accumulates observations, wants to make sense of them in order to predict incoming observations, and for other reasons as well, which we'll see. And what it does is that, okay, it gives the apperception engine actor its observations over time and says, please explain to me what I'm observing. Give me a causal theory so I can predict future observations. Given this causal theory, if one is found successfully, then the cognition actor can predict incoming observations. And what does it observe? It observes the beliefs of cognition actors in its Umwelt, more concrete cognition actors. And then if the prediction is correct, if the causal theory is correct and accurate, we don't get a prediction error. If the causal theory is partially correct, sometimes correct, then we get a prediction error. So getting prediction errors undermine confidence in the causal theory that the cognition actor has received from the apperception engine to explain what it sees in its Umwelt. So it's quite possible that there's a moment in time when the observations, when the causal theory is quite effective and it's accurate, but then something changes in the state of the Umwelt cognition actors such that the causal theory is missing, is very hit and miss, and it may come a point where the cognition actor says, I don't like that causal theory anymore. It's producing too many prediction errors, so it's going to ask the apperception engine actor, give me a new causal theory based on the latest observations that I've accumulated in my memory. Okay, so we looked at how cognition actors predict incoming observations in order to accumulate those new observations, to update those new observations based on whether or not these predictions are contested by prediction errors or not. So now, once we have a new set of current observations within this time frame that we are operating in, it's time to update beliefs. Beliefs are, if you want, are the integration of observations into a more aggregated analytical assertion. So a cognition actor updates its belief from analyzing remembered observations and also remembered actions that it took. So and we'll see what kind of integration of observations and analysis of observations lead to what type of beliefs. But whatever type of belief it is, a belief will be desirable or undesirable depending on how it correlates with the agent's well-being. If a belief is being held mostly while the agent as a whole is feeling bad, it has low resources or low integrity or limited engagement, then these beliefs are going to be tainted by the well-being levels of the agent at the time those beliefs are held. Now, that's what makes a belief desirable or undesirable. What makes a belief strongly held is if it is supported by observations, those observations from which analysis the belief is derived. If it is supported by observations that are predicted by an accurate causal theory, we have an excellent causal theory. It rarely misses. So the cognition actor is feeling confident about its observations, and it makes the whatever belief is produced from analysis of these successfully predicted observations better supported, more strongly held. Now, if a belief persists over many time frames, thanks to or in spite of actions taken to validate or invalidate it, if the belief persists, then it's even more strongly held. There's increased confidence that the belief represents what's really going on in the Umwelt of the cognition actor. Now, there are different kinds of beliefs. Beliefs are produced from the analysis of current and past observations. And, okay, so there's adduction. One type of belief is abduction, and it's a direct consequence of having requested a causal theory and using a causal theory. Remember, in a causal theory may imagine a latent object or a latent relationship between objects. Well, that's a form of belief. I believe there's an object that I don't see but must exist in order for a causal theory to make sense of actual observations I made. So an abduction belief would be like, I assume there's a hidden thing next to the one I see. Another kind of belief is just counting. I'm next to two things. I have made two observations that represent, let's say, being next to something, and so I have two of them. So I can have a belief that I'm next to two things. A count belief. Now, a trend belief it's a belief that represents the discovery of a trend in certain observations over time. For example, if the cognition actor observes distances to some obstacle, and those distances are getting smaller over time, then that's a trend. My distance to a thing is getting smaller. And then there's another kind of belief is some observation ending, stopping. My getting closer to a thing stopped. So that's an ending kind of belief. And then if the cognition actor has taken some action, well, there's the belief that he tried to do something. It's like, I tried to stop my distance to a thing from getting smaller. So if the action was trying to end the belief in a trend, as you can see now that beliefs are composed, they're getting more and more abstract. So I tried to stop my distance to a thing from getting smaller is a kind of another kind of belief. It's an attempt kind of belief. So we have all these different kinds of beliefs. And when a cognition actor synthesizes the belief from analyzing its observations, it assigns the belief a globally unique predicate name. Parent cognition actors, the cognition actors in which Umwelt this cognition actor belongs, the parent cognition actors predict the beliefs of cognition actors in their Umwelt and reference them by name. So if there's a belief in an Umwelt cognition actor that some trend exists, we're getting closer to an obstacle. Well, this belief will be exposed, will be made available for observation to the parent as a named predicate. Why and how that belief came about, what the observations are by the Umwelt cognition actor that led to that belief, it's opaque. There's a name, and that's the name that's available for observation. There's a statement, a predicate, a named predicate that's available for observation by the parent cognition actor. Only the cognition actor that holds the belief it named knows which of its own observations support the belief and how. So if I say to you, I believe getting closer. That's something that you can observe as a parent cognition actor. My child cognition actor believes in getting closer. But the parent cognition actor doesn't know why I believe we're getting closer, doesn't have access to the set of observations that led to me holding the belief that we are getting closer. All these distance observations that led to me holding the belief that getting closer. All that parent knows is that I hold the belief called getting closer, and it's able to observe it, ending or starting, etc. So that's a key concept, that beliefs are essentially named. There are predicates, they're names, if you wish, that hide the reason why the belief is held to parent function actors that observe my beliefs. So there's information hiding going on here. So a cognition actor observes the beliefs of its children cognition actors, and these beliefs that are observed are the consequences of themselves observations of cognition actors one level below. So my belief is another. If I'm a cognition actor, my belief is another cognition actor's observation. So it's really beliefs. It's beliefs about beliefs about beliefs. So it's beliefs all the way down. That's maybe a little tricky concept. If I'm at the top as a cognition actor, I observe beliefs of cognition actors under me. These beliefs of cognition actors under me are supported by their observations of beliefs of cognition actors under them. So beliefs about beliefs about beliefs. Time to open a little parentheses here. Maybe take a break. The implementation that I'm working on of agency is a symbolic implementation. So it's agency realized from symbolic reasoning. All the various agency actors, the cognition actors, the metacognition actors, the well-being actors, the perception engine actors, all run Prolog programs. Prolog is the programming language. And those Prolog programs do symbolic inferencing. The cognition actor, as we've seen, invents symbols, gives names to beliefs it discovers from analyzing observations. So it invents symbols, and it synthesizes these beliefs as symbolic statements, getting closer to X, Y, Z. The apperception engine, as we've seen very kind of briefly, its job is to discover causal models, and these causal models are symbolic programs. They're little logic programs. So agency is built on symbolic reasoning in my implementation. Closing the parenthesis. Now let's talk about precision and belief strength. The more accurate a causal theory, the more precise are considered its predictions. So we saw that earlier. Now, precise predictions, if they're not contradicted by prediction errors, do strengthen the beliefs the predicted observations support. So you have a bunch of observations held by the cognition actor, observations in the moment, remembered observations. These observations are the result of predictions and or prediction errors. And we analyze these observations coming from predictions to generate beliefs. I'm getting closer to an obstacle from observations of distances. Now, if my observations of distances were predicted by a really top-notch causal theory, one that almost never misses, then I have confidence in the beliefs that I have derived from my predictions. I feel confident that I am indeed getting closer to an obstacle, given all the distance observations that I've accumulated, because I've accumulated them by making predictions using a very accurate, empirically accurate causal theory. So precise predictions strengthen the belief that are derived from observations, from predicted observations. Now, the stronger beliefs are, because I may have strongly held beliefs and weakly held beliefs, the more strongly held beliefs are, the more attention they will receive when selecting, when the cognition actor wants to select one and say, I don't like this belief. It's associated with poor well-being, and I want to change that belief. I want to impact it. I want to get rid of that belief. I want to make that belief not true. Or if it's a very pleasant belief, I want to make sure that it is. I want to validate it. I want to keep that belief. I want to keep holding that belief because it's a good one. But I care whether the belief is strongly held or weakly held, because strongly held belief will get more attention, will be the ones that will be selected for validation or invalidation above the weakly held beliefs. So how do we impact beliefs? That's the next step in the next two steps in the OODA loop of our cognition actor within each time frame. It predicted based on its understanding of past observations. It updated its belief from analyzing predictions that were realized or errors to those predictions, i.e. those observations. It updated its beliefs. And now it says it needs to select a goal, it may need to select a goal that says, I want to get rid of this belief or I want to validate this belief. And how am I going to accomplish this goal? I'm going to select a policy and then and ask my Umwelt to act to realize this policy. So that's what we're looking at now. So a cognition actor acts via policies it formulates. A cognition actor strives to invalidate unpleasant beliefs and to validate pleasant beliefs, but it will prioritize strongly held beliefs, whether unpleasant or pleasant. A cognition actor will impact the belief, validate or invalidate it, it holds, by promoting or inhibiting the observations that led to it. Now, I have a belief that we are getting closer to an obstacle, and somehow it's an unpleasant belief. Maybe it's associated with, in the past, with a decrease in integrity. It leads to bumping into things. So I want to put an end to getting closer to an obstacle. I don't want this belief that I'm getting closer to an obstacle to go away. Now, I hold this belief because I had observations of reducing distances over time to some obstacle. So I want to change these observations. Basically, I want to stop getting close, having distances that get smaller. I want to stop this. So my observations of distances happen to be beliefs of cognition actors in my Umwelt. So what I'm going to do, I'm going to say, okay, I'm going to select a number of observations that support the belief I want to get rid of, and I'm going to formulate a policy as a list of goals to my Umwelt CA. I'm going to say, I want you to get rid of the fact that I have small distances to an obstacle. That's your goal. So I'm gonna set a number of goals. Me, the cognition actors who believes we're getting closer to something and it's not, doesn't feel good. I'm going to formulate a policy so that my Umwelt cognition actors will try to impact their own beliefs that we have a small distance to an obstacle, for example. Okay, so that's a little bit subtle here. So as a cognition actor, I want to modify a belief. That belief is based on observations. These observations are beliefs of Umwelt cognition actors. So I'm going to say to my Umwelt cognition actors, I want you to modify your own beliefs that I've observed. I want you to change your beliefs that I'm observing that lead me to believe that I'm getting closer to an obstacle. So I'm setting up a bunch of goals for my Umwelt cognition actors so that if they realize, if they modify these beliefs, then it will modify indirectly my own belief that I'm trying to get rid of. Okay, so I'm basically telling my Umwelt, these are the goals I want you to realize, so that I would indirectly realize my own goal. Okay, so a policy that I put together are a set of goals for my Umwelt cognition actors to realize. Now, an Umwelt cognition actor will then, given the goal it receives, formulate its own policy. Because I'm asking a cognition actor in my Umwelt to modify some belief or other. Okay, says the cognition actor, then I will formulate my own policies to do that, to achieve the goal that my parent cognition actor sent to me. So a cognition actor will receive goals from parent cognition actors, and these goals received from higher up will have higher priority than whatever goals the cognition actor might want to formulate on its own, because the Umwelt cognition actor has its beliefs, has beliefs that it wants to validate, has beliefs it wants to invalidate, and left on its own to its own devices will do just that. But if it receives goals from a parent cognition actor, these take priority, and it will put aside its own concerns to address the concerns of the parent cognition actor. A cognition actor can now execute only one policy at a time, which is why it will prioritize the ones that it receives from its parent. And when all is said and done, the cognition actor that initiated the policy will will verify if this was successful or failure over time, if the belief that it wanted to impact was indeed impacted. And a policy that's known to work will be reused. That's how cognition actors develop habits. Okay. So, where does the causal theory that a cognition actor holds guide the formulation of its policies? Because there was causal theory serves two roles. One is to predict incoming observations, and the other role is to formulate an effective policy. So let's say that cognition actor has a belief it wants to impact because the well-being levels are low associated to that belief. So he wants to modify that belief, get rid of it. Well, it needs to formulate a candidate policy. Which of the observations that I made that I've analyzed into this belief, which observations that support this belief I want to modify? So which policy do I want to formulate? Well, what it will do is we'll say, okay, what do I need to do given what I'm observing right now, so that I will observe something differently that will either remove the belief or reduce it. So it will use the causal theory. So what would happen if I did X? If I asked my Umwelt to do X, Y, Z? So the causal theory will answer that question. We'll say, well, plug that into the causal theory, turn the crank, and this is what you would be observing next. If you were doing this, if you executed this action, this is what you would observe next. And then, given what you would observe next, you can calculate, these will be the anticipated beliefs out of these anticipated observations. Might the policy work? Would the belief that I want to impact be impacted the way I want to impact it? If so, yeah, let's use that policy. Otherwise, let's look for another one. So the cognition actor searches for an effective policy given its understanding of how things work in its Umwelt, its causal theory, and then applies the causal theory, predicts what would happen if it took this action, if it requested this goal to be realized, looks at the resulting anticipated beliefs, and decides, was this a a good, effective policy, and then it would emit that policy and ask its Umwelt, please achieve these goals so that I achieve my goal. So, and that percolates down because each cognition actor being given a goal from the parent cognition actor says, how should I best realize that goal? What policy should I formulate for my own child, my own Umwelt, in order to realize the goal that was given to me by my parent? So it's policies all the way down. And it bottoms out when at the level where effects are produced, moving motors, turning, moving forward, moving backward, whatever. Okay, so that's a lot of content describing this cognitive architecture, this generative cognitive architecture. What I hope will happen is through this growing, shrinking, evolving, refining of this society of mind composed of cognition actors, with in the context of homeostatic measures provided by well-being actors. I'm hoping that with the policies going down, beliefs percolating up, predictions going down, prediction errors going up, all this changes and evolution of the society of mind, all these activities, from all of this would emerge agency. And I'm looking at that as a form of operational closure, with constraints flowing down, constraints flowing up, and eventually, hopefully, the society of mind will explore a space of possible organizations and space of possible ways of defining cognition actors, relating cognition actors together, such that it leads to behaviors of the robot that preserves the life of the society of mind. That society of mind never reaches a point where it runs out of fuel, where it is damaged beyond repair. That's the overall goal. I think of this society of mind as kind of autopoietic, with all these elements of the society of mind leading to other elements. For example, a causal theory will lead to predictions. Predictions will lead to prediction errors. Prediction errors will lead to observations. Observations will be fed into apperceptions, which will lead to an updated causal theory. And observations lead to beliefs. Beliefs lead to policy. A causal theory will determine which policy is more likely to work. Policy leads to effect. Effects lead to new sensations. Sensations lead to new observations, and so forth and so on. So this, I look at this as a kind of a set of processes that support each other, and in something of a closed set of complex loops, leading to a society of mind that survives over time. Now, there's a number of philosophical stances that are taken by this project, and by philosophical stance, I mean pragmatically justified perspectives, a way of seeing the world. First, I look at active inference as a normative framework. I don't think that's controversial at all. I mean, that's what it's defined to be. And to persist, an agent must behave as if it acts to minimize surprisal. Now, clearly, I'm not implementing the society of mind using the mathematics of the free energy principle, but I'm implementing it hopefully such that doing an active inference analysis of the robot's observable behaviors and states will demonstrate that the society of mind the agent as a whole is acting such as to reduce surprisal. So I'm implementing an agent and also its environment as a system of generative processes. The active inference analysis will be done in terms of generative models that are inferred from observing the behaviors of the robot and observing the states that are visible to an outside observer. Other philosophical stances, I'm just going to go through them very quickly. Each one is worth an entire presentation. I take the stance that cognition arises from an embodied agent engaging its environment, that sense-making is the discovery of unified causal theories, that meaning is grounded in the agent's drive to survive. No mortality, no meaning. That intelligence emerges from interactions between a collective of parts, that's the society of mind, and that the parts constrain the whole and the whole constrains the part, so constraint closure. I'm in the process of implementing this system that will hopefully demonstrate artificial agency. And here's the current progress. There are 3 phases in this project. Phase 1, I developed in our cognitive architecture. That's what I presented today. Implemented one version of the apperception engine, and that's what I presented last year. I implemented the subsystem to realize to connect to sensors and actuators. That's the karma body. And I implemented a simulated grid world in which a simulated agent would operate and interact. That's to speed up implementation, because it takes a long time to, if I were to do this only in the real world, the edit, run, debug loop would be extremely long. And so I'm in the process right now of implementing the agency capabilities. In phase 2, which would be about 6 months to a year from now, I will have a redesigned robot body. I will be testing in a real-life environment, and I will be collecting a lot of data through the observer subsystem. And in the third and final phase, the data gathered from runs, both in real life and in the virtual world, will be subjected to active inference analysis to validate that my agent does survive because it minimizes surprisal. That's it. If you are interested, you can contact me at this email address, jf.cloutier@activeinference.institute. You can also reach me on the SimCog robotic channel of the Institute's Discord. And if you're interested in the source code, it is on GitHub. So I'd like to thank the Active Inference Institute for support and encouragement.